So in the last video, I left you with a cliffhanger. I introduced you to the minimum cut problem. I introduced you to a very simple and elegant randomized algorithm in the form of the contraction algorithm. We observed that sometimes it finds a min cut and sometimes it doesn't. And so the $64,000 question is just how frequently does it succeed and just how frequently does it fail? So now that hopefully you've brushed up on your conditional probability and independence, we're going to give a very precise answer to that question in this lecture. So recall on this problem we're given as input an undirected graph, possibly with parallel edges, and the goal is to compute among the exponential number of possible different cuts, that with the fewest number of crossing edges. So for example, in this graph here, which you've seen in a previous video, the goal is to compute the cut AB here, because there are only two crossing edges, and that's as small as it gets. That's the minimum cut problem, and Karger proposed the following random contraction algorithm based on random sampling. So we have n-2 iterations, and the number of vertices gets decremented by 1 in each iteration. So we start with n vertices, we get down to 2. And how do we decrease the number of vertices? We do it by contracting or fusing two vertices together. How do we pick which pair of edges, which pair of vertices to fuse? Well, we pick one of the remaining edges uniformly at random. So there's however many edges there are remaining, we pick each one equally likely. If the endpoints of that edge are u and v, then we collapse u and v together into a single supernode. So that's what we mean by contracting two nodes into a single vertex. And then if that causes any self-loops, and as we saw the examples, we will in general have self-loops, then we delete them before proceeding. After the n-2 iterations, only two vertices remain. You'll recall that those two vertices naturally correspond to a cut. The first group of the cut A corresponds to the vertices that were fused into one of the super vertices remaining at the end. The other super vertex corresponds to the set B, the other original vertices of the graph. So the goal of this video is to give an answer to the following question: what is the probability of success? Whereas by success we mean outputs particular min cut A comma B. So let's set up the basic notation. We're going to fix any old input graph, undirected graph. And as usual, we use n to denote the number of vertices and m to denote the number of edges. We're also going to fix a minimum cut A comma B. If a graph has only one minimum cut, then it's clear what I'm talking about here. If a graph has multiple minimum cuts, I'm actually selecting just one of them. Okay, so I'm going to focus on a distinguished minimum cut A comma B, and we're only going to define the algorithm as successful if it outputs this particular minimum cut AB. If it outputs some other minimum cut, we don't count it. We don't count it as successful. Okay, so we really want this distinguished minimum cut A comma B. In addition to n and m, we're going to have a parameter k, which is the size of the minimum cut. That is, it's the number of crossing edges of a minimum cut, for example, that cross A comma B. The k edges that cross the minimum cut AB we're going to call capital F. So the picture you want to have in mind is there is out there in the world this minimum cut AB. There's lots of edges with both endpoints in A, lots of edges possibly with both endpoints in B, but there's not a whole lot of edges with one endpoint in A and one endpoint in B. So the edges F would be precisely these three crossing edges here. So our next step is to get a very clear understanding of exactly when the execution of the contraction algorithm can go wrong and exactly when it's going to work, exactly when we're going to succeed. So let me redraw the same picture from the previous slide. So given that we're hoping that the contraction algorithm outputs this cut AB at the end of the day, what could possibly go wrong? Well, to see what could go wrong, suppose at some iteration, one of the edges in capital F, remember F are the edges crossing the min cut AB, so it's these three magenta edges in the picture. Suppose at some iteration one of the edges of F gets chosen for contraction. Well, because this edge of F has one endpoint in A and one endpoint in B, when it gets chosen for contraction, it causes this node from A and this node from B to be fused together. What does that mean? That means in the cut that the contraction algorithm finally outputs, this node from A and this node from B will be in the same side of the output cut. Okay, so the cut output by the contraction algorithm will have on one side both the node from A and a node from B. Therefore, the output of the contraction algorithm, if this happens, will be a different cut than AB. Okay, it will not output AB if some edge of f is contracted. And if you think about it, the converse is also true. So let's assume now that in each of the n-2 iterations, the contraction algorithm never contracts an edge from capital F. Remember, capital F are exactly the edges with one endpoint in A and one endpoint in B. So if it never contracts any edge of F, then it only contracts edges where both endpoints lie in capital A or both endpoints lie in capital B. Well, if this is the case, then vertices from A always stick together in fused nodes, and vertices from B always stick together in the fused nodes. There is never an iteration where a node from A and a node from B are fused together. What does that mean? That means that when the algorithm outputs a cut, all of the nodes in A have been grouped together, all of the nodes in B have been grouped together in each of the two supernodes, which means that the output of the algorithm is indeed the desired min cut A, B. Summarizing, the contraction algorithm will do what we want. It will succeed and output the cut A, B if and only if it never chooses an edge from capital F for contraction. Therefore, the probability of success, that is the probability that the output is the distinguished min cut A, B, is exactly the probability that it never contracts an edge of capital F. So this is what we're going to be interested in here. This will be the object of our mathematical analysis. The probability that in all of the n-2 iterations we never contract an edge of capital F. So to think about that, let's think about each iteration in isolation and actually define some events describing that. So for an iteration I, let SI denote the event that we screw up in iteration I. With this notation, we can succinctly say what our goal is. So to compute the probability of success, what we want to do is we want to compute the probability that none of the events S1, S2 up to Sn-2 ever occur. So I'm going to use this not symbol to say that S1 does not happen. So we don't screw up in iteration 1, we don't screw up in iteration 2, we don't screw up in iteration 3, and so on, all the way up to we don't screw up, we don't contract anything from capital F in the final iteration either. So summarizing, analyzing the success probability of the contraction algorithm boils down to analyzing the probability of this event, the intersection of all of the not SIs with I ranging from iteration 1 to iteration n-2. So we're going to take this in baby steps, and the next quiz will lead you through the first one, which is let's have a more modest goal. Let's just think about iteration number 1. Let's try and understand what's the chance we screw up, what's the chance we don't screw up just in the first iteration. So the answer to this quiz is the second option. The probability is k over m, where k is the number of edges crossing the cut A, B, and m is the total number of edges. And that's just because the probability of S1, probability that we screw up, is just the number of crossing edges. That's the number of outcomes which are bad, which trigger S1, divided by the number of edges. That's the total number of things that could happen. And since all edges are equally likely, it just boils down to this. And by the definition of our notation, this is exactly k over m. So this gives us an exact calculation of the failure probability in the first iteration as a function of the number of crossing edges and the number of overall edges. Now it turns out it's going to be more useful for us to have a bound, not quite as exact, an inequality, that's in terms of the number of vertices n rather than the number of edges m. The reason for that is it's a little hard to understand how the number of edges is changing in each iteration. It's certainly going down by 1 each iteration because we contract an edge each iteration, but it might go down by more than 1 when we delete self-loops. By contrast, the number of vertices is this very steady, obvious process. One less vertex with each successive iteration. So let's rewrite this bound in terms of the number of vertices n. To do that in a useful way, we make the following key observation. I claim that in the original graph G that we were given as input, every vertex has at least k edges incident on it. That is, in graph theoretic terminology, every edge has degree at least k. Where, recall, k is the number of edges crossing our favorite min cut A, B. So why is that true? Why must every vertex have a decent number of neighbors, a decent number of edges incident to it? Well, it's because if you think about it, each vertex defines a cut by itself. Remember, a cut is just any grouping of the vertices into two groups that are non-empty, that don't overlap. So one cut is to take a single vertex and make that the first group A, and take the other n-1 vertices and make that the second group capital B. So how many edges cross this cut? Well, it's exactly the edges that are incident on the first node, on the node on the left side. So if every single cut, if all exponentially many cuts have at least k crossing edges, then certainly the n cuts defined by single vertices have at least k crossing edges, so therefore the degree of every vertex is at least k. So our assumption that every single cut in the graph has at least k crossing edges gives us a lower bound on the number of edges incident on each possible vertex. So why is that useful? Well, let's recall the following general fact about any graph, which is that if you sum up over the degrees of the nodes, so if you go node by node, look at how many edges are incident on that node, that's the degree of v, and then sum them up over all n vertices, what do you get? You get exactly twice the number of edges. Okay, so this is true for any undirected graph, that the sum of the degrees of the vertices is exactly double the number of edges. To see this, you might think about taking a graph, starting with the empty set of edges, and then adding the edges of the graph one at a time. Each time you add a new edge to a graph, obviously the number of edges goes up by 1, and the degree of each of the endpoints of that edge also go up by 1. And there are, of course, 2 endpoints. So every time you add an edge, the number of edges goes up by 1, the sum of the degrees goes up by 2. Therefore, when you've added all the edges, the sum of the degrees is double the number of edges that you've added. That's why this is true. Now, in this graph that we have at hand here, every degree is at least k, and there's n nodes. So this left-hand side, of course, is at least kn for us. So therefore, if we just divide through by 2 and flip the inequality around, we have the number of edges has to be at least the size of the crossing cut, or the degree of every vertex, times the number of vertices divided by 2. So this is just the previous inequality rearranging. Putting this together with your answer on the quiz, since the probability of S1 is exactly k over m, and m is at least kn over 2, if we substitute, we get that the probability of S1 is, at worst, 2 over n, 2 over the number of vertices, and the k cancels out. So that's sort of our first milestone. We've figured out the chance that we screw up in the first iteration, that we pick some edge from that crosses the cut AB, and things look good. This is a small number, right? So in general, the number of vertices might be quite big, and this says that the probability we screw up is only 2 over the number of vertices. So far, so good. Of course, this was only the first iteration. Who knows what happens later? So now that we understand the chances of screwing up in the first iteration, let's take our next baby step and understand the probability that we don't screw up in either of the first 2 iterations. That is, we're going to be interested in the following probability: the probability that we don't screw up in the first iteration nor in the second iteration. Now, you should go back to the definition of a conditional probability to realize that we can rewrite an intersection like this in terms of conditional probabilities, namely as the probability that we don't screw up in the second iteration, given that we didn't do it already, times the probability that we didn't screw up in the first iteration. Okay, so the probability that we miss all of these k vulnerable edges in the second iteration, given that we didn't contract any of them in the first iteration. Now, notice this we already have a good understanding of. On the previous slide, we gave a nice lower bound of this. We said there's a good chance that we don't screw up, probability at least 1 minus 2 to the n. And in some sense, we also have a very good understanding of this probability. We know this is 1 minus the chance that we do screw up. And what's the chance that we do screw up? Well, these k edges are still hanging out in the graph. Remember, we didn't contract any in the first iteration. That's what's given. So there are k ways to screw up. And we choose an edge to contract uniformly at random. So the total number of choices is the number of remaining edges. Now the problem is, what's nice is we have an exact understanding of this probability. This is an equality. The problem is we don't have a good understanding of this denominator. How many remaining edges are there? We have an upper bound on this. We know this is at most m minus 1. We certainly got rid of one edge in the previous iteration, but actually, if you think about it, what we need on this quantity is a lower bound. And that's a little unclear because in addition to contracting the one edge and getting that out of the graph, we might have created a bunch of self loops and deleted all of them. So it's hard to understand exactly what this quantity is. So instead, we're going to rewrite this bounded in terms of the number of remaining vertices. And of course, we know there's exactly n minus 1 vertices remaining. We took 2 in the last iteration, we contracted it down to 1. So how do we relate the number of edges to the number of vertices? Well, we do it just in exactly the same way as in the first iteration. We make a sort of more general observation. For the first iteration, we observe that every node in the original graph induces a cut. Okay, with that node on one side, the other n minus 1 edges on the other side. But in fact, that's a more general statement. Even after we've done a bunch of contractions, any single node in the contracted graph, even if it represents a union of a bunch of nodes in the original graph, we can still think of that as a cut in the original graph. Right? So if there's some supernode in the contracted graph, which is the result of fusing 12 different things together, that corresponds to a cut where those 12 nodes in the original graph are the one side A, and the other n minus 12 vertices are the other side of the cut B. Okay, so even after contractions, as long as we have at least 2 nodes left in our contracted graph, you can take any node and think of it as half of a cut, one side of a cut in the original graph. Now remember, k is the number of edges crossing our minimum cut, a comma b, so any cut in the original graph G has to have at least k crossing edges. So, since every node in the contracted graph naturally maps over to a cut in the original graph with at least k edges crossing it, that means that in the contracted graph all of the degrees have to be at least k. If you ever had a node in the contracted graph that had only, say, k minus 1 incident edges, well then you'd have a cut in the original graph with only k minus 1 edges, a contradiction. So just like in the first iteration, now that we have a lower bound on the degree of every single vertex, we can derive a lower bound on the number of edges that remain in the graph. The number of remaining edges is at least 1/2, that's because when you sum over the degrees of the vertices, you double count the edges, times the degree of each vertex, and we just argued that that's at least k in this contracted graph, times the number of vertices, and we know there's exactly n minus vertices left in the graph at this point. So now what we do is we plug this inequality, we plug this lower bound on the number of remaining edges on, and we substitute that for this denominator. So in lower bounding the denominator, we upper bound this fraction, which gives us a lower bound on 1 minus that fraction, and that's what we want. So what we find is that the probability that we don't screw up in the second iteration, given that we didn't screw up in the first iteration, where again by screwing up means picking one of these k edges crossing AB to contract, is at least 1 minus 2 over n minus 1. So that's pretty cool. We took the first iteration, we analyzed it, we showed the probability that we screw up is pretty low. We succeed with probability at least 1 minus 2 over n. In the second iteration, our success probability has dropped a little bit, but it's still looking pretty good for reasonable values of n. 1 minus 2 over n minus 1. Now, as I hope you've picked up, we can generalize this pattern to any number of iterations. So the degree of every node in the contracted graph remains at least k. The only thing which is changing is the number of vertices is dropping by 1. So extending this pattern to its logical conclusion, we get the following lower bound on the probability that the contraction algorithm succeeds. So the probability that the contraction algorithm outputs the cut AB, you'll recall we argued, is exactly the same thing as the probability that it doesn't contract anything, any of the k crossing edges, any of the set F in the first iteration, nor in the second iteration, nor in the third iteration, and so on, all the way up to the final n minus 2th iteration. Using the definition of conditional probabilities, this is just the probability that we don't screw up in the first iteration times the probability that we don't screw up in the second iteration, given that we didn't screw up in the first iteration, and so on. In the previous 2 slides, we showed that we don't screw up in the first iteration with probably at least 1 minus 2 over n, in the second iteration with probably at least 1 minus 2 over n minus 1, and of course you can guess what that pattern looks like, and that results in the following product. Now because we stop when we get down to 2 nodes remaining, the last iteration in which we actually make a contraction there are 3 nodes, and in the second to last iteration in which we make a contraction there are 4 nodes. So that's where these last two terms come from. Rewriting, this is just n minus 2 over n times n minus 3 over n minus 1, and so on. And now something very cool happens, which is massive cancellation. And to this day, this is always just incredibly satisfying to be able to cross out so many terms. So you get an n minus 2 crossing out here. It's going to be a pair of n minus 3s that get crossed out, n minus 4s, and so on. On the other side, there's going to be a pair of 4s that get crossed out, and a pair of 3s that get crossed out. And we'll be left with only the two largest terms on the denominator and the two smallest terms in the numerator, which is exactly 2 over n times n minus 1. And to keep things simple, among friends, let's just be sloppy and lower bound this by 1 over n squared. So that's it. That's our analysis of the success probability of Karger's contraction algorithm. Pretty cool, pretty slick, huh? Okay, I'll concede, probably you're thinking, hey, wait a minute. We're analyzing the probability that the algorithm succeeds, and we're thinking of the number of vertices n as being big. So what we see here is a success probability of only 1 over n squared, and that kind of sucks. So that's a good point. Let me address that. Problem. This is a low success probability. So that's disappointing. So why are we talking about this algorithm or this analysis? Well, here's something I want to point out. Maybe this is not so good. 1 in n squared, you're going to succeed. But this is still actually shockingly high for an oblivious algorithm, which honestly seems to be doing almost nothing. This is a non-trivial lower bound, a non-trivial success probability, because, don't forget, there's an exponential number of cuts in the graph. So if you try to just pick a random cut, i.e. you put every vertex 50-50 left or right, you'd be doing way worse than this. You'd have a success probability of like 1 over 2 to the n. So this is way, way better than that. And the fact that it's an inverse polynomial means that using repeated trials, we can turn a success probability that's incredibly small into a failure probability that's incredibly small. So let me show you how to do that next. So we're going to boost the success probability of the contraction algorithm in, if you think about it, a totally obvious way. We're going to run it a bunch of times, each one independently, using a fresh batch of random coins. And we're just going to remember the smallest cut that we ever see. And that's what we're going to return, the best of a bunch of repeated trials. Now the question is, how many trials are we going to need before we're pretty confident that we actually find the min cut we're looking for? To answer this question rigorously, let's define some suitable events. So by TI, I mean the event that the ith trial succeeds. That is, the ith time that we run the contraction algorithm, it does output the desired min cut A comma B. For those of you that watched the part 2 of the probability review, I said a rule of thumb for dealing with independence is that you should maybe, as a working hypothesis, assume random variables are dependent unless they're explicitly constructed to be independent. So here's a case where we're just going to define the random variables to be independent. We're just going to say that we run the contraction algorithm over and over again with fresh randomness. So they're going to be independent trials. Now we know that the probability that a single trial fails could be pretty big. Could be as big as 1 minus 1 over n squared. But here now with repeated trials, we're only in trouble if every single trial fails. If even one succeeds, then we find a min cut. So a different way of saying that is we're interested in the intersection of T1 and T2 and so on. That's the event that every single trial fails. And now we use the fact that the trials are independent. So the probability that all of these things happen is just the product of the relevant probabilities. So the product from I equal 1 to capital N of the probability of not TI. Recall that we argued that the success probability of a single trial was bounded below by 1 over n squared. So the failure probability is bounded above by 1 minus 1 over n squared. So since that's true for each of the capital N terms, we get an overall failure probability for all capital N trials of 1 minus 1 over little n squared raised to the capital N. All right, so that's a little calculation. Don't lose sight of why we're doing the calculation. We want to answer this question. How many trials do we need? How big does capital N need to be before we are confident that we get the answer that we want? Well, to answer that question, I need a quick calculus fact, which is both very simple and very useful. So for all real numbers x, we have the following inequality. 1 plus x is bounded above by e to the x. So I'll just give you a quick proof by a picture. So first think about the line 1 plus x. What does that cross through? Well, that crosses through the points when x is minus 1, y is 0, and when x is 0, y is 1. And it's a line, so this looks like this blue line here. What does e to the x look like? Well, if you substitute x equals 0, it's going to be 1. So in fact, the two curves kiss each other at x equals 0. But exponentials grow really quickly. So as you jack up x to higher positive numbers, it becomes very, very steep. And for x negative numbers, it stays non-negative the whole way. So this sort of flattens out for the negative numbers. So pictorially, and I encourage you to type this into your own favorite graphing program, you see that e to the x bounds above everywhere the line 1 plus x. For those of you that want something more rigorous, there's a bunch of ways to do it. For example, you can look at the Taylor expansion of e to the x at the point 0. What's the point? The point is this allows us to do some very simple calculations on our previous upper bound on the failure probability by working with exponentials instead of working with these ugly 1 minus whatever's raised to the whatever term. So let's combine our upper bound from the previous slide with the upper bound provided by the calculus fact. And to be concrete, let's substitute some particular number of capital N. So let's use little n squared trials, where little n is the number of vertices of the graph. In which case, the probability that every single trial fails to recover the cut a comma b is bounded above by e to the minus 1 over n squared. That's using the calculus fact applied with x equal to minus 1 over n squared. And then we inherit the capital N in the exponent, which we just instantiated to little n squared. So of course the n squareds are going to cancel. This is going to give us e to the minus 1, also known as 1 over e. So if we're willing to do little n squared trials, then our failure probability has gone from something very close to 1 to something which is more like, say, 30 some odd %. Now, once you get to a constant success probability, it's very easy to boost it further by just doing a few more trials. So if we just add a natural log factor, so instead of little n squared trials, we do little n squared times the natural log of little n. Now the probability that everything fails is bounded above by the 1 over e that we had last time, but still with a residual natural log of n up top, and this is now merely 1 over n. So I hope it's clear what happened. We took a very simple, very elegant algorithm that almost always didn't do what we want. It almost always failed to output the cut AB. It did it with only probability 1 over little n squared. But 1 over little n squared is still big enough that we can boost it so that it almost always succeeds just by doing repeated trials. And the number of repeated trials that we need is the reciprocal of its original success probability boosted by a further logarithmic factor. So that transformed this almost always failing algorithm into an almost always succeeding algorithm. And that's a more general lesson, more general algorithmic technique, which is certainly worth remembering. Let me conclude with a couple comments about the running time. This is probably the first algorithm of the course where we haven't obsessed over just what the running time is. Now that said, it's simple enough, it's not hard to figure out what it is, but it's actually not that impressive, and that's why I haven't been obsessing over it. This is not almost linear. This is not a for-free primitive as I've described it here. So it's certainly a polynomial time algorithm. Its running time is bounded above by some polynomial in n and m, so that's way better than the exponential time you get from brute force search through all 2 to the n possible cuts. But it is certainly, the way I've described it, you've got to do n squared trials plus a log factor, which I'm not even going to bother writing down. And also, each trial, well, at the very least, you look at all the edges, so that's going to be another factor of m. So this is a bigger polynomial than in almost any of the algorithms that we're going to see. Now, I don't want to undersell this application of random sampling to computing cuts, because I've just shown you the simplest, most elegant, most basic, but therefore also the slowest implementation of using contractions to compute cuts. There's been follow-up work with a lot of extra optimizations, in particular doing stuff much more clever than just repeated trials. So basically using work that you did in previous trials to inform how you look for cuts in subsequent trials, and you can shave large factors off of the running time. So there are much better implementations of this randomized contraction algorithm than the one I'm showing you here. Those are, however, outside the course scope of this course. So in this short optional video, really just for fun, I want to point out an interesting consequence that the contraction algorithm has about a problem that's in pure graph theory. So to motivate the question, I want to remind you of something that we discussed in passing, which is that a graph may have more than one minimum cut. So there may be distinct cuts which are tied for the fewest number of crossing edges. For a concrete example, you could think about a tree. So if you just look at a star graph that is hubs and spokes, it's evident that if you isolate any leaf by itself, then you get a minimum cut with exactly one crossing edge. In fact, if you think about it for a little while, you'll see that in any tree, you'll have n-1 different minimum cuts, each with exactly one crossing edge. The question concerns counting the number of minimum cuts. Namely, given that a graph might have more than one minimum cut, what is the largest number of minimum cuts that a graph with n vertices can have? We know the answer is at least n-1. We already discussed how trees have n-1 distinct minimum cuts. We know the answer is at most something like 2 to the n because a graph only has roughly 2 to the n cuts. In fact, the answer is both very nice and wedged in between. So the answer is exactly n choose 2, where n is the number of vertices. This is also known as n times n-1 divided by 2. So it can be bigger than it is in trees, but not a lot bigger. In particular, undirected graphs have only polynomially many minimum cuts. And that's been a useful fact in a number of different applications. So I'm going to prove this fact to you. All I need is one short slide on the lower bound, and then one slide for the upper bound, which follows from properties of the random contraction algorithm. So for the lower bound, we don't have to look much beyond our trees example. We're just going to look at cycles. So for any value of n, consider the n cycle. So here, for example, is the n cycle with n equal to 8. That would be an octagon. And the key observation is that just like in a tree, how removing each of the n-1 edges breaks the tree into 2 pieces and defines a cut, with a cycle, if you remove just one edge, you don't get a cut. The thing remains connected. But if you remove any pair of edges, then that induces a cut of the graph corresponding to the 2 pieces that remain. No matter which pair of edges you remove, you get a distinct pair of groups, distinct cuts. So ranging over all n choose 2 choices of pairs of edges, you generate n choose 2 different cuts. Each of those cuts has exactly 2 crossing edges, and it's easy to see that's the fewest possible. So that's the lower bound, which was simple enough. Let's now move on to the upper bound, which a purely combinatorial fact will follow from an algorithm. So consider any graph that has n vertices, and let's think about the different minimum cuts of that graph. What we're going to use is that the analysis of the contraction algorithm proceeded in a fairly curious way. So remember how we defined the success probability of the contraction algorithm? We fixed up front some min cut a comma b. And we defined the contraction algorithm, the basic contraction algorithm, before the repeated trials. We defined the contraction algorithm as successful if and only if it output the minimum cut a comma b that we designated up front. If it output some other min cut, we didn't count it. We said, nope, that's a failure. So we actually analyzed a stronger property than what we were trying to solve, which is outputting a given min cut ab rather than just any old min cut. So how is that useful? Well, let's apply it here. For each of these t minimum cuts of this graph, we could think about the probability that the contraction algorithm outputs that particular min cut. So we can instantiate the analysis with a particular minimum cut, ai, bi, and what we proved in the analysis is that the probability that the algorithm outputs the cut ai, bi, not just any old min cut, but in fact this exact cut, ai comma bi, is bounded below by, in the end we made a sloppy inequality. We said it's at least 1 over n squared, but if you go back to the analysis, you'll see that it was in fact 2 over n times n minus 1 also known as 1 over n choose 2. So instantiating the contraction algorithm success probability analysis, without all of the repeated trials business, we show that for each of these t cuts, for each fixed cut AI BI, the probability that this algorithm outputs that particular cut is at least 1 over n choose 2. Let's introduce a name for this event, the event that the contraction algorithm outputs the ith min cut. Let's call this SI. The key observation is that the SIs are disjoint events. Remember, an event is just a subset of stuff that could happen. So one thing that could happen is that the algorithm outputs the ith min cut. And by disjoint, we just mean that there's no outcome that's in a given pair of events. And that's because the contraction algorithm at the end of the day, once it makes its coin flips, it outputs a single cut. These are distinct cuts. It can only output at best one of them. Why is it important that these SIs are disjoint events? Well, with disjoint events, the probabilities add. The probability of the union of a bunch of disjoint events is the sum of the probabilities of the constituent events. If you want to think about this pictorially, you can just draw a big box denoting everything that could happen, omega, and then these SIs are just these blobs that don't overlap. So S1, S2, S3, and so on. Now the sum of probabilities of disjoint events can sum to, at most, 1. Right? The probability of all of omega is 1, and these SIs have no overlap and are packed into omega, so the sum of their probabilities can only be smaller. Writing that formally, we have that the sum of their probabilities, which we can lower bound by the number of different events, and remember there are t, different min cuts for some parameter t. For each min cut AI BI, a lower bound on the probability that that gets spit out as output is 1 over n choose 2. So a lower bound on the sum of all of these probabilities is the number of them t times the probability, lower bound, 1 over n choose 2. And this has got to be at most 1. Rearranging, what do we find? T, the number of different min cuts, is bounded above by n choose 2. Exactly the lower bound provided by the n cycle. The n cycle has n choose 2 distinct minimum cuts. No other graph has more. Every graph has only a polynomial number, indeed at most a quadratic number of minimum cuts. So let's talk about the absolutely fundamental problem of searching a graph and the very related problem of finding paths through graphs. So why would one be interested in searching a graph or figuring out if there's a path from point A to point B? Well, there's many reasons. I'm going to give you a highly non-exhaustive list on this slide. So let me begin with a very sort of obvious and literal example, which is if you have a physical network. Then often you want to make sure that the network is fully connected in the sense that you can get from any starting point to any other point. So for example, think back to the phone network. It would have been a disaster if callers from California could only reach callers in Nevada, but not their family members in Utah. So obviously a minimal condition for functionality of something like a phone network is that you can get from any one place to any other place. Similarly for road networks within a given country, and so on. It can also be fun to think about other non-physical networks and ask if they're connected. So one network that's fun to play around with is the movie network. So this is the graph where the nodes correspond to actors and actresses, and you have an edge between two nodes if they played a role in a common movie. So this is going to be an undirected graph where the edges correspond to not necessarily co-starring, but both the actors appearing at least at some point in the same movie. So versions of this movie network you should be able to find publicly available on the web, and there's lots of fun questions you can ask about the movie network, like for example, what's the minimum number of hops, where a hop here again is a movie that two people both played a role in. The minimum number of hops or edges you can get from one actor to another actor. So perhaps the most famous statistic that's been thought about with the movie network is the Bacon number. So this refers to the fairly ubiquitous actor Kevin Bacon, and the question, the Bacon number of an actor is defined as the minimum number of hops you need in this movie graph to get to Kevin Bacon. So for example, you could ask about John Hamm, also known as Don Draper from Mad Men, and you could ask how many edges do you need on a path through the movie graph to get to Kevin Bacon, and it turns out that the answer is 1. two edges. You need one intermediate point, namely Colin Firth. And that's because Colin Firth and Kevin Bacon both starred in the Adam McGoyan movie Where the Truth Lies, and John Hamm and Colin Firth were both in the movie A Single Man. So that would give John Hamm a Bacon number of 2. So these are the kind of questions you can ask about connectivity, not just in physical networks like telephone and telecommunication networks, but also logical networks about pairwise relationships between objects more generally. So the Bacon number is fundamentally not just about any path, but actually shortest paths, the minimum number of edges you need to traverse to get from one actor to Kevin Bacon. And shortest paths also have a very practical use that you might use yourself in driving directions. So when you use a website or a phone app and you ask for the best way to get from where you are now to, say, some restaurant where you're going to have dinner, obviously you're trying to find some kind of path through a network, through a graph, and indeed often you want the shortest path, perhaps in mileage or perhaps in anticipated travel time. Now I realize that when you're thinking about paths and graphs, it's natural to focus on sort of very literal paths and quite literal physical networks. Things like routes through a road network or paths through the internet and so on. But you should really think more abstractly as a path as just a sequence of decisions, taking you from some initial state to some final state. And it's this abstract mentality which is what makes graph search so ubiquitous and feels like artificial intelligence, where you want to formulate a plan of how to get from an initial state to some goal state. So to give a simple recreational example, you could imagine just trying to understand how to compute automatically a way to fill in a Sudoku puzzle so that you solve the puzzle correctly. So you might ask, what is the graph that we're talking about when we want to solve a Sudoku puzzle? Well, this is going to be a directed graph, where here the nodes correspond to partially completed puzzles. So for example, at one node of this extremely large graph, perhaps 40 out of the 81 cells are filled in with some kind of number. And now, again, remember, a path is supposed to correspond to a sequence of decisions. So what are the actions that you take in solving Sudoku? Well, you fill in a number into a square. So an edge, which here is going to be directed, is going to move you from one partially completed puzzle to another, where one previously empty square gets filled in with one number. And of course, then the path that you're interested in computing, or what you're searching for when you search this graph, you begin with the initial state of the Sudoku puzzle, and you want to reach some goal state where the Sudoku puzzle is completely filled in without any violations of the rules of Sudoku. And of course, it's easy to imagine millions of other situations where you want to formulate some kind of plan like this. Like, for example, if you have a robotic hand and you just want to grasp some object, you need to think about exactly how to approach the object with this robotic hand so that you can grab it without, for example, first knocking it over. And you can think of millions of other examples. Another thing which turns out to be closely related to graph search, as we'll see, and has many applications in its own right, is that of computing connectivity information about graphs. So in particular, the connected components. So this, especially for undirected graphs, corresponds to the pieces of a graph. We'll talk about these topics in their own right, and I'll give you applications for them later. So for undirected graphs, I'll briefly mention an easy clustering heuristic you can derive out of computing connected components. For directed graphs, where the very definition of computing components is a bit more subtle, I'll show you applications to understanding the structure of the web. So these are a few of the reasons why it's important for you to understand how to efficiently search graphs. It's a fundamental and widely applicable graph primitive. And I'm happy to report that in this section of the course, pretty much any questions we want to answer about graph search, computing connected components, and so on, there's going to be really fast algorithms to do it. So this will be a part of the course where there's lots of what I call for-free primitives, processing steps, subroutines you can run without even thinking about it. All of these algorithms we're going to discuss in the next several lectures are going to run in linear time, and they're going to have quite reasonable constants. So they're really barely slower than reading the input. So if you have a graph and you're trying to reason about it, you're trying to make sense about it, you should, in some sense, feel free to apply any of these subroutines we're going to discuss to try and glean some more information about what they look like, how you might use the network data. There's a lot of different approaches to systematically searching a graph. So there's many methods. In this class, we're going to focus on two very important ones, namely breadth-first search and depth-first search. But all of the graph search methods share some things in common. So on this slide, let me just tell you the high-order bits of really any graph search algorithm. So graph search subroutines generally are passed as input a starting vertex from which the search originates. So that's often called a source vertex. And your goal then is to find everything findable from this source vertex. And obviously you're not going to find anything that you can't find, that's not findable. What do I mean by findable? I mean there's a path from the starting point to this other node. So for any other node to which you can get along a path from the starting point, you should discover it. So for example, if you're given an undirected graph that has 3 different pieces, like this one I'm drawing on the right, and perhaps S is this leftmost node here, then the findable vertices starting from S, i.e. the ones to which you can reach from a path to S, is clearly precisely these 4 vertices. So you would want graph search to automatically discover and efficiently discover these 4 vertices if you started at S. You could also think about a directed version of the exact same graph, where I'm going to direct the vertices like so. So now the definition of the findable nodes is a little bit different. We're only expecting to follow arcs forward along the forward direction. So we should only expect at best to find all of the nodes that you can reach by following a succession of forward arcs. That is, any node that there's a path to from S. So in this case, these 3 nodes would be the ones we'd be hoping to find. This blue node to the right, we would no longer expect to find, because the only way to get there from S is by going backward along arcs, and that's not what we're going to be thinking about in our graph searches. So we want to find everything findable, i.e. that we can get to along paths, and but we want to do it efficiently, and efficiently means we don't explore anything twice, right? So the graph has m arcs, m edges, and n nodes or n vertices, and really we want to just look at each piece of the graph only once or a small constant number of times. So we're looking for running time, which is linear in the size of the graph, that is big O of m plus n. Now when we were talking about representing graphs, I said that in many applications it's natural to focus on connected graphs, in which case m is going to dominate n. You're going to have at least as many edges as nodes, essentially. But connectivity is the classic case where you might have the number of edges being much smaller than the number of nodes. There might be many pieces, and the whole point of what you're trying to do is discover them. So for this sequence of lectures where we talk about graph search and connectivity, we will usually write m plus n. We'll think that either one could be bigger or smaller than the other. So let me now give you a generic approach to graph search. So it's going to be underspecified. There'll be many different ways to instantiate it. 2 particular instantiations will get us breadth first search and depth first search. But here's just a general systematic method for finding everything findable without exploring anything more than once. So motivated by the second goal, the fact that we don't want to explore anything twice, with each node, with each vertex, we're going to remember whether or not we've explored it before. So we just need one Boolean per node, and we'll initialize it by having everything unexplored, except S, our starting point, will have it start off as explored. And it's useful to think of the nodes thus far as being in some sense territory conquered by the algorithm. And then there's going to be a frontier in between the conquered and unconquered territory, and the goal of the generic algorithm is at each step we supplement the conquered territory by one new node, assuming that there is one adjacent to the territory we've already conquered. So, for example, in this top example with the undirected network, initially the only thing we've explored is the starting point S. So that's sort of our home base, it's all that we have conquered so far. And then in our main while loop, which we iterate as many times as we can until we don't have any edges meeting the following criterion, we look for an edge with one endpoint that we've already explored, one endpoint inside the conquered territory and then the other endpoint outside. So this is how we can, in one hop, supplement the number of nodes we've seen by one new one. If we can't find such an edge, then this is where the search stops. If we can find such an edge, well then we suck V into the conquered territory, we think of it being explored, and we return to the main while loop. So for example, in this example on the right, we start with the only explored node being S. Now, there's actually 2 edges that cross the frontier, in the sense one of the endpoints is explored, namely one of the endpoints is S, and the other one is some other vertex, right? There's these two edges to the left, 2 vertices adjacent to S. So in this algorithm, we pick either one. It's underspecified which one we pick, but maybe we pick the top one, and so then all of a sudden this second top vertex is now also explored. So the conquered territory is the union of them. And so now we have a new frontier. So now again we have 2 edges that cross from the explored nodes to the unexplored nodes. These are the edges that are in some sense going from northwest to southeast. Again, we pick one of them. It's not clear how. The algorithm doesn't tell us. We just pick any of them. So maybe, for example, we pick this rightmost edge crossing the frontier. Now the rightmost edge of these rightmost vertex of these 4 is explored. So our conquered territory is the top 3 vertices. And now again, we have 2 edges crossing the frontier, the 2 edges that are incident to the bottom node. We pick one of them, not clear which one, maybe this one. And now the bottom node is also explored. And now there are no edges crossing the frontier. So there are no edges who on the one hand have one endpoint being explored and the other endpoint being unexplored. So these will be the 4 vertices, as one would hope, that the search will explore started from S. More generally, the claim is that this generic graph search algorithm does what we wanted. It finds everything findable from the starting point, and moreover, it doesn't explore anything twice. I think it's fairly clear that it doesn't explore anything twice, right? As soon as you look at a node for the first time, you suck it into the conquered territory, never to look at it again. Similarly, as soon as you look at an edge, you suck it in. But when we explore breadth and depth first search, we'll be more precise about the running time and exactly what I mean by you don't explore something twice. So at this level of generality, I just want to focus on the first point, that any way you instantiate this search algorithm, it's going to find everything findable. So what do I really mean by that? The formal claim is that at the termination of this algorithm, the nodes that we've marked explored are precisely the ones that can be reached via a path from S. That's the sense in which the algorithm explores everything that could potentially be findable from the starting point S. And one thing I want to mention is that this claim and the proof I'm going to give of it holds whether or not G is an undirected graph or a directed graph. In fact, almost all of the things that I'm going to say about graph search, and in particular about breadth first search and depth first search, work in essentially the same way, either in undirected graphs or directed graphs. The obvious difference being in an undirected graph, you can traverse an edge in either direction. In a directed graph, we're only supposed to traverse it in the forward direction, from the tail to the head. The one big difference between undirected and directed graphs is when we do connectivity computations, and I'll remind you when we get to that point which one we're talking about. Okay? But for the most part, when we just talk about basic graph search, it works essentially the same way, whether it's undirected or directed. So keep that in mind. All right, so why is this true? Why are the nodes that get explored precisely the nodes for which there's a path to them from S? Well, one direction is easy, which is you can't find anything which is not findable. That is, if you wind up exploring a node, the only reason that can happen is because you traversed a sequence of edges that got you there. And that sequence of edges obviously defines a path from S to V. If you really want to be pedantic about the forward direction, that explored nodes have to have paths from S, then you can just do an easy induction. And I'll leave this for you to check if you want in the privacy of your own home. So the important direction of this claim is really the opposite. Why is it that no matter how we instantiate this generic graph search procedure, it's impossible for us to miss anything? That's the crucial point. We don't miss anything that we could in principle find via a path. Well, we're going to proceed by contradiction. So what does that mean? We're going to assume that the statement that we want to prove is true is not true, which means that it's possible that G has a path from S to V, and yet somehow our algorithm misses it, doesn't mark it as explored. Right? That's the thing we're really hoping doesn't happen. So let's suppose it does happen and then derive a contradiction. So suppose G does have a path from S to some vertex V, call the path P. I'm going to draw the picture for an undirected graph, but the situation would be same in the directed case. So there's a bunch of hops, there's a bunch of edges, and then eventually this path ends at V. Now, the bad situation, the situation from which we want to derive a contradiction, is that V is unexplored at the end of this algorithm. So let's take stock of what we know. S, for sure, is explored. Right? We initialize the search procedure so that S is marked as explored. V, by hypothesis, in this proof by contradiction, is unexplored. So S is explored, V is unexplored. So now imagine we, just in our heads, as a thought experiment, we traverse this path P. We start at S and we know it's explored. We go to the next vertex. It may or may not have been explored. We're not sure. We go to the third vertex again. Who knows? Might be explored, might be unexplored, and so on. But by the time we get to V, we know it's unexplored. So we start at S, it's been explored. We get to V, it's been unexplored. So at some point, there's some hop along this path P from which we move from an explored vertex to an unexplored vertex. There has to be a switch at some point, because at the end of the day, at the end of the path, we're at an unexplored node. So consider the first edge, and there must be one, that we switched from being at an explored node to being at an unexplored node. So I'm going to call the endpoints of this purported edge U and W, where U is the explored one and W is the unexplored one. Now, for all we know, U could be exactly the same as S. That's a possibility. Or for all we know, W could be the same as V. That's also a possibility. In the picture, I'll draw it as if this edge UX was somewhere in the middle of this path. But again, it may be at one of the ends. That's totally fine. But now in this case, there's something I need you to explain to me. How is it possible that, on the one hand, our algorithm terminated, and on the other hand, there's this edge, U comma X, where U has been explored and X has not been explored? That, my friends, is impossible. Our generic search algorithm does not give up. It does not terminate unless there are no edges where the one endpoint is explored and the other endpoint is unexplored. As long as there's such an edge, it's going to suck in that unexplored vertex into the conquered territory. It's going to keep going. So the upshot is there's no way that our algorithm terminated with this picture, with there being an edge UX, U explored, X unexplored. So that's the contradiction. This contradicts the fact that our algorithm terminated with V unexplored. So that is a general approach to graph search. So that, I hope, gives you the flavor of how this is going to work. But now there's two particular instantiations of this generic method that are really important and have their own suites of applications. So we're going to focus on breadth-first search and depth-first search. We'll cover them in detail in the next couple of videos. I want to give you the highlights to conclude this video. Now let me just make sure it's clear where the ambiguity in our generic method is, why we can have different instantiations of it that potentially have different properties and different applications. The question is, at a given iteration of this while loop, what do you got? You got your nodes that you've already explored, so that includes S plus probably some other stuff. And then you've got your nodes that are unexplored. And then you have your crossing edges, right? So they're edges with one point in each side. And for an undirected graph, there's no orientation to worry about. These crossing edges just have one endpoint on the explored side, one endpoint on the unexplored side. In the directed case, you focus on edges where the tail of the edge is on the explored side and the head of the edge is on the unexplored side. So they go from the explored side to the unexplored side. And the question is, in general, in an iteration of this while loop, there's going to be many such crossing edges. There are many different unexplored nodes we could go to next. And different strategies for picking the unexplored node to explore next leads us to different graph search algorithms with different properties. So the first specific search strategy we're going to study is breadth-first search, colloquially known as BFS. So let me tell you sort of the high-level idea and applications of breadth-first search. So the goal is going to be to explore the nodes in what I call layers. So the starting point S will be in its own layer, layer 0. The neighbors of S will constitute layer 1. And then layer 2 will be the nodes that are neighbors of layer 1, but that are not already in layer 0 or layer 1, and so on. So layer I plus 1 is the stuff next to layer I that you haven't already seen yet. You can think of this as a fairly cautious and tentative exploration of the graph. And it's going to turn out that there's a close correspondence between these layers and shortest path distances. So if you want to know the minimum number of hops, the minimum number of edges you need in a path to get from point A to point B in a graph, the way we wanted to know the fewest number of edges in the movie graph necessary to connect John Hamm to Kevin Bacon, that corresponds directly to these layers. So if a node is in layer I, then you need I edges to get from S to I in the graph. Once we discuss breadth-first search, we'll also discuss how to compute the connected components, or the different pieces, of an undirected graph. Turns out this isn't that special to breadth-first search. You can use any number of graph search strategies to compute connected components in undirected graphs, but I'll show you how to do it using a simple looped version of breadth-first search. And we'll be able to do this stuff in the linear time that we want, the very ambitious goal of getting linear time. To get the linear time implementation, you do want to use the right data structure, but it's a super simple data structure, something probably you've seen in the past, namely a queue, so something that's first in, first out. So the second search strategy that's super important to know is depth-first search, also known as DFS to its friends. Depth-first search has a rather different feel than breadth-first search. It's a much more aggressive search where you immediately try and plunge as deeply as you can. It's very much in the spirit of how you might explore a maze, where you go as deeply as you can, only backtracking when absolutely necessary. Depth-first search will also have its own set of applications. It's not, for example, very useful for computing shortest path information, but especially in directed graphs, it's going to do some remarkable things for us. So in a directed acyclic graph, so a directed graph with no directed cycles, it will give us what's called the topological ordering. So it'll sequence the nodes in a linear ordering from the first to the last so that all of the arcs of the directed graph go forward. So this is useful, for example, if you have a number of tasks that have to get completed with certain precedence constraints. Like, for example, you have to take all of the classes in your undergraduate major and there are certain prerequisites. Topological ordering will give you a way in which to do it, respecting all of the prerequisites. And finally, where for undirected graphs, it doesn't really matter whether you use BFS or DFS to compute connected components. In directed graphs, where even defining connected components is a little tricky, it turns out depth-first search is exactly what you want. That's what you're going to get a linear time implementation for computing the right notion of connected components in the directed graph case. Time-wise, both of these are superb strategies for exploring a graph. They're both linear time with very good constants. So depth-first search again, we're going to get O of m plus n time in a graph with m edges and n vertices. You do want to use a different data structure reflecting the different search strategy. So here, because you're exploring aggressively, as soon as you get to a node, you immediately start exploring its neighbors. You want a last in, first out data structure, also known as a stack. Depth-first search also admits a very elegant recursive formulation, and in that formulation, you don't even need to maintain a stack data structure explicitly. The stack is implicitly taken care of in the recursion. So that concludes this overview of graph search, both what it is, what our goals are, what kind of applications they have, and two of the most common strategies. The next couple of videos are going to explore these search strategies as well as a couple of these applications in greater depth. So in this lecture, we're going to drill down into our first specific search strategy for graphs and also explore some applications, namely breadth-first search. So let me remind you the intuition and applications of breadth-first search. The plan is to systematically explore the nodes of this graph, beginning with the given starting vertex in layers. So let's think about the following example graph, where S is the starting point for our breadth-first search. So the start vertex S will constitute the first layer. So we'll call that L0. And then the neighbors of S are going to be the first layer. And so those are the vertices that we explore just after S. So those are L1. Now the second layer is going to be the vertices that are neighboring vertices of L1 but are not themselves in L1, or for that matter, L0. So that's going to be C and D. That's going to be the second layer. Now you'll notice, for example, S is itself a neighbor of these nodes in layer 1, but we've already counted that in the previous layer, so we don't count S toward L2. And then finally, the neighbors of L2, which are not already put in some layer, is E. So that'll be layer 3. Again, notice C and D are neighbors of each other, but they've already been classified in layer 2, so that's where they belong, not in layer 3. So that's the high-level picture of breadth-first search you should have. We'll talk about how to actually precisely implement it on the next slide. Again, just a couple of the things that you can do with breadth-first search, which we'll explore in this video, is computing shortest paths. So it turns out shortest path distances correspond precisely to these layers. So, for example, if you had as S, you had that as the Kevin Bacon node in the movie graph, then John Hamm would pop up in the second layer from the breadth-first search from Kevin Bacon. I'm also going to show you how to compute the connected components of an undirected graph, that is, compute its pieces. We'll do that in linear time. And for this entire sequence of videos on graph primitives, we will be satisfied with nothing less than the holy grail of linear time. And again, remember, in a graph, you have two different size parameters, the number of edges m and the number of nodes n. For these videos, I'm not going to assume any relationship between m and n. Either one could be bigger. So linear time is going to mean O of m plus n. So let's talk about how you'd actually implement breadth-first search in linear time. So the subroutine is given as input both a graph, G. I'm going to explain this as if it's undirected, but this entire procedure will work in exactly the same way for a directed graph. Again, obviously, in an undirected graph, you can traverse an edge in either direction. For a directed graph, you have to be careful only to traverse arcs in the intended direction, from the tail to the head. That is, traverse them forward. So as we discussed when we talked about just generic strategies for graph search, we don't want to explore anything twice. That would certainly be inefficient. So we're going to keep a Boolean at each node, marking whether we've already explored it or not. And by default, we're just going to assume that nodes are unexplored. They're only explored if we explicitly mark them as such. So we're going to initialize the search with the starting vertex S. So we mark S as explored, and then we're going to put that in what I was previously calling conquered territory, the nodes we've already started to explore. So to get linear time, we're going to have to manage those in a slightly non-naive, but pretty straightforward way, namely via a queue, which is a first in, first out data structure that I assume you've seen. If you've never seen a queue before, please look it up in a programming textbook or on the web. But basically a queue is just something where you can add stuff to the back in constant time, and you can take stuff from the front in constant time. You can implement these, for example, using a doubly linked list. Now recall that in the general systematic approach to graph search, the trick was to, in each iteration of some while loop, to add one new vertex to the conquered territory, to identify one unexplored node that is now going to be explored. So that while loop is going to translate into one in which we just check if the queue is non-empty. So we're assuming that the queue data structure supports that query in constant time, which is easy to implement. And if the queue is non-empty, we remove a node from it. And because it's a queue, removing nodes from the front is what you can do in constant time. So call the node that you get out of the queue V. So now we're going to look at V's neighbors, vertices with which it shares edges, and we're going to see if any of them have not already been explored. So if W is something we haven't seen before, if it's unexplored, that means it's in the unconquered territory, which is great. So we have a new victim. We can mark W as explored. We can put it in our queue, and we've advanced the frontier. And now we have one more explored node than we did previously. And again, a queue, by construction, it supports adding constant time additions at the end of the queue. So that's where we put W. So let's see how this code actually executes in the same graph that we were looking at in the previous slide. And what I'm going to do is I'm going to number the nodes in the order in which they are explored. So obviously the first node to get explored is S. That's where the queue starts. So now when we follow the code, what happens? Well, in the first iteration of the while loop, we ask, is the queue empty? No, it's not, because S is in it. So we remove, in this case, the only node of Q. It's S. And then we iterate over the edges incident to S. Now there are two of them. There's the edge between S and A, and there's the edge between S and B. And again, this is still a little underspecified in the sense that the algorithm doesn't tell us which of those two edges we should look at. Turns out it doesn't matter. Either of those is a valid execution of breadth first search. But for concreteness, let's suppose that of the two possible edges, we look at the edge S comma A. So then we ask, has A already been explored? No, it hasn't. This is the first time we've seen it. So we say, oh, goody, this is sort of new grist for the mill. So we can add A to the queue at the end, and we mark mark A as explored. So A is going to be the second vertex that we mark. So after marking A as explored and adding it to the queue, so now we go back to the for loop, and so now we move on to the second edge incident to S. That's the edge between S and B. So we ask, have we already explored B? Nope, this is the first time we've seen it, so now we do the same thing with B. So B gets marked as explored, it gets added to the queue at the end. So the queue at this juncture has first a record for A, because that was the first one we put in it after we took S out, and then B follows A in the queue. And again, depending on the execution, this could go either way, but for concreteness, I've done it so that A got added before B. So at this point, this is what the queue looks like. So now we go back up to the while loop. We say, is the queue empty? Certainly not. It actually has two elements. Now we remove the first node from Q. In this case, that's the node A. That was the one we put in before the node B. And so now we say, well, let's look at all of the edges incident to A. And in this case, A has two incident edges. It has one that it shares with S, and it has one that it shares with C. And so if we look at the edge between A and S, then we'd be asking in the if statement, has S already been explored? Yes, it has. That's where we started. So there's no reason to do anything with S. That's already been taken out of the queue. So in this for loop for A, there's two iterations. One involves the edge with S, and that one we completely ignore. But then there's the other edge that A shares with C, and C we haven't seen yet. So at that part of the for loop, we say, aha, C is a new thing, new node we can mark as explored and put in the queue. So that's going to be our number 4. And so now how is the queue changed? Well, we got rid of A, and so now B is in the front, and we added C at the end. And so now the same thing happens. We go back to the while loop, the queue is not empty. We take off the first vertex. In this case, that's going to be B. B has 3 incident edges. It has one incident to S, but that's irrelevant. We've already seen S. It has one incident to C. That's also irrelevant. That's also relevant because we've already seen C. True, we just saw it very recently, but we've already seen it. But the edge between B and D is new, and so that means we can take the node D, mark it as explored, and add it to the queue. So D is going to be the 5th one that we see. And now the queue has the element C followed by D. So now we go back to the while loop, and we take C off of the Q. It again has 4 now edges. The one with A is irrelevant, we've already seen A. The one with B is irrelevant, we've already seen B. The one with D is irrelevant, we've already seen D. But we haven't seen E yet. So when we get to the part of the for loop of the edge between C and E, we say, aha, E is new. So E will be the 6th and final vertex to be marked as explored. And that will get added at the end of the Q. So then in the final 2 iterations of the while loop, the D is going to be removed. We'll iterate through its 3 edges. None of those will be relevant because we've seen all of the other 3 endpoints. And then we'll go back to the while loop and we'll get rid of E. E is irrelevant because it has 2 edges. We've already seen the other endpoints. And now we go back to the while loop. The Q is empty and we stop. And that is breadth first search. And to see how this simulates the notion of the layers that we were discussing in the previous slide, notice that the nodes are numbered according to the layer that they're in. So S was layer 0, and then the 2 nodes that S caused to get added to the Q, the A and the B, are numbered 2 and 3. And the edges of layer 3 are precisely the ones, the edges of layer 2 are precisely the ones that got added to the Q while we were processing the nodes from layer 1. That is, C and D are precisely the nodes that got added to the Q while we were processing A and B. So this is level 0, level 1, and level 2. E is the only node that got added to the queue while we were processing layer 2, the vertices C and D. So E will be the 3rd layer. So in that sense, by using a first in, first out data structure, this queue, we do wind up processing the nodes according to the layers that we discussed earlier. So the claim is that breadth first search is a good way to explore a graph, in the sense that it meets the 2 high-level goals that we delineated in the previous video. First of all, it finds everything findable, and obviously nothing else. And second of all, it does it without redundancy. It does it without exploring anything twice, which is the key to its linear time implementation. So a little bit more formally, claim number 1, at the end of the algorithm, the vertices that we've explored are precisely the ones such that there is a path from S to that vertex. And again, this claim is equally valid whether you're running BFS in an undirected graph or a directed graph. Of course, in an undirected graph, we mean an undirected path from S to V, whereas in a directed graph, we mean a directed path from S to V. That means a path where every arc in the path gets traversed in the forward direction. So why is this true? Well, this is true. We basically prove this more generally for any graph search strategy of a certain form, of which breadth first search is one. If it's hard for you to see the right way to interpret breadth first search as a special case of our generic search algorithm, you can also just look at our proof for the generic search algorithm and copy it down for breadth first search. So it's clear that you're only going to, again, the forward direction of this claim is clear. If you actually find something, if something's marked as explored, it's only because you found a sequence of edges that led you there. So the only way you mark something that is explored is if there's a path from S to V. Conversely, to prove that anything with an S to V, with a path from V will be found, you can proceed by contradiction. You can look at the part of the path from S to V that BFS does successfully explore, and then you get asked, why didn't it go one more hop? It never would have terminated before reaching all the way to V. So you can also just copy that same proof that we had for the generic search strategy in the previous video. Okay, so again, the upshot, breadth first search, it finds everything you'd want to find. Okay, so it only traverses paths, so you're not going to find anything where there isn't a path to it, but it never misses out. Okay, anything where there's a path, BFS guaranteed to find it, no problem. Claim number 2 is that the running time is exactly what we want, and I'm going to state it in a form that will be useful later when we talk about connected components. So the running time of the main while loop, ignoring any kind of pre-processing or initialization, is proportional to what I'm going to call NS and MS, which is the number of nodes that can be reached from S and the number of edges that can be reached from S. And the reason for this claim, this just becomes clear if you inspect the code, which we'll do in a second. So let's return to the code and just tally up all the work that gets done. So I'm going to ignore this initialization. I'm just going to focus on the main while loop. So we can summarize the total work done in this while loop as follows. First, we just think about the vertices. So in this search, we're only going to ever deal with the vertices that are findable from S, so that's NS. And what do we do with a given node? Well, we insert it into the queue and we delete it from the queue, right? So we're never going to deal with a single node more than once. So that's constant time overhead per vertex that we ever see. So that's the proportional to the ns part. Now, a given edge, we might look at it twice. So for an edge VW, we might consider it once when we first look at the vertex V, and we might consider it again when we look at the vertex W. Each time we look at an edge, we do constant work. So that means we're only going to do constant work per edge. Okay, so we look at each vertex at most once. We look at each edge findable from S at most twice. We do constant time, constant work when we look at something. So the overall running time is going to be proportional to the number of vertices findable from S plus the number of edges findable from S. So that's really cool. We have a linear time implementation of a really nice graph search strategy. And moreover, we just need very basic data structures, a queue, to make it run fast with small constants. But it gets even better. We can use breadth-first search as a workhorse for some interesting applications. So that's what we'll talk about in the rest of this video. And let's begin with the idea of shortest paths. So again, I give you the movie graph, I give you Kevin Bacon as a starting point. What's the fewest number of hops, the fewest number of edges on a path that leads to, say, John Hamm? So some notation, I'm going to use dist of v to denote the shortest path distance. So with respect to a starting node S, the fewest number of hops or the fewest number of edges on a path that starts at S and goes to V. And again, you can define this in the same way for undirected graphs or directed graphs. In a directed graph, you always want to traverse arcs in the forward direction, in the correct direction. And to do this, we just have to add a very small amount of extra code to the BFS code that I showed you earlier. It's just going to be a very small constant overhead, and basically it just keeps track of what layer each node belongs to, and the layers are exactly tracking shortest path distances away from the starting point S. So what's the extra code? Well, first in the initialization step, you set your preliminary estimate of the distance, the shortest path distance from S to a vertex V, as well. If V equals S, you know you can get from S to S on a path of length 0, the empty path. And if it's any other vertex, all bets are off. You have no idea if there's a path to V at all. So let's just initially put plus infinity for all vertices other than the starting point. This is something we will, of course, revise once we actually discover a path to a vertex V. And the only other extra code you have to add is when you're considering, so when you take a vertex off of the front of the queue and then you iterate through its edges and you're considering one of those edges VW, so here V would be the vertex that you just removed from the front of the queue. And as usual, if the other end of the edge W has already been dealt with, then you just throw it out. That would be redundant work to look at it again. But if this is the first time you're seeing the vertex W, then, in addition to what we did previously, in addition to marking it as explored and putting it in the queue at the back, we also compute its distance. And its distance is just going to be one more than the distance of the vertex V responsible for W's addition to the queue, responsible for first discovering this vertex W. So returning to our running example of breadth-first search, let's see what happens. So again, remember the way this worked is we start out with from the vertex S, and we set the distance, in our initialization equal to 0. We don't know what the distance is of anything else. So then, how did breadth-first search work? So in the initial step, we put S in the queue. We go to the main while loop, and then the queue's not empty. We extract S from the queue. We look at its neighbors. Those neighbors are A and B. We handle them in some order. Let's again think of that we first handle the edge between S and A. So then what do? We say we haven't seen A yet. So we mark A as explored. We put A in the queue at the front. And now we have this extra step. It's the first time we're seeing A. So we want to compute its distance. And we compute its distance as one more than the vertex responsible for discovering A. And so in this case, S was the vertex whose exploration unveiled the existence of the vertex A to us. S's distance is 0. So we set A's distance to 1. Okay? And that's tantamount to being a member of the ith layer. So what happens in the next iteration of the while loop? So now the queue contains, the next iteration of the for loop, So after we've handled the edge S comma A, we're still dealing with S's edges. Now we handle the edge S comma B. This is the first time we've seen B. We put B at the end of the queue. We mark it as explored, and then we also execute this new step. We set B's distance to one more than the vertex responsible for discovering it. That would again be the vertex S. S led to B's discovery. And so we set B's distance to be one more than S's distance, also known as 1. And that corresponds to being the other node in layer 1. Now, having handled all of S's adjacent arcs, we go back to the while loop. We ask if the Q is empty. Certainly not. It contains two vertices, first A, then B. We extract the first vertex because it's FIFO. That would be the vertex A. Now we look at A's incident edges. There's S comma A, which we ignore. There's A comma C. This is the first time we've seen C. So as before, we mark C as explored. We add C to the end of the Q, and now again we have this additional line. We set C's distance to be one more than the vertex responsible for its discovery. In this case, it's A that first discovered C. So we're going to set C's distance to be one more than A's distance, also known as 2. So then, having handled A, we move on to the next vertex in the Q, which in this case is B. Again, we can forget about the edge between S and B. We've already seen S. We can forget about the edge between B and C. We've already seen C. But D is now discovered for the first time via B. It gets marked as explored. It goes to the end of the Q, and its distance is set equal to one more than B's distance, which is 2. So then we deal with C. Again, it has 4 arcs, 4 edges. 3 of them are irrelevant. The one to E is not irrelevant because this is the first time we've seen E. So E's distance is computed as one more than C because C was the one who first found E. And so E gets a distance of 3. And then the rest of the algorithm proceeds as before. And you will notice that the labelings, the shortest path labels, are exactly the layers as promised. I hope you find it very easy to believe at this point that that claim is true in general. That the distance computed by breadth first search for an arbitrary vertex V that's reachable from S, that's going to be equal to I if and only if V is in the ith layer, as we've been defining it previously. And what does it really mean to be in the ith layer? It means that the shortest path distance between V and S has I hops, I edges. So I don't want to spend time giving a super rigorous proof of this claim, but let me just sort of give you, the gist, the basic idea, and I encourage you to produce a formal proof at home if that's something that interests you. So one way to do it is you can do it by induction on the layer I. And so what you want to prove is that all of the nodes that belong to a given layer I do indeed, the breadth first search does indeed compute the distance of I for them. So what does it mean to be a node in layer I? Well, first of all, you can't have been seen in any of the previous layers. You weren't a member of layers 0 through I minus 1. And furthermore, you're a neighbor of somebody who's in layer I minus 1. Right? You're seen for the first time once all of the layer I minus 1 nodes are processed. So the inductive hypothesis tells you that distances were correctly computed for everybody from the lower layers. So in particular, whoever this node V was from layer I minus 1, who is responsible for discovering you in layer I, it has a distance computed as I minus 1. Yours is assigned to be one more than its, namely I. So that pushes through the inductive step. Everything in layer I indeed gets the correct label of shortest path distance of I away from S. So before we wrap up with this application, I do want to emphasize it is only breadth first search that gives us this guarantee of shortest paths. So we had a wide family of graph search strategies, all of which find everything findable. Breadth first search is one of those, but this is a special additional property that breadth first search has. You get shortest path distances from it. So in particular, depth first search does not in general compute shortest path distances. This is really a special property of breadth first search. By contrast, in this next application, which is going to be computing the connected components of an undirected graph, this is not really fundamental to breadth first search. For example, you could use depth first search in here instead, and that would work just as well. So what's the problem? Well, so I did say most of the stuff about graph search, it really doesn't matter, undirected or directed. It's pretty much cosmetic changes. But the big exception is when you're computing connectivity, when you're computing the pieces of a graph. So right now, I'm only going to talk about undirected graphs. The directed case, we can again get very efficient algorithms for it, but it's quite a bit harder work. So that's going to be covered in detail in a separate video. So for now, focus just on an undirected graph, G. And we're certainly not going to assume that G is connected. Indeed, part of the point here is to figure out whether or not it's connected, i.e. in one piece. So maybe the graph looks like this. So for example, maybe the graph has 10 vertices and looks like this on the right. And intuitively, especially given that I've drawn it in such a clean way, it's clear that this graph has 3 pieces. And those are the things that we want to call the connected components. But we do want a somewhat more formal definition, something which is actually, in math that we could say is true or false about a given graph. And roughly, we define the connected components of an undirected graph as the maximal regions that are connected, in the sense you can get from any vertex in the region from any other vertex in the region using a path. So maximal connected regions in that sense. Now the slick way to do this is using an equivalence relation, and I'm going to do this here in part because it's really the right way to think about the directed graph case, which we'll talk about in some detail later. So for undirected graphs, so this isn't super important, but let me go ahead and state the formal definition just for completeness about what is a connected component. What do I mean by a maximal region that's mutually connected? So a good formal definition is as the equivalence classes of the relation on vertices, which we define by u being related to v if and only if there's a path between u and v in the graph G. So I'll leave it for you to do the simple check that this squiggle is indeed an equivalence relation. Let me remind you what equivalence relations are. This is something you generally learn in your first class on proofs or your first class in discrete math. So it's just something which may or may not be true about pairs of objects. And to be an equivalence relation, you have to satisfy three properties. So first you have to be reflexive, meaning everything has to be related to itself. And indeed, in a graph, there is a path from any node to itself, namely the empty path. So also equivalence relations have to be symmetric, meaning if u and v are related, then v and u are related. Because this is an undirected graph, it's clear that this is symmetric. If there's a path from u to v in the graph, there's also a path from v to u, so no problem there. Finally, equivalence classes got to be transitive. So that means if u and v are related, and so are v and w, then so are u and w. That is, if u and v have a path, v and w have a path, then so does u and w. And you can prove transitivity just by pasting the two paths together. And so the upshot is, when you want to say something like the maximal subset of something where everything is the same, the right way to make that mathematical is using equivalence relations. So over in this blue graph, we want to say 1, 3, 5, 7, and 9 are sort of all the same in the sense that they're mutually connected. And so that's exactly what this relation is making precise. All 5 of those nodes are related to each other. 2 and 4 are related to each other. 6, 8, and 10, all pairs of them are related to each other. So equivalence relations always have equivalence classes, the maximal mutually related stuff. And in this graph context, that's exactly these connected components. It's exactly what you want. So what I want to show you is that you can use a breadth-first search wrapped in an outer for loop over all of the vertices to identify all of the connected components of a graph in time linear in the graph, in over n plus m time. Now you might be wondering, why do you want to do that? Well, there's a lot of reasons. So an obvious one, which is relevant for physical networks, is to check if a network has broken into two pieces. So certainly if you're an internet service provider, you want to make sure that from any point in your network, you can reach any other point in the network. And that boils down to just understanding whether the graph that represents your network is a connected graph, that is, if it's in one piece or if it's not in one piece. So obviously you can ask this same question about recreational examples. So if you return to the movie graph, maybe you're wondering, can you get from every single actor in the IMDb database to Kevin Bacon? Or are there actors for which you cannot reach Kevin Bacon via a sequence of edges, a sequence of movies in which two actors have both played a role? So that's something that boils down to a connectivity computation. If you have network data and you want to display it, you want to visualize it and show it to a group of people so that they can interpret it, obviously one thing you want to do is you want to know if there's multiple pieces, and then you want to display the different pieces separately. So let me mention one probably a little less obvious application of undirected connectivity, which is it gives a nice quick and dirty heuristic for doing clustering if you have pairwise information about objects. So let me be a little more concrete. Suppose you have a set of objects that you really care about. So this could be a set of documents, maybe web pages that you've crawled, something like that. It could be a set of images, either your own or drawn from some database, or it could be, for example, a set of genomes. Suppose further that you have a pairwise function, which for each pair of objects tells you whether they're very much like each other or very much different. And so let's suppose that if two objects are very similar to each other, like they're two web pages that are almost the same, or they're two genomes where you can get from one to the other with a small number of mutations, then they have a low score. So low numbers close to 0 indicates that the objects are very similar to each other. High numbers, let's say they could go up to even 1,000 or something, indicate that they're very different objects. Two web pages that have nothing to do with each other, two genomes for totally unrelated parts, or two images that seem to be of completely different people or even completely different objects. Now here's a graph you can construct using these objects and the similarity data that you have about them. So you can have a graph where the nodes are the objects. Okay, so for each image, for each document, whatever, you have a single node. And then for a given pair of nodes, you put in an edge if and only if the two objects are very similar. So for example, you could put in an edge between two objects if and only if the score is at most 10. So remember, the more similar two objects are, the closer their score is to 0. So you're going to get an edge between very similar documents, very similar genomes, very similar images. Now, in this graph you've constructed, you can find the connected components. So each of these connected components will be a group of objects which more or less are all very similar to each other. So this will be a cluster of closely related objects in your database. And you can imagine a lot of reasons why, given a large set of unstructured data, just a bunch of pictures, a bunch of documents, or whatever, you might want to find clusters of highly related objects. So we'll probably see more sophisticated heuristics for clustering in some SQL course, but already undirected connectivity gives you a super fast, linear time, quick and dirty heuristic for identifying clusters of similar objects, given pairwise data about similarity. So that's some reasons you might want to do it. Now let's actually talk about how to compute the connected components in linear time using just a simple for loop and breadth first search as its inner workhorse. So here's the code to compute all the connected components of an undirected graph. So first we initialize all nodes as being unexplored. I'm also going to assume that the nodes have names. Let's say their names are from 1 to n. So these names could just be the position in the node array that these nodes occupy. So there's going to be an outer for loop which walks through the nodes in an arbitrary order, let's say from 1 to n. This outer for loop is to ensure that every single node of the graph will be inspected for sure at some point in the algorithm. Now again, one of our maxims is that we should never do redundant work. So before we start exploring from some node, we check if we've already been there. And if we haven't seen I before, then we invoke the breadth first search subroutine we were talking about previously in the lecture in the graph G, starting from the node I. So to make sure this is clear, let's just run this algorithm on this blue graph to the right. So we start in the outer for loop and we set I equal to 1 and we say, have we explored node number 1 yet? And of course not, we haven't explored anything yet. So the first thing we're going to do is we're going to invoke BFS on node number 1 here. So now we start running the usual breadth first search subroutine starting from this node 1. And so we explore, layer 1 here is going to be nodes 3 and 5, so we explore them in some order. For example, maybe node number 3 is what we explore second, then node number 5 is what we explore third. And then the second layer in this component is going to be the nodes 7 and 9. So we'll explore them in some order as well. Let's say 7 first, followed by 9. So after this BFS initiated from node number 1 completes, of course it will have found everything that it could possibly find, namely the 5 nodes in the same connected component as node number 1, and of course all of 5 of these nodes will be marked as explored. So now we return, once that exits, we return to the outer for loop, we increment I, we go to I equal 2, and we say, oh, we already explored node number 2. No, we have not. And so now we invoke BFS again from node number 2. So that'll be the 6th node we explore. There's not much to do from 2. All we can do is go to node number 4. So that's the 7th node we explore. That BFS terminates, finding the nodes in this connected component. Then we go back to the outer for loop. We increment I to 3. We say, oh, have we already seen node number 3? Yes, we have. We saw that in the first breadth first search. So we certainly don't bother to BFS from node 3. Then we increment I to 4. Have we seen 4? Yes, we have. In the second call to BFS. Have we seen node 5? Yes, we have. In the first call to BFS. Have we seen node 6? No, we have not. So the final invocation of breadth first search begins from node number 6. That's going to be the 8th node overall that we see. And then we're going to see the nodes 8 and 10 in some order. So for example, maybe we first explore node number 8. That's one of the first layer in this component. And then node number 10 is the other node of the first layer in this component. So in general, what's going on? Well, what we know what will happen when we invoke breadth first search from a given node I, we're going to discover exactly the nodes in I's connected component, right? Anything where there's a path from I to that node, we'll find it. That's the BFS guarantee. That's also the definition of a connected component. All the other nodes which have a path to I. Another thing that I hope was clear from the example, but just to reiterate it, is every breadth first search call, when you explore a node, you remember that through the entire for loop. Right? So when we invoke breadth first search from node number 1, we explore nodes 1, 3, 5, 7, and 9, and we keep those marked as explored for for the rest of this algorithm, right? So that's so that we don't do redundant work when we get to later stages of the for loop. So as far as what does this algorithm accomplish, well, it certainly finds every connected component. Right? There is absolutely no way it can miss a node because this for loop literally walks through the nodes, all of them, one at a time. Okay? So you're not going to miss a node. Moreover, we know that as soon as you hit a connected component for the first time and you do breadth first search from that node, you're going to find the whole thing. That's the breadth first search guarantee. As far as what's the running time, well, it's going to be exactly what we want. It's going to be linear time, which again means proportional to the number of edges plus the number of vertices. And again, depending on the graph, one of these might be bigger than the other. So why is it O of m plus n? Well, as far as the nodes, we have to do this initialization, there where we mark them all as unexplored, so that takes constant time per node. We have just the basic overhead of a for loop, so that's constant time per node. And then we have this check, constant time per node, so that's O of n. And then recall, we proved that within breadth first search, you do amount of work proportional. You do constant time for each node in that connected component. Now, each of the nodes of the graph is in exactly one of the connected components, so you'll do constant time for each node in the BFS in which you discover that node. So that's, again, O of n over all of the connected components. And as far as the edges, no, we don't even bother to look at edges until we're inside one of these breadth first search calls. They play no role in the outer for loop or in the pre-processing. And remember what we proved about an invocation of breadth first search. The running time, you only do constant amount of work per edge in the connected component that you're exploring. In the worst case, you look at an edge once from either endpoint, and each of that triggers a constant amount of work. So when you discover a given connected component, the edge work is proportional to the number of edges in that connected component. Each edge of the graph is in exactly one of the connected components. So over this entire for loop, over all of these BFS calls, for each edge of the graph, you'll only be responsible for a constant amount of work of the algorithm. So summarizing, because breadth first search from a given starting node works in time proportional to the size of that component, piggybacking on that subroutine and looping over all of the nodes of the graph, we find all of the connected components in time proportional to the number of edges and nodes in the entire graph. Let's explore our second strategy for graph search, namely depth first search. And again, like with breadth first search, I'll open by just reminding you what depth first search is good for, and we'll trace through it in a particular example, and then we'll tell you what the actual code is. So if breadth first search is the cautious and tentative exploration strategy, then depth first search, or DFS for short, is its more aggressive cousin. So the plan is to explore aggressively and only backtrack when necessary. And this is very much the strategy one often uses when trying to solve a maze. To explain what I mean, let me show you how this would work in the same running example we used when we discussed breadth first search. So here, if we invoke depth first search from the node number S, here's what's going to happen. So obviously we start at S, and obviously there's two places where we can go next. We can go to A or to B. And depth first search is underdetermined. Like breadth first search, we can pick either one. So like with the breadth first search example, let's go to A first. So A will be the second one that we explore. But now, unlike breadth first search, where we automatically went to node B next, since that was the other layer 1 node, here the only rule is that we have to go next to one of A's immediate neighbors. So we might go to B, but we're not going to B because it's one of the neighbors of S. We go because it's one of the neighbors of A. And actually, to make sure the difference is clear, let's assume that we aggressively pursue deeper and we go from A to C. And now the depth first search strategy is again just to pursue deeper, so you go to one of C's immediate neighbors. So maybe we go to E next. So E is going to be the fourth one visited. Now from E, there's only one neighbor, not counting the one that we came in on. So from E, we go to D, and D is the fifth one we see. Now from D, we have a choice. We could either go to B or we could go to C. So let's suppose we go to C from D. Well, then we get to a node number 3 where we've been before. Okay, and as usual, we're going to keep track of where we've already been. So at this point, we have to backtrack from C back to D. We retreat to D. Now, there's still another outgoing edge from D to explore, namely the one to B. And so what happens is we actually wind up wrapping all the way around this outer cycle, and we hit B sixth. And now, of course, anywhere we try to explore, we see somewhere we've already been. So from B, we try to go to S, but we've been there, so we retreat to B. We can try to go to A, but we've been there, so we retreat to B. Now we've explored all of the options out of B. So we have to retreat from B, we have to go back to D. Now from D, we've explored both B and C, so we have to retreat back to E. E, we've explored the only outgoing arc D, so we have to retreat to C. C, we retreat to A. From A, we actually haven't yet looked along this arc, but that just sends us to B where we've been before. So then we retreat back to A. Finally, we retreat back to S. And S, even at S, there's still an extra edge to explore. At S, we say, oh, we haven't tried this SB edge yet. But of course, when we look across, we get to B where we've been before, and then we backtrack to S. Then we've looked at every edge once, and so we stop. So that's how depth first search works. You just pursue your path. You go to an immediate neighbor as long as you can until you hit somewhere you've been before, and then you retreat. So you might be wondering, why bother with another graph search strategy? After all, we have breadth first search, which seemed pretty awesome, right? It runs in linear time. It's guaranteed to find everything you might want to find. It computes shortest paths. It computes connected components if you embed it in a for loop. Kind of seems like, what else would you want? Well, it turns out depth first search is going to have its own impressive catalog of applications, which you can't necessarily replicate with breadth first search. And I'm going to focus on applications in directed graphs. So there's going to be a simple one that we discuss in this video, and then there's going to be a more complicated one that has a separate video devoted to it. So in this video, we're going to be discussing computing topological orderings of directed acyclic graphs, that is, directed graphs that have no directed cycle. The more complicated application is computing strongly connected components in directed graphs. The runtime will be essentially the same as it was for breadth first search, and the best we could hope for, which is linear time. And again, we're not assuming that there's necessarily that many edges. There may be much fewer edges than vertices. So linear time in these connectivity applications means O of m plus n. So let's now talk about the actual code of depth first search. There's a couple ways to do it. One way to do it is to just make some minor modifications to the code for breadth first search. The primary difference being, instead of using a queue and its first in, first out behavior, you swap in a stack with its last in, first out behavior. Again, if you don't know what a stack is, you should read about that in the programming textbook or on the web. It's something that supports constant time insertions to the front and constant time deletions from the front, unlike a queue, which is meant to support constant time deletions to the back. Okay, so stack, it operates just like those cafeteria trays that where you put in a tray, and the last one that got pushed in, when you take the first one out, that's the last one that got put in. So these are called push and pop. In a stack context, both are constant time. So if you swap out the queue, you swap in the stack, make a couple other minor modifications, breadth first search turns into depth first search. For the sake of both variety and elegance, I'm instead going to show you a recursive version. So depth first search is very naturally phrased as a recursive algorithm, and that's what we'll discuss here. So depth first search, of course, takes as input a graph G, and again, it could be undirected or directed. It doesn't matter. Just with a directed graph, be sure that you only follow arcs in the appropriate direction, which should be automatically handled in the adjacency lists of your graph data structure anyways. So as always, we keep a Boolean local to each vertex of the graph, remembering whether we've been there before or not. And of course, as soon as we start exploring from S, we better make a note that now we have been there. We better plant a flag, as it were. And remember, depth first search is an aggressive search. So we immediately try to recursively search from any of S's neighbors that we haven't already been to. And if we find such a vertex, if we find somewhere we've never been, we recursively call depth first search from that node. The basic guarantees of depth first search are exactly the same as they were for breadth first search. We find everything we could possibly hope to find, and we do it in linear time. And once again, the reason is this is simply a special case of the generic search procedure that we started this sequence of videos about. So it just corresponds to a particular way of choosing amongst multiple crossing edges between the region of explored nodes and the region of unexplored nodes, essentially always being biased toward the most recently discovered explored nodes. And just like breadth first search, the running time is going to be proportional to the size of the component that you're discovering. And the basic reason is that each node is looked at only once, right? This Boolean makes sure that we don't ever explore a node more than once. And then for each edge, we look at it at most twice, once from each endpoint. And given that these exact same two claims hold for depth first search as for breadth first search, that means if we wanted to compute connected components in an undirected graph, we could equally well use an outer for loop with depth first search as our workhorse in the inner loop. It wouldn't matter. Either of those for undirected graphs, depth first search, breadth first search, is going to find all the connected components in O of m plus n time, in linear time. So instead, I want to focus on an application particular to depth first search, and this is about finding a topological ordering of a directed acyclic graph. So let me begin by telling you what a topological ordering of a directed graph is. Essentially, it's an ordering of the vertices of the graph so that all of the arcs, the directed edges of the graph, only go forward in the ordering. So let me encode an ordering by a labeling of the vertices with the numbers 1 through n. This is just to encode the position of each vertex in this ordering. So formally, there's going to be a function which takes vertices of G and maps them to integers between 1 and n. Each of the numbers 1 through n should be taken on by exactly one vertex. Here n is the number of vertices of G. So that's just a way to encode an ordering, and then here's really the important property, that every directed edge of G goes forward in the ordering. That is, if UV is a directed edge of the directed graph G, then it should be that the f value of the tail is less than the f value of the head. That is, this directed edge has a higher f value as you traverse it in the correct direction. Let me give you an example just to make this more clear. So suppose we have this very simple directed graph with 4 vertices. Let me show you 2 different, totally legitimate topological orderings of this graph. So the first thing you could do is you could label S1, V2, W3, and T4. Another option would be to label them the same way, except you can swap the labels of V and W. So if you want, you can label V3 and W2. So again, what these labelings are really meant to encode is an ordering of the vertices. So the blue labeling you can think of as encoding the ordering in which we put S first, then V, then W, and then T, whereas the green labeling can be thought of as the same ordering of the nodes except with W coming before V. What's important is that the pattern of the edges is exactly the same in both cases, and in particular all of the edges go forward in this ordering. So in either case we have S with edges from S to V and S to W. So that looks the same way pictorially, whichever order V and W are in, and then symmetrically there are edges from V and W to T. So you'll notice that no matter which order we put V and W in, all 4 of these edges go forward in each of these orderings. Now if you tried to put V before S, it wouldn't work because the edge from S to V would be going backward if V preceded S. Similarly, if you put T anywhere other than the final position, you would not have a topological ordering. So in fact, these are the only 2 topological orderings of this directed graph. I encourage you to convince yourself of that. Now, who cares about topological orderings? Well, this is actually a very useful subroutine. This has come up in all kinds of applications. Really, whenever you want to sequence a bunch of tasks when there's precedence constraints among them. By precedence constraint, I mean one task has to be finished before another. You can think, for example, about the courses in some kind of undergraduate major, like a computer science major. Here the vertices are going to correspond to all of the courses, and there's a directed edge from course A to course B if course A is a prerequisite for course B, if you have to take it first. So then, of course, you'd like to know a sequence in which you can take these courses so that you always take a course after you've taken its prerequisites, and that's exactly what a topological ordering will accomplish. So it's reasonable to ask the question, when does a directed graph have a topological ordering? And when a graph does have such an ordering, how do we get our grubby little hands on it? Well, there's a very clear necessary condition for a graph to have a topological ordering, which is it had better be acyclic. Put differently, if a directed graph has a directed cycle, then there's certainly no way there's going to be a topological ordering. So I hope the reason for this is fairly clear. Consider any directed graph which does have a directed cycle, and consider any purported way of ordering the vertices. Well, now just traverse the edges of the cycle one by one. So you start somewhere on this cycle, and if the first edge goes backward, well, you're already screwed. You already know that this ordering is not topological. No edges can go backward. So evidently the first edge of this cycle has to go forward. But now you have to traverse the rest of the edges on this cycle, and eventually you come back to where you started. So if you started out by going forward, at some point you have to go backward. So that edge goes backward in the ordering, violating the property of a topological ordering. That's true for every ordering, so directed cycles exclude the possibility of topological orderings. Now the question is, well, what if you don't have a cycle? Is that a strong enough condition that you're guaranteed to have a topological ordering? Is the only obstruction to sequencing jobs without conflicts the obvious one of having circular precedence constraints? So it turns out not only is the answer yes, as long as you don't have any directed cycles, you're guaranteed a topological ordering, but we can even compute one in linear time, no less, via depth first search. So before I show you the super slick and super efficient reduction of computing topological orderings to depth-first search, let me first go over a pretty good, but slightly less slick and slightly less efficient solution to help build up your intuition about directed acyclic graphs and their topological orderings. So for the straightforward solution, we're going to begin with a simple observation. Every directed acyclic graph has what I'm going to call a sinc vertex. That is a vertex without any outgoing arcs. So in the 4-node directed acyclic graph we were exploring on the last slide, there's exactly one source vertex, and that's, sinc vertex. That's this rightmost vertex here, right? That has no outgoing arcs. The other 3 vertices all have at least one outgoing arc. Now, why is it the case that a directed acyclic graph has to have a sinc vertex? Well, suppose it didn't. Suppose it had no sinc vertex. That would mean every single vertex has at least one outgoing arc. So what could we do if every vertex has one outgoing arc? Well, we could start in an arbitrary node. We know it's not a sinc vertex because we're assuming there aren't any. So there's an outgoing arc, so let's follow it. We get to some other node. By assumption, there's no sinc vertex, so this isn't a sinc vertex, so there's an outgoing arc. So let's follow it. We get to some other node. That also has an outgoing arc. Let's follow that. And so on. So we just keep following outgoing arcs. And we do this as long as we want, because every vertex has at least one outgoing arc. Well, there's a finite number of vertices, right? This graph has, say, n vertices. So if we follow n arcs, we're going to see n plus 1 vertices. So by the pigeonhole principle, we're going to have to see a repeat, right? So if n plus 1 vertices, there's only n distinct vertices, we're going to see some vertex twice. So for example, maybe after I take the outgoing arc from this vertex, I get back to this one that I saw previously. Well, what have we done? What happens when we get a repeated vertex? By tracing these outgoing arcs and repeating a vertex, we have exhibited a directed cycle. And that's exactly what we're assuming doesn't exist. We're talking about directed acyclic graphs. So put differently, we just proved that a vertex with no sinc vertex has to have a directed cycle. So a directed acyclic graph, therefore, has to have at least one sinc vertex. So here's how we use this very simple observation now to compute a topological ordering of a directed acyclic graph. Well, let's do a little thought experiment. Suppose, in fact, this graph did have a topological ordering. Let's think about the vertex which goes last in this topological ordering. Remember, any arc which goes backward in the ordering is a violation. So we have to avoid that. We have to make sure every arc goes forward in the ordering. Now, any vertex which has an outgoing arc, we better put somewhere other than in the final position. Right? So the node that we put in the final position, all of its arcs are going to wind up, all of its outgoing arcs are going to wind up going backward in the topological ordering. There's nowhere else they can go. This vertex is last. So in other words, if we plan to successfully compute a topological ordering, the only candidate vertices for that final position in the ordering are the sinc vertices. That's all that's going to work. We put a non-sinc vertex there, we're toast. It's not going to happen. Fortunately, if it's directed acyclic, we know there is a sinc vertex. So let V be a sinc vertex of G. If there's many sinc vertices, we pick one arbitrarily. We set V's label to be the maximum possible. So if there's n vertices, we're going to put that in the nth position. And now we just recurse on the rest of the graph, which has only n minus 1 vertices. So how would this work in the example on the right? Well, in the first iteration, or the first outermost recursive call, the only sinc vertex is this rightmost one circled in green. So there's 4 vertices, so we're going to give that the label 4. So then, having labeled that 4, we delete that vertex and all the edges incident to it, and we recurse on what's left of the graph. So that would be the leftmost 3 vertices plus the leftmost 2 edges. Now, this graph has 2 sinc vertices after we've deleted 4 and everything from it. So both this top vertex and this bottom vertex are sincs in the residual graph. So now in the next recursive call, we can choose either of those as our sinc vertex. Because we have 2 choices, that generates 2 topological orderings. Those are exactly the ones that we saw in the example. But if, for example, we choose this one to be our sinc vertex, then that gets the label 3. Then we recurse just on the northwesternmost 2 edges. This vertex is the unique sinc in that graph. That gets the label 2. And then we recurse on the one-node graph, and that gets the label 1. So why does this algorithm work? Well, there's just two quick observations we need. So first of all, we need to argue that it makes sense that in every iteration or in every recursive call, we can indeed find a sinc vertex that we can assign in the final position that's still unfilled. And the reason for that is just if you take a directed acyclic graph and you delete one or more vertices from it, you're still going to have a directed acyclic graph, right? You can't create cycles by just getting rid of stuff. You can only destroy cycles. And we started with no cycles, so through all the intermediate recursive calls, we have no cycles. By our first observation, there's always a sinc. So the second thing we have to argue is that we really do produce a topological ordering. So remember what that means. That means for every edge of the graph, it goes forward in the ordering. That is, the head of the arc is given a position later than the tail of the arc. And this simply follows because we always use sinc vertices. So consider the vertex V, which is assigned to the position I. This means then that when we're down to a graph that has only I vertices remaining, V is a sinc vertex. So if V is a sinc vertex when only the first I vertices remain, what property does it have in the original graph? Well, it means all of the outgoing arcs that it has have to go to vertices that were already deleted and assigned higher positions. So for every vertex, by the time it actually gets assigned a position, it's a sinc, and it only has incoming arcs from the as yet unsigned vertices. Its outgoing arcs all go forward to vertices that were already assigned higher positions and got deleted previously from the graph. So now we have under our belt a pretty reasonable solution for computing a topological ordering of a directed acyclic graph. In particular, remember we observed that if a graph does have a directed cycle, then of course there's no way there's a topological ordering. However you order the vertices, some edge of the cycle is going to have to go backward. And the solution on the previous slide shows that as long as you don't have a cycle, it guarantees a topological ordering does indeed exist. And in fact, it's a constructive proof, a constructive argument. It gives an algorithm. What you do is you just keep plucking off sinc vertices one at a time and populating the ordering from right to left as you keep peeling off these sincs. So that's a pretty good algorithm. It's not too slow, and actually if you implement it just so, you can even get it to run in linear time. But I want to conclude this video with an application of depth-first search, which is a very slick, very efficient computation of a topological ordering of a directed acyclic graph. So we're just going to make two really quite minor modifications to our previous depth-first search subroutine. The first thing is we have to embed it in a for loop, just like we did with breadth-first search when we were computing the connected components of an undirected graph. That's because in computing a topological ordering, we better give every single vertex a label. We better look at every vertex at least once. So to do that, we'll just make sure there's an outer for loop, and then if we have multiple components, we'll just make sure to invoke DFS as often as we need to. The second thing we'll do is we'll add a little bit of bookkeeping, and this will make sure that every node gets a label. And in fact, these labels will define a topological ordering. So let's not forget the code for depth-first search. This is where you're given a graph G. In this case, we're interested in a directed acyclic graph, and you're given a start vertex S. And what you do is as soon as you get to S, you very aggressively start trying to explore its neighbors. Of course, you don't visit any vertex you've already been to. You keep track of who you visited. And if you find any vertex that you haven't seen before, you immediately start recursing on that node. So I said the first modification we need is to embed this into outer for loop to ensure that every single node gets labeled. So I'm going to call that subroutine DFS-loop. It does not take a start vertex. Initialization, all nodes start out unexplored, of course. And we're also going to keep track of a global variable, which I'll call current label. This is going to be initialized to n, and we're going to count down each time we finish exploring a new node. And these will be precisely the f values. These will be exactly the positions of the vertices in the topological ordering that we output. In the main loop, we're going to iterate over all of the nodes of the graph. So for example, we just do a scan through the node array. As usual, we don't want to do any work twice. So for if a vertex has already been explored in some previous invocation of DFS, we don't search from it. This should all be familiar from our embedding of breadth-first search and a for loop when we computed the connected components of an undirected graph. And if we get to a vertex V of the graph that we haven't explored yet, then we just invoke DFS in the graph with that vertex as the starting point. So the final thing I need to add is I need to tell you what the f values are, what the actual assignments of vertices to positions are. And as I foreshadowed, we're going to use this global current label variable, and that'll have us assign vertices to positions from right to the left, very much mimicking what was going on in our recursive solution where we plucked off sinc vertices one at a time. So when's the right time to assign a vertex its position? Well, it turns out the right time is when we're completely finished with that vertex. So we're about to pop the recursive call from the stack corresponding to that vertex. So after we've gone through the for loop of all the edges outgoing from a given vertex, we set f of s equal to whatever the current label is, and then we decrement the current label. And that's it. That is the entire algorithm. So the claim is going to be that the f values produced, which you'll notice are going to be the integers between n through 1, because DFS will be called eventually once on every vertex, and it will get some integer assignment at the end, and everybody's going to get a distinct value, and the largest one is n and the smallest one is 1. The claim is that is a topological ordering. Clearly this algorithm is just as blazingly fast as DFS itself, with just a trivial amount of extra bookkeeping. Let's see how it works on our running example. So let's just say we have this 4-node directed graph that we're getting quite used to. So this has 4 vertices, so we initialize the current label variable to be equal to 4. So let's say that in the outer DFS loop, let's say we start somewhere like the vertex v. So notice in this outer for loop, we wind up considering the vertices in a totally arbitrary order. So let's say we first call DFS from this vertex v. So what happens? Well, the only place you can go from v is to t, and then at t there's nowhere to go. So we recursively call DFS at t, there's no edges to go through, we finish the for loop, and so t is going to be assigned an f value equal to the current label, which is n, and here n is the number of vertices, which is 4. So f of t is going to get, t is going to get the assignment, the label 4. So then now we're done with t, we backtrack back to v. We decrement the current label as we finish up with t. We get to v, and now there's no more outgoing arcs to explore, so it for loops finish. So we're done with it with depth first search. So it gets what's the new current label, which is now 3. And again, having finished with v, we decrement the current label, which is now down to 2. So now we go back to the outer for loop. Maybe the next vertex we consider is the vertex t, but we've already been there, so don't bother to DFS on t. And then maybe after that, we try it on S. So maybe S is the third vertex that the for loop considers. We haven't seen S yet, so we invoke DFS starting from the vertex S. From S, there's 2 arcs to explore. The one with V we've already seen, so nothing's going to happen with the arc SV. But on the other hand, the arc SW will cause us to recursively call DFS on W. From W, we try to look at the arc from W to T, but we've already been to T, so we don't do anything. That finishes up with W. So depth first search then finishes up at the vertex W. W gets the assignment of the current label. So f of W equals 2. We decrement current label. Now its value is 1. Now we backtrack to S. We've already considered all of S's outgoing arcs, so we're done with S. It gets the current label, which is 1. And this is indeed one of the 2 topological orderings of this graph that we exhibited a couple slides ago. So that's the full description of the algorithm and how it works in a concrete example. Let's just discuss what are its key properties, its running time and its correctness. So as far as the running time of this algorithm, the running time is linear. It's exactly what you'd want it to be. And the reason the running time is linear is for the usual reasons that these graph search algorithms have run in linear time. You're explicitly keeping track of which nodes you've been to so that you don't visit them twice. So you only do a constant amount of work for each of the n nodes, and each edge, in a directed graph, you actually only look at each edge once when you visit the tail of that edge. So you only do a constant amount of work per edge as well. Of course, the other key property is correctness. That is, we need to show that you all are guaranteed to get a topological ordering. So what does that mean? That means every edge, every arc travels forward in the ordering. So if uv is an edge, then f of u, the label assigned to u, in this algorithm is less than the label assigned to v. The proof of correctness splits into 2 cases, depending on which of the vertices u or v is visited first by depth first search. Because of our for loop, which iterates over all of the vertices of the graph G, depth first search is going to be invoked exactly once from each of the vertices. Either u or v could be first. Both are possible. So first let's assume that u is visited by DFS before v. So then what happens? Well, remember what depth first search does. When you invoke it from a node, it's going to find everything findable from that node. So if U is visited before V, that means V isn't yet explored. So it's a candidate for being discovered. Moreover, there's an arc straight from U to V. So certainly DFS invoked at U is going to discover V. Furthermore, the recursive call corresponding to the node V is going to get popped off the program stack before that of U. The easiest way to see this is just to think about the recursive structure of depth first search. So when you call depth first search from U, that recursive call, that's going to make further recursive calls to all of the relevant neighbors, including V, and U's call is not going to get popped off the stack until V's does beforehand. That's because of the last in, first out nature of a stack or of a recursive algorithm. So because V's recursive call finishes before that of U, that means it will be assigned a larger label than U. Remember, the labels keep decreasing as more and more recursive calls get popped off the stack. So that's exactly what we wanted. Now what's up in the second case, case 2? So this is where V is visited before U. And here's where we use the fact that the graph has no cycles. So there's a direct arc from U to V. That means there cannot be any directed path from V all the way back to U. That would create a directed cycle. Therefore, DFS invoked from V is not going to discover U. There's no directed path from V to U. Again, if there was, there'd be a directed cycle. So it doesn't find U at all. So the recursive call of V, again, is going to get popped before U's is even pushed onto the stack. So we're totally done with V before we even start to consider U. So therefore, for the same reasons, since V's recursive call finishes first, its label is going to be larger, which is exactly what we wanted to prove. So that concludes the first quite interesting application of depth first search. In the next video, we'll look at an even more interesting one, which computes the strongly connected components of a directed graph. This time, we can't do it in one depth first search. We'll need two. Having mastered computing the connected components of an undirected graph in linear time, let's now turn our attention to directed graphs, which also arise in all kinds of different applications. Now the good news is we'll be able to get just a blazingly fast primitive for computing connectivity information for directed graphs. The bad news, if you want to call it that, is we'll have to think a little bit harder. So it won't be as obvious how to do it, but by the end of this lecture, you will know a linear time algorithm with very good constants, really just based on depth first search for computing all of the pieces of a directed graph. In fact, it's not even so obvious how to define pieces, how to define connected components in a directed graph. Certainly not as obvious as it was with undirected graphs. So to see what I mean, let's consider the following 4-node directed graph. So on the one hand, this graph is in some sense in one piece. If this was an actual physical object made, say, of a bunch of strings connected to each other and we picked it up with our hands, it wouldn't fall apart into two pieces. It would hang together in one piece. On the other hand, when you think about moving around this network, it's not connected in the sense that we might think about. You cannot get from any one point A to any other point B. For example, if you start at the rightmost node in this graph, certainly there's no directed path that will get you to the leftmost node. So what's typically studied and most useful for directed graphs is what's called strong connectivity. And a graph is strongly connected if you can get from any one point to any other point, and vice versa. And the strongly connected components then informally are the maximal portions of this graph, the maximal regions, which are internally strongly connected. So the maximal regions from within which you can get from any one point A to any other point B along a directed graph. For the record, let me go ahead and give you a formal definition, although this intuition is perfectly valid, just regions where you can get from anywhere to anywhere else. So we say that the strongly connected components of a directed graph, or the SCCs for short, and as in the undirected case, we're going to give a somewhat slick definition. Rather than talking about maximal regions satisfying some property, we're going to talk about the equivalence classes of a particular equivalence relation. But really it means the same thing. This is just sort of the more mathematically mature way of writing it down. So the equivalence relation we're going to use, it's on nodes of the graph, and we'll say that U, a node, is related to a node V, if you can get from U to V via a directed path, and also from V to U and some other directed path. I'm not going to bore you with the verification that this is an equivalence relation. That's something you can work out in the privacy of your own home. So remember what it means to be an equivalence relation. It's reflexive, that is, everybody's related to itself, but of course there is a path from every node to itself. It also means that it's symmetric, so if U is related to V, then V is related to U. Well, again, by definition, we're saying that the vertices are mutually reachable from each other, so that's clearly symmetric by definition. And then it has to be transitive, and the way you prove it's transitive is you just paste paths together, and it just works the way you'd expect it to. So let's illustrate this concretely with a somewhat more complicated directed graph. So here's a directed graph, and I claim that it has exactly 4 strongly connected components. It has a triangle on the left, a triangle on the right, it has this single node in top, and then it has this directed 4 cycle with a diagonal at the bottom. So what I hope is pretty clear is that each of these circled regions is indeed strongly connected. That is, if you start from one node in one of these circled regions, you can have a directed path to any other node. So that's certainly true because on a directed cycle, you can get from any one starting point to any other place. And all of these have directed cycles. And then there's the one strong component that just has the one node, which is obviously strongly connected. What I also claim is true is that all of these regions are maximal, subject to being strongly connected. That's why they're the strongly connected components. That's why they're the equivalence classes of this equivalence relation we just defined. So if you take any 2 pairs of nodes, which lie in 2 different circles, you either won't have a path from the first one to the second one, or you won't have a directed path from the second one back to the first one. In fact, the structure of the strong components in this black graph exactly mirrors the directed acyclic graph that we started with in red. So in the same way in the red 4-node graph, you can't move from right to left. Here in this bigger graph, you can't move from any of the circled SECs to the right to any of the circled SECs to the left. So for example, from the rightmost nodes, there are no directed paths to the leftmost nodes. So that's a recap of the definition of the strongly connected components. I've motivated in a separate video some reasons why you might care about computing strongly connected components, in particular on extremely large graphs, which motivates the need for blazingly fast subroutines, so for-free primitives that will let you compute connectivity information. So you'd love to be able to just know the pieces of a directed graph. Maybe you don't even know why they're going to be useful, but you just compute them because why not? It's a for-free primitive. So that's what I'm going to give you in this lecture. So the algorithm we're going to present is based on depth-first search, and that's going to be the main reason why it's going to be so blazingly fast, is because depth-first search is blazingly fast. Now, you might be wondering, what on earth does graph search have to do with computing components? They don't seem obviously related. So let's return to the same directed graph that I showed you on the previous slide. And to see why something like depth-first search might conceivably have some use for computing strong components, suppose we call depth-first search starting from this red node as a starting point. What would it explore? So remember what the guarantee of something like depth-first search, or breadth-first search for that matter, is. You find everything that's findable, but naturally nothing else. So what is findable from this red node? Where by findable I mean you can reach it from a directed path emanating from this red node. Well, there's not much you can do. So from here you can explore this arc, and you can explore this arc, and then you can go backward. And so if you do DFS or BFS from this node, you're going to find precisely the nodes in this triangle. All of the other arcs involved go the wrong direction, and they won't be traversed by, say, a depth-first search call. So why is that interesting? What's interesting is that if we invoke DFS from this red node, or any of the 3 nodes from this triangle, then it's going to discover precisely this strongly connected component, precisely the 3 nodes in this circled SCC. So that seems really cool. It seems like maybe we just do a DFS and boom, we get an SCC. So maybe if we can do that over and over again, we'll get all the SCCs. So that's a good initial intuition, but something can go wrong. Suppose that instead of initiating DFS from one of these 3 nodes on the triangle, we say initiate it from this bottommost node in green. So remember, what is the guarantee of a graph search subroutine like DFS? It'll find everything findable, but of course nothing more. So what's findable from this green node? Well, naturally everything in its own SCC, right? So the 4 nodes here, it'll certainly find those 4 nodes. On the other hand, if we start from this green node, since there are arcs that go from this bottommost SCC to the rightmost SCC, not only will this DFS call find the 4 nodes in the green node's strong component, but it'll also traverse these blue arcs and discover the 3 nodes in the red triangle. So if we call DFS from this green node, we'll capture all 7 of these. So the point is, if we call DFS, it looks like we're going to get a union of possibly multiple SCCs. In fact, in the worst case, if we invoke DFS from the leftmost node, what's it going to discover? It's going to discover the entire graph. And that didn't give us any insight into the strong component structure at all. So what's the takeaway point is? The takeaway point is, if you call DFS from just the right place, you'll actually uncover an SCC. If you call it from the wrong place, it will give you no information at all. So the magic of the algorithm that we're going to discuss next is we'll show how in a super slick pre-processing step, which ironically is itself called the depth first search, we can in linear time compute exactly where we want to start the subsequent depth first searches from, so that each invocation gets us exactly one strongly connected component and nothing more. So the algorithm that I'm going to show you is due to Kazaraju, and it will show the following theorem, that the strongly connected components of a directed graph can be computed in linear time. And as we'll see, the constants are also very small. It's really just going to be 2 passes of depth first search. And again, let me remind you that for many problems, it's natural to assume that the number of edges is at least the number of nodes, because you're only interested in cases where the graph is connected. Of course, when you're computing connected components, that's one of the most natural cases where you might have a super sparse, broken up graph. So we're not going to assume m is at least n, so that's why linear time is going to be m plus n, because that's the size of the input. And we don't know, either m could be bigger than n or n could be bigger than m. We have no idea. Kazaraju's algorithm is shocking in its simplicity. It has 3 steps. Let me tell you what they are. First, very mysteriously, we're going to reverse all of the arcs of the given graph. Totally not clear why that would be an interesting thing to do yet. Then we're going to do our first pass, our first depth first search, and we're going to do it on the reverse graph. Now, the naive way to implement this would be you literally construct a new copy of the input graph with all of the arcs in the reverse direction and then just run depth first search on it. Of course, the sort of obvious optimization would be to just run DFS on the original graph, but going across arcs backward. So I'll let you think through the details of how you do that, but that just works. You run DFS, and instead of going forward along edges, you go backward along edges. That simulates depth first search on the reverse graph. Now, I've written here DFS loop, and that just means the usual trick where to make sure that you see all of the nodes of the graph, even if it's disconnected, you have an outer loop where you just try each starting point separately. If you haven't already seen it, then you run DFS from that given node. I'll be more detailed on the next slide. And the third step is just you run depth first search again, but this time on the original graph. Now, at this point, you should be thinking that I'm totally crazy, right? So what are we trying to do? We're trying to compute these strongly connected components. We're trying to actually compute real objects, these maximal strongly connected regions. And all I'm doing is searching the graph. And I do it once forward, I do it once backward. I mean, it doesn't really seem like I'm computing anything. So here's the catch, and it's a very minor catch. So we're going to need to do a little bit of bookkeeping. It's going to be very low overhead, so we'll still have a blazingly fast algorithm. But with a little bit of bookkeeping, here's what's going to happen. The second depth first search, which searches the graph, will, in its search process, discover the strongly connected components one at a time in a very natural way. And that'll be really obvious when we do an example, which we'll do in just a second. Now, for the second depth first search to work in this magical way, where it just discovers the strongly connected components one at a time, it's really important that it executes the depth first searches in a particular order, that it goes through the nodes of the graph in a particular order. And that is exactly the job of the first pass. The depth first search on the reverse graph is going to compute an ordering of the nodes, which, when the second depth first search goes through them in that order, it will just discover the SCCs one at a time in linear time. So let me say a little bit more about the form of the bookkeeping, and then I'll show you how that bookkeeping is kept as we do depth first search. So we're going to have a notion of a finishing time of a vertex, and that's going to be computed in the first pass when we do depth first search on the reverse graph. And we're going to make use of this data in the second pass. So rather than just going through the nodes of the graph in an arbitrary order, like we usually do when we sort of have a looped depth first or breadth first search, we're going to make sure that we go through the vertices in decreasing order of these finishing times. Now, there's still the question of in what sense does this second depth first search discover and report the strongly connected components that it finds. So we're going to label each node in the second pass with what we call a leader. And the idea is that the nodes in the same strongly connected component will be labeled with exactly the same leader node. And again, all of this will be much more clear once we do a concrete example. But I want to have it down for the record right now. So that's the algorithm at a high level. It's really just 2 passes of DFS with some bookkeeping, but this is underspecified. You really shouldn't understand how to implement the algorithm just yet. So what do I owe you? I owe you exactly what I mean by DFS loop, although this you've seen more or less in the past. It's just a loop over all the vertices of the graph, and then if you haven't seen something yet, you DFS from that starting point. I need to tell you what finishing times are and how they get computed. They're just going to be integers 1 to n, which is basically when depth first search gets finished with one of the nodes. And then I need to tell you how you compute these leaders. So let me tell you all 3 of those things on the next slide. So the workhorse for Casaraju's strongly connected components algorithm is this DFS loop subroutine. And it takes as input a graph. Okay, so it does not take as input a starting node. It's going to loop over possible starting nodes. Now for the bookkeeping, to compute finishing nodes, we're going to keep track of a global variable that I'll call t, which we initialize to 0. The point of t is to count how many nodes we've totally finished exploring at this point. So this is the variable we use to compute those finishing times in the first pass, that magical ordering that I was talking about. Now we're also going to have a second global variable to compute these things I was calling leaders, and these are only relevant for the second pass. So what S is going to keep track of is the most recent vertex from which a DFS was initiated. So to keep the code simple, I'm just going to do all of the bookkeeping in DFS loop. But really DFS loop gets called twice, once on the reverse graph, once in the forward graph, and we only need to compute these finishing times in the first pass on the reverse graph, and we only need to compute these leaders on the second pass for the forward graph. But let's just keep them both in there just for kicks. Now we're going to need to loop through the vertices. And so the question is, in what order are we going to loop through the vertices? And that's going to happen differently in the 2 different passes. But let me just use some common notation. Let's just assume in the subroutine that the nodes are somehow labeled from 1 to n. In our first depth first search, it's going to be labeled totally arbitrary. So these are basically just the names of the node or their position in the node array, whatever. You just do it in some arbitrary order. Now, the second time we run DFS loop, as indicated on the previous slide, we're going to use the finishing times as the labeling. And as we'll see, the finishing times are indeed numbers between 1 and n. So now what we do is we just iterate through the nodes in decreasing order. And if we haven't already seen node I, then we initiate a DFS from it. So as usual, we're going to be maintaining a local Boolean to keep track of whether we've already seen a node yet in one of the DFS passes. Now remember, the global variable S is responsible for keeping track of the most recent node from which depth first search had been initiated. So if I is not explored and we initiate a depth first search from it, we better reset S. And then we do the usual DFS in G, starting from the source node I. So for completeness, let me just remind you what the depth first search subroutine looks like. So now we're given a graph and a starting node. So the first time we see a node, we mark it as explored. And just a side note that once a node is marked explored, it's explored for this entire invocation of DFS loop. Okay, so even if this DFS from a given node I finishes and then the outer for loop marches on and encounters I again, it's still going to be marked as explored. Now, one of our bookkeeping jobs is to keep track of from which vertex did the DFS that discovered I get called. So when I is first encountered, we remember that S was the node from which this DFS originated. And that, by definition, is the leader of I. And then we do what we always do with depth first search. We immediately look at the arcs going out of I, and we try to recursively DFS on any of those, although, of course, we don't bother to do it if we've already seen those nodes. Now, once this for loop has completed, once we've examined every outgoing arc from I, and for each node j, either we already saw it in the past or we've recursively explored from j and have returned, at that point we call ourselves done with node I. There's no more outgoing arcs to explore. We think of it being finished. Remember, t is the global variable that's keeping track of how many nodes we're done with. So we increment t because now we're done with I. And we also remember that I was the tth vertex with which we finished. That is, we set I's finishing time to be t. Because depth first search is guaranteed to visit every node exactly once, and that therefore finish with every node exactly once, this global counter t, well, when the first node is finished, it'll be value 1. Then when the next node gets finished, it'll have value 2. Then it'll have value 3, and so on. When the final node gets finished with, it'll have value n. So the finishing times of the nodes are going to be exactly the integers from 1 to n. Let's make this much more concrete by going through a careful example. In fact, I think it'll be better for everybody if you yourself trace through part of this algorithm on a concrete example. So let me draw a 9-node graph for you. So to be clear, let's assume that we've already executed step 1 of the algorithm. That is, we've already reversed the graph. So that is, this blue graph that I've drawn on the slide, this is the reversal. We've already reversed the arcs. Moreover, the nodes are labeled in some arbitrary way from 1 to 9. Just assume these are how they show up in the node array, for example. And remember, in the DFS loop routine, you're supposed to process the nodes from top to bottom, from n down to 1. So my question for you then is, in the second step of the algorithm, when we run DFS loop and we process the nodes from the highest named 9 in order down to the lowest named 1, what are the finishing times that we're going to compute as we run DFS loop? Now, it is true that you can get different finishing times depending on the different choices that DFS loop has to make about which outgoing arc to explore next. But I've given you 4 options for what the finishing times of the nodes 1, 2, 3, all the way up to 9 respectively might be, and only one of these 4 could conceivably be an output of the finishing times of DFS loop on this graph. So which one is it? All right, so the answer is the 4th option. That is the only one of these 4 sets of finishing times that you might see being computed by DFS loop on this blue graph. So let's go ahead and trace through DFS loop and see how we might get this set of finishing times. So remember, in the main loop, we start from the highest node, 9, and then we descend down to the lowest node, 1. So we start by invoking DFS from the node 9. So now, from here, there's only one outgoing arc. We have to go to, so we mark 9 as explored. And then there's only one place we can go. We can go to 6, so we mark 6 as explored. Now there's 2 places we can go next. We can either go to 3 or we can go to 8. And, in general, DFS could do either one. Now, to generate this 4th set of finishing times, I'm going to need to assume that I go to 3 first. Okay? So, again, what DFS does, what we're assuming it does, it starts at 9, then it has to go to 6, it marks those as explored, then it goes to 3. It does not go to 8 first, it goes to 3 first. Now from 3 there's only one outgoing arc which goes to 9, but 9 we've already marked as explored. So it's not going to re-explore 9, it's going to skip that arc. Since that's 3's only outgoing arc, then that for loop completes, and so then 3 is the first node to finish. So when we finish with 3, we increment t, it started at 0, now it's 1, and we set the finishing time of 3 to be 1. Just like we said it was in the example. So now we go back, now we backtrack to 6. Now we have another outgoing arc from 6 to explore, so now we go to 8. From 8 we have to go to 2, from 2 we have to go to 5, from 5 we have to go to 8. 8 we've already seen, so then we're going to be done with 5, because that was its only outgoing arc. So then we increment t, now it's 2, and the finishing time of 5 is going to be 2, as promised. So now we backtrack to 2, there's no more outgoing arcs from 2. So 2 is going to be the 3rd one that we finish, as promised. Then we finish with 8, so the finishing time for 8 is going to be the 4th node to be done, as promised. Now we backtrack to 6, we're done with 6. That's the 5th node to be completed, as promised. And then finally we get all the way back to where we started at 9, and 9 is the 6th node to be completed, as promised. Now, if we were computing those leaders, all of these nodes would get the leader 9. But again, the leaders are only relevant for the second pass, so we're just going to ignore the leaders as we're doing this trace. We're just going to keep track of the finishing times. So now we're not done. So all we did is we finished with the DFS that is invoked from the node 9, and we found 6 of the nodes total in that depth first search. So now we return to the outer for loop, and we decrement I. So it started at 9, we're done with that. Now we go down to 8. We say, have we already seen 8? Yes, 8's already explored, so we skip it. We decrement I down to 7. We say, have we already seen node 7? No, we have not. Okay, 7 is not yet explored. So we invoke DFS now from node 7. 7 has 2 outgoing arcs. It can either go to 4 or it can go to 9. Let's say it checks the outgoing arc to 9 first. Now 9 we already explored. Granted, that was in an earlier part of the for loop, but we remember that. We were going to keep track of who got explored on previous iterations of the for loop, so we don't bother to re-explore 9, so we skip that. So now from 7 we have to go to 4, from 4 we have to go to 1, from 1 we have to go back to 7. 7's already been explored, so we backtrack. Now we're done with 1. So 1 is the next one we're completed with, and the finishing time of 1 is going to be 7, as promised. We backtrack to 4. There's no more outgoing arcs from 4 to explore, so that's going to be the 8th one to finish, as promised. And then the last one to finish is poor node 7. It is last. So that would be an example of how the DFS loop subroutine computes finishing times on a reversed graph. So now let's work through the second pass on the forward version of the graph using the same example. Now remember, the point of the first pass is to compute a magical ordering, and the magical ordering is these finishing times. So we're going to throw out the original node names, and we're going to replace the node names in blue by the finishing times in red. We're also going to work with the original graph, which means we have to reverse the arcs back to where they were originally. So those are the two changes you're going to see when I redraw this graph. First of all the arcs will reverse orientation. Second of all of the nodes will change names from their original ones to the finishing times that we just computed. So here's our new graph with the new node names and all of the arcs with their orientation reversed. And now we run DFS again on this graph. And again, we're going to process the nodes in order from the highest label 9 down to the lowest label 1. Moreover, we don't need to compute finishing times in the second pass. We only need to do that in the first pass. But in the second pass, we have to keep track of the leaders. And remember, the leader of a vertex is the vertex from which DFS was called that first discovered that node. All right, so what's going to happen? Well, in the outer for loop, again, we start with I equal to 9, and we invoke DFS from the node 9. And so that's going to be the current leader, because that's where the current DFS got initiated. Now, from 9, there's only one choice. We have to go to 7. From 7, there's only one choice. We have to go to 8. From 8, there's only one choice. We have to go back to 9. And then 9's already been seen, so we backtrack. We go back to 8. We go back to 7. We go back to 9, and that's it. So when we invoke DFS from node 9, the only things that we encounter are the nodes 7, 8, and 9. And these are all going to be given the leader vertex 9. You will notice that this is indeed one of the strongly connected components of the graph. We just sort of found it with this invocation of DFS from the node 9. So now we go back to the outer for loop, and we say, okay, let's go to node 8. Have we already seen 8? Yes. What about 7? Have we already seen 7? Yes. What about 6? Have we already seen 6? We have not. We have not yet discovered 6. So we invoke DFS from node 6. We reset the global source vertex S to 6. From 6, we can go to 9 or we can go to 1. So let's say we explore 9 first. Well, we already saw 9 in an earlier iteration of the for loop, so we don't explore it again. So we don't discover 9 now. So we backtrack to 6. We go to 1. From 1, we have to go to 5. From 5, we have to go to 6. And then we start backtracking again. So the only new nodes that we encounter when we invoke DFS from the node 6 are the vertices 6, 1, and 5. And all of these will have a leader vertex of 6, because that's where we called DFS from when we first discovered these 3 nodes. And you'll notice this is another SCC of this directed graph. So we invoke DFS again, now from a new node, the new node 6, and what it discovered, the new nodes it discovered, was exactly an SCC of the graph. Nothing more, nothing less. So now we return to the outer for loop. We go to node 5. Have we already seen 5? Yes. Have we already seen 4? No, we haven't seen 4 yet. So now we invoke DFS from 4. Again, we can try to explore 5, but we've seen that before. We're not going to explore it again. So from 4 then, we have to go to 2. From 2, we have to go to 3. From 3, you have to go back to 4. And then after all the backtracking, we're done. So the final call to DFS will be from the node 4. And that DFS will newly discover precisely the nodes 2, 3, and 4. They will all have the leader vertex 4, because that was where this DFS was called from. It's true, we'll go back to the for loop and we'll check, have we seen 3 yet? Yes. Have we seen 2 yet? Yes. Have we seen 1 yet? Yes. And then the whole thing completes. And what we see is that using the finishing times computed from that first depth first search pass, somehow the strongly connected components of this graph just showed up and presented themselves to us one at a time on a silver platter. Every time we invoked DFS, the nodes we discovered newly were precisely one of the SCCs. Nothing more, nothing less. And that's really what's going on in this algorithm. It turns out this is true in general. The first pass, DFS on the reverse graph, computes finishing times so that if you then process nodes according to decreased ordering of finishing times, in the second pass, Each invocation to DFS will discover one new SCC and exactly one SCC. So they'll just present themselves to you, one per DFS call in that second passes for loop. This is, of course, merely an example. You should not just take a single example as proof that this algorithm always works. I will give you a general argument in the next video. But hopefully there's at least a plausibility argument. No longer does this three-step algorithm seem totally insane, and maybe you could imagine perhaps it works. At least there's some principles going on where you first compute the right ordering to process the nodes, and then the second pass peels off SCCs one at a time like layers from an onion. One thing that I hope is pretty clear is that this algorithm, correct or not, is blazingly fast. Pretty much all you do is 2 depth-first searches. And since depth-first search, as we've seen in the past, runs in time linear in the size of the graph, so does Kazaraju's 2-pass algorithm. There are a couple subtleties, and I encourage you to think about this, and you'll be forced to think about this in the programming project for week 4. So for example, in the second pass, how do you process the nodes in decreasing order of finishing time? You don't want to sort the nodes by their finishing time because that would take n log n time. So you need to make sure that you remember in the first pass, that you sort of remember the nodes in a way that you can just do a linear scan through them in a second pass. So there are some details, but if your intuition is that this is really just double DFS properly implemented, that's pretty much exactly right. So having spelled out the full implementation, argued that it's definitely a linear time algorithm, and given at least a plausibility argument via an example that it might conceivably be correct, let's now turn to the general argument. So the goal of this video is to prove the correctness of Kazaraju's 2-pass depth-first search-based linear time algorithm that computes the strongly connected components of a directed graph. So I've given you the full specification of the algorithm. I've also given you a plausibility argument of why it might work, in that at least it does something sensible on an example. Namely, it first does a pass of depth-first search on the reverse graph. It computes this magical ordering. And what's so special about this ordering is then when we do a depth-first search using this ordering on the forward graph, it seems to do exactly what we want. Every invocation of depth-first search to some new node discovers exactly the nodes of a strong component and no extra stuff. Remember, that was our first observation about that was unclear whether depth-first search would be useful or not for computing strong components. If you call depth-first search from just the right place, you're going to get exactly the nodes of an SCC and nothing more. If you call it from the wrong place, you might get all of the nodes of the graph and get no information at all about the structure of the strong components. And at least in this example, this first pass with the finishing time seems to be leading us to invoking depth-first search from exactly the right places. So remember how this worked in the example. So in the top graph, I've shown you the graph with the arcs reversed. This is where we first invoke DFS loop with a loop over the nodes going from the highest node name 9 all the way down to the node name 1. And here we compute finishing times. That's the bookkeeping that we do in the first pass. So we just keep a running count of how many nodes we've finished processing. That is how many we've both explored that node as well as explored all of the outgoing arcs. And so that gives us these numbers in red, these finishing times between 1 and 9 for the various nodes. Those became the new node names in the second graph, and then we reversed the arcs again to get the original graph back. And then we saw that every time we invoked DFS in our second pass, we uncovered exactly the nodes of an SCC. So when we invoked it from the node 9, we discovered 9, 8, and 7. Those all have the leader vertex 9. Then when we next invoked DFS from 6, we discovered 6, 5, and 1, and nothing else. And then finally we invoked it from 4, and we discovered 2, 3, and 4, and nothing else. And those are exactly the 3 SCCs of this graph. So let's now understand why this works in any directed graph, not just in this one example. So let's begin with a simple observation about directed graphs, which is actually interesting in its own right. The claim is that every directed graph has 2 levels of granularity. If you squint, if you sort of zoom out, then what you see is a directed acyclic graph, of course, comprising its strongly connected components. And if you want, you can zoom in and focus on the fine-grained structure with one SCC. A little bit more precisely, the claim is that the strongly connected components of a directed graph induce in a natural way an acyclic metagraph. So what is this metagraph? What are the nodes and what are the arcs? What are the edges? Well, the metanodes are just the SCCs. So we think of every strongly connected component as being a single node in this metagraph. So call them, say, C1 up to CK. So what are the arcs in this metagraph? Well, they're basically just the ones corresponding to the arcs between SCCs in the original graph. That is, we include in the metagraph an arc between the strong components C and C hat, from C to C hat, if and only if there's an arc from a node in C to a node in C hat in the original graph G. So for example, if this is your C and this other triangle is your C hat, and you have one or maybe multiple edges going from C to C hat, then in the corresponding metagraph you're just going to have a node for C, a node for C hat, and a directed arc from C to C hat. So if we go back to some of the directed graphs that we've used as running examples, so if we go back to the one that at the beginning of the previous video, which looked maybe something like this, the corresponding directed acyclic graph has 4 nodes and 4 arcs. And for the running example we used to illustrate Casaragi's algorithm with the 3 triangles, the corresponding metagraph would just be a path with 3 nodes. So why is this metagraph guaranteed to be acyclic? Well, remember, metanodes correspond to strong components, and in a strong component you can get from anywhere to anywhere else. So if you had a cycle that involved 2 different metanodes, that is 2 different strong connected components, remember on a directed cycle you can also get from anywhere to anywhere else. So if you had 2 supposedly distinct SCCs, but you could get from the one to the other and vice versa, they would collapse into a single SCC. You can get from anywhere to anywhere in one, anywhere from anywhere in the other one, and you can also go between them at will. So you can get from anywhere in one, you can get from anywhere in this union to anywhere in the union. So not just in this context of computing strong components, but also just more generally, this is a useful fact to know about directed graphs. On the one hand, they can have very complex structure within a strong component. You have paths going from everywhere to everywhere else, and it may be sort of complicated looking. But at a higher level, if you abstract out at the level of SCCs, you're guaranteed to have this simple DAG, the simple directed acyclic graph structure. So to reinforce these concepts and also segue into thinking about Casaragi's algorithm in particular, let me ask you a question about how reversing arcs affects the strong components of a directed graph. So the correct answer to this quiz is the 4th one. The strong components are exactly the same as they were before. In fact, the relation that we described is exactly the same as it was before, so therefore the equivalence classes of the strong components is exactly the same. So if 2 nodes are related in the original graph, that is, there's a path from U to V and a path from V to U, that's still true after you reverse all the arcs. You just use the reversal of the 2 paths that you had before. Similarly, if the 2 nodes weren't related before, for example, because you could not get from U to V, well then after you reverse everything, then you can't get from V to U. So again, you don't have this relation holding. So the SCCs are exactly the same in the forward or the backward graph. So in particular, in Casaragi's algorithm, the strong component structure is exactly the same in the first pass of DFS and in the second pass of DFS. So now that we understand how every directed graph has a metagraph where the nodes correspond to its strongly connected components and you have an arc from one SCC to another, if there's any arc from any node in that SCC to the other SCC in the original graph, I'm in a position to state what's the key lemma that drives the correctness of Casaragi's 2-pass algorithm for computing the strongly connected components of a directed graph. So here's the lemma statement. It considers 2 strongly connected components that are adjacent in the sense that there's an arc from one node in one of them to one node in the other one. So let's say we have one SCC C1 with a node I and another SCC C2 with a node J, and that in G, in the graph, there's an arc directly from I to J. So in this sense, we say that these SCCs are adjacent, with the second one being in some sense after the first one. Now let's suppose we've already run the first pass of the DFS loop subroutine, and remember that works on the reversed graph. So we've invoked it on the reversed graph, we've computed these finishing times. As usual, we'll let F denote the finishing times computed in that depth first search subroutine on the reversed graph. The lemma then asserts the following. It says, first, amongst all the nodes in C1, look at the one with the largest finishing time. Similarly, amongst all nodes in C2, look at the one with the biggest finishing time. Amongst all of these, the claim is the biggest finishing time will be in C2, not in C1. So what I want to do next is I want to assume that this lemma is true temporarily, and I want to explore the consequences of that assumption. And in particular, what I want to show you is that if this lemma holds, then we can complete the proof of correctness of Casaragi's 2-pass SCC computation algorithm. Okay, Okay, so if the lemma is true, then after I'll give you the argument about why we're done, about why we just peel off the strongly connected components one at a time with the second pass of depth first search. Now, of course, a proof for the hole in it isn't a proof, so at the end of the lecture I'm going to fill in the hole. That is, I'm going to supply a proof of this key lemma. But for now, as a working hypothesis, let's assume that it's true. Let's begin with a corollary, that is, a statement which follows essentially immediately from the statement of the lemma. So for the corollary, let's forget about just trying to find the maximum finishing time in a single SCC. Let's think about the maximum finishing time in the entire graph. Now, why do we care about the maximum finishing time in the entire graph? Well, notice that's exactly where the second pass of depth first search is going to begin. Right? So it processes nodes in order from largest finishing time to smallest finishing time. So equivalently, let's think about the node at which the second pass of depth first search is going to begin, i.e. the node with the maximum finishing time. Where could it be? Well, the corollary is that it has to be in what I'm going to call a sync, strongly connected component. That is a strongly connected component without any outgoing arcs. So, for example, let's go back to the metagraph of SCCs for the very first directed graph we looked at. You recall that in the very first directed graph we looked at when we started talking about this algorithm, there were 4 SCCs. So there was a C1, a C2, a C3, and a C4. And of course, within each of these components, there could be multiple nodes, but they're all strongly connected to each other. Now, let's use F1, F2, F3, and F4 to denote the maximum finishing time in each of these SCCs. So we have F1, F2, F3, and F4. So now we have 4 different opportunities to apply this lemma, right? There's 4 different pairs of adjacent SCCs. And so what do we find? We find that, well, comparing F1 and F2, because C2 comes after C1, that is, there's an arc from C1 to C2, the max finishing time in C2 has to be bigger than that in C1. That is, F2 is bigger than F1. For the same reasoning, F3 has to be bigger than F1. Symmetrically, we can apply the lemma to the pairs C2, C4 and C3, C4, and we get that F4 has to dominate both of them. You'll notice we actually have no idea whether F2 or F3 is bigger, so that pair we can't resolve, but we do know these relationships. Okay, F1 is the smallest and F4 is the smallest. And you'll also notice that C4 is a sync SCC in the sense that it has no outgoing arcs. And if you think about it, that's a totally general consequence of this lemma. So a simple proof by contradiction would go as follows. Consider the strongly connected component with the maximum F value. Suppose it was not a sync SCC, then it has an outgoing arc. Follow that outgoing arc to get to some other SCC. By the lemma, the SCC you've gotten to has an even bigger maximum finishing time. So that contradicts the fact that you started in the SCC with a maximum finishing time. Okay? So just like in this cartoon where the unique sync SCC has to have the largest finishing time, that's totally general. As another sanity check, we might return to the 9-node graph where we actually ran Kazaraju's algorithm. And looking at the forward version of the graph, which is the one on the bottom, we see that the maximum finishing times in the 3 SCCs are 4, 6, and 9. Okay, it turns out they're the same as the leader nodes, which is not an accident if you think about it for a little while. And again, you'll observe the maximum finishing time in this graph, namely 9, is indeed in the leftmost SCC, which is the only SCC with no outgoing arcs. Okay, but it's totally general. Basically, you can keep following arcs and you keep seeing bigger and bigger finishing times. So the biggest one of all, it has to be somewhere where you get stuck, where you can't go forward, where there's no outgoing arcs, and that's what I'm calling a sync SCC. Okay, so assuming the lemma is true, we now know this corollary is true. Now, using this corollary, let's finish the proof of correctness of Kazaraju's algorithm modulo a proof of the key lemma. So I'm not going to do this super rigorously, although everything I say is correct and can be made rigorous. And if you want a more rigorous version, I'll post some notes on the course website, which you can consult for more details. So what the previous corollary accomplished, it allows us to locate the node with maximum finishing time. We can locate it in somewhere in some sync SCC. Well, let me remind you about the discussion we had at the very beginning of talking about computing strong components. We were trying to understand whether depth first search would be a useful workhorse for finding the strong components. And the key observation was that it depends where you begin that depth first search. So for example, in this graph with 4 SCCs shown in blue on the right, a really bad place to start a DFS call, depth first search, would be somewhere in C1. somewhere in this source SCC. So this is a bad DFS. Why is it bad? Well, remember what depth first search does. It finds everything findable from its starting point. And from C1, you can get to the entire world. You can get to all the nodes in the entire graph. So you'll discover everything. And this is totally useless because we wanted to discover much more fine-grained structure. We wanted to discover C1, C2, C3, and C4 individually. So that would be a disaster if we invoked depth first search somewhere from C1. Fortunately, that's not what's going to happen. Right? We computed this magical ordering in the first pass to ensure that we look at the node with the maximum finishing time first, and by the corollary, the maximum finishing time is going to be somewhere in C4. That's going to be a good DFS in the sense that when we start exploring from anywhere in C4, there's no outgoing arcs. So of course we're going to find everything in C4. Everything in C4 is strongly connected to each other, but we can't get out. We will not have the option of trespassing on other strong components, and we're not going to find them. So we're only going to find C4, nothing more. Now here's where I'm going to be a little informal, although again everything I'm going to say is going to be correct. So what happens now once we've discovered everything in C4? Well, all the nodes in C4 get marked as explored as we're doing depth first search, and then they're basically dead to us, right? The rest of our depth first search loop will never explore them again. They're already marked as explored. If we ever see them, we don't even go there. So the way to think about that is when we proceed with the rest of our for loop in DFS loop, it's as if we're starting afresh. We're doing depth first search from scratch on a smaller graph, on the residual graph. The graph G with this newly discovered strong component C star deleted. So in this example on the right, all of the nodes in C4 are dead to us, and it's as if we run DFS anew just on the graph containing the strong components C1, C2, and C3. So in particular, where is the next invocation of depth first search going to come from? It's going to come from some sync SCC in the residual graph, right? It's going to start at the node that remains and that has the largest finishing time left. So there's some ambiguity in this picture. Again, recall we don't know whether F2 is bigger or F3 is bigger. It could be either one. So maybe F2 is the largest remaining finishing time, in which case the next DFS invocation is going to begin somewhere from C2. Again, the only things outgoing from C2 are these already explored nodes. They're effectively deleted. We're not going to go there again. So this is essentially a sync SCC. We newly discover the nodes in C2 and nothing else. Those are now effectively deleted. Now the next invocation of DFS will come from somewhere in F3, somewhere in C3. That's the only remaining sync SCC in the residual graph. So the third call to DFS will discover this stuff. And now, of course, we're left only with C1. And so the final invocation of DFS will emerge from and discover the nodes in C1. And in this sense, because we've ordered the nodes by finishing times in a DFS with a reverse graph, that ordering has this incredible property that when we process the nodes in the second pass, we will just peel off the strongly connected components one at a time. If you think about it, it's in reverse topological order with respect to the directed acyclic graph of the strongly connected components. So we've constructed a proof of correctness of Kazaraju's algorithm for computing strongly connected components, but again, there's a hole in it. So we completed the argument assuming a statement that we haven't proved. So let's fill in that last gap in the proof, and we'll be done. And so what we need to do is prove the key lemma. Let me remind you what it says. It says if you have two adjacent SCCs, C1 and C2, there's an arc from a node in C1, call it I, to a node in C2, say J, then the max finishing time in C2 is bigger than the max finishing time in C1. Whereas always, these finishing times are computed in that first pass of depth first search loop in the reversed graph. All right, now the finishing times are computed in the reversed graph, so let's actually reverse all the arcs and reason about what's happening there. We still have C1, it still contains the node I. We still have C2, it still contains the node J. But now, of course, the orientation of the arc has reversed. So the arc now points from J to I. Recall we had a quiz which asked you to understand the effect of reversing all arcs on the SCCs, and in particular, there is no effect. So the SCCs in the reverse graph are exactly the same as in the forward graph. So now we're going to have two cases in this proof, and the cases correspond to where we first encounter a node of C1 union C2. Now remember, when we do this DFS loop, this second pass, because we have this outer for loop that iterates over all of the nodes, we're guaranteed to explore every single node of the graph at some point. So in particular, we're going to explore at some point every single node in C1 union C2. What I want you to do is pause the algorithm when it first, for the first time, explores some node that's in either C1 or C2. There's going to be two cases, of course, because that node might be in C1, you might see that first, or it might be in C2. You might see something from C2 first. So our case 1 is going to be when the first node that we see from either one happens to lie in C1. And the second case is where the first node V that we see happens to lie in C2. So clearly exactly one of these will occur. So let's think about case 1, when we see a node of C1 before we see any nodes of C2. So in this case, where we encounter a node in C1 before we encounter any node in C2, the claim is that we're going to explore everything in C1 before we ever see anything in C2. Why is that true? The reason is there cannot be a path that starts somewhere in C1, like for example at the vertex V, and reaches C2. And this is where we're using the fact that the metagraph on strongly connected components is acyclic. Right, C1 is strongly connected, C2 is strongly connected. You can get from C2 to C1, and if you can also get from C1 back to C2, this all collapses into a single strongly connected component. But that would be a contradiction. We're assuming C1 and C2 are distinct strongly connected components. Therefore, you can't have paths in both directions. We already have a path from right to left via JI, so there's no path from left to right. That's why if you originate a depth first search from somewhere inside C1, like this vertex V, you finish exploring all of C1 before you ever are going to see C2. You're only going to see C2 at some later point in the outer for loop. So what's the consequence that you completely finish with C1 before you ever see C2? Well, it means every single finishing time in C1 is going to be smaller than every single finishing time in C2. So that's even stronger than what we're claiming. We're just claiming that the biggest thing in C2 is bigger than the biggest of C1. But actually, finishing times in C2 totally dominate those in C1, because you finish C1 before you ever see C2. So let's now have a look at case 1 actually in action. Let's return to the 9-node graph on which we actually ran Kajarajou's algorithm to completion. So if we go back to this graph which has the 3 connected components, and remember it's the bottom version is the forward version, the top version is the reversed version. So if you think about the middle SCC as being C1, playing the role of C1, and the leftmost SCC playing the role of C2, then what we have exactly is case 1 of the key lemma. So which was the first of these 6 vertices visited during the DFS loop in the reversed graph? Well, that would just be the node with the highest name, so the node 9. So this was the first of these 6 vertices that depth first search ever looked at in the first pass. That lies in what we're calling C1, and indeed everything in C1 was discovered in that pass before anything in C2, and that's why all of the finishing times in C2, the 7, 8, and 9, are bigger than all of the finishing times in C1, the 1, 5, and 6. So we're good to go in case 2. We've proven, in case 1, we've proven the lemma when it's the case that amongst the vertices in C1 union C2, depth first search in the first pass sees something from C1 first. So now let's look at this other case, this gray case, which could also happen, totally possible, where the first thing we see when depth first searching in the first pass is something from C2. And here now is where we truly use the fact that we're using depth first search rather than some other graph search algorithm like breadth first search. There's a lot of places in this algorithm you could swap in breadth first search, but in this case too you'll see why it's important we're using depth first search to compute the finishing times. And what's the key point? The key point is that when we invoke depth first search beginning from this node V, which is now assuming the line C2, remember depth first search will not complete. We won't be done with V until we've found everything there is to find from it. Right? So we recursively explore all of the outgoing arcs, they recursively explore all of their outgoing arcs, and so on. It's only when all paths going out of V have been totally explored and exhausted that we finally backtrack all the way to V and we consider ourselves done with it. That is, depth first search in the reverse graph initiated at V won't finish until everything findable has been completely explored. Because there's an arc from C2 to C1, obviously everything in C2 is findable from V, that's strongly connected. We can get from C2 to C1 just using this arc from J to I. C1 being strongly connected, we can then find all of that. Maybe we can find other strongly connected components as well, but for sure, depth first search starting from V will find everything in C1 union C2, maybe some other things, and we won't finish with V until we finish with everything else. That's the depth first search property. For that reason, the finishing time of this vertex V will be the largest of anything reachable from it. So in particular, it'll be larger than everything in C2, but more to the point, it'll be larger than everything in C1, which is what we were trying to prove. Again, let's just see this quickly in action in the 9-node network on which we traced through Casaragiu's algorithm. So to show the role that case 2 is playing in this concrete example, let's think of the rightmost strongly connected component as being C1. And let's think of the middle strongly connected component as being C2. Remember last time we called the middle one C1 and the leftmost one C2. Now we're calling the rightmost one C1 and the middle one C2. So again, we have to ask the question, of the 6 nodes in C1 union C2, what is the first one encountered in the depth first search that we do in the first pass? And that again is the node 9. Okay, the node which is originally labeled 9. So that's the same node that was relevant in the previous case. But now with this relabeling of the components, 9 appears in the strongly connected component C2, not in the one labeled C1. So that's the reason now we're in case 2, not in case 1. And what you'll see is, what is the finishing time that this originally labeled 9 node gets? It gets the finishing time 6. And you'll notice 6 is bigger than any of the other finishing times of any of the other nodes in C1 or C2. All the other 5 nodes have the finishing times 1 through 5. And that's exactly because when we ran depth first search in the first pass and we started it at the node originally labeled 9, it discovered these other 5 nodes and finished exploring them first before finally backtracking all the way back to 9 and deeming 9 fully explored. It was only at that point that 9 got its finishing time, after everything reachable from it had already gotten their lower finishing times. So that wraps it up. We had 2 cases depending on whether in these 2 adjacent SCCs the first vertex encountered was in the C1 or in C2. Either way, it doesn't matter. The largest finishing time has to be in C2. Sometimes it's bigger than everything. Sometimes it's just bigger than the biggest in C1, but it's all the same to us. And to recap how the rest of the proof goes, we had a corollary based on this lemma, which says maximum finishing times have to lie in sync strongly connected components, and that's exactly where we want our depth first search to initiate. If you're initiated in a strong component with no outgoing arcs, you do DFS, the stuff you find is just the stuff in that strongly connected component. You do not have any avenues by which to trespass on other strong components. So you find exactly one SCC. In effect, you can peel that off and recurse on the rest of the graph. And our slick way of implementing this recursion is to just do the single second DFS pass where you just treat the nodes in decreasing order of finishing times. That, in effect, unveils all of the SCCs in reverse topological ordering. So that's it, Casaragiu's algorithm and the complete proof of correctness. A blazingly fast graph primitive that in any directed graph will tell you its strong components. So we've now put in a lot of work designing and analyzing super fast algorithms for reasoning about graphs. So in this optional video, what I want to do is show you why you might want such a primitive, especially for computation on extremely large graphs. Specifically, we're going to look at the results of a famous study that computes the strongly connected components of the web graph. So what is the web graph? Well, it's the graph in which the vertices correspond to web pages. So for example, I have my own web page where I list my research papers and also links to courses such as this one. And the edges are going to be directed, and they correspond precisely to hyperlinks. So the links that bring you from one web page to another. Note, of course, these are directed edges, where the tail is the page that contains the hyperlink, and the head is the page that you go to if you click the hyperlink. And so this is a directed graph. So from my home page, you can get to my papers. You can get to my courses. Sometimes I have random links up to things I like say my favorite record store. And of course, for many of these web pages, there are additional links going out or going in. So for example, from my papers, I might link to some of my co-authors. Some of my co-authors might be linking from their home pages to me. Or of course, there's web pages out there which list the currently available free online courses, and so on. So obviously, this is just part of a massive web graph, just a tiny, tiny piece of it. So the origins of the web were probably around 1990 or so, but it started to really explode in the mid-90s. And by the year 2000, it was sort of already beyond comprehension, even though in internet years, the year 2000 is sort of the Stone Age relative to right now, relative to 2012. But still, even by 2000, people were so overwhelmed with the massive scale of the web graph, they wanted to understand anything about it, even the most basic things. Now, of course, one issue with understanding what the graph looks like is you don't even have it locally, right? It's distributed over all these different servers over the entire world. So the first thing people really focused on when they wanted to answer this question was on techniques for crawling. So having software which just follows lots of hyperlinks, reports back to the home base, from which you can assemble at least some kind of sketch of what this graph actually is. So, but then the question is, even once you have this crawled information, even if once you've accessed a good chunk of the nodes and the edges of this network, what does it look like? So what makes this a difficult question? More difficult than, say, for any other directed graph you might encounter? Well, it's simply the massive scale of the web graph. It's just so big. So for the graph used in the particular study I'm going to discuss, like we said, it was in the year 2000, which was sort of the Stone Age compared to 2012. So the graph was small, relatively, but still the graph was really, really big. So it was something like 200 million nodes and 1 billion edges, really 1.5 billion edges. So the reference for the work I'm going to discuss is a paper by a number of authors. The first author is Andre Broder, and then he has many co-authors. And this was a paper that appeared in the WWW conference of the year 2000. That's the World Wide Web Conference. And I encourage you, those of you who are interested, to go track down the paper online and read the original source. So Andre Broder, the lead author, at this time he was at a company that was called Alta Vista. So how many of you remember a company called Alta Vista? Well, some of you, especially the youngest ones among you, maybe have never heard of Alta Vista, and the youngest ones among you maybe can't even conceive of a world in which we didn't have Google. But in fact, there was a time when we had web search, but Google did not yet exist. That was sort of in the maybe 97 or so. And so this was in the very embryonic years of Google, and this data set actually came out of Alta Vista instead. So Broder et al. Wanted to give some answers to this question: what does the web graph look like? And they approached it in a few ways. But the one I'm going to focus on here is they asked, well, what's the most detailed structure we can get about this web graph without doing an infeasible amount of computation, really just sticking to linear time algorithms at the worst. And what have we seen? We've seen that in a directed graph you can get full connectivity information just really using depth-first search. You can compute strongly connected components in linear time with small constants. And that's one of the major things that they did in this study. Now, if you wanted to do the same computation today, you'd have one thing going against you and one thing going for you. The obvious thing that you'd have going against you is that the web is still very much bigger than it was here, certainly by an order of magnitude. The thing that you'd have going for you is now there's specialized systems which are meant to operate on massive data sets. And in particular, they can do things like compute connectivity information on graph data. So what you have to remember, for those of you who are aware of these terms, in 2000, there was no MapReduce, there was no Hadoop, there were no tools for automated processing of large data sets. These guys really had to do it from scratch. So let me tell you about what Broder et al. Found when they did strong connectivity computations on the web graph. They explained their results in what they called the bow tie picture of the web. So let's begin with the center, or the knot, of the bow tie. So in the middle we have what we're going to call a giant strongly connected component, with the interpretation being this is the core of the web in some sense. All right, so all of you know what an SCC is at this point. A strongly connected component is the region from which you can get from any point to any other point along a directed path. So in the context of the web graph, with this giant SCC, what this means is that from any web page inside this blob, you can get to any other web page inside this blob just by traversing a sequence of hyperlinks. And hopefully it doesn't strike you as too surprising that a big chunk of the web is strongly connected, is well connected in this sense. Right, so if you think about all the different universities in the world, probably all of the web pages corresponding to all of the different universities, you can get from any one place to any other place. For example, from the home page on which I put my papers, I often include links to my co-authors, which very commonly are at other universities. So that already provides a web link from some Stanford page to some page at, say, Berkeley or Cornell or whatever. And of course, I'm just one person. I'm just one of many faculty members at Stanford. So you put all of these together, you would expect all of the different SCCs corresponding to different universities to collapse into a single one. And so on for other sectors as well. And then, of course, if you knew that a huge chunk of the web was in the same strongly connected component, so let's say 10% of the web, which would be tens of millions of web pages, you wouldn't expect there to be a second one, right? It would be super weird if there were two different blobs, 10 million web pages each, that somehow were not mutually reachable from each other. That would just, all it takes to collapse two SCCs into one is a lone arc going from one to the other, and then a lone arc in the reverse direction. And then those two SCCs collapse into one. So we do expect a giant SCC, just sort of thinking anecdotally about what the web looks like. And then once we realize there's one giant SCC, we don't expect there to be more than one. All right, so is that the whole story? Is the web graph just one big SCC? Well, one of the perhaps interesting findings of this Broder et al. Paper is that, there is a giant SCC, but it doesn't actually take up the whole web or anything really that close to the entire web. So what else would there be in such a picture? Well, there's the other two ends of the bow tie, which are called the in and the out regions. In the out regions, you have a bunch of strongly connected components, not giant SCCs. We've established there shouldn't be any other giant SCCs, but small SCCs, which you can reach from the giant strongly connected component, but from which you cannot go back to the giant strongly connected component. I encourage you to think about what types of websites you would expect to see in this out part of the bow tie. I'll give you one example. Very often, if you look at a corporate site, including those of well-known corporations, which you would definitely expect to be reachable from the giant SCC, it's actually a corporate policy that no hyperlinks can go from something in the corporate site to something outside the corporate site. So that means the corporate site is going to be a collection of web pages which are certainly strongly connected. Because it's a major corporation, you can certainly get there from the giant SCC, but because of this corporate policy, you can't get back out. Symmetrically, in the in part of the bow tie, you have strongly connected components, generally small ones, from which you can reach the giant SCC, but you cannot get to them from the giant SCC. Again, I encourage you to think about all the different types of web pages you might expect to see in this in part of the bow tie. Certainly, I think one really obvious example would be new web pages. So if you just create something, and then if I just created a web page and pointed it to Stanford University, that would immediately be in this in component, or this in collection of components. Now, if you think about it, this does not exhaust all of the possibilities of where nodes can lie. There's a few other cases that frankly are pretty weird, but they're there. You can have passive hyperlinks which bypass the giant SCC and go straight from the in part of the bow tie to the out part. So Broder et al. Suggested calling these tubes. And then there's also kind of very curious outgrowths going out of the in component, but which don't make it all the way to the giant SCC. And similarly, there's stuff which goes into the out component. And Broder et al. Recommended calling these strange creatures tendrils. And then in fact, you can also just have some weird isolated islands of SCCs that are not connected even weakly to the giant SCC. So this is the picture that emerged from Broder et al.'s strong component computation on the web graph. And here's qualitatively some of the main findings that they came up with. So first of all, that picture on the previous slide I drew roughly to scale, in the sense that all four parts, so the giant SCC, the in part, the out part, and then the residual stuff, the tubes and tendrils, have roughly the same size. More or less 25% of the nodes in the graph. I think this surprised some people. I think some people might have thought that the core, that the giant SCC might have been a little bit bigger than just 25 or 28%. But it turns out there's a lot of other stuff outside of this strongly connected core. You might wonder if this is just an artifact of this data set being from the Stone Age, being from 2000 or so. But people have rerun this experiment on the web graph again in later years. And of course, the numbers are changing because the graph is growing rapidly. But these qualitative findings have seemed pretty stable throughout subsequent reevaluations of the structure of the web. On the other hand, while the core of the web is not as big as you might have expected, it's extremely well connected, perhaps better connected than you might have expected. Now, you'd be right to ask the question, what could I mean by unusually well connected? We've already established that this giant core of the web is strongly connected. You can get from any one place to any other place via a sequence of hyperlinks. What else could you want? Well, in fact, it has a very richer notion of connectivity called the small world property. So let me tell you about the small world property, or the phenomenon colloquially known as 6 degrees of separation. So this is an idea that had been in the air at least since the early 20th century, but really kind of was studied in a major way and popularized by Stanley Milgram, who's a social scientist, back in 1967. So Milgram was interested in understanding, are people at great distance in fact connected by short change of intermediaries? So the way he evaluated this, he ran the following experiment. He identified a friend in Boston, Massachusetts, a doctor, I believe, and so this was going to be the target. And then he identified a bunch of people who were thought to be far away, both culturally and geographically, specifically Omaha. So for those of you who don't live in the U.S., just take it on faith that many people in the U.S. would regard Boston and Omaha as being fairly far apart geographically and otherwise. And what he did is he wrote each of these residents of Omaha the following letter. He said, look, here's the name and address of this doctor who lives in Boston. Okay? Your job is to get this letter to this doctor in Boston. Now, you're not allowed to mail the letter directly to the doctor. Instead, you need to mail it to an intermediary, someone who you know on a first name basis. So, of course, if you knew the doctor on a first name basis, you could mail it straight to them, but that was very unlikely. So, what people would do in Omaha is they'd say, well, I don't know any doctors, or I don't know anyone in Boston, but at least I know somebody in Pittsburgh, and at least that's closer to Boston than Omaha, that's further eastward. Or maybe someone would say, well, I don't really know anyone on the East Coast, but at least I do know some doctors here in Omaha, and so they'd give the letter to somebody that they knew on a first-name basis in Omaha. And then the situation would repeat. Whoever got the letter, again, they'd be given the same instructions. If you know this doctor in Boston on a first-name basis, send them the letter. Otherwise, pass the letter on to somebody who seems more likely, closer to them than you are. Now, of course, many of these letters never reached their destination, but shocking, at least to me, is that a lot of them did. So something like 25% at least of the letters that they started with made it all the way to Boston, which I think says something about people in the late 60s just having more free time on their hands than they do in the early 21st century. I find this hard to imagine. But it's a fact. So you had dozens and dozens of letters reaching this doctor in Boston, and they were able to trace exactly which path of individuals the letter went along before it eventually reached this doctor in Boston. And so then what they did is they looked at the distribution of chain lengths. So how many intermediaries were required to get from some random person in Omaha to this doctor in Boston? Some were as few as 2, some were as big as 9, but the average number of hops, the average number of intermediaries, was in the range of 5.5 or 6. And so this is what has given rise to the colloquialism, even the name of a popular play, the 6 degrees of separation. So that's the origin myth. That's where this phrase comes from, these sort of experiments with physical letters. But now in network science, the small world property is meant to be a network which on the one hand is richly connected, but also in some sense there are enough cues about which links are likely to get closer to some target. So that if you need to route information from point A to point B, not only is there a short path, but if you in some sense follow your nose, then you'll actually exhibit a short path. So in some sense, routing information is easy in small world networks. And this is exactly the property that Broder et al. Identified within this giant SCC. Very rich with short paths, and if you want to get from point A to point B, just follow your nose and you'll do great. You don't need a very sophisticated shortest path algorithm to find a short path. Some of you may have heard of Stanley Milgram not for this small world experiment, but for another famous or maybe infamous experiment he did earlier in the 60s, which consisted into tricking volunteers into thinking they were subjecting other human beings to massive doses of electric shocks. So that wound up causing a rewrite to certain standards of ethics in experimental psychology. You don't hear about that so much when people are talking about networks, but that's another reason why Milgram's work is well known. And just as a point of contrast, outside of this giant strongly connected component, which has this rich small world structure, very poor connectivity in the other parts of the web graph. So there's lots of cool research going on these days about the study of information networks like the web graph. So I don't want you to get the impression that the entire interaction between algorithms and thinking about information networks has just been this one strongly connected component computation in 2000. Of course, there's all kinds of interactions. I just singled one out that was easy to explain and also highly influential and interesting back in the day. But these days lots of stuff's going on. People are thinking about information networks in all kinds of different ways, and of course algorithms, like in almost everything, is playing a very fundamental role. So let me just dash off sort of a few examples, maybe to whet your appetite. Maybe you want to go explore this topic in greater depth outside of this course. So one super interesting question is, rather than looking at a static snapshot of the web, like we were doing so far in this video, right, the web's changing all the time. New pages are getting created, new links are getting created and destroyed, and so on. And how does this evolution proceed? Can we have a mathematical model which faithfully reproduces the most important first-order properties of this evolutionary process? So a second issue is to think not just about the dynamics of the graph itself, but the dynamics of information that gets carried by the graph. And you could ask this both about the web graph and about other social networks like, say, Facebook or Twitter. Another really important topic, which there's been a lot of work on, but we still don't fully understand by any means, is getting at the finer grained structure in networks, including the web graph. In particular, what we'd really like to do is have foolproof methods for identifying communities. So groups of nodes, these could either be web pages in the web graph or individuals in a social network, which we should think of as grouped together. We discussed this a little bit when we talked about applications of cuts. One motivation for cuts is to identify communities. If you think of communities as being relatively densely connected inside and sparsely connected outside, and that's just a baby step. Really, we need much better techniques for both defining and computing communities in these kinds of networks. So I think these questions are super interesting, both from a mathematical/technical level, but also they're very timely. Answering them really helps us understand our world better. Unfortunately, these are going to be well outside the course of just the bread and butter design and analysis of algorithms, which is what I'm tasked with covering here. But I will leave you with a reference book that I recommend if you want to read more about these topics. Namely, the quite recent book by David Easley and John Kleinberg called Networks, Crowds, and Markets. We've arrived at another one of computer science's greatest hits, namely Dijkstra's shortest path algorithm. So let me tell you about the problem. It's a problem called single source shortest paths. Basically what we want to do is compute something like driving directions. So we're given as input a graph. In this lecture I'm going to work with directed graphs, although the same algorithm would work for undirected graphs with cosmetic changes. As usual, we'll use m to denote the number of edges and n to denote the number of vertices. The input also includes two extra ingredients. First of all, for each edge E, we're given as input a non-negative length, which I'll denote by L sub E. In the context of a driving directions application, L sub E could denote the mileage, how long this particular road is, or it could also denote the expected travel time along the edge. The second ingredient is a vertex from which we are looking for paths. This is exactly the same as we had in breadth first search and depth first search. We have an originating vertex, which we'll call here the source. Our responsibility then is to, given this input, compute for every other vertex v in this network the length of a shortest path from the source vertex S to that destination vertex v. And so just to be clear, what is the length of a path that has, say, 3 edges in it? Well, it's just the sum of the length of the first edge in the path plus the length of the second edge in the path plus the length of the third edge in the path. So if you had a path like this with 3 edges and lengths 1, 2, and 3, then the length of the path would just be 6. And then we define the shortest SV path in the natural way. So amongst all of the paths directed from S to V, each one has its own respective path length, and then the minimum over all SV paths is the shortest path distance in the graph G. So I'm going to make 2 assumptions for these lectures. One is really just for convenience. The other is really important. The other assumption without which Dijkstra's algorithm is not correct, as we'll see. So for convenience, we'll assume that there is a directed path from S to every other vertex V in the graph. Otherwise, the shortest path distance is something we define to be plus infinity. And the reason this is not a big assumption is if you think about it, you could detect which vertices are not reachable from S just in a pre-processing step using, say, breadth first or depth first search. And then you could delete the irrelevant part of the graph and run Dijkstra's algorithm as we'll describe it on what remains. Alternatively, Dijkstra's algorithm will quite naturally figure out which vertices there are paths to from S and which ones there are not. So this won't really come up. So to keep it simple, just think about we have an input graph where you can get from S to V for every different vertex V, and the challenge then is amongst all the ways to get from S to V, what is the shortest way to do it? So the second assumption already appears in the problem statement, but I want to reiterate it just so it's really clear. When we analyze Dijkstra's algorithm, we always focus on graphs where every length is non-negative. No negative edge lengths are allowed, and we'll see why a little bit later in the video. Now, in the context of a driving directions application, it's natural to ask the question, why would you ever care about negative edge lengths? Until we invent a time machine, it doesn't seem like negative edge lengths are going to be relevant when you're computing literal paths through literal networks. But again, remember that paths can be thought of as more abstractly as a just sequence of decisions. And some of the most powerful applications of shortest paths are coming up with optimal weight such sequences. So, for example, maybe you're engaging in financial transactions and you have the option of both buying and selling assets at different times. If you sell, then you get some kind of profit, and that would correspond to a negative edge length. So there are quite interesting applications in which negative edge lengths are relevant. If you are dealing with such an application, Dijkstra's algorithm is not the algorithm to use. There's a different shortest path algorithm, a couple other ones, but the most well-known one is called Bellman-Ford. That's something based on dynamic programming, which we may well cover in a sequel course. Okay, so for Dijkstra's algorithm, we always focus on graphs that have only non-negative edge lengths. So with the next quiz, I just want to make sure that you understand the single source shortest path problem. Okay, let me draw for you here a simple Ford node network and ask you for what are the 4 shortest path lengths. So from the source vertex S to each of the 4 vertices in the network. All right, so the answer to this quiz is the final option, 0, 1, 3, 6. To see why that's true, well, all of the options had 0 as the shortest path distance from S to itself, so that just seemed kind of obvious. So the empty path will get you from S to itself and have 0 length. Now suppose you wanted to get from S to V. Well, there's actually only one way to do that. You have to go along this one-hop path. So the only path has length 1. So the shortest path distance from S to V is 1. Now W is more interesting. There's a direct one-hop path, SW, that has length 4, but that is not the shortest path from S to W. In fact, the 2-hop path that goes through V as an intermediary has total path length 3, which is less than the length of the direct arc from S to W. So therefore, the shortest path distance from S to W is going to be 3. And finally, for the vertex T, there's 3 different paths going from S to T. There's the 2-hop path that goes through V. There's the 2-hop path which goes through W. Both of those have path length 7. And then there's the 3-hop path which goes through both V and W. And that actually has a path length of 1 plus 2 plus 3 equal to 6. So despite having the largest number of edges, the zigzag path is in fact the shortest path from S to T, and it has length 6. All right, so before I tell you how Dijkstra's algorithm works, I feel like I should justify the existence of this video a little bit, right? Because this is not the first time we've seen shortest paths. You might be thinking, rightfully so, we already know how to compute shortest paths. That was one of the applications of breadth first search. So the answer to this question is both yes and no. Breadth first search does indeed compute shortest paths. We had an entire video about that. But it works only in the special case where the length of every edge of the graph is 1. At the moment, we're trying to solve a more general problem. We're trying to solve shortest paths when edges can have arbitrary non-negative edge lengths. So, for example, in the graph that we explored in the previous quiz, if we ran breadth first search starting from the vertex S, it would say that the shortest path distance from S to T is 2. And that's because there's a path with 2 hops going from S to T. Put differently, T is in the second layer emanating from S. But as we saw in the quiz, there is not in fact a shortest 2-hop path from S to T if you care about the edge lengths. Rather, the minimum length path, the shortest path with respect to the edge weights, is this 3-hop path, which has a total length of 6. So breadth first search is not going to give us what we want when the edge lengths are not all the same. And if you think about an application like driving directions, then needless to say, it's not the case that every edge in the network is the same. Some roads are much longer than others. Some roads will have much larger travel times than others. So we really do need to solve this more general shortest path problem. Similarly, if you're thinking more abstractly about a sequence of decisions like financial transactions, in general, different transactions will have different values. So you really want to solve general shortest paths. You're not in the special case that breadth first search solves. Now, if you're feeling particularly sharp today, you might have the following objection to what I just said. You might say, big deal. General edge weights, unit edge weights, it's basically the same. Say you have an edge that has length 3. How is that fundamentally different than having a path with 3 edges, each of which has length 1? So why not just replace all the edges with a path of edges of the appropriate length? Now we have a network in which every edge has unit length, and now we can just run breadth first search. So, put succinctly, isn't it the case that computing shortest paths with general edge weights reduces to computing shortest paths with unit edge weights? Well, the first comment I want to make is I think this would be an excellent objection to raise. And indeed, as programmers, as computer scientists, this is the way you should be thinking. If you see a problem that seems superficially harder than another one, you always want to ask, well, maybe just with a clever trick, I can reduce it to a problem I already know how to solve. That's a great attitude in general for problem solving. And indeed, if all of the edge lengths were just small numbers like 1, 2, and 3 and so on, this trick would work fine. The issue is when you have a network where the different edges can have very different lengths. And that's certainly the case in many applications. Definitely road networks would be one where you have both sort of long highways and you have neighborhood streets. And potentially in financial transaction-based networks, you would also have a wide variance between the value of different transactions. And the problem then is some of these edge lengths might be really big. They might be 100, they might be 1,000. It's very hard to put a priori bounds on how large these edge weights could be. So if you start wantonly replacing single edges with these really long paths of length 1,000, you've blown up the size of your graph way too much. So you do have a faithful representation of your old network, but it's too wasteful. So even though breadth first search runs in linear time, it's now on this much larger graph, and we'd much prefer something which is linear time or almost linear time that works directly on the original graph. And that is exactly what Dijkstra's shortest path algorithm is going to accomplish. Let's now move on to the pseudocode for Dijkstra's shortest path algorithm. So this is another one of those algorithms where no matter how many times I explain it, it's always just super fun to teach. And the main reason is because it exposes the beauty that pops up in good algorithm design. So the pseudocode, as you'll see in a second, is itself very elegant. We're just going to have one loop, and in each iteration of the loop, we will compute the shortest path distance to one additional vertex. And by the end of the loop, we'll have computed shortest path distances to everybody. The proof of correctness, which we'll do in the next video, is a little bit subtle, but also quite natural, quite pretty. And then finally, Dijkstra's algorithm will give us our first opportunity to see the interplay between good algorithm design and good data structure design. So with a suitable application of the heap data structure, we'll be able to implement Dijkstra's algorithm so it runs blazingly fast, almost linear time, namely m times log n. But I'm getting a little ahead of myself. Let me actually show you this pseudocode. At a high level, you really should think of Dijkstra's algorithm as being a close cousin of breadth first search. And indeed, if all of the edge lengths are equal to 1, Dijkstra's algorithm becomes breadth first search. So this is sort of the slick generalization of breadth first search when edges can have different lengths. So like our generic graph search procedures, we're going to start at the source vertex S, and in each iteration we're going to conquer one new vertex, and we'll do that once each iteration. After n-1 iterations we'll be done. And in each iteration we'll correctly compute the shortest path distance to one new possible destination vertex V. So let me just start by initializing some notation. So capital X is going to denote the vertices that we've dealt with so far. And by dealt with, I mean we've correctly computed shortest path distance from the source vertex to every vertex in X. We're going to augment X by one new vertex in each iteration of the main loop. Remember that we're responsible for outputting n numbers, one for each vertex. We're not just computing one thing, we're computing the shortest path distance from the source vertex S to every other vertex. So I'm going to frame the output in terms of this array capital A. So for each vertex, we're going to have an entry in the array A, and the goal is at the end of the algorithm, A will be populated with the correct shortest path distances. Now, to help you understand Dijkstra's algorithm, I'm going to do some additional bookkeeping, which you would not do in a real implementation of Dijkstra's algorithm. Specifically, in addition to this array capital A, in which we compute shortest path distances from the source vertex to every other destination, there's going to be an array capital B, in which we'll keep track of the actual shortest path itself from the source vertex S to each destination V. So the arrays A and B will be indexed in the same way. There'll be one entry for each possible destination vertex V. Capital A will store just a number for each destination, shortest path distance. The array B in each position will store an actual path, the shortest path from S to V. But again, you would not include this in an actual implementation. I just find, in my experience, it's easier for students to understand this algorithm if we think of the paths being carried along as well. So now that I've told you the semantics of these two arrays, I hope it's no surprise how we initialize them for the source vertex itself, S. Right, the shortest path distance from S to itself is 0. The empty path gets you from S to S with length 0. There's no negative edges by assumption, so there's no way you can get from S back to S with non-positive length. So this is definitely the shortest path distance for S. By the same reasoning, the shortest path from S to S is just the empty path, the path with no edges in it. So now let's proceed to the main while loop. So the plan is we want to grow this set capital X like a mold until it covers the entire graph. So in each iteration it's going to grow and cover up one new vertex, and that vertex will then be processed, and at the time of processing we're responsible for computing the shortest path distance from S to this vertex and also figuring out what the actual shortest path from S to this vertex is. So in each iteration, we need to grow X by one node to ensure that we make progress. So the obvious question is, which node should we pick? Which one do we add to X next? So there's going to be two ideas here. The first one we've already seen in terms of all of these generic graph search procedures, which is we're going to look at the edges and the vertices which are on the frontier. So we're going to look at the vertices that are just one hop away from vertices we've already put into X. So that motivates, at a given iteration of the while loop, to look at the stuff we've already processed, that's X, and the stuff we haven't already processed, that's V minus X. S, of course, starts in X, and we never take anything out of X, so S is still there. You know, in some generic iteration of the while loop, we might have some other vertices that are in X, and in a generic iteration of this while loop, there might be multiple vertices which are not in X. And now, as we've seen in our graph search procedures, there are edges crossing this cut. So there are edges which have one endpoint in each side, one endpoint in X and one endpoint outside of X. This is a directed graph, so they can cross in two directions. They can cross from left to right, or they can cross from right to left. So you might have some edges internal to X. Those are things we don't care about at this point. You might have edges which are internal to V minus X. We also don't care about those, at least not quite yet. And then you have edges which can cross from X to V minus X, as well as edges that can cross in the reverse direction, from V minus X back to X. And the ones we're going to be interested in, just like when we did graph search and directed graphs, are the edges crossing from left to right. The edges whose tail is amongst the vertices we've already seen, and whose head is some not yet explored vertex. So the first idea is that at each iteration of the while loop, we scan or we examine all of the edges with tail in X and head outside of X. One of those is going to lead us to the vertex that we pick next. So that's the first idea, but now we need a second idea, because this is again quite underdetermined. There could be multiple such vertices which meet this criterion. So for example, in the cartoon in the bottom left part of this slide, you'll notice that there's one vertex here, which is the head of an arc that crosses from left to right, and there's yet another vertex down here in V minus X, which again is the head of an arc which crosses from left to right. So there are two options of which of those two to suck into our set X, and we might want some guidance about which one to pick next. So the key idea in Dijkstra is to give each vertex a score corresponding to how close that vertex seems to the source vertex S, and then to pick among all candidate vertices the one that has the minimum score. Let me be more precise. So among all crossing edges, with tail on the left side and head on the right side, we pick the edge that minimizes the following criterion: the shortest path distance that we previously computed from S to the vertex V, plus the length of the edge that connects V to W. So this is quite an important expression, so I will call this Dijkstra's greedy criterion. This is a very good idea to use this method to choose which vertex to add to the set X, as we'll see. I need to give a name to this edge, which minimizes this quantity over all crossing edges. So let's call it V star W star. So for example, in the cartoon in the bottom left, maybe of the two edges crossing from left to right, maybe the top one is the one that has a smaller value of Dijkstra's greedy criterion. So in that case, this would be the vertex V star, and the other end of the edge would be the vertex W star. So this edge V star W star is going to do wonders for us. It will both guide us to the vertex that we should add to X next. That's going to be W star. It's going to tell us how we should compute the shortest path distance to W star, as well as what the actual shortest path from S to W star is. So specifically, in this iteration of the while loop, after we've chosen this edge V star W star, we add W star to X. Remember, by definition, W star was previously not in capital X, so we're making progress by adding it to X. That's one more vertex in X. Now, X is supposed to represent all of the nodes that we've already processed. So an invariant of this algorithm is that we've computed shortest path distances for everybody in X, as well as the actual shortest paths. So now that we're putting W star in X, we're responsible for all of this information, shortest path information. So what we're going to do is we're going to set our estimate of W star's shortest path distance from S to be equal to the value of this Dijkstra greedy criterion for this edge. That is, whatever our previously computed shortest path distance from S to V star was, plus the length of the direct edge from V star to W star. Now, a key point is to realize that this code does make sense, by which I mean, if you think about this quantity AV, this has been previously computed. And that's because an invariant of this algorithm is we've always computed shortest path distances to everything that's in capital X. And of course, the same thing holds when we need to assign W star shortest path distance, because V star was a member of capital X. We had already computed its shortest path distance, so we can just look up the V star entry position in the array A. So over in our picture on our left, we would just say, well, what did we compute the shortest path distance to V star previously? Maybe it's something like 17. And then we'd say, what is the length of this direct edge from V star to W star? Maybe that's 6. Then we would just add 17 and 6, and we would put 23 as our estimate of the shortest path distance from S to W star. So we do something analogous with the shortest paths itself and the array B. That is, again, we're responsible, since we just added W star to capital X, we're responsible for suggesting a path from S to W star in the B array. So what we're going to do is we're just going to inherit the previously computed path to V star, and we're just going to tack on the end one extra hop, namely the direct edge from V star to W star. That'll give us a path from S all the way to W star via V star as an intermediate bit stop. And that is the entirety of Dijkstra's algorithm. I've explained all of the ingredients about how it works at a conceptual level. So the two things I owe you is, why is it correct? Why does it actually compute shortest paths correctly to all of the different vertices? And then secondly, how fast can we implement it? So the next two videos are going to answer both of those questions. But before we do that, let's go through an example to get a better feel for how this algorithm actually works. And I also want to go through a non-example so that you can appreciate how it breaks down when there are negative edges. And that'll make it clearer why we do need a proof of correctness, because it's not correct without any assumptions about the edge lengths. So let's just see how it works on the same example we traced through earlier. So we start out just by initializing things in the obvious way. So the shortest path distance from S to itself we say is 0, and the shortest path from S to itself is just the empty path. And initially our X is going to be just the source vertex itself. So now we enter the main while loop, and so remember in the while loop we say, well, let's scan all of the edges whose tail is in the vertices we've already looked at, whose tail is in X, and whose head is outside of X. Now in this first iteration, there are two such edges. There's the edge S comma V and the edge S comma W. So how do we know which of these two to choose? Well, we evaluate Dijkstra's greedy criterion. And so remember what that is. Dijkstra's greedy score for a given edge VW that's crossing the frontier is just the previously computed shortest path distance for the tail of the arc plus the length of the arc itself. So at this point, SV has a greedy score of 0 plus 1, which is 1, and the arc S comma W has a greedy score of 0 plus 4, which is 4. So obviously SV is going to be the shorter of those two. So we use the edge SV. This is playing the role of V star W star on the previous slide. And the algorithm then suggests that we should add V to our set X. So we suck in V. And our new X consists of S and V. And it also tells us how to compute the shortest path distance and the shortest path from S to V. Namely, in the A array, we just write down what was the Dijkstra's greedy score for this particular edge, and that was 0 plus 1 or 1. It also tells us how to compute the shortest path for V. Namely, we just inherit the shortest path to the tail of the arc, which in this case is the empty path from S to itself, and then we tack on the end, we append the arc we used to get here, the arc SV. So now we go to the next iteration of the while loop, so with our new set capital X consisting of S and V. And now again, we want to look at all edges which are crossing the frontier, edges that have tail in X and head outside X. And now we see there's three such crossing edges. There's S comma W, there's V comma W, and there's V comma T. All of those have the tail in X and the head outside of X. So we need to compute Dijkstra's greedy score for each of those three and then pick the minimum. So let's go from bottom to top. So first of all, we can look at the arc S comma W, excuse me. And the greedy score here is the shortest path distance for the tail, so that's 0, plus the length of the arc, which is 4. So here we get a 4 in this iteration. Then if we do this crossbar edge, this VW edge, the Dijkstra greedy score is the A value, or the shortest path distance value of the tail, and we computed that last iteration. The A of V value is 1. We add to that the length of the arc, which in this case is 2. So this edge V comma W has a score of 3. Finally, there's the arc V comma T, and here we're going to add 1, which is the shortest path distance of the tail of the arc, plus the edge length, which is 6. So that has the worst score. So since the edge V comma W has the smallest score, that's the one that guides how we supplement X and how we compute the shortest path distances and the shortest path for the newly acquired vertex W. So the changes are, first of all, we enlarge X. So X is now everything but T. And then how do we compute things for W? Well, the shortest path, so our entry in the A array, is just going to be Dijkstra's greedy score in the previous iteration. So that was 1 plus 2, so that's going to be equal to 3. And then what is the shortest path? How do we fill up the array B? Well, we inherit the shortest path to the tail of the arc, which in this case is the arc S comma V, and then we append the arc that we used to choose this new vertex W, so that's the arc VW. So the new path is just the SVW path. Okay, so that's what we compute as the shortest path from S to W in this graph. So now we proceed to the final iteration of Dijkstra's algorithm. We know what vertex we're going to bring into X. It's going to be the vertex T, that's the only one left, but we still have to compute by which edge we discover T and bring it into the set X. So we have to compute the greedy score for each of the two crossing arcs, V comma T and W comma T. And in this final iteration, the score for the arc VT is unchanged. So this is still going to be the A value of its tail 1 plus the length of the arc 6. So the score here is still 7. And now, for the first time, W comma T is a crossing edge of the frontier. And when we compute its score, it's the A value of its tail W, which is 3, plus the length of this arc, which is 3. So we get a greedy score of 6. So by Dijkstra's greedy criterion, we pick the edge WT instead of the edge VT. And of course, that doesn't matter who gets brought into X, but it does matter how we compute the A and B values for T. So in the final iteration, we compute AT to be the Dijkstra greedy score of the edge that we picked, which is the edge WT, and the score was 6. So we compute the shortest path distance from S to T to be 6. And then what is the path itself? Well, we inherit the shortest path to the tail of the arc that we used to discover T. So that's the shortest path to W, which we previously computed as being the path through V. And then we append the edge we used to discover T. So we append the edge WT. So the shortest path from S to T we're going to compute as the zigzag path. S goes to V, goes to T, goes to W, goes to T. And then now, indeed, x is all of the vertices. We've computed it for everything. This is our final output. The contents of the, especially the A array, is the final output. Shortest path distances from S to all of the 4 possible destinations. And if you go back and compare this to the example you went through to the quiz, you will see, at least on this example, indeed, Dijkstra's algorithm corrects the shortest path distances. Now, I've said it before, I'm going to say it again. If someone shows you their algorithm works just on some example, especially a pretty simple 4-node example, you should not jump to the conclusion that this algorithm always works. Sometimes algorithms work fine on small examples, but break down once you go to more interesting, complicated examples. So I definitely owe you a proof that Dijkstra's algorithm works not only in this network, but in any network. And actually, it doesn't work in any network. It's only going to work in any network with non-negative edge lengths. So to help you appreciate that, let's conclude this video with a non-example showing what goes wrong in Dijkstra's algorithm when you have networks with negative edge lengths. So before I actually give you a real non-example, let me just answer a preliminary question, which you might have, and this would be a very good question if it's something that's occurred to you. The question would be, well, why are these negative edge lengths such a big deal? Why can't we just reduce shortest path computation with negative edge lengths to the problem of computing shortest paths with non-negative edge lengths? Right? So why don't we just sort of clear things out? We just add a big number to all the edges. That makes them all non-negative, and now we just run Dijkstra's algorithm, and we're good to go. So this is exactly the sort of question you should be looking to ask if, as a computer scientist, as a serious programmer. When confronted with a problem, you always want to look for ways to reduce it to simpler problems that you already know how to solve. And this is a very natural idea of how to reduce a seemingly harder shortest path problem to one we already know how to solve using Dijkstra's algorithm. The only problem is it doesn't quite work. Why doesn't it work? Well, let's say you have a graph and the most negative edge is -10. So all the edge lengths are -10 and above. So then what you'd want to do is add 10 to every single edge in the network. And that ensures that all of the edge lengths are non-negative. Run Dijkstra's algorithm, get your shortest path. The issue is that different paths between a common origin and destination have differing numbers of edges. So some might have 5 edges, some might have 2 edges. Now, if you add 10 to every single edge in the graph, you're going to change path lengths by different amounts. If a path has 5 edges, it's going to go up by 50 when you add 10 to every edge. If a path has only 2 edges, it's only going to go up by 20 when you add 10 to every edge. So as soon as you start changing the path lengths of different paths by different amounts, you might actually screw up which path is the shortest. The path which is shortest under the new edge lengths need not be the one which is shortest under the old edge lengths. So that's why this reduction doesn't work. To be concrete, let's look at this very simple 3-vertex graph with vertices S, V, and T and edge lengths as shown, 1, -5, and -2. Now, what I hope is clear is that in this graph, the shortest path, the one with the minimum length, is the 2-hop path, SVT. That has length -4. The direct ST arc has length -2, which is bigger than -4. So the upper path is the shortest path. Now suppose we tried to massage this by adding a constant to every edge so that all edge lengths were non-negative. We'd have to add 5 to every edge because that's the biggest negative number, the VT edge. So that would give us new edge lengths of 6 and 0 and 3. And now the problem is we've changed which path is the shortest one. We added 10 to the top path and only 5 to the bottom path, and as a result, they've reversed. So now the bottom path ST is actually the shorter one. So if we run Dijkstra on this graph, it's going to come back with the path ST, even though that's not in fact the shortest path in the original network, the one that we actually care about. Okay, so that's why you can't just naively reduce shortest paths with negative edge lengths to shortest paths with non-negative edge lengths. Moreover, on this very same super simple 3-node graph, we can try running Dijkstra's shortest path algorithm. It's perfectly well defined. It'll produce some output, but it's actually going to be wrong. It is not going to compute shortest path distances correctly in this graph. So let me show you why. Well, so of course the initialization will work as it always does. So it's going to start by saying the shortest path distance from S to itself is 0 via the empty path. And then what's it going to do next? It's going to say, okay, well, we need to enlarge the set capital X by 1 vertex, and there are 2 crossing edges. There's the XV edge and the ST edge. And what's it going to do? It's going to use the Dijkstra greedy score. So the score of this upper edge is going to be 1, and the score of this bottom edge is going to be -2. Because remember, you take the previously computed shortest path value of the tail, that's 0 in both cases, and then you add the edge length. So the edge lengths are 1 and -2, so the scores are 1 and -2. Which of these is smaller? Well, evidently, the ST arc has the smaller score, -2. So what is Dijkstra's algorithm going to do? It's going to say, yes, let's go for this edge ST. Let's bring T into the set capital X. T is now part of the conquered territory. And of course, as soon as you bring a node into the set X, into the conquered territory, you have to commit, or Dijkstra's algorithm chooses to commit to its shortest path distance and its shortest path. What is the definition of its shortest path distance as computed by Dijkstra? Well, it's just its greedy score. So it's going to assign the vertex T the shortest path distance of -2, and the path is going to be just the arc ST. But notice that this is in fact wrong. The shortest path distance from S to T is not -2 in this graph. There is another path, namely the one that goes through V, that has length -4, less than -2. So Dijkstra computes incorrect shortest path distances on this trivial 3-node graph. So to summarize the story so far, we've described Dijkstra's algorithm. I've showed you that it works in a very simple example that doesn't have negative edge lengths, and I've showed you that it doesn't work in an even simpler example that does have negative edge lengths. So I've both given you some plausibility that it might work generally, at least for non-negative edge lengths, but I've also tried to sow some seeds of doubt that it's not at all clear at this point if Dijkstra's algorithm is always correct or not, even if you have non-negative edge lengths. And certainly, if it is always correct, there better be a foolproof argument for why. You should be demanding an explanation of a claim that Dijkstra's is correct in any kind of generality. That's the subject of the next video. In this video, I'll prove to you that Dijkstra's algorithm does indeed compute correct shortest paths in any directed graph where all edge lengths are non-negative. Let me remind you about what is Dijkstra's algorithm. It's very much in the spirit of our graph search primitives, in particular breadth first search. So there's going to be a subset X of vertices, which are the ones that have been processed so far. Initially, X contains only the source vertex. Of course, the distance from the source vertex to itself is 0, and the shortest path from S to itself is the empty path. So then we'll have a main while loop. There's going to be n-1 iterations, and each iteration will bring one vertex which is not currently an X into capital X. An invariant that we're going to maintain is that all the vertices in X, we will have computed estimates of the shortest path distance from S to that vertex, and also we'll have computed the shortest path itself from S to that vertex. Remember our standing assumptions stated in the previous video. We're always going to assume there's at least one path from the source vertex S to every other destination V. Our job is just to compute the shortest one, and also we have to assume that the edge lengths are non-negative, as we've seen, otherwise Dijkstra's algorithm might fail. Now, the key idea in Dijkstra's algorithm is a very careful choice of which vertex to bring from outside of X into capital X. So what we do is we scan the edges crossing the frontier, meaning given the current edges vertices that we've already processed, we look at all of the edges whose tail has been processed and whose head has not been processed. So the tail is in capital X, the head is outside of X. That is, they cross the cut from left to right in the diagrams that we usually draw. Now, there may be many such edges. How do we decide amongst them? Well, we compute the Dijkstra greedy score for each. The Dijkstra greedy score is defined as the shortest path distance we computed for the tail, and that's been previously computed because the tail's in capital X, and then we add to that the length contributed by this edge itself, by the edge VW, which is crossing the cut from left to right. So amongst all edges crossing the cut from left to right, we compute all those Dijkstra greedy scores. We pick the edge with the smallest greedy score, calling that edge just V star W star for the purposes of notation. W star is the one that gets added to X, so it's the head of the arc with the smallest greedy score, and then we compute the shortest path distance of that new vertex W star to be the shortest path distance to V star plus the length contributed by this edge V star W star. And then what is the shortest path? It's just the shortest path previously computed to V star plus this extra edge V star W star tacked onto the end. Here's the formal statement we're going to prove. For this video, we're not going to worry at all about running time. That'll be the discussion of the next video. We'll discuss both the running time of the basic algorithm and a super fast implementation that uses the heap data structure. For now, we're going to just focus on correctness. So the claim is that for every directed graph, not just the 4-node 5-arc example we studied, as long as there's no negative edge links, Dijkstra's algorithm works perfectly. It computes all of the correct shortest path distances. So just to remind you about the notation, what does it mean to correct all shortest path distances correctly? It means that what the algorithm actually computes, which is A of V, is exactly the correct shortest path distance, which we were denoting by capital L of V in the previous video. So both the algorithm and the proof of correctness were established by Edgar Dijkstra. This is back in the late 1950s. So Dijkstra was a Dutch computer scientist and certainly one of the forefathers of the field as a science, as an intellectual discipline. He was awarded the ACM Turing Award, so that is the Nobel Prize in Computer Science, effectively. I believe it was 1972. And he worked for a long time in the Netherlands, but then also spent a lot of his later career at UT Austin. So the way this proof is going to go, it's going to be by induction. And basically what we're going to do is we're going to say every iteration, when we have to commit to shortest path distance to some new vertex, we do it correctly. And so then the form of the induction will be, well, given that we made all of our previous decisions correctly, we computed all our earlier shortest paths in the correct way, that remains true for the current iteration. So formally it's induction on the number of iterations of Dijkstra's algorithm. And as is more often than not the case in proofs by induction, the base case is completely trivial. So that just says before we start the while loop, what do? Well, we commit to the shortest path distance from S to itself. We set it to 0. We set the shortest path to be the empty path. That is, of course, true. Of course, even here we're using the fact that there are no edges with negative edge length. That makes it obvious that sort of having a non-empty path can't get you negative edge length better than 0. So the first shortest path computation we do from S to S is trivially correct. The hard part, of course, is the inductive step, justifying all of the future decisions done by the algorithm. And of course, mindful of that example, that non-example we had at the end of the previous video, in the proof by induction, we better make use of the hypothesis that every edge has non-negative length. Okay? Otherwise, the theorem would be false. So we better, somewhere in the proof, use the fact that edges cannot be negative. So let's move on to the inductive step. Remember, in the inductive step, the first thing to do is state the inductive hypothesis. You're assuming you haven't made any mistakes up to this point. Let's be a little bit more formal about that. So that is, everything we computed in the past. Okay, what did we compute in the past? Well, for each vertex, which is in our set capital X, for each vertex that we've already processed, we want to claim that our computed shortest path distance matches up exactly with the true correct shortest path distance. So in our running notation, for every already processed vertex, so for all vertices V in our set capital X, what we computed as our estimate of the shortest path distance for V is in fact the real shortest path distance, and also the computed shortest path is in fact a true shortest path from S to V. So again, remember, this is a proof by induction. We are assuming this is true, and we're going to certainly make use of this assumption when we establish the correctness of the new iteration, the current iteration. So what happens in an iteration? Well, we pick an edge, which we've been calling V star W star, and we add the head of this edge W star to the set X. So let's get our bearings and remember what Dijkstra's algorithm computes as the shortest path and shortest path distance for this new vertex W star. So by the definition of the algorithm, we assign as a shortest path, a purported shortest path from S to W star, the previously computed purportedly shortest path from S to V star, and then we tack on the end the direct arc V star W star. So pictorially, we already had some path that started at S and ended up at V star, and then we tack on the end this arc going to W star in one hop. And this whole shebang is what we're going to assign as B of W star. So let's use the inductive hypothesis. The inductive hypothesis says that all previous iterations are correct. So that is, any shortest path we computed in a previous iteration is in fact a bona fide shortest path from the source S to that vertex. Now V star, remember, is in X. So that was previously computed. So by the inductive hypothesis, this path B V star from S to V star is in fact a true shortest path from S to V star in the graph. So therefore, it has length L of V star. Remember, L of V star is just by definition the true shortest path distance in the graph from S to V star. And now, given that the path that we've exhibited from S to W star is just the same one as we inherited to V star plus this extra edge tacked on, it's pretty obvious what the length of the left-hand side is. So it has length, just the length of the old path, which we just argued is the shortest path distance from S to V star, plus the length of this arc that we tacked on. So that's going to be L of V star W star. So by the definition of the algorithm, what we compute for W star is just the Dijkstra-Greedy score, which is just the computed shortest path distance to the tail, V star, plus the length of the direct edge. By the inductive hypothesis, we've correctly computed all previous shortest path distances. V star is something we computed in the past. By the inductive hypothesis, it's correct. So this is equal to L of V star by the inductive hypothesis. All right, so don't worry if you're feeling a little lost at this point. We've actually really done no content in this proof yet. We haven't done the interesting part of the argument. All we've been doing is setting up our dominoes, getting them ready to be knocked down. So what have we done in the current iteration? Well, first of all, our estimate of the shortest path distance from the source to W star, to the new vertex that we're including in the set capital X, is the true shortest path distance to V star plus the length of the edge from V star to W star. That's the first thing. Secondly, the path that we have in the B array is a bona fide path from S to W star with exactly this distance. And the point is, now it's clear what has to be proven for us to complete the inductive step and therefore the proof of correctness of Dijkstra's algorithm. So what do we need to prove? We need to prove that this isn't just any old path that we've exhibited from S to this vertex W star, but that it's the shortest path of them all. Put differently, we need to show that every other SW star path in this graph has length at least this circled value. So let's proceed. Let's show that no matter how you get from the source vertex S to this destination W star, the total length of the path that you travel is going to be at least this circled value, at least L of V star plus L of V star W star. Now, on the one hand, we don't have a lot going for us because this path P could be almost anything. It could be a crazy looking path. So how do we argue that it has to be long? Well, here's the one thing we've got going for us for any path P that starts in S and goes to W star. Any such path must cross the frontier. Remember, it starts on the left side of the frontier. It starts at the source vertex, which is initially and forever in the set capital X. And remember that we only choose edges that cross the frontier, whose head is outside of X. And W star is exactly the head of the edge we chose in this iteration. So this is not in X. So any path that starts in X and goes outside of X, at some point it crosses from one to the other. So let's think about the graph in its two pieces, that to the left of the frontier and that to the right. The stuff is already processed and the stuff which has not yet been processed. S, of course, is on the left-hand side. And at the beginning of this iteration of the while loop, W star was on the right-hand side. Any path, no matter how wacky, has to, at some point, cross this frontier. Maybe it does it a bunch of times, who knows, but it's got to do it once. Let's focus on the first time that it crosses the frontier. And let's say that it crosses the frontier with the vertex Y going to the vertex Z. That is, any path P has the form where there's an initial prefix, where all the vertices are in X, and then there's some first point at which it crosses the frontier and goes to a vertex which is not in X. We're calling the first such vertex outside of X Z. And then it can skip back and forth, who knows, but certainly it ends up in this vertex W star, which is not in X. So we're going to make use of just this minimal information about an arbitrary path P, and yet this will give us enough of a foothold to lower bound its length, and this lower bound will be strong enough we can conclude that our path that we computed is the best, smaller than any possible competitor. So let's just summarize where we left on the previous slide. We established that every directed path from S to W star, P, no matter what it is, has to have a prescribed form where it ambles for a while inside X, and then the portal through which it escapes X for the first time we're calling Y, and then the first vertex it sees outside of X is Z, and there has to be one, and then it perhaps ambles further, and eventually reaches W star. It could well be that Z and W star are exactly the same. That's totally fine for this argument. So here's one of our competitors, this path P. We have to show it's at least as long as our path. So we need a lower bound on the length of this arbitrary path from S to W star. So let's get that lower bound by arguing about each piece separately and then invoking Dijkstra's greedy criterion. So remember, we said we better use the hypothesis that edge lengths are non-negative. Otherwise we're toast. Otherwise we know the algorithm is not correct. So here's where we use it. This final part of the path from Z to W star, if it's non-empty, then it's got to have non-negative length, right? Every edge as part of this subpath has non-negative edge length, so the total length of this part of the path is non-negative. So Y to Z by construction is a direct arc. Remember, this is the first arc that path P uses to go from X to get outside of X. Okay, so it's how it escapes the conquered territory X, and this just has some length L of YZ. So that leaves the first part of this path, the prefix of the path that lies entirely in capital X. So how do we get a lower bound on the length of this path? Well, let's begin with something trivial. This is some path from S to Y. So certainly it's at least as long as a shortest path from S to Y. And now we're going to use the inductive hypothesis again. So this vertex Y, this is something we treated in a previous iteration, right? This belongs to the set capital X. We've already processed it. We've already computed our estimate of its shortest path length. And the inductive hypothesis assures us that we did it correctly. So whatever value we have hanging out in our array capital A, that is indeed the length of a true shortest path. So the length of a shortest SY path is L of Y by definition, and it's AY by the inductive hypothesis. And now we're in business, right? So what does this mean we can say about the total length of this arbitrary path P? Well, we've broken it into three pieces, and we have a lower bound on the length for each of the three pieces. Our lower bounds are our computed shortest path distance to Y, the length of the direct edge from Y to Z, and 0. So adding those up, we get that the length of path P is at least our computed shortest path distance to Y plus the length of the arc from Y to Z. So why is this useful? Well, we've got one remaining trick up our sleeve. There's a hypothesis which is presumably very important, which you have not yet invoked. And that is the choice of Dijkstra's greedy criterion. At no point in the proof yet have we used the fact that we select which vertex to add next according to Dijkstra's greedy score. So that is going to be the final nail in the coffin. That's what's going to complete the proof. How do we do that? Well, we've taken an arbitrary path P. We've lower bounded its length in terms of the computed shortest path distance up to the last vertex of this prefix Y, plus the arc length to get from X to outside of X, CYZ. So remember, this means Y is on the left part of the frontier and Z is not. And therefore, in this iteration, the edge YZ was totally a candidate for us to use to enlarge our frontier. Remember, we looked at all of the edges crossing from left to right. YZ is one such edge, and amongst all of them, we chose the one with the smallest Dijkstra greedy score. That was the Dijkstra greedy criterion. So what have we shown? We've shown that the length of our path is no more than what's a lower bound on the length of this arbitrary other path P. So this completes the proof. So let me just remind you of all of the ingredients in case you got lost along the way. So what we started out with is we realized our algorithm, or Dijkstra's algorithm, it does compute some path from S to W star. Right? It just takes the path it computed previously to V star, and it just appends this final hop at the end. So that gives us some path from S to W star. Moreover, it was easy to figure out exactly what the length of that path is, and the length of the path that we came up with is exactly this circled quantity at the bottom of this slide. It's the shortest path distance from S to V star plus the length of the direct arc from V star to W star. So that was how well we did. But we had to ask the question, is it possible to do better? Right? We're trying to argue that our algorithm does the best possible, that no competing path could possibly be shorter than ours. So how did we do that? Well, we considered an arbitrary competing path P. The only thing we know about it is that it starts at S and it ends up at W star. And we observed that any path can be decomposed into three pieces: a prefix, a direct edge, and a suffix. Then we gave a lower bound on this path P, right? The direct edge, the length is just whatever it is. The suffix, we just use the trivial lower bound that's at least 0, and that's where we use the hypothesis that every edge has non-negative edge length. And for the prefix, because that's all in the stuff we already computed, we can invoke the inductive hypothesis and say, well, whatever this path is, it goes from S to some vertex in Y. It's at least the shortest path distance from S to Y, which is something we computed in a previous iteration. We've lower bounded the length of any other path in terms of the Dijkstra greedy score for that path. Since we choose the path with the best greedy score, that's why we wind up with the shortest path of them all from S to W star. This, of course, is embedded in an outer proof by induction on the number of iterations, but this is the inductive step which justifies a single iteration. Since we can justify every iteration given correctness of the previous ones, that means by induction all of them are correct, so all of the shortest paths are correct. And that is why Dijkstra's algorithm correctly computes shortest paths in any directed graph with non-negative edge lengths. In this video, we'll discuss how we actually implement Dijkstra's shortest path algorithm, and in particular, using the heap data structure, will give a blazingly fast implementation, almost linear time. Let me just briefly remind you the problem we're solving. It's the single source shortest path problem. So we're given a directed graph and a source vertex S. We're assuming that there's a path from S to every other vertex V. If that's not true, we can detect it with an easy pre-processing step. So our task then is just to find the shortest path amongst all of them from the source vertex S to each possible destination V. Moreover, every edge of the graph has a non-negative edge length, which we're denoting L sub E. So recall that Dijkstra's algorithm is driven by a single while loop. So we're going to add one additional vertex to an evolving set capital X as the algorithm proceeds. So X is the vertices that have been processed so far. We maintain the invariant that for every processed vertex, we've computed what we think the shortest path distance is to that vertex. So initially X is just the source vertex S. Of course, the shortest path distance from S to itself is 0. And then the cleverness in Dijkstra's algorithm is in how we figure out which vertex to add to the set capital X each iteration. So the first thing we do is we focus only on edges that cross the frontier, edges that have their tail in capital X and their head outside of capital X. Now, of course, there may be many such edges that cross this frontier, and we use Dijkstra's greedy criterion to select one of them. So for each crossing edge, each edge with a tail in X and head outside X, we compute the Dijkstra greedy score that is defined as the previously computed shortest path distance to the tail of the arc plus the length of the arc. So we compute that for each crossing edge, and then the minimum edge, we're calling it V star W star. That determines how we proceed. So we add the head of that arc W star to the set capital X, and then we compute the shortest path distance to W star to be the previously computed shortest path distance to V star plus the length of this extra hop V star W star. Now, back when I explained this algorithm, I did it using two arrays, an array capital A and an array capital B. A is what computed the shortest path distances, and remember that's what the problem asks us to compute. And for clarity, I also filled up this array capital B just to keep track of the shortest paths themselves. Now, if you look at the code of this algorithm, we don't actually need the array capital B for anything. When we fill in the array capital A, we don't actually refer to the B array. And so now that we're going to talk about real implementations of Dijkstra, I'm actually going to cross out all of the instructions that correspond to the B array, okay? Because you would not, as I told you earlier, use this in a real implementation of Dijkstra. You would just fill in the shortest path distances themselves. So in the next quiz, what I want you to think about is the running time of this algorithm if we implemented it more or less as is, according to the pseudocode on this slide, without any special data structures. And in the answers to the quiz, we're going to be using the usual notation where M denotes the number of edges in the graph and N denotes the number of vertices of the graph. So the correct answer to this quiz is the fourth one, that the straightforward implementation of Dijkstra's algorithm would give you a running time proportional to the product of the number of edges and the number of vertices. And the way to see that is to just look at the main while loop and look at how many times it executes and then how much work we do per iteration of the while loop if we implemented it in a straightforward way. So there's going to be n-1 iterations of the while loop. And the reason is that the algorithm terminates once every single vertex has been added to capital X. There are n vertices. Initially, there's one vertex in X. So after n-1 iterations, we'll have sucked up all of the vertices. Now, what's the work done in each while loop? Well, basically, we do, naively, a linear scan through all of the edges. So we go through the edges, we check if it's an eligible edge, that is, if its tail is an X and its head is outside of X. We can keep track of that just by having an auxiliary Boolean variable for each vertex, remembering whether it's an X or not. And then amongst all of the eligible edges, those crossing the frontier, we just, by exhaustive search, remember which edge has the smallest Dijkstra score. Now we can compute the Dijkstra score in constant time for each of the edges. So that's a reasonable algorithm. We might be able to get away with graphs that have, say, hundreds or thousands of vertices using this straightforward implementation, but of course we'd like to do better. We'd like the algorithm to scale up to much larger graphs, even graphs with potentially, say, 1 million vertices. So the answer is yes, we can do better, not by changing the algorithm, but rather changing how we organize the data as the algorithm proceeds. So this will be the first time in the course where we use a data structure to get an algorithmic speed up. So we're going to see a really lovely interplay between, on the one hand, algorithm design, and on the other hand, data structure design in this implementation of Dijkstra's algorithm. So you might well ask, what's the clue that indicates that a data structure might be useful in speeding up Dijkstra's shortest path algorithm? And the way you'd figure this out is you'd say, well, where is all this work coming from? Why are we doing a linear amount of work in the edges for a linear number in the vertices iterations? Well, at each iteration of this while loop, what we're doing is we're just doing an exhaustive search to compute a minimum. We look at every edge, we look at those that cross the frontier, and we compute the one with the minimum Dijkstra score. So we can ask ourselves, oh, if we're doing minimum computations over and over and over again, is there some data structure whose raison d'etre, whose reason for being, is in fact to perform fast minimum computations? And in fact, there is such a data structure. It's the heap data structure. So in the following description of a fast implementation of Dijkstra's algorithm, I'm going to assume you're familiar with this heap data structure. For example, that you watched the review video elsewhere on the course site that explains them. So let me just remind you with a lightning quick review of what we learned in that video. So heaps are generally logically thought of as a complete binary tree, even though they're usually implemented as laid out in an array. And the key property that you get to leverage, but that you also have to maintain in a heap, is the heap property, that at every node, the key at that node has to be at least as small as that of both of the children. This property ensures that the smallest key of them all has to be at the root of this tree. To implement extract min, you just pluck off the root. That's what you return. That's the minimum element. And then you swap up the bottommost rightmost leaf, the last element, make that the new root, and then you bubble that down as necessary to restore the heap property. When you do insertion, you just make the new element the new last leaf, bottommost rightmost leaf, and then you swap up as needed to restore the heap property. When we use heaps in Dijkstra's algorithm, we're also going to need the ability to delete an element from the middle of the heap. But again, you can do that just by swapping things and bubbling up or down as needed. I'll leave it as an exercise for you to think through carefully how to delete elements from the middle of a heap. Because you maintain a heap as an essentially perfectly balanced binary tree, the height of the tree is roughly the log base 2 of n, where n is the number of elements in the heap. And because for every operation you implement it just by doing a constant amount of work at each level of the tree, all of these operations run in O of log n time, where n is the number of items that are being stored in the heap. As far as the intuitive connection between the heap data structure and Dijkstra's algorithm, in the main while loop of Dijkstra's algorithm, we're responsible for finding a minimum every single iteration. What are heaps good for? They're good for finding minimums in logarithmic time. That sounds a lot better than the linear time we're spending in the naive implementation of Dijkstra's algorithm. So let's now see how to use heaps to speed up Dijkstra's shortest path algorithm. Now, because every iteration of the while loop is responsible for picking an edge, you might expect that we're going to store edges in the heap. So the first subtle but really good idea is to actually use a heap to store vertices rather than edges. Going back to the pseudocode for Dijkstra's algorithm, remember that the only reason we focused on an edge was so that we could then deduce which vertex, namely the head of that edge, to add to our set capital X. So we're just going to cut to the chase. We're just going to keep vertices not yet in X, and then when we extract them in from the heap, it'll tell us which is the next vertex to add into the set capital X. So the picture we're going to want to have in mind is Dijkstra's shortest path algorithm at some intermediate iteration. So there'll be a bunch of vertices in the set capital X, the source vertex plus a bunch of other stuff that we've sucked into the set so far. And then there'll be all the vertices we haven't processed yet, a big group V minus X. Then there's going to be edges crossing this cut in both directions, from X to V minus X and vice versa. Now, before I explain the second invariant, let's just recall what the straightforward implementation of Dijkstra's algorithm needs to do. What it would do is search through all the edges, and it would look for any eligible edges, those with tail in X and head in V minus X. So in this picture, there would be 3 such edges. I've drawn the example so that 2 of the edges, the top 2 edges, both share a common head vertex, whereas the third edge has its own head vertex. The straightforward implementation of Dijkstra's algorithm would compute Dijkstra's greedy score for each of these 3 edges. And remember, by definition, that's the previously computed shortest path distance to the tail of the arc V plus the length of the arc VW. So the straightforward implementation just computes this. In this case, it would compute it for 3 edges, and whichever the 3 edges won had the smallest score, the head of that edge would be the next vertex that gets added to X. So let me specify the second invariant, and then I'll tell you how to think about it. So because we're storing vertices rather than edges in the heap, we're going to have to be fairly clever with the way we define the key of a vertex that's in this heap. So we're going to maintain the property that the key of a vertex V is the smallest greedy Dijkstra score of any edge which has that vertex as its head. So let me show you what I mean in terms of our example where we have 3 crossing edges. Suppose for these 3 edges in the upper right, they happen to have Dijkstra greedy scores of 7, 3, and 5. Let's look at what the key should be for each of these 3 vertices I've drawn in V minus X. Now for the topmost vertex, this is pretty interesting. There are 2 different edges whose tail is an X and have this vertex as their head. So what should the key of this vertex be? Well, it should be the smallest Dijkstra greedy score of any of the edges whose tail lies on the left-hand side that terminate at this vertex. So there's 2 candidate edges. One has Dijkstra greedy score 3, one has Dijkstra greedy score 7. So the key value should be 3, the smaller of those 2. Now, the second vertex, there's only a single edge that has tail in X and that terminates at this vertex. So the key for this vertex should just be the score of that unique edge. So in this case, it's going to be 5. And then this poor third vertex, there's actually no edges at all that start at X and terminate at this vertex. There's only one arc going the wrong direction. So for any vertex outside of X that doesn't have any eligible edges terminating at it, we think of the key as being plus infinity. So the way I recommend thinking about these heap keys is that we've taken what used to be a 1-round tournament, winner takes all, and we've turned it into a 2-round knockout tournament. So in our straightforward implementation of Dijkstra's algorithm, we did a single linear search through all of the edges, and we just computed the greedy Dijkstra score for each, and we picked the best. So in this example, we would have discovered these 3 edges in some order. Their scores are 3, 5, and 7. And we would have remembered the edge with score 3 as being the best. That would have been our winner of this winner-take-all tournament. Now, when we use the heap, we're factoring it into 2 rounds. So first, each vertex in V minus X runs a local tournament to elect a local winner. So each of these vertices in V minus X says, well, let me look at all of the edges for whom I'm the head, and also the tail of that edge is in X. And amongst all of those edges that start in X and terminate at me, I'm going to remember the best of those. So that's the winners of the local tournament of the first round. And now the heap is only going to remember this set of first round winners, right? There's no point in remembering the existence of edges who aren't even the smallest score that terminate at a given vertex, because you only care about the smallest score overall. Now when you extract min from the heap, that's in effect executing the second and final round of this knockout tournament. So each of the vertices of V minus X has proposed their local winner, and then the heap in an extract min just chooses the best of all of those local winners. So that's the final proposed vertex that comes out of the heap. So the point is that if we can successfully maintain these 2 invariants, then when we extract min from this heap, we'll get exactly the correct vertex, W star, that we're supposed to add to the set capital X next. That is, the heap will just hand to us on a silver platter exactly the same choice of vertex that our previous exhaustive search through the edges would have computed. The exhaustive search was just computing the minimum in a brute force way in a single winner-take-all tournament. The heap implemented in this way chooses exactly the same winner, it just does it in this two-round process. Now in Dijkstra's algorithm, we weren't supposed to merely just find the next vertex W star to add to X, we also had to compute its shortest path distance. But remember, we computed the shortest path distance as simply the Dijkstra-Greedy score. And here, the Dijkstra-Greedy score is just going to be the key for this heap that's immediate from invariant number 2. So we're using the fact here that our keys are, by definition, just the smallest greedy scores of edges that stick into that vertex W star. So it would be, again, exactly replicating the computation that we would have done in the straightforward implementation, just in a much slicker way. Okay? But we're adding exactly the same vertices in exactly the same order, and we're computing exactly the same shortest path distances in this heap implementation, provided, of course, that we do successfully maintain these two invariants throughout the course of the algorithm. So that is now what I owe you. We have to pay the piper. We've shown that if we can have a data structure with these properties, then we can simulate the straightforward implementation. Now I have to show you how we maintain these invariants without doing too much work. All right, so maintaining invariant number 1 will really take care of itself. Really, sort of by definition, the vertices which remain in the heap are those that we haven't processed yet, and those are the ones that are outside of capital X. So really the trick is, how do we maintain invariant number 2? Now before I explain this, let me point out that this is a tricky problem. Okay, there is something subtle going on. So as usual, I want you to think about this shortest path algorithm. It's some intermediate iteration. Okay, so take a snapshot. A bunch of vertices have already been added to X. A bunch of vertices are still hanging out in the heap. They haven't been added to X. There's some frontier. There's edges crossing, possibly in both directions. And suppose at the end of a current iteration, we identify the vertex W, which we're going to extract from the heap and conceptually add to the set X. Now, the reason things get complicated is when we move a vertex from outside X to inside X, the frontier between X and V minus X changes. So in this picture, the old black X becomes this new blue X. And what's really interesting about the frontier changing is that then the edges which cross the frontier change. Now, there are some edges which used to cross the frontier and now don't. Those are the ones that are coming into W. Those we're not so concerned with. Those don't really play any role. What makes things tricky is that there are edges which used to not be crossing the frontier, but now they are crossing the frontier. And those are precisely the edges sticking out of W. So in this picture, there are 3 such edges, which I will highlight here in pink. To see why it's tricky when new edges all of a sudden are crossing the frontier, let's remember what invariant number 2 says. It says that for every vertex which is still in the heap, which is not yet an X, the key for that vertex better be the smallest Dijkstra-Greedy score of any edge which comes from capital X and sticks into this vertex V. Now, in moving one vertex into X, namely this vertex W, now there can be new edges sticking into vertices which are still in the heap. As a result, the appropriate key value for vertices in the heap might be smaller now that W has been moved into X. And the candidates for the vertices in the heap whose keys might have dropped are precisely those vertices on the other end of edges sticking out of W. So summarizing, the fact that we've added a new vertex to capital X and extracting something from the heap, it's potentially increased the number of crossing edges across the frontier because the frontier has changed, and therefore for vertices that remain in the heap, the smallest greedy score of an edge that sticks into them from the set X might have dropped. So we need to update those keys to maintain invariant number 2. Now, that's the hard part. Here's what we have going for us. We've damaged the keys, perhaps, by changing the frontier, but the damage is local. We can understand exactly whose keys might have dropped. So as suggested by the picture, the vertices whose keys we need to update are precisely those at the head of edges that stick out of W. So for each outgoing edge from W, the vertex we just extracted from the heap, we need to go to the other end of the edge and check if that vertex needs its key to be decreased. So here's the pseudocode to do this. So when we extract the vertex W from the heap, that is, when we conceptually add a new vertex W to the set X, thereby changing the frontier, we say, well, we know the only vertices that might have to have their key changed. They're the ones on the other side of these outgoing arcs from W. So we just have a simple iteration over the outgoing edges WV from the vertex V. Now, I haven't shown you any edges in the picture like this, but there might well be some edges where the head of the arc V is also in the set X, has also already been processed. But anything in X is not in the heap. Remember, the heap is only the stuff outside of X. So we could care less about stuff outside of the heap. We're not maintaining their keys. So we do an extra check if the head of this edge is in fact still in the heap, that is, if it's not in X. So in the picture, for example, this would be true for all three of the vertices that are on the other end of arcs pointing out of W. And for each of these vertices V, we update its key. And the way we're going to update its key is we're just going to rip this vertex out of the heap. We're going to recompute its key in constant time, and then we're going to reinsert it into the heap. And since all heap operations take logarithmic time, this key update will be logarithmic time. As an additional optimization, I want to point out that if one of these vertices V's key does change, it can only change in one way. So remember, what is the key? The key is the smallest greedy Dijkstra score of all of the edges that start next and stick into this vertex. So that's the local tournament or the first round tournament happening at this vertex V. Now, the only thing which has changed before and after we added this vertex W to X is that now one new edge is sticking into this vertex V. All of the old edges sticking into it from X are still sticking into it, and now there's one extra candidate in its local tournament, namely this edge WV. So either WV is the local winner, either it has the smallest Dijkstra greedy score of them all that terminated this vertex, or it doesn't, in which case the previous winner is still the new winner. So that is, the new key value can only be one of two things. Either it's the old key value, that's the case where this extra entrant, the edge from W to V, is irrelevant, or if it's changed, it has to have changed to the greedy Dijkstra score of this edge WV. And the formula for that is the shortest path distance that we just computed for W, where W has been processed at this point, plus the length of the direct arc from WV. And again, conceptually, this formula is just the greedy Dijkstra score for the arc WV, the new entrant in V's local first-round tournament. So now, having updated V's key appropriately so that invariant number 2 is restored, and once again the key of every vertex does reflect the smallest greedy Dijkstra greedy score of any edge sticking into it from the set X, we can safely reinsert this node back into the heap with its new key value. And these three lines together are just a key update in logarithmic time for one of these vertices that's at the other end of an arc sticking out of the vertex W. So let's tally up the running time in this new implementation. One thing I want you to check, and this will definitely help you understand this refined implementation of Dijkstra's algorithm, is that essentially all the work done is through the heap API. That is, all of the running time that we have to account for is in heap operations. We don't really do non-trivial work outside of heap operations. And again, recall that the running time of any heap operation is logarithmic in the number of elements in the heap. Our heap is storing vertices. It's never going to have more than n things in it, so the running time of every heap operation is big O of log n. So what are the heap operations that we do? Well, we extract min, and we do it once per iteration of the while loop. So there's n-1 iterations of the while loop, just like before, but now instead of doing an exhaustive search through the edges, we just do a simple extract min from the heap, and it gives us on a silver platter the vertex that we should add to X next. So what do we do beside extract mins? Well, we have to do this work paying the piper. We have to maintain invariant number 2, and every time we extract a min, that then triggers some subsequent key updates. And remember, each of these key updates is a deletion of an element from the heap followed by an insertion. So how many deletions and insertions do we do? Well, at first this might seem a little bit scary, right? Because we do a roughly linear number of extract mins, and a vertex might have as many as n-1 outgoing arcs. So it seems like a vertex could trigger as many as n-1 key updates, which is theta of n heap operations. And if we sum that up over the n iterations of the while loop, that would give us n squared heap operations. So, and indeed, in dense graphs, that can be the case. It is true that a single vertex might trigger a linear in n number of heap operations, But that's the wrong way to think about it. Rather than have this vertex-centric perspective on who's responsible for heap operations, let's have an edge-centric view. So for each edge of the graph, let's think about when can this be responsible for some heap operations, in particular a decrease in key and the resulting insertion and deletion. Well, if you have an edge and it points from the vertex V to the vertex W, there's actually only one situation in which this edge is going to be responsible for a decrease in key. And that's in the case where the tail of the edge, V, gets sucked into the set X before the head W of this edge gets sucked into the set X. If that happens, if V gets sucked into X and W is still outside of X, then indeed we're going to have to decrease the key of W, just like we did in the examples. But that's all that's going to happen. V can only get sucked into X once. It's never going to leave it. So it's only responsible for this single decrease in key of its head W. And that's one insertion and one deletion. And in fact, if the endpoints of this edge get sucked into X in the opposite order, if the if the head of this edge W gets sucked into X first, that doesn't even trigger a key decrease for V. And V will never have its key decreased because of this particular arc from V to W. So the upshot is that each edge VW of the graph triggers at most one insert delete combo. So what does this mean? This means that the number of heap operations is big O of n, that's for the extract mins, plus big O of m, that's for the insert delete combos triggered by edges during the decrease keys. Now, I'm going to write this in a simplified way. This is just O of m, the number of edges. And this is because of our assumption that there's a path from S to every other vertex. If you think about it, that means the graph is at least weakly connected. If you picked it up, it would stay together in one piece. So that means it at least contains a tree, at least in the undirected sense, which means it contains at least n minus 1 edges. So we're in the case of weakly connected graphs where n dominates n. M is always at least as big as n, at least up to a plus 1. So what that means is the running time of Dijkstra's algorithm with this heap implementation is just a log factor larger. Remember, every heap operation takes time logarithmic. So we do a linear in m number of operations. Each takes time logarithmic in n. So the running time is m log n. With, I should say, quite good constants. So this is a really, really impressively fast algorithm for computing such a useful problem as shortest paths. So we got a little bit spoiled in our discussion of graph search and connectivity, where it seemed like any problem we cared about we could solve in linear time, O of m plus n. So here we're picking up this extra logarithmic factor, but I mean, come on, this is still awesome. A running time of m log n is unbelievably faster than a running time of m times n, which is what we had in the straightforward implementation. So this deft use of the heap data structure has given us a truly blazingly fast algorithm for an extremely well-motivated problem, computing shortest paths. In this video, I'm going to tell you a little bit about my approach toward teaching data structures in this course. So knowing when and how to use basic data structures is an essential skill for the serious programmer. Data structures are used in pretty much every major piece of software. So let me remind you what's the point, the raison d'etre of a data structure. Its job is to organize data in a way that you can access it quickly and usefully. There's many, many examples of data structures, and hopefully you've seen a few of them and perhaps even used a few of them in your own programs. And they range from very simple examples like lists, stacks, and queues, to more intricate but still very useful ones like heaps, search trees, hash tables, relatives thereof like Bloom filters, union find structures, and so on. So why do we have such a laundry list of data structures? Why is there such a bewildering assortment? It's because different data structures support different sets of operations and are therefore well suited for different types of tasks. Let me remind you of a concrete example that we saw back when we were discussing graph search, and in particular breadth first search and depth first search. So we discussed how implementing breadth first search, the right data structure to use is a queue. This is something that supports fast, meaning constant time insertion to the back and constant time deletion from the front. Depth first search, by contrast, is a different algorithm with different needs, and because of its recursive nature, a stack is much more appropriate for depth first search. That's because it supports constant time deletion from the front, but constant time insertion to the front. So the last in, first out support of a stack is good for depth first search. The first in, first out operations of a queue work for breadth first search. Now, because different data structures are suitable for different types of tasks, you should learn the pros and cons of the basic ones. Generally speaking, the fewer operations that a data structure supports, the faster the operations will be and the smaller the space overhead required by the data structure. Thus, as a programmer, it's important that you think carefully about the needs of your application. What are the operations that you need a data structure to export? And then you should choose the right data structure, meaning the one that supports all of the operations you need, but ideally no superfluous ones. Let me suggest 4 levels of data structure knowledge that someone might have. So level 0 is the level of ignorance for someone who's never heard of a data structure and is unaware of the fact that organizing your data can produce fundamentally better software. For example, fundamentally faster algorithms. Level 1 I think of as being cocktail party level awareness. Now obviously here I'm talking only about the nerdiest of cocktail parties, but nonetheless this would be someone who could at least hold a conversation about basic data structures. They've heard of things like heaps and binary search trees, they're perhaps aware of some of the basic operations, but this person would be shaky using them in their own program or say in a technical interview context. Now with level 2 we're starting to get somewhere. So here I would put someone who has solid literacy about data structures. They're comfortable using them as a client in their own programs, and they have a good sense of which data structures are appropriate for which types of tasks. Now level 3, the final level, is the hardcore programmers and computer scientists. And these are people who are not content to just be a client of data structures and use them in their own programs, but they actually have an understanding of the guts of these data structures, how they are coded up, how they're implemented, not merely how they are used. Now my guess is that really a large number of you will wind up using data structures in your own programs, and therefore learning about what are the operations of different data structures and what are they good for will be a quite empowering skill for you as a programmer. On the other hand, I'll bet that very few of you will wind up having to implement your own data structures from scratch, as opposed to just using as a client the data structures that already come with the various standard programming libraries. So with this in mind, I'm going to focus my teaching on taking you up to level 2. My discussion is going to focus on the operations supported by various data structures and some of the canonical applications. So through this, I hope I'll develop your intuition for what kinds of data structures are suitable for what kinds of tasks. Time permitting, however, I'll also include some optional material for those of you wanting to take it to the next level and learn some about the guts of these data structures, the canonical implementations of how you'd code them up. So in this video, we'll start talking about the heap data structure. So in this video, I want to be very clear on what are the operations supported by a heap, what running time guarantees you can expect from canonical implementations, and I want you to get a feel for what kinds of problems they're useful for. In a separate video, we'll take a peek under the hood and talk a little bit about how heaps actually get implemented. But for now, let's just focus on how to use them as a client. So the number one thing you should remember about a given data structure is what operations it supports and what is the running time you can expect from those operations. So basically a heap supports 2 operations. There's some bells and whistles you can throw on, but the 2 things you got to know is insertion and extract min. Alright, so the first thing I have to say about a heap is that it's a container for a bunch of objects, and each of these objects should have a key, like a number, so that for any given object you can compare their keys and say one key is bigger than the other key. So for example, maybe the objects are employee records and the key is social security numbers. Maybe the objects are the edges of a network and the keys are something like the length or the weight of an edge. Maybe each object indicates an event and the key is the time at which that event is meant to occur. Now the number one thing you should remember about a given data structure is, first of all, what are the operations that it supports, and second of all, what is the running time you can expect from those operations. For a heap, essentially there's 2 basic operations: insert and extract the object that has the minimum key value. So in our discussion of heaps, we're going to allow ties. They're pretty much equally easy with or without ties. So when you extract min from a heap that may have duplicate key values, then there's no specification about which one you get. You just get one of the objects that has a tied for the minimum key value. Now, of course, there's no special reason that I chose to extract the minimum rather than the maximum. Either you can have a second notion of a heap, which is a max heap, which always returns the object with a maximum key value, or if all you have at your disposal is one of these extract min type heaps, you can just negate the sign of all of the key values before you insert them, and then extract min will actually extract the max key value. So just to be clear, I'm not proposing here a data structure that supports simultaneously an extract min operation and an extract max operation. If you wanted both of those operations, there'd be data structures that would give it to you. Probably a binary search tree is the first thing you'd want to consider. So I'm just saying you can have a heap of one of two flavors. Either the heap supports extract min and not extract max, or the heap will support extract max and not extract min. So I mentioned that you should remember not just the supported operations of a data structure, but what is the running time of those operations. Now, for the heap, the way it's canonically implemented, the running time you should expect is logarithmic in the number of items in the heap. And it's log base 2 with quite good constants. So when you think about heaps, you should absolutely remember these two operations. Optionally, there's a couple other things about heaps that might be worth remembering. Some additional operations that they can support. So the first is an operation called heapify. Like a lot of the other stuff about heaps, it has a few other names as well, but I'm going to call it heapify, one standard name. And the point of heapify is to initialize a heap in linear time. Now, if you have n things and you want to put them all in a heap, obviously you could just invoke insert once per each object. If you have n objects, it seems like that would take n times log n time. Log n for each of the n inserts. But there's a slick way to do them in a batch, which takes only linear time. So that's the heapify operation. And another operation which can be implemented, although there are some subtleties, is you can delete not just the minimum, but you can delete an arbitrary element from the middle of a heap, again in logarithmic time. I mention this here primarily because we're going to use this operation when we use heaps to speed up Dijkstra's algorithm. So that's the gist of a heap. You maintain objects that have keys, you can insert in logarithmic time, and you can find the one with the minimum key in logarithmic time. So let's turn to applications. I'll give you several. But before I dive into any one application, let me just say, what's the general principle? What should trigger you to think that maybe you want to use a heap data structure in some task? So the most common reason to use a heap is if you notice that your program is doing repeated minimum computations, especially via exhaustive search. And most of the applications that we go through will have this flavor. There'll be a naive program which does a bunch of repeated minimums using just brute force search, and we'll see that a very simple application of a heap will allow us to speed it up tremendously. So let's start by returning to the mother of all computational problems, sorting an unsorted array. Now, a sorting algorithm which is sort of so obvious and suboptimal that I didn't even really bother to talk about it at any other point in the course is selection sort. What do you do in selection sort? You do a scan through the unsorted array, you find the minimum element, you put that in the first position, you scan through the other n-1 elements, you find the minimum among them, you put that in the second position, you scan through the remaining n-2 unsorted elements, you find the minimum, you put that in the third position, and so on. So evidently, this sorting algorithm does a linear number of linear scans through this array. So this is definitely a quadratic time algorithm. That's why I didn't bother to tell you about it earlier. So this certainly fits the bill as being a bunch of repeated minimum computations, or for each computation, we're doing exhaustive search. So this, a light bulb should go off and say, aha, can we do better using a heap data structure? And we can, and the sorting algorithm that we get is called heap sort. And given a heap data structure, the sorting algorithm is totally trivial. We just insert all of the elements from the array into the heap, then we extract the minimum one by one. From the first extraction, we get the minimum of all n elements. The second extraction gives us the minimum of the remaining n-1 elements, and so on. So when we extract min one by one, we can just populate a sorted array from left to right. Boom, we're done. What is the running time of heap sort? Well, we insert each element once and we extract each element once, so that's 2n heap operations, And what I promised you is that you can count on heaps being implemented so that every operation takes logarithmic time. So we have a linear number of logarithmic time operations for a running time of n log n. So let's take a step back and appreciate what just happened. We took the least imaginative sorting algorithm possible, selection sort, which is evidently quadratic time. We recognized the pattern of repeated minimum computations. We swapped in the heap data structure, and boom, we get an n log n sorting algorithm, which is just 2 trivial lines. And remember, n log n is a pretty good running time for a sorting algorithm. This is exactly the running time we had from merge sort. This was exactly the average running time we got from randomized quicksort. Moreover, heap sort is a comparison-based sorting algorithm. We don't use any data about the key elements. We just use it as a totally ordered set. And as some of you may have seen in an optional video, there does not exist a comparison-based sorting algorithm with running time better than n log n. So for the question, can we do better? The answer is no if we use a comparison-based sorting algorithm like heap sort. So that's pretty amazing. All we do is swap in a heap and the running time drops from the really quite unsatisfactory quadratic to the optimal n log n. Moreover, heap sort's a pretty practical sorting algorithm. You run this, it's going to go really fast. Is it as good as quicksort? Maybe not quite, but it's close. It's getting into the same ballpark. So let's look at another application, which frankly in some sense is almost trivial, but this is also a canonical way in which heaps are used. And in this application, it will be natural to call a heap by a synonymous name, a priority queue. So what I want you to think about for this example is that you've been tasked with writing software that performs a simulation of the physical world. So you might pretend, for example, that you're helping write a video game which is for basketball. Now, why would a heap come up in a simulation context? Well, the objects in this application are going to be events records. So an event might be, for example, that the ball will reach the hoop at a particular time, and that would be because a player shot it a couple seconds ago. When, if, for example, the ball hits the rim, that could trigger another event to be scheduled for the near future, which is that a couple players are going to vie for the rebound. That event, in turn, could trigger the scheduling of another event, which is one of these players commits an over-the-back foul on the other one and knocks him to the ground. That, in turn, could trigger another event, which is the player that got knocked on the ground gets up and argues the foul call, and so on. So when you have event records like this, there's a very natural key, which is just the timestamp, the time at which this event in the future is scheduled to occur. Now, clearly a problem which has to get solved over and over and over again in this kind of simulation is you have to figure out what's the next event that's going to occur. You have to know what other events to schedule, you have to know how to update the screen, and so on. So that's a minimum computation. So a very silly thing you could do is just maintain an unordered list of all of the events that have ever been scheduled and do a linear pass through them and compute the minimum. But you're going to be computing minimums over and over and over again. So again, that light bulb should go on and you could say, maybe a heap is just what I need for this problem. And indeed it is. So if you're storing these event records in a heap with the key being the timestamps, then when you extract min, the heap hands for you on a silver platter using only logarithmic time exactly which event is going to occur next. So let's move on to a less obvious application of heaps, which is a problem I'm going to call median maintenance. The way that this is going to work is you and I are going to play a little game. So on my side, what I'm going to do is I'm going to pass you index cards one at a time when there's a number written on each index card. Your responsibility is to tell me at each time step the median of the numbers that I've passed you so far. So after I've given you the first 11 numbers, you should tell me as quickly as possible the 6th smallest. After I've given you 13 numbers, you should tell me the 7th smallest, and so on. Moreover, we know how to compute the median in linear time, but the last thing I want is for you to be doing a linear time computation every single time step. Right? I only give you one new number. Do you really have to do linear time just to recompute the median if I just gave you one new number? So to make sure that you don't run a linear time selection algorithm every time I give you one new number, I'm going to put a budget on the amount of time that you can use at each time step to tell me the median. And it's going to be logarithmic in the number of numbers I've passed you so far. So I encourage you to pause the video at this point and spend some time thinking about how you would solve this problem. Alright, so hopefully you've thought about this problem a little bit. So let me give you a hint. What if you use 2 heaps? Do you see a good way to solve this problem then? All right, so let me show you a solution to this problem that makes use of two heaps. So the first heap we'll call H low. This heap will support extract max. Remember, we discussed that a heap you could pick whether it supports extract min or extract max. You don't get both, but you can get either one. It doesn't matter. And then we'll have another heap H high, which supports extract min. And the key idea is to maintain the invariant that the smallest half of the numbers that you've seen so far are all in the low heap, and the largest half of the numbers that you've seen so far are all in the high heap. So for example, after you've seen the first 10 elements, the smallest 5 of them should reside in H low, and the biggest 5 of them should reside in H high. After you've seen 20 elements, then the bottom 10, the smallest 10 should reside in H low, and the largest 10 should reside in H high. If you've seen an odd number, either one can be bigger, it doesn't matter. So if you have 21, you have the smallest 10 in the one and the biggest 11 in the other, or vice versa. It's not important. Now, given this key idea of splitting the elements in half according to the two heaps, you need two realizations, which I'll leave for you to check. So first of all, you have to prove you can actually maintain this invariant with only O of log I work in step I. Second of all, you have to realize this invariant allows you to solve the desired problem. So let me just quickly talk through both of these points, and then you can think about it in more detail on your own time. So let's start with the first one. How can we maintain this invariant using only log I work at time step I? And this is a little tricky. So let's suppose we've already processed the first 20 numbers, and the smallest 10 of them we've all worked hard to put only in H low, and the biggest 10 of them we've worked hard to put only in H high. Now here's your preliminary observation. What's true? So what do we know about the maximum element in H low? Well, these are the 10th smallest overall, and the maximum then is the biggest of the 10th smallest. So that would be the 10th order statistic, so the 10th smallest overall. Now what about in the high heap? What is its minimum value? Well, those are the biggest 10 values, so the minimum of the 10 biggest values would be the 11th order statistic. Okay? So the maximum of H low is the 10th order statistic. The minimum of H high is the 11th order statistic. They're right next to each other. These are, in fact, the two medians right now. So when this new element comes in, this 21st element comes in, we need to know which heap to insert it into. And, well, if it's smaller than the 10th order statistic, then it's still going to be in the bottom, then it's in the bottom half of the elements. It needs to go in the low heap. If it's bigger than the 11th order statistic, if it's bigger than the minimum value of the high heap, then that's where it belongs, in the high heap. If it's wedged in between the 10th and 11th order statistics, it doesn't matter. We can put it in either one. This is the new median anyways. Now, we're not done yet with this first point because there's a problem with potential imbalance. So imagine that the 21st element comes up and it's less than the maximum of the low heap, so we stick it in the low heap, and now that has a population of 11. And now imagine the 22nd number comes up, and that again is less than the maximum element in the low heap. So again we have to insert it in the low heap. Now we have 12 elements in the low heap, but we only have 10 in the right heap. So we don't have a 50-50 split of the numbers. But we can easily rebalance. We just extract the max from the low heap and we insert it into the high heap. And boom, now they both have 11, and the low heap has the smallest 11 and the high heap has the biggest 11. So that's how you maintain the invariant, that you have this 50-50 split in terms of the small and the high between the two heaps. You check where it lies with respect to the max of the low heap and the min of the high heap. You put it in the appropriate place, and whenever you need to do some rebalancing, you do some rebalancing. And this uses only a constant number of heap operations when a new number shows up, so that's log I work. So now, given this discussion, it's easy to see the second point. Given that this invariant is true at each time step, how do we compute the median? Well, it's going to be either the maximum of the low heap and or the minimum of the high heap, depending on whether I is even or odd. If it's even, both of those are medians. If I is odd, then it's just whichever heap has one more element than the other one. So the final application we'll talk about in detail in a different video, a video concerned with the running time of Dijkstra's shortest path algorithm, but I do want to mention it here as well, just to reiterate the point of how careful use of data structures can speed up algorithms, especially when you're doing things like minimum computations in an inner loop. So Dijkstra's shortest path algorithm, hopefully many of you have watched that video at this point, but basically what it does is it has a central while loop, and so it operates once per vertex of the graph, and at least naively it seems like what each iteration of the while loop does is an exhaustive search through the edges of the graph, computing a minimum. So if we think about the work performed in this naive implementation, it's exactly in the wheelhouse of a heap, right? So what we do in each of these loop iterations is do an exhaustive search computing a minimum. You see repeated minimum computations, a light bulb should go off and you should think, maybe a heap can help. And a heap can help in Dijkstra's algorithm. The details are a bit subtle and they're discussed in a separate video, but the upshot is we get a tremendous improvement in the running time. So recalling that M denotes the number of edges and N denotes the number of vertices of a graph. With the careful deployment of heaps in Dijkstra's algorithm, the runtime drops from this really rather large polynomial, the product of the number of vertices and the number of edges, down to something which is almost linear time. Namely O of M log N, where M is the number of edges and N is the number of vertices. So the linear time here would be O of M, linear the number of edges. We're picking up an extra log factor, but still this is basically as good as sorting. So this is a fantastically fast shortest path algorithm, certainly way, way better than what you get if you don't use heaps and just do repeated exhaustive searches for the minimum. So that wraps up our discussion of what I think you really want to know about heaps. Namely, what are the key operations that it supports? What is the running time you can expect from those operations? What are the types of problems that the data structure will yield speedups for? And a suite of applications. For those of you that want to take it to the next level and see a little bit about the guts of the implementation, there is a separate optional video that talks a bit about that. So in this video, we're going to take it at least partway to the next level for the heap data structure. That is, we'll discuss some of the implementation details, i.e. how would you code up a heap data structure from scratch. So remember what the point of a heap is. It's a container and it contains objects, and each of these objects, in addition to possibly lots of other data, should have some kind of key, and we should be able to compare the keys of different objects, social security numbers for different employers, edge weights for different edges in a network, or timestamps on different events, and so on. Now remember, for any data structure, the number one thing you should remember is what are the operations that it supports, i.e. what is the data structure good for, and also what is the running time you can count on of those operations. So something we promised in a previous video, and I'll indicate the implementation of in this video, is these two primary operations that a heap exports. First of all, you can insert stuff into it, and it takes time only logarithmic in the number of objects that the heap is storing. And second of all, you can extract an object that has the minimum key value. And again, we're going to allow duplicates in our heaps. So if there's multiple objects that all have a common minimum key value, the heap will return one of those. It's unspecified which one. As I mentioned earlier, you can also dress up heaps with additional operations, like you can do batch inserts in linear time rather than n log n time. You can delete from the middle of the heap. I'm not going to discuss those in the video. I'm just going to focus on how you'd implement insert and extract min. If you want to know how heaps really work, it's important to keep in mind simultaneously two different views of a heap. One as a tree and one as an array. So we're going to start on this slide with the tree view. Conceptually, this will be useful to explain how the heap operations are implemented. And conceptually, we'll think of a heap not just as any old tree, but as a tree that's rooted. It'll be binary, meaning that each node will have 0, 1, or 2 children nodes. And third, it will be as complete as possible. So let me draw for your amusement an as complete as possible binary tree that has 9 nodes. So if the tree had had only 7 nodes, it would have been obvious what as complete as possible means. It would have meant we just would have had 3 completely filled in levels. If it had had 15 nodes, it would have been 4 completely filled in levels. If you're in between these two numbers that are powers of 2 minus 1, well, we're going to call a complete tree as just the bottom level. You fill in the leaves from left to right. So here the 2 extra leaves on the 4th level are both pushed as far to the left as possible. So in our minds, this is how we visualize heaps. Let me next define the heap property. This imposes an ordering on how the different objects are arranged in this tree structure. The heap property dictates that at every single node of this tree, doesn't matter if it's the root, if it's a leaf, if it's an internal node, whatever, at every node x, the key of the object stored at x should be no more than the keys of x's children. Now, x may have 0 children if it's a leaf, it may have 1 child, or it may have 2 children. Whatever of those cases, 0, 1, or 2 children, all of those children's keys should be at least that of the key at x. For example, here is a heap with 7 nodes. Notice that I am allowing duplicates. There are 3 different objects that have the key value 4 in this heap. Another thing to realize is that while the heap property imposes useful structure on how the objects can be arranged, it in no way uniquely pins down their structure. So this exact same set of 7 keys could be arranged differently and it would still be a heap. The important thing is that in any heap, the root has to have a minimum value key. Just like in these 2 organizations of these 7 keys, the root is always a 4, the minimum key value. So that's a good sign, given that one of the main operations we're supposed to quickly implement is to extract the minimum value. So at least we know where it's going to be. It's going to be at the root of a heap. So while in our minds we think of heaps as organized in a tree fashion, we don't literally implement them as trees. So in something like search trees, you actually have pointers at each node, and you can traverse pointers to go from a node to the children, from the children to the parents, yada, yada, yada. It turns out it's much more efficient in a heap to just directly implement it as an array. Let me show you by example how a tree, like we had on the last slide, maps naturally onto an array representation. So let's look at a slightly bigger heap, one that has 9 elements. So let me draw an array with 9 positions, labeled 1, 2, 3, all the way up to 9. And the way we're going to map this tree, which is in our mind, to this array implementation is really very natural. We're just going to group the nodes of this tree by their level. So the root is going to be the only node at level 0. Then the children of the root are level 1. Their children constitute level 2, and then we have a partial level 3, which is just these last 2 nodes here. And now we just stick these nodes into the array one level at a time. So the root winds up in the privileged first position. So that's going to be the object, which is the first copy of the 4. Then we put in the level 1 objects, so that's the second copy of the 4 and the 8. Then we put in level 2, which has our third 4 along with the 2 9s. And then we have the last 2 nodes from level 3 rounding out the penultimate and final position of the array. And you might be wondering how it is we seem to be having our cake and eating it too. On the one hand, we have this nice logical tree structure. On the other hand, we have this array implementation, and we're not wasting any space on the usual pointers you would have in a tree to traverse between parents and children. So where's the free lunch coming from? Well, the reason is that because we're able to keep this binary tree as balanced as possible, we don't actually need pointers to figure out who is whose parent and who is whose child. We can just read that off directly from the positions in the array. So let me be a little bit more specific. If you have a node in the ith position, and I'm assuming I here is not 1, right? So the root doesn't have any parent, does not have a parent, but any other object in position I does have a parent. And what the position of that is depends on, in a simple way, on whether I is even or odd. So if I is even, then the parent is just at the position I over 2. And if I is odd, then it's going to be I over 2. Okay, that's a fraction, so we take the floor. That is, we round down to the nearest integer if I is odd. So, for example, the objects in positions 2 and 3 have as their parent the object in position 1. Those in 4 and 5 have the one in position 2 as its parent. 6 and 7 have as their parent the node in the object in position 3, and so on. And of course, we can invert this function. We can equally easily determine who the children are of a given node. So if you have an object that's at position I, then you notice that the children of I are going to be at the positions 2i and 2i plus 1. Of course, those may be empty. So if you have a leaf, of course, it doesn't have any children, and there may be one node that has only one child. But in the common case of an internal node, there's going to be 2 children. They're going to be at positions 2i and 2i plus 1. So rather than traversing pointers, it's very easy to just go from a node to its parent or to either one of its children just by doing these appropriate trivial calculations with respect to its position. So this slide illustrates some of the lower level reasons that heaps are quite a popular data structure. So the first one, just in terms of storage, we don't need any overhead at all. We have these objects, we're storing them directly in an array with no extra space. Second of all, not only do we not have to have the space for pointers, but we don't even have to do any traversing. All we do are these really simple divide by 2 or multiply by 2 operations, and using bit shifting tricks, those can also be implemented extremely quickly. So the next two slides let me indicate at a high level how you would implement the two exported operations, namely insertion and extract min in time logarithmic in the size of the heap. And rather than give you any pseudocode, I'm just going to show you how these work by example. I think it will be obvious how they extend to the general case. I think just based on this discussion, you'll be able to code up your own versions of insert and extract min if you so desire. So let's redraw the 9-node heap that we had on the previous slide. And again, I'm going to keep drawing it as a tree, and I'm going to keep talking about it as a tree, but always keep in mind the way it's really implemented is in terms of these array. And when I talk about the parent of a node, again, what that means is you go to the appropriate position given the position of the node from where you started. So let's suppose we have an existing heap like this blue heap here, and we're called upon to insert a new object, let's say with a key value k. Now remember, heaps are always supposed to be perfectly balanced binary trees. So if we want to maintain the property that this tree is perfectly balanced, there's pretty much only one place we can try to put the new key k, and that's as the next leaf. That is, it's going to be the new rightmost leaf on the bottom level. Or in terms of the array implementation, we just stick it in the first non-empty slot in the array. And if we keep track of the array size, we can in constant time, of course, know where to put the new key. Now whether or not we can get away with this depends on what the actual key value k is. But, for starters, we could say, what if we insert a key that's 7? Well, then we get to say, phew, we're done. So the reason we're done is because we have not violated the heap property. It is still the case that every node has key no bigger than that of its children. In particular, this third copy of a 4, it picked up a new child, but its key 7 was bigger than its key 4. So you can imagine that maybe we get lucky with another insert. Maybe the next insertion is a 10. And again, we put that in the next available spot in the last level. And that becomes the second child of the third copy of the 4. And again, we have no violation of the heap property. No worries. Still got a heap. And in these lucky events, insertion is even taking constant time. Right? Really, all we're doing is putting elements at the end of an array and not doing any rearranging. So what gets interesting is when we do an insertion that violates the heap property. So let's suppose we do yet another insertion, and the left child of this 12, it becomes a 5. Well, now we got a problem. Okay, so now we still have a as perfectly balanced as possible binary tree, but the heap property is not satisfied. In particular, it's violated at the node 12. It has one child. The key of that child is less than its own key. That's no good. So, is there some way we can restore the heap property? Well, a natural idea is just to swap the positions of the 5 and the 12. And that's something that, of course, can be done in constant time, because, again, from any node, we can go to the parent or the child in constant time just with a suitable trivial computation. So we say, okay, for starters, we put the 5 at the end, but that's no good. So we're going to swap the 5 with the 12. And now we see we're not out of the woods. No longer is there a heap violation at the node 12. That's been fixed. We've made it a leaf. But we've pushed up the heap violation. So now, instead, it's the 8 that has a problem. The 8 used to have 2 children with keys 12 and 9. That was fine. Now the 8 has 2 children with keys 5 and 9. The 5 is less than the 8. That's a violation of the heap property. But again, that's the only violation of the heap property. There's no other node we could have screwed up because 8 was the only person whose children we messed around with. All right, so now we just do it again. Let's try to again locally fix the heap violation by swapping the 5 with the 8. And now we see we've restored order. The only place where there could possibly be a violation of the heap property is at the root. The root, when we did this swap, the only person whose children we really messed with was the root 4, but fortunately its new child has key 5, which is bigger than it. One subtle point is you might be thinking that, in addition to screwing up the root node by messing around with its children, maybe we could have screwed up the 12 by messing around with its parent. Right? Its parent used to be 5, and now its parent is 8. So is there some possibility that its parent would all of a sudden have a key bigger than it? But if you think about it, this 8 and this 12, they were a parent-child relationship in the original heap. right? So back in the blue heap, the 12 was under the 8. Now the 12 is under the 8 yet again. Since we had the heap property for that pair before, we certainly have it now. So in general, as you push up this 5 up the tree, there's only going to be one possible edge that could be out of order, and that's between where the 5 currently resides and whatever its parent is. So when the 5's parent was 12, that was a violation. When 5's parent was 8, that was a violation. But now that we've pushed it up 2 levels and 5's parent is 4, that's not a violation because 4 is less than 5. So in general, step 2 of insertion is you do this swap, which it's called a lot of different things. I'm going to call it bubble up because that's how I learned it more years ago than I care to admit. But also this is called sometimes sift up, heapify up, and so on. So I've now told you the gist of how to implement insertion via repeated bubbling ups in a heap data structure. And this is really how it works. There's nothing I haven't told you. But I'm not going to really fill in all of the details. But I do encourage you to do that on your own time if this is something that interests you. And the two main things that you should check is, first of all, this bubbling up process has got to stop. And when it stops with the heap property restored. The second thing that needs to be checked, and this I think is easier to see, is that we do have the desired runtime, logarithmic in the number of elements in the heap. The key observation there is that because this is a perfectly balanced binary tree, we know exactly how many levels there are. So this is basically log base 2 of n levels, where n is the number of items in the heap. And what is the running time of this insertion procedure? Well, you only do a constant amount of work at each level, just doing the swap and a comparison. And then in the worst case, you have to swap at every single level, and there's a logarithmic number of levels. So that's insertion. Let's now talk about how to implement the extract min operation. And again, I'm going to do this by example, and it's going to be via repeated invocation of a bubble down procedure. So the extract min operation is responsible for removing from the heap an object with minimum key value and handing it back to the client on a silver platter. So we pretty much have to rip out the root. Remember, the minimum is guaranteed to be at the root. So that's how we have to begin in the extract min subroutine, is we just pluck off the root and hand it back to the client. So this removal, of course, leaves a gaping hole in our tree structure, and that's no good. One of the invariants we're responsible for maintaining is that we always have an as perfectly balanced as possible binary tree. And if you're missing a root, you certainly don't have an almost perfect binary tree. So what are we going to do about it? How do we fill this hole? Well, there's pretty much only one node that could fill this hole without causing other problems with the tree structure, and that is the very last node. So the rightmost leaf at the bottom level, one simple fix is to swap that up and have that take the place of the original root. So in this case, the 13 is going to get a massive promotion and get teleported all the way to be the new root of this tree. So now we've resolved our structural challenges. We now again have a as perfectly balanced as possible binary tree, but of course now we've totally screwed up the heap property, right? So the heap property says that at every node, including the root, the key value at that node has to be less than both of the children, and now it's all messed up, right? So at the root, the key value is actually bigger than both of the children. And matters are a little bit more tricky than they were with insertion, right? When we inserted at the bottom, because every node has a unique parent, if you want to push a node upward in the tree, there's sort of only one place it can go, right? All you can do is swap with your parent, unless you're going to try to do something really crazy. But if you want to do something local, pretty much you only have a unique parent you could try to swap with. Now, when we're trying to push nodes down to their rightful position in the tree, there's two different swaps we could do. One for the left child, one for the right child. And the decision that we make matters. To see that concretely, let's think about this example. There's this 13 at the root, which is totally not where it should be. And there's the two children, the 4 and the 8, and we could try swapping it with either one. So suppose we swap it in a misguided way with the right child, with the 8. So now the 8 becomes the new root, and the 13 gets pushed down a level. So on the one hand, we made some progress, because now at least we don't have a violation between the 13 and the 8. On the other hand, we still have violations involving the 13. The 13 is still violated with respect to the 12 and 9. And moreover, we've created a new problem between the 8 and the 4. Right? So now that the 8 is the root, that's still bigger than its left child, this 4. So it's not even clear we made any progress at all when we swapped the 13 with the 8. Okay? So that was a bad idea. And if you think about it, what made it a bad idea, the stupid thing was to swap it with the larger child. That doesn't make any sense. we really want to swap it with the smaller child. Remember, every node should have a key bigger than both of its children, so if we're going to swap up either the 4 or the 8, one of those is going to become the parent of the other. The parent's supposed to be smaller, so evidently we should take the smaller of the 2 children and swap the 13 with that. So we should swap the 13 with the 4, not with the 8. And now we observe a phenomenon very much analogous to what we saw in insert when we were bubbling up during insertion. It wasn't necessarily that we fixed violations of the heap property right away, but we would fix one and then introduce another one that was higher up in the tree, and we had confidence that eventually we could just push this violation up to the root of the tree and squash it, just like we're trying to win a game of whack-a-mole. Here, it's the opposite, just in the opposite direction. So we swap the 13 with the 4. It's true we've created one new violation of the heap property. That's again involving the 13 with its children 9 and 4, but we haven't created any new ones. We've pushed the heap violation further down the tree, and hopefully, again, like in whack-a-mole, we'll squash it at the bottom. So after swapping the 13 and the 4, now we just got to do the same thing. We say, okay, we're not done. We still don't have a heap. This 13 is bigger than both of its children. But now, with our accumulated wisdom, we know we should definitely swap the 13 with the 4. We're not going to try swapping with a 9, that's for sure. So we move the 4 up here, and the 13 takes the 4's old place, and boom, now we're done. So now we have no violations remaining. The 13 in its new position has no children, so there's no way it can have any violations. And the 4, because it was the smaller child, that's going to be bigger than the 9, so we haven't introduced a heap violation there. And again, we have these consecutive 4s, but we know that's not going to be a problem because those were consecutive 4s in the original heap as well. So you won't be surprised to hear that this procedure by which you push something down by swapping it with its smaller children is called bubble down. And extract min is nothing more than taking this last leaf, promoting it to the top of the tree, and bubbling down until the heap violation has been fixed. So again, on a conceptual level, that's all of the ingredients necessary for a complete from-scratch implementation of extracting the minimum from a heap. And as before, I'll leave it for you to check the details. So first of all, you should check that, in fact, this bubble down has to at some point halt, and when it halts, you do have a bona fide heap. The heap property is definitely restored. And second of all, the running time is logarithmic. Here, the running time analysis is exactly the same as before, so we already have observed that the height of a heap, because it's perfectly balanced, is essentially the log base 2 of the number of elements in the heap, and in bubbling down, all you do is a constant amount of work per level. All you got to do is a couple comparisons and a swap. So that's a peek at what's under the hood in the heap data structure, a little bit about the guts of its implementation. So having seen this, I hope you feel like a little bit more hardcore of a programmer, a little bit more hardcore of a computer scientist. In this sequence of videos, we'll discuss our last but not least data structure, namely the balanced binary search tree. Like our discussion of other data structures, we'll begin with the what. That is, we'll take the client's perspective and we'll ask what operations are exported by this data structure, what can you actually use it for. Then we'll move on to the how and the why. We'll peer under the hood of the data structure and look at how it's actually implemented. And in understanding the implementation, we'll understand why the operations have the running times that they do. So what is a balanced binary search tree good for? Well, I recommend thinking about it as a dynamic version of a sorted array. That is, if you have data stored in a balanced binary search tree, you can do pretty much anything on the data that you could if it was just a static sorted array, but in addition, the data structure can accommodate insertions and deletions. You can accommodate a dynamic set of data that you're storing over time. So to motivate the operations that a balanced binary search tree supports, let's just start with a sorted array and look at some of the things you can easily do with data that happens to be stored in such a way. So let's think about an array that has numerical data, although generally, as we've said, in data structures there's usually associated other data, that's what you actually care about, and the numbers are just some unique identifier for each of the records. So these might be an employee ID number, social security numbers, packet ID numbers in a network context, etc. So what are some things that are easy to do given that your data is stored as a sorted array? Well, there's a bunch of things. First of all, you can search. And recall that searching in a sorted array is generally done using binary search. So this is how we used to look up phone numbers when we had physical phone books. You'd start at the middle of the phone book. If the name you were looking for was less than the midpoint, you'd recurse on the left-hand side. Otherwise, you'd recurse on the right-hand side. As we discussed back in the master method lectures long ago, this is going to run in logarithmic time. Roughly speaking, every time you recurse, you've thrown out half of the array, so you're guaranteed to terminate within a logarithmic number of iterations. So binary search gives us logarithmic search time. Something else we discussed in previous lectures is the selection problem. So previously we discussed this in the much harder context of unsorted arrays. Remember, in the selection problem, in addition to an array, you're given an order statistic. So if your order statistic that your target is 17, that means you're looking for the 17th smallest number that's stored in the array. So in previous lectures, we worked very hard to give a linear time algorithm for this problem in unsorted arrays. Now, in a sorted array, if you want to know the 17th smallest element in the array, pretty easy problem. Just return whatever element happens to be in the 17th position of the array. Since the array is sorted, that's where it is. So no problem. If it's already sorted, constant time, you can solve the selection problem. Of course, two special cases of the selection problem are finding the minimum element of the array. That's just the order statistic problem with I equal 1. And the maximum element, that's just when I equals n. So this just corresponds to returning the element that's in the first position and the last position of the array, respectively. Well, let's do some more brainstorming. What other operations could we implement on a sorted array? Well, here's a couple more. So there are operations called the predecessor and successor operations. And so the way these work is you start with one element. So say you start with a pointer to the 23, and you want to know where in this array is the next smallest element. That's the predecessor query. And the successor operation returns the next largest element in the array. So the predecessor of the 23 is the 17. The successor of the 23 would be the 30. And again, in a sorted array, these are trivial, right? You just know the predecessor is just one position back in the array. The successor is one position forward. So given a pointer to the 23, you can return the 17 or the 30 in constant time. What else? Well, how about the rank operation? So we haven't discussed this operation in the past. So what rank is, this asks for how many keys stored in the data structure are less than or equal to a given key. So for example, the rank of 23 would be equal to 6 because 6 of the 8 elements in the array are less than or equal to 23. And if you think about it, implementing the rank operation is really no harder than implementing search. All you do is search for the given key, and wherever the search terminates in the array, you just look at the position of the array, and boom, that's the rank of that element. So for example, if you do a binary search for 23, and then when it terminates, you discover it is there in position number 6, then you know the rank is 6. If you do an unsuccessful search, say you search for 21, well then you get stuck in between the 17 and the 23, and at that point you can conclude that the rank of 21 in this array is 5. Let me just wrap up the list with a final operation which is trivial to implement in a sorted array. Namely, you can output or print, say, the stored keys in sorted order, let's say from smallest to largest. And naturally, all you do here is a single scan from left to right through the array, outputting whatever element you see next. The time required is constant per element or linear overall. So that's a quite impressive list of supported operations. Could we really be so greedy as to want still more from our data structure? Well, yeah, certainly. We definitely want more than just what we have on this slide. The reason being, these are operations that operate on a static data set, which is not changing over time. But the world, in general, is dynamic. For example, if you're running a company and keeping track of the employees, sometimes you get new employees, sometimes employees leave. That is, we want a data structure that not only supports these kinds of operations, but also insertions and deletions. Now, of course, it's not that it's impossible to implement insert or delete in a sorted array. It's just that they're going to run way too slow. In general, you have to copy over a linear amount of stuff on an insertion or deletion if you want to maintain the sorted array property. So this linear time performance for insertion and deletion is unacceptable unless you barely ever do those operations. So the raison d'etre of a balanced binary search tree is to implement this exact same set of operations, just as rich as that's supported by a sorted array, but in addition, insertions and deletions. Now, a few of these operations won't be quite as fast. We're going to have to give up a little bit. Instead of constant time, they'll run in logarithmic time, but we'll still get logarithmic time for all of these operations, linear time for outputting the elements in sorted order, plus we'll be able to insert and delete in logarithmic time. So let me just spell that out in a little more detail. So a balanced binary search tree will act like a sorted array, plus it will have fast, meaning logarithmic time, inserts and deletes. So let's go ahead and spell out all of those operations. So search is going to run in log n time, just like before. Select runs in constant time in a sorted array, and here it's going to take logarithmic, so we'll give up a little bit on the selection problem, but we'll still be able to do it quite quickly. Even on the special cases of finding the minimum or finding the maximum, in our data structure, we're going to need logarithmic time in general. Same thing for finding predecessors and successors. They're no longer constant time. They go up to logarithmic. Rank took us logarithmic time even in the sorted array version, and that will remain logarithmic here. As we'll see, we lose essentially nothing over the sorted array if we want to output the key values in sorted order, say from smallest to largest. And crucially, we have two more fast operations compared to the sorted array data structure. We can insert stuff. So if you hire a new employee, you can insert them into your data structure. If an employee decides to leave, you can remove them from the data structure. You do not have to spend linear time like you do for a sorted array. You only have to spend logarithmic time, where, as always, n is the number of keys being stored in the data structure. So the key takeaway here is that if you have data and it has keys which come from a totally ordered set, like say numeric keys, then a balanced binary search tree supports a very rich collection of operations. So if you anticipate doing a lot of different processing using the ordering information of all of these keys, then you really might want to consider a balanced binary search tree to maintain them. One thing to keep in mind, though, is we have seen a couple other data structures which don't do quite as much as balanced binary search trees, but what they do better. We just discussed in the last slide the sorted array. So if you have a static data set, you don't need inserts and deletes. Well, then by all means, don't bother with balanced binary search trees. Just use a sorted array because it'll do everything super fast. But we also saw two dynamic data structures which don't do as much, but what they do very well. So we saw a heap. So what a heap is good for is it's just as dynamic as a search tree. It allows insertions and deletions, both in logarithmic time, and in addition, it keeps track of the minimum element or the maximum element. Remember, in a heap, you can choose whether you want to keep track of the minimum or keep track of the maximum, but unlike in a search tree, a heap does not simultaneously keep track of the minimum and the maximum. So if you just need those three operations, insertions, deletions, and remembering the smallest, and this would be the case, for example, in a priority queue or a scheduling application, as discussed in the heap videos, then a binary search tree is overkill. You might want to consider a heap instead. In fact, the benefits of a heap don't show up in the big O notation here. Both have logarithmic operation time, but the constant factors both in space and time are going to be faster with a heap than with a balanced binary search tree. The other dynamic data structure that we discussed is a hash table. And what hash tables are really, really good at is handling insertions and searches, that is lookups. Sometimes, depending on the implementation, they'll also handle deletions really well also. So if you don't actually need to remember things like minima, maxima, or remember ordering information on the keys, you just have to remember what's there and what's not, then the data structure of choice is definitely the hash table, not the balanced binary search tree. Again, a balanced binary search tree would do fine. It would give you logarithmic lookup time, but it's kind of overkill for the problem. If all you need are fast lookups, a hash table, recall, will give you constant time lookups. So that'll be a noticeable win over the balanced binary search tree. But if you want a very rich set of operations for processing your data, then the balanced binary search tree could be the optimal data structure for your needs. So in this video, we'll go over the basics behind implementing binary search trees. We're not going to focus on the balance aspect in this video. That'll be discussed in later videos. We're going to talk about things which are true for binary search trees in general, balanced or otherwise. But let's just recall, why it is are we doing this? What is the raison d'etre of this data structure, the balanced version of a binary search tree? And basically, it's a dynamic version of a sorted array. So it does pretty much everything you can do on a sorted array, maybe in slightly more expensive time, but still really fast. But in addition, it's dynamic. It accommodates insertions and deletions. So remember, if you want to keep a sorted array data structure, every time you insert, every time you delete, you're probably going to wind up paying a linear factor, which is way too expensive in most applications. By contrast, with a search tree, a balanced version, you can insert and delete in logarithmic time in the number of keys in the tree. And moreover, you can do stuff like search in logarithmic time, no more expensive than binary search on a sorted array. And also you can solve, say, the selection problem, in the special cases, the minimum and maximum. Okay, it's not constant time like in a sorted array, but still logarithmic, pretty good. And in addition, you can print out all of the keys from smallest to largest in linear time, constant time per element, just like you could with a linear scan through a sorted array. So that's what they're good for. Everything a sorted array can do more or less, plus insertions and deletions, everything in logarithmic time. So how are search trees organized? And again, what I'm going to say in the rest of this video is true both for balanced and unbalanced search trees. We're going to worry about the balancing aspect in the later videos. All right, so let me tell you the key ingredients in a binary search tree. Let me also just draw a simple cartoon example up in the upper right part of the slide. So there's a one-to-one correspondence between nodes of the tree and keys that are being stored. And as usual in our data structure discussions, we're going to act as if the only thing that we care about, the only thing that exists at each node is this key, when generally there's associated data that you really care about. So each node in the tree will generally contain both a key plus a pointer to some data structure that has more information. Maybe the key is the employee ID number, and then there's a pointer to lots of other information about that employee. Now, in addition to the nodes, you have to have links amongst the nodes. And there's a lot of different ways to do the exact implementation of the pointers that connect the nodes of a tree together. For the video, I'm just going to keep it as straightforward as possible. And we're just going to assume that at each node, there's 3 pointers, one to a left child, another one to a right child, and then a third pointer which points to the parent. Now, of course, some of these pointers can be null. And in fact, in the 5-node binary search tree I've drawn on the right, for each of the 5 nodes, at least one of these 3 pointers is null. So for example, for the node with key 1, it has a null left child pointer. There's no left child. Its right child pointer is going to point to the node with key 2. Its parent pointer is going to point to the node that has key 3. Similarly, 3 is going to have a null parent pointer, and the root node, in this case 3, is the unique node that has a null parent pointer. Here, the node with key value 3, of course, has a left child pointer. It points to 1. It has a right child pointer. It points to 5. Now, here is the most fundamental property of search trees. Let's just go ahead and call it the search tree property. So the search tree property asserts the following condition at every single node of a search tree. If the node has some key value, then all of the keys stored in the left subtree should be less than that key. And similarly, all of the keys stored in the right subtree should be bigger than that key. So if we have some node whose stored key value is x, and this is somewhere, say deep in the middle of the tree. So upward we think of as being toward the root. And then if we think about all the nodes that are reachable after following the left child pointer from x, that's the left subtree. And similarly, the right subtree being everything reachable via the right child pointer from x, it should be the case that all keys in the left subtree are less than x, and all keys in the right subtree are bigger than x. And again, I want to emphasize this property holds not just at the root, but at every single node in the tree. I've defined the search tree property assuming that all of the keys are distinct. That's why I wrote strictly less than in the left subtree and strictly bigger than in the right subtree. But search trees can easily accommodate duplicate keys as well. You just have to have some convention about how you handle ties. So for example, you could say that everything in the left subtree is less than or equal to the key at that node, and then everything in the right subtree should be strictly bigger than that node. That works fine as well. So if this is the first time you've ever heard of the search tree property, maybe at first blush it seems a little arbitrary. It seems like I pulled it out of thin air. But actually, you would reverse engineer this property if you sat down and thought about what property would make search really easy in a data structure. The point is the search tree property tells you exactly where to look for some given key. So looking ahead a little bit, stealing my fire from a slide to come, suppose you were looking for, say, a key 23. And you start at the root, and the root is 17. The point of the search tree property is you know where 23 has to be. If the root is 17 and you're looking for 23, if it's in the tree, no way is it in the left subtree. It's got to be in the right subtree. So you can just follow the right child pointer and forget about the left subtree for the rest of the search. This is very much in the spirit of binary search, where you start in the middle of the array, and again, you compare what you're looking for to what's in the middle, and either way, you can recurse on one of the two sides, forgetting forevermore about the other half of the array. And that's exactly the point of the search tree property. We're going to search from root on down. The search tree property guarantees we have a unique direction to go next, and we never have to worry about any of the stuff that we don't see. We could also draw a very loose analogy with our discussion of heaps. You might recall heaps were also, logically, we thought of them as a tree, even though they're implemented as an array. And heaps had some heap property. And if you go back and review the heap property, you'll find that it is not the same thing as the search tree property. Those are two different properties, and that's because they're trying to make different things easy. Back when we talked about heaps, the property was that, this was for the extract min version, parents always have to be smaller than their children. That's different than the search tree property, which says stuff to the left is smaller than you, stuff to the right is bigger than you. In heaps, we had the heap property so that identifying the minimum value was trivial. It was guaranteed to be at the root. Heaps are designed so that you can find the minimum easily. Search trees are defined so that you can search easily. That's why we have this different search tree property. If you want to get smaller, you go left. If you want to get bigger, you go right. One point that's important to understand early, and this will be particularly relevant once we try to enforce balancing in our subsequent videos, is that for a given set of keys, you could have a lot of different search trees. On the previous slide, I drew one search tree containing the key values 1, 2, 3, 4, 5. Let me redraw that exact same search tree here. If you stare at this tree a little while, you'll agree that in fact at every single node of this tree, all of the things in the left subtree are smaller, all of the things in the right subtree are bigger. However, let me show you another valid binary search tree with this exact same set of keys. So in this second search tree, the root is 5, the maximum value, and everybody has null right children. Only the left children are populated, and it goes 5, 4, 3, 2, 1 in descending order. If you check, here again, it has the property that at every node, everything in the left subtree is smaller, everything in the right subtree, in this case empty, is bigger. So extrapolating from these two cartoon examples, we surmise that for a given set of n keys, search trees that contain these keys could vary in height anywhere from the best case scenario of a perfectly balanced binary tree, which is going to have like logarithmic height, to the worst case of one of these linked list-like chains, which is going to be linear in the number of keys n. And so just to remind you, the height of a search tree, which is also sometimes called the depth, is just the longest number of hops it ever takes to get from a root to a leaf. So in the first search tree, here the height is 2, and in the second search tree the height is 4. If the search tree is perfectly arranged with the number of nodes essentially doubling at every level, then the depth is, you're going to run out of nodes around the depth of log base 2 of n. And in general, if you have a chain of n keys, the depth is going to be n minus 1. But let's just call it n amongst friends. So now that we understand the basic structure of binary search trees, we can actually talk about how to implement all of the operations that they support. So as we go through most of the supported operations one at a time, I'm just going to give you a really high-level description. It should be enough for you to code up your own implementation if you want, or as usual, if you want more details or actual working code, you can check on the web or in one of a number of good programming or algorithms textbooks. So let's start with really the primary operation, which is search. Searching, we've really already discussed how it's done when we discussed the search tree property. Again, the search tree property makes it obvious how to look for something in a search tree. Pretty much you just follow your nose, you have no other choice. So you start at the root, it's the obvious place to start. If you're lucky, the root is what you're looking for, and then you stop and you return the root. More likely, the root is either bigger than or less than the key that you're looking for. Now, if the key is smaller, the key you're looking for is smaller than the key at the root, where are you going to look? Well, the search tree property says if it's in the tree, it's got to be in the left subtree. So you follow the left subchild pointer. If the key you're looking for is bigger than the key at the root, where's it got to be? Got to be in the right subtree. So you're just going to recurse on the right subtree. So in this example, if you're searching for, say, the key 2, obviously you're going to go left from the root. If you're searching for the key 4, obviously you're going to go right from the root. So how can the search terminate? Well, it can terminate in one of two ways. First of all, you might find what you're looking for. So in this example, if you search for 4, you're going to traverse a right child pointer, then a left child pointer, and then boom, you're at the 4, and you return successfully. The other way the search can terminate is with a null pointer. So in this example, suppose you were looking for a node with key 6. What would happen? Well, you start at the root, 3 is too small, so you go to the right. You get to 5. 5 is still too small because you're looking for 6. So you try to go right, but the right child pointer is null. And that means 6 is not in the tree. If it was anywhere in the tree, it had to be to the right of the 3, it had to be to the right of the 5, but you tried it and you ran out of pointers, so the 6 isn't there, and you return correctly with an unsuccessful search. Next, let's discuss the insert operation, which really is just a simple piggybacking on the search that we just described. So for simplicity, let's first think about the case where there are no duplicate keys. The first thing to do on this insertion is search for the key K. Now, because there are no duplicates, this search will not succeed. This key K is not yet in the tree. So for example, in the picture on the right, we might think about trying to insert the key 6. What's going to happen when we search for 6, we follow a right child pointer, we go from 3 to 5, and then we try to follow another one and we get stuck. There's a null pointer going to the right of 5. Then when this unsuccessful search terminates at a null pointer, we just rewire that pointer to point to a node with this new key K. So if you want to permit duplicates in your data structure, you got to tweak the code of insert a little bit, but really barely at all. You just need some convention for handling the case when you do encounter the key that you're about to insert. So for example, if the current node has a key equal to the one you're inserting, you could have the convention that you always continue on the left subtree. And then you continue the search as usual, again, eventually terminating in a null pointer, and you stick the new inserted node, you rewire the null pointer to point to it. One good exercise for you to think through, which I'm not going to say more about here, is that when you insert a new node, you retain the search tree property. That is, if you start with a search tree, you start with a tree where at every node, stuff to the left is smaller, stuff to the right is bigger. You insert something and you follow this procedure, you will still have the search tree property after this new node has been inserted. That's something for you to think through. So what I want to do next is test your understanding of both the search and insertion procedures by asking you about their running time. So of the following 4 parameters of a search tree that contains n different keys, which one governs the worst case time of a search or of an insertion? So the correct answer is the third one. So the height of a search tree governs the worst case time of a search or of an insertion. Notice that means merely knowing the number of keys n is not enough to deduce what the worst case search time is. You also have to know something about the structure of the tree. So to see that, just let's think about the 2 examples that we've been running so far, one of which is nice and balanced, and the other of which contains exactly the same 5 keys, is super unbalanced. It's this crazy linked list in effect. So in any search tree, the worst case time to do a search or an insertion is proportional to the largest number of pointers, left or right child pointers, that you might have to follow to get from the root all the way to a null pointer. Of course, in a successful search, you're going to terminate before you encounter a null pointer, but in the worst case, or an insertion, you go all the way to a null pointer. Now in the tree on the left, you're going to follow at most 3 such pointers. So for example, if you're searching for 2.5, you're going to follow a left pointer, followed by a right pointer, followed by another right pointer, and then that one's going to be null. So you're only going to follow 3 pointers. On the other hand, in the right tree, you might follow as many as 5 pointers before that 5th pointer is null. For example, if you search for the key 0, you're going to traverse 5 left pointers in a row, and then you're finally going to encounter the null at the end. So it is not constant time, certainly. You have to get to the bottom of the tree. It's going to be proportional to the logarithm in the number of keys. If you have a nicely balanced binary search tree like this one on the left, it's going to be proportional to the number of keys n, as in the fourth answer, if you have a really lousy search tree like this one on the right. And in general, the search time or the insertion time is going to be proportional to the height, the largest number of hops you need to take to get from the root to a leaf of the tree. Let's move on to some more operations that search trees support, but that, for example, the dynamic data structures of heaps and hash tables do not. So let's start with the minimum and the maximum. So by contrast, in a heap, remember, you can choose one of the two. You can either find the minimum easily or find the maximum easily, but not both. In a search tree, it's really easy to find either the min or the max. So let's start with the minimum. One way to think of it is that you do a search for negative infinity in the search tree. So you start at the root, and you just keep following left child pointers until you run out, until you hit a null. And whatever the last key that you visit has to be the smallest key of the tree, right? Because think about it. Suppose you start at the root, right? Suppose that the root is not the minimum. Then where's the minimum got to be? It's got to be in the left subtree. So you follow the left child pointer, and then you just repeat the argument. If you haven't already found the minimum, where's it got to be with respect to the current place? It's got to be in the left subtree. And you just iterate until you can't go to the left any further. So for example, in our running search tree, you'll notice that if we just keep following left child pointers, we'll start at the 3, we'll go to the 1, we'll try to go left from the 1, we'll hit a null pointer, and we return 1. And 1 is indeed the minimum key in this tree. Now, given that we've gone over how to compute the minimum, no prizes to guess how we compute the maximum. Of course, if we want to compute the maximum, instead of following left child pointers, we follow right child pointers by symmetric reasoning that's guaranteed to find the largest key in the tree. It's like searching for the key plus infinity. All right, so what about computing the predecessor? So remember, this means you're given a key in the tree, an element of the tree, and you want to find the next smallest element. So for example, the predecessor of the 3 is 2, the predecessor of the 2 in this tree is the 1, the predecessor of the 5 is the 4, the predecessor of the 4 is the 3. So here I'll be a little hand-wavy just in the interests of getting through all of the operations in a reasonable amount of time, but let me just point out that there's one really easy case, and then there's one slightly trickier case. So the easy case is when the node with the key k has a non-empty left subtree. If that's the case, then what you want is simply the biggest element in this node's left subtree. So I'll leave it for you to prove formally that this is indeed the correct way to compute predecessors for keys that do have a non-empty left subtree. Let's just verify it in our example by going through the trees that have a left subtree and checking that this is in fact what we want. Now, if you look at it, there's actually only 2 nodes that have a non-empty left subtree. The 3 has a non-empty left subtree, and indeed the largest key in the left subtree of 3 is the 2, and that is the predecessor of the 3, so that worked out fine. And then the other node with a non-empty left subtree is the 5, and its left subtree is simply the element 4. Of course, the maximum in that tree is also 4, and you'll notice that is indeed the predecessor of 5 in this entire search tree. So the trickier case is what happens if you have a key with no left subtree at all. Okay, so what are you going to do if you're not in the easy case? Well, given at this node with key k, you only have 3 pointers, and by assumption, the left one is null. So that's not going to get you anywhere. Now, the right child pointer, if you think about it, is totally pointless for computing the predecessor. Remember, the predecessor is going to be a key less than the given key k. The right subtree, by definition of a search tree, only has keys that are bigger than k. So it stands to reason to find the predecessor, we got to follow the parent pointer. Maybe, in fact, more than one parent pointer. So to motivate exactly how we're going to follow parent pointers, let's look at a couple of examples in our favorite search tree here on the right. So let's start with the node 2. So we know we got to follow a parent pointer. When we follow 2's parent pointer, we get to 1. And boom, 1 in fact is 2's predecessor in this tree. So that was really easy. To compute 2's predecessor, it seems that all we have to do is follow the parent pointer. So for another example though, let's think about the node 4. Now 4, when we follow its parent pointer, we get to 5. And 5 is not 4's predecessor, it's 4's successor. Right? We want a key that is less than where we started. We followed the parent pointer and it was bigger. But if we follow one more parent pointer, then we get to the 3. So from the 2, we needed to follow one parent pointer. From the 4, we needed to follow 2 parent pointers. But the point is, you just need to follow parent pointers until you get to a node with key smaller than your own. And at that point, you can stop, and that's guaranteed to be the predecessor. So hopefully you found this intuitive. I should say I have definitely not formally proved that this works, and that is a good exercise for those of you that want to have a deeper understanding of search trees and this magical search tree property and all of the structure that it grants you. The other thing I should mention is another way to interpret the terminating criterion. So what I've said is you stop your search of parent pointers as soon as you get to a key smaller than yours. If you think about it a little bit, you'll realize you'll get to a key smaller than yours the very first time you take a left turn. So the very first time that you go from a right child to its parent. Look at the example. When we started from 2, we took a left turn, right? We went up a link going leftward. 2 is a right child of 1, and that's when we got to the predecessor in just one step. By contrast, when we started from the 4, our first step was to the right. So we got to a node that was bigger than where we started. 4 is 5's left child, so it's got to be smaller than 5. But the first time we took a left turn on the next step, we got to a node that was not only smaller than 5, but actually smaller from 4, smaller from our starting point. So in fact, you're going to see a key smaller than your starting point the very first time you take a left turn, the very first time you go from a node to a parent, and in fact, that node is that parent's right child. So this is another statement which I think is intuitive, but which formally is not totally obvious. And again, I encourage you to think carefully about why these two descriptions of the terminating criterion are exactly the same. So it doesn't matter if you stop when you first find a key smaller than your starting point. It doesn't matter if you first stop when you follow a parent pointer that goes from a node that's the right child of a node. Either way, you're going to stop at exactly the same time. So I encourage you to think about why those are the exact same stopping condition. A couple of other details. If you start from the unique node that has no predecessor at all, you're never going to trigger this terminating condition. So for example, if you start from the node 1 in the search tree, not only is the left subtree empty, which says you're supposed to start traversing parent pointers, but then when you traverse a parent pointer, you only go to the right. You never turn left. And that's because there's no predecessor. So that's how you detect that you're at the minimum of a search tree. And then, of course, if you wanted to compute the successor of a key instead of the predecessor, obviously you would just flip left and right throughout this entire description. So that's the high-level explanation of all of these different ordering operations, minimum, maximum, predecessor, and successor, work in a search tree. Let me ask you the same question I asked you when we talked about search and insertion. How long do these operations take in the worst case? Well, the answer is the same as it was before. It's proportional to the height of the tree, and the explanation is exactly the same as it was before. So to understand the dependence on the height, let's just focus on the maximum operation as is stated in the question. The other three operations, the running time is proportional to the height in the worst case for exactly the same reasons. So what does the max operation do? Well, you start at the root and you just follow right child pointers until you run out of them, until you hit null. So, that the running time is going to be no worse than the longest such path. It's a particular path from the root to essentially a leaf. So it's never going to have running time more than the height of the tree. On the other hand, for all you know, the path from the root to the maximum key might well be the longest one in the tree. It might be the path that actually determines the height of the search tree. So for example, in our running unbalanced example, that would be a bad tree for the minimum operation. If you look for the minimum in this tree, then you'd have to traverse every single pointer from 5 all the way down to 1. Of course, there's an analogous bad search tree for the maximum operation, where the 1 is the root and the 5 is all the way down as a leaf. Another thing you can do with search trees, which mimics what you can do with sorted arrays, is you can print out all of the keys in sorted order in linear time, with constant time per element. Obviously, in a sorted array, this is trivial. You just use a for loop starting at the beginning, going to the end of the array, printing out the keys one at a time. And there's a very elegant recursive implementation for doing the exact same thing in a search tree. And this is known as an in-order traversal of a binary search tree. So as always, you begin at the beginning, namely at the root of the search tree. And a little bit of notation, let's call all of the search tree that starts at R's left child T sub L, and the search tree rooted at R's right child T sub R. In our running example, of course, the root is 3. T sub L would correspond to the search tree comprising only the elements 1 and 2. T sub R would correspond to the subtree comprising only the elements 5 and 4. Now remember, we want to print out the keys in increasing order. So in particular, the first key we want to print out is the smallest of them all. So something we definitely don't want to do is we don't want to first print out the key at the root. For example, in our search tree example, the root's key is 3. We don't want to print that out first. We want to print out the 1 first. So where's the minimum lie? Well, by the search tree property, it's got to lie in the left subtree T sub L. So we're just going to recurse on T sub L. So by the magic of recursion, or if you prefer induction, what recursing on T sub L is going to accomplish is we're going to print out all of the keys in T sub L in increasing order, from smallest to largest. Now that's pretty cool, because T sub L contains exactly the keys that are smaller than the key at the root. Remember, that's the search tree property. Everything bigger than the root's key has to be in the left subtree. Everything bigger than the root's key has to be in its right subtree. So in our concrete example, this first recursive call is just going to print out the keys 1 and then 2. And now, if you think about it, it's the perfect time to print out the key at the root, right? We want to print out all the keys in increasing order. We've already done everything less than the root's key. We're, recursing on the right-hand side will take care of everything bigger than it. So in between the two recursive calls, and this is why it's called an in-order traversal, that's when we want to print out R's key. And clearly this works in our concrete example. The first recursive call prints out 1 and 2. It's the perfect time to print out 3, and then the recursive call will print out 4 and 5. And more generally, the recursive call on the right subtree will print out all of the keys bigger than the root's key in increasing order, again by the magic of recursion or induction. So the fact that this pseudocode is correct, the fact that this so-called in-order traversal indeed prints out the keys in increasing order, is a fairly straightforward proof by induction. It's very much in the spirit of the proofs by induction of correctness of divide and conquer algorithms that we discussed earlier in the course. So what about the running time of an in-order traversal? The claim is that the running time of this procedure is linear. It's O of n, where n is the number of keys in the search tree. And the reason is there's exactly one recursive call for each node of the tree, and constant work is done in each of those recursive calls. In a little more detail, so what does the in-order traversal do? Well, it prints out the keys in increasing order. In particular, it prints out each key exactly once. Each recursive call prints out exactly one key's value. So there's exactly n recursive calls, and all a recursive call does is print one thing. So n recursive calls, constant time for each, that gives us a running time of O of n overall. In most data structures, deletion is the most difficult operation, and in search trees, they're no exception. So let's get into it and talk about how deletion works. There are 3 different cases. So the first order of business is to locate the node that has the key k, to locate the node that we want to get rid of. All right, so for starters, maybe we're trying to delete the key 2 from our running example search tree. So the first thing we need to do is figure out where it is. So there are 3 possibilities for the number of children that a node in a search tree might have. It might have 0 children, it might have 1 child, it might have 2 children. Corresponding to those 3 cases, the deletion pseudocode will also have 3 cases. So let's start with the happy case, where there's only 0 children, like in this case where we're deleting the key 2 from the search tree. Then, of course, we can, without any reservations, just delete the node directly from the search tree. Nothing can go wrong. There's no children depending on that node. Then there's the medium difficult case. This is where the node containing k has 1 child. An example here would be if we wanted to delete 5 from the search tree. So the medium case is also not too bad. All you got to do is splice out the node that you want to delete. That creates a hole in the tree, but then that node, deleted node's unique child, assumes the previous position of the deleted node. I could make a nerdy joke about Shakespeare right here, but I'll refrain. For example, in our 5-node search tree, if we wanted to, let's say we haven't actually deleted 2 out of this one. If we wanted to delete the 5, we'd take it out of the tree. That would leave a hole, but then we just replace the position previously held by 5 by its unique child 4. And if you think about it, that works just fine in the sense that that preserves the search tree property. Remember, the search tree property says that everything in, say, a right subtree has to be bigger than everything in the node's key. So we've made 4 the new right child of 3, but 4 and any children that it might have were always part of 3's right subtree. So all that stuff has got to be bigger than 3. So there's no problem in putting 4 and possibly all of its descendants as the right child of 3. The search tree property is in fact retained. So the final difficult case then is when the node being deleted has both of its children, has two children. So in our running example with 5 nodes, this would only transpire if we wanted to delete the root, if we wanted to delete the key 3 from the tree. The problem, of course, is that you can try ripping out this node from the tree, but then there's this hole, and it's not clear that it's going to work to promote either child into that spot. You might stare at our example search tree and try to understand what would happen if you tried to bring 1 up to be the root, or if you tried to bring 5 up to be the root. Problems would happen. That's what would happen. This is an interesting contrast to when we face the same issue with heaps, because the heap properties in some senses perhaps less stringent. There we didn't have an issue. When we wanted to delete something with 2 children, we just promoted the smaller of the 2 children, assuming we wanted to export an extract min operation. Here we're going to have to work a little harder. In fact, this is going to be a really neat trick. We're going to do something that reduces the case of 2 children to the previously solved cases of 0 or 1 children. So here's the very sneaky way we identify a node to which we can apply either the case 0 or the case 1 operation. What we're going to do is we're going to start from k, and we're going to compute k's predecessor. Remember, this is the next smallest key in the tree. So for example, the predecessor of the key 3 is 2. That's the next smallest key in the tree. In general, let's call k's predecessor L. Now, this might seem complicated, right? We're trying to implement one tree operation, namely deletion, and all of a sudden we're invoking a different tree operation predecessor, which we covered a couple slides ago. And to some extent, you're right. Delete, this is a non-trivial operation, but it's not quite as bad as you think for the following reason. When we compute this predecessor, we're actually in the easy case of the predecessor operation, conceptually. Remember, how do you compute a predecessor? Well, it depends. What does it depend on? It depends on whether you've got a non-empty left subtree or not. If you don't have a non-empty left subtree, that's when you got to do this thing where you follow parent pointers upward until you find a key which is smaller than where you started. But if you've got a left subtree, then it's easy. You just find the maximum of the left subtree, and that's got to be the predecessor. And remember, finding maximum are easy. All you do is follow right child pointers until you can't anymore. Now what's cool is, because we only bother with this predecessor computation in the case where k's node has both children, we only have to do it in the case where it has a non-empty left subtree. So really, when we say compute k's predecessor L, all you got to do is follow k's left child, that's not null because it has both children, and then follow right child pointers until you can't anymore, and that's the predecessor. Now here's the fairly brilliant part of the way you implement deletion in a search tree, which is you swap these 2 keys, k and l. So for example, in our running search tree, instead of this 3 at the root, we would put a 2 there, and instead of this 2 at the leaf, we would put a 3 there. Now the first time you see this, it should strike you as a little crazy, maybe even cheating, like we're just completely disregarding the rules of search trees. And actually it is. Like, check out what happened to our example search tree. We swapped the 3 and the 2, and this is not a search tree anymore, right? So we have this 3, which is in 2's left subtree, and the 3 is bigger than the 2. And that is not allowed. That is a violation of the search tree property. Oops. So how can we get away with this? We can get away with this because we're going to delete 3 anyways. So we're going to wind up with a search tree at the end of the day. So we may have messed up the search tree property a little bit, but we've swapped k into a position where it's really easy to get rid of. Well, how did we compute k's predecessor L? Ultimately, that was the result of a maximum computation, which involves following right child pointers until you get stuck. And L was the place we got stuck. What does it mean to get stuck? It means L's right child pointer is null. It does not have 2 children. In particular, it does not have a right child. Once we swap k's into L's old position, k now does not have a right child. It may or may not have a left child. In the example on the right, it does not have a left child either in its new position, but in general, it might have a left child. But it definitely doesn't have a right child because that was a position at which a maximum computation got stuck. And if we want to delete a node that has only 0 or 1 child, well, that we know how to do. That we covered on the last slide. Either you just delete it, that's what we do in the running example here, or in the case where k's new node does have a left child, you would do the splice out operation. So you would rip out the node that contains k, and the unique child of that node would assume the previous position of that node. Now, an exercise which I'm not going to do here, but I strongly encourage you to think through in the privacy of your own home, is that In fact, this deletion operation retains the search tree property. So roughly speaking, when you do this swap, you can violate the search tree property as we see in this example, but all of the violations involve the node you're about to delete. So once you delete that node, there's no other violations of the search tree property, so bingo, you're left with a search tree. The running time, this time no prizes for guessing what it is, because it's basically just one of these predecessor computations plus some pointer rewiring, just like predecessor and search. It's going to be governed by the height of the tree. So let me just say a little bit about the final two operations mentioned earlier, select and rank. So remember, select is just the selection problem. I give you an order statistic like 17, and I want you to return the 17th smallest key in the tree. Rank is I give you a key value, and I want to know how many keys in the tree are less than or equal to that value. So to implement these operations efficiently, we actually need one small new idea, which is to augment binary search trees with additional information at each node. So now a search tree will contain not just a key, but also information about the tree itself. So this idea is often called augmenting your data structure, and perhaps the most canonical augmentation of a search tree like these is to keep track at each node, not just of a key value, but also of the population of tree nodes in the subtree that's rooted there. So let's call this size of x, which is the number of tree nodes in the subtree rooted at x. So to make sure you know what I mean, let me just tell you what the size field should be for each of the 5 nodes in our running search tree example. So again, remember, we're thinking about how many nodes are in the subtree rooted at a given node, or equivalently, following child pointers from that node, how many different tree nodes can you reach? So from the root, of course, you can reach everybody. Everybody's in the tree rooted at the roots. So the size there is 5. By contrast, if you start at the node 1, well, you can get to the 1, or you can follow the right child pointer to get to the 2. So at the 1, the size would be 2. At the node with the key value 5, for the same reason, the size would be 2. At the 2 leaves, the subtree rooted at a leaf is just the leaf itself, so there the size would be 1. There's an easy way to compute the size of a given node once you know the size of its 2 subtrees. So if a given node in a search tree has children y and z, then how many nodes are there in the subtree rooted at x? Well, there's those that are rooted at y. There are those in the left subtree. There are those that are reachable from z. That is, there are the children that are also children of z. And then there's x itself. Now, in general, whenever you augment a data structure, and this is something we'll talk about again when we discuss red-black trees, you got to pay the piper. So the extra data that you maintain, it might be useful for speeding up certain operations, but whenever you have operations that modify the tree, specifically insertion and deletion, you have to take care to keep that extra data valid, to keep it maintained. Now, in the case of these subtree sizes, they're quite straightforward to maintain under insertion and deletion without affecting the running time of insertion and deletion very much. But that's something you should really think about offline. For example, when you perform an insertion, remember how that works. You do essentially a search. You follow left and right child pointers down to the bottom of the tree until you hit a null pointer. Then that's where you stick the new node. Now what you have to do is you have to trace back up that path, all of the ancestors of the new node you just inserted, and increment their subtree sizes by 1. So let's wrap up this video by showing you how to implement the selection procedure given an order statistic in a search tree that's been augmented so that at every node you know the size of the subtree rooted at that node. Well, of course, as always, you start at the beginning, which in a search tree is the root. And let's say the root has subchildren y and z. Y or z could be null, that's no problem. We just think of the size of a null node as being 0. Now, what's the search tree property? It says the keys that are less than the keys stored at x are precisely the ones that are in the left subtree at x. The keys in the tree that are bigger than the key at x are precisely the ones you're going to find in the x's right subtree. So suppose we're asked to find the 17th order statistic in a search tree, the 17th smallest key that's stored in the tree. Where is it going to be? Where should we look? Well, it's going to depend on the structure of the tree, and in fact, it's going to depend on the subtree sizes. This is exactly why we're keeping track of them, so we can quickly make decisions about how to navigate through the tree. So for a simple example, suppose that X's left subtree contains, say, 25 keys. So remember, Y knows locally exactly what the population of its subtree is. So in constant time from X, we can figure out how many keys are in Y subtree, and let's say it's 25. Now, by the defining property of search trees, these are the 25 smallest keys anywhere in the tree, right? X is bigger than all of them. Everything in X's right subtree is bigger than all of them. So the 25 smallest ordered statistics are all in the subtree rooted at Y. Clearly, that's where we should recurse. Clearly, that's where the answer lies. So we can recurse on the subtree rooted at Y, and then we are again looking for the 17th order statistic in this new smaller search tree. On the other hand, suppose when we start at X and we ask Y, how many nodes are there in your subtree, and maybe Y locally has stored the number 12. So there's only 12 things in X's left subtree. Well, okay, X itself is bigger than all of them, so X is going to be the 13th biggest order statistic. It's going to be the 13th biggest element in the tree. Everything else is in the right subtree. So in particular, the 17th order statistic is going to be in the right subtree. So we're going to recurse in the right subtree. Now, what are we looking for? We're not looking for the 17th order statistic anymore. The 12 smallest things are all in X's subtree. X itself is the 13th smallest, so we're looking for the 4th smallest of what remains. So the recursion is very much along the lines of what we did in the divide and conquer selection algorithms earlier in the course. So to fill in some more details, let's let A denote the subtree size at Y. And if it happens that X has no left child, we'll define A to be 0. So the super lucky case is when there's exactly I-1 nodes in the left subtree. That means the root here, X, is itself the ith order statistic. Remember, it's bigger than everything in its left subtree, it's smaller than everything in its right subtree. But in the general case, we're going to be recursing either on the left subtree or on the right subtree. We recurse on the left subtree when its population is large enough that we're guaranteed it encompasses the ith order statistic. And that happens exactly when its size is at least I. That's because the left subtree has the smallest keys that are anywhere in the search tree. And in the final case, when the left subtree is so small that not only does it not contain the ith order statistic, but also X is too small to be the ith order statistic, then we recurse in the right subtree, knowing that we've thrown away A plus 1, the A plus 1 smallest key values anywhere in the original tree. So correctness of this procedure is pretty much exactly the same as the inductive correctness for the selection algorithms we discussed earlier. In effect, the root of the search tree is acting as a pivot element, with everything in the left subtree being less than the root, everything in the right subtree being greater than the element in the root. So that's why the recursion is correct. As far as the running time, I hope it's evident from the pseudocode that we do constant time each time we recurse. How many times can we recurse? Well, we keep moving down the tree. The maximum number of times we can move down the tree is proportional to the height of the tree. So this, again, is proportional to the height. So that's the select operation. There is an analogous way to write the rank operation. Remember, this is where you're given a key value and you want to count up the number of stored keys that are less than or equal to that target value. Again, you use these augmented search trees, and again, you can get running time proportional to the height. And I encourage you to think through the details of how you'd implement rank offline. So in this video, we'll graduate beyond the domain of just vanilla binary search trees, like we've been talking about before, and we'll start talking about balanced binary search trees. These are the search trees you really want to use when you want to have real-time guarantees on your operation time, because they're search trees which are guaranteed to stay balanced, which means the height is guaranteed to stay logarithmic, which means all of the operations search trees support that we know and love will also be logarithmic in the number of keys that they're storing. So let's just quickly recap what is the basic search tree property. It should be the case that at every single node of your search tree, if you go to the left, you only see keys that are smaller than where you started, and if you go to the right, you only see keys that are bigger than where you started. And a really important observation, which is that given a set of keys, there are going to be lots and lots of different legitimate, valid binary search trees with those keys. So we've been having these running examples with the keys 1, 2, 3, 4, 5. On the one hand, you can have a nice and balanced search tree that has height only 2 with the keys 1 through 5. On the other hand, you can also have these crazy chains, basically devolved to linked lists, where the height for n elements could be as high as n minus 1. So in general, you could have an exponential difference in the height. It could be as small in the best case as logarithmic, as big in the worst case as linear. So this obviously motivates search trees that have the additional property that you never have to worry about their height. You know they're going to be well balanced. You know they're going to have height logarithmic. You're never worried about them having this really lousy linear height. Remember why it's so important to have a small height. It's because the running time of all of the operations of search trees depends on the height. You want to do search, you want to do insertion, you want to find predecessors, whatever. The height is going to be what governs the running time of all of those properties. So the high-level idea behind balanced search trees is really exactly what you'd think, which is that, because the height can't be any better than logarithmic in the number of things you're storing, that's because the trees are binary, so the number of nodes can only double each level, so you need a logarithmic number of levels to accommodate everything that you're storing. But it's got to be logarithmic. Let's make sure it stays logarithmic all the time, even as we do insertions and deletions. If we can do that, then we get a very rich collection of supported operations all running in logarithmic time. As usual, n denotes the number of keys being stored in the tree. There are many, many, many different balanced search trees. Most of them are not super different from each other. I'm going to talk about one of the more popular ones, which are called red-black trees. So these were invented back in the 70s. These were not the first balanced binary search tree data structure. That honor belongs to AVL trees, which again are not very different from red-black trees, though the invariants are slightly different. Another thing you might want to look up and read about is a very cool data structure called splay trees due to Slater and Tarjan. Unlike red-black trees and AVL trees, which only are modified on insertions and deletions, which if you think about it is sort of what you'd expect, splay trees modify themselves even when you're doing lookups, even when you're doing searches. So they're sometimes called self-adjusting trees for that reason. And they're super simple, but they still have kind of amazing guarantees. And then finally, going beyond just the binary tree paradigm, many of you might want to look up examples of B trees or also B plus trees. These are very relevant for implementing databases. Here, what the idea is, in a given node, you're going to have not just one key, but many keys. And from a node, you have multiple branches that you can take, depending on where you're searching for falls with respect to the multiple keys that are at that node. The motivation in a database context for going beyond the binary paradigm is to have a better matchup with the memory hierarchy. So that's also very important, although a little bit outside of the scope here. That said, what we discuss about red-black trees, much of the intuition will translate to all of these other balanced tree data structures if you ever find yourself in a position where you need to learn more about them. So red-black trees are just the same as binary search trees, except they also always maintain a number of additional invariants. And so what I'm going to focus on in this video is, first of all, what the invariants are, and then how the invariants guarantee that the height will be logarithmic. Time permitting, at some point there'll be optional videos more about the guts, more about the implementations of red-black trees, namely how do you maintain these invariants under insertions and deletions. That's quite a bit more complicated, so that's appropriate for optional material. But understanding what the invariants are and what role they play in controlling the height is very accessible, and it's something I think every programmer should know. So I'm going to write down 4 invariants, and really the bite comes from the second 2, okay, from the third and the fourth invariants. The first 2 invariants, are just really cosmetic. So the first one, we're going to store 1 bit of information additionally at each node beyond just the key, and we're going to call this bit as indicating whether it's a red or a black node. You might be wondering, why red-black? Well, I asked my colleague Leo Gibas about that a few years ago, and he told me that when he and Professor Sedgwick were writing up this article, the journals had access to a certain kind of new printing technology that allowed very limited color in the printed copies of the journals. And so they were eager to use it, and so they named their data structure red-black so they could have these nice red and black pictures in the journal article. Unfortunately, there was then some snafu, and at the end of the day, that technology wasn't actually available, so it wasn't actually printed the way they were envisioning it, but the name has stuck. So that's the rather idiosyncratic reason why these data structures got the name that they did, red-black trees. So secondly, we're going to maintain the invariant that the root of the search tree is always black, can never be red. Okay, so with the superficial pair of invariants out of the way, let's go to the 2 main ones. So first of all, we're never going to allow 2 reds in a row. by which I mean if you have a red node in the search tree, then its children must be black. If you think about it for a second, you realize this also implies that if a node is red and it has a parent, then that parent has to be a black node. So in that sense, there are no two red nodes in a row anywhere in the tree. And the final invariant, which is also rather severe, is that every path you might take from root to a null pointer passes through exactly the same number of black nodes. So to be clear on what I mean by a root null path, what you should think about is an unsuccessful search. Right, so what happens in an unsuccessful search? You start at the root, depending on whether you need to get smaller or bigger, you go left or right respectively. You keep going left, right as appropriate until eventually you hit a null pointer. So I want you to think about that process by which you start at the root and then eventually fall off into the tree. In doing so, you traverse some number of nodes. Some of those nodes will be black, some of those nodes will be red, and I want you to keep track of the number of black nodes. And the constraints that a red-black tree by definition must satisfy is that no matter what path you take through the tree, starting from the root, terminating in a null pointer, the number of black nodes traversed has to be exactly the same. Cannot depend on the path, has to be exactly the same on every single root null path. Let's move on to some examples. So here's a claim, and this is meant to kind of whet your appetite for the idea that red-black trees must be pretty balanced. They have to have height basically logarithmic. So remember, what's the most unbalanced search tree? Well, that's these chains. So the claim is even a chain with 3 nodes cannot be a red-black tree. So what's the proof? Well, consider such a search tree. Right, so maybe with the key values 1, 2, and 3. So the question that we're asking is there a way to color these 3 nodes, red and black, so that all 4 of the invariants are satisfied? So we need to color each red or black. Remember, invariant 2 says the root, the 1, has to be black. So we have 4 possibilities for how to color 2 and 3. But really, because of the third invariant, we only have 3 possibilities. We can't color 2 and 3 both red, because then we'd have 2 reds in a row. So we can either make 2 red, 3 black, 2 black, 3 red, or both 2 and 3 black. And all of the cases are the same. Just to give one example, suppose that we color the node 2 red, and 1 and 3 are black. The claim is invariant 4 is then broken. And invariant 4 is going to be broken no matter how we try and color 2 and 3 red and black. What does invariant 4 says? It says really on any unsuccessful search you pass through the same number of black nodes. And so one unsuccessful search would be you search for 0. And if you search for 0, you go to the root, you immediately go left and hit a null pointer, so you see exactly 1 black node, namely 1. On the other hand, suppose you searched for 4. Then you'd start at the root, you'd go right, you go to 2, you'd go right, you go to 3, you'd go right again, and only then would you hit a null pointer. And on that unsuccessful search, you'd encounter 2 black nodes, both the 1 and the 3. So that's a violation of the 4th invariant. Therefore, this would not be a red-black tree. I'll leave it for you to check that no matter how you try to color 2 and 3 red or black, you're going to break one of the invariants. If they're both red, you break the 3rd invariant. If at most one is red, you break the 4th invariant. So that's a non-example of a red-black tree. So let's look at an example of a red-black tree. A search tree where you actually can color the nodes red or black so that all 4 invariants are maintained. So one search tree which is very easy to make red-black is a perfectly balanced one. So for example, let's consider this 3-node search tree. It has the keys 3, 5, and 7. And let's suppose the 5 is the root. So it has 1 child on each side, the 3 and the 7. So can this be made a red-black tree? So remember what that question really means. It's asking, can we color these 3 nodes some combination of red and black so that all 4 of the invariants are satisfied? If you think about it a little bit, you realize, yeah, you can definitely color these nodes red or black to make and satisfy all 4 of the invariants. In particular, suppose we color all 3 of the nodes black. We've satisfied invariant number 1, we've colored all the nodes. We've satisfied invariant number 2, in particular the root is black. We've satisfied invariant number 3, there's no reds at all, so there's certainly no 2 reds in a row. And if you think about it, we satisfy invariant 4 because this tree is perfectly balanced. No matter what you unsuccessfully search for, you're going to encounter 2 black nodes. If you search for, say, 1, you're going to encounter 3 and 5. If you search for, say, 6, you're going to encounter 5 and 7. So all root null paths have exactly 2 black nodes. Invariant number 4 is also satisfied. So that's great. But of course, the whole point of having a binary search tree data structure is you want to be dynamic. You want to accommodate insertions and deletions. Every time you have an insertion or a deletion into a red-black tree, you get a new node. Let's say an insertion, you get a new node, you have to color it something, and now all of a sudden you got to worry about breaking one of these four invariants. So let me just show you some easy cases where you can accommodate insertions without too much work. Time permitting, we'll include some optional videos with the notion of rotations, which do more fundamental restructuring of search trees so that they can maintain the four invariants and stay nearly perfectly balanced. So if we have this red-black tree where everything's black and we insert, say, 6, that's going to get inserted down here. Now, if we try to color it black, it's no longer going to be a red-black tree. And that's because if we do an unsuccessful search now for, say, 5.5, we're going to encounter 3 black nodes, where if we do an unsuccessful search for 1, we only encounter 2 black nodes. So that's not going to work. But the way we can fix it is instead of coloring the 6 black, we color it red. And now this 6 is basically invisible to invariant number 4. It doesn't show up in any root null paths. So because you had 2 black nodes on all root null paths before the 6 was there, that's still true now that you have this red 6. So all 4 invariants are satisfied once you insert the 6 and color it red. If we then insert, say, an 8, we can pull exactly the same trick. We can color the 8 red. Again, it doesn't participate in invariant 4 at all, so we haven't broken it. Moreover, we still don't have 2 reds in a row, so we haven't broken invariant number 3 either. So this is yet another red-black tree. In fact, this is not the unique way to color the nodes of this search tree so that it satisfies all 4 of the invariants. If we instead recolor 6 and 8 black, but at the same time recolor the node 7 red, we're also golden. Clearly, the first 3 invariants are all satisfied, but also in pushing the red upward, consolidating the red at 6 and 8, and putting it at 7 instead, we haven't changed the number of black nodes on any given path. Any path that previously went through 6 went through 7. Anything that went through 8 went through 7. So there's exactly the same number of red and black nodes on each such path as there was before. So all paths still have equal number of black nodes, and invariant 4 remains satisfied. As I said, I've shown you here only very simple examples where you don't have to do much work on an insertion to retain the red-black properties. In general, if you keep inserting more and more stuff, and certainly if you do deletions, you have to work much harder to maintain those 4 invariants. Time permitting, we'll cover just a taste of it in some optional videos. So what's the point of these seemingly arbitrary 4 invariants of a red-black tree? Well, the whole point is that if you satisfy these 4 invariants in your search tree, then your height is going to be small. And because your height's going to be small, all your operations are going to be fast. So let me give you a proof that if a search tree satisfies the 4 invariants, then it has super small height. In fact, no more than double the absolute minimum it could conceivably have, at most 2 times log base 2 of n. So the formal claim is that every red-black tree with n nodes has height O of log n. More precisely, at most 2 times log base 2 of n plus 1. So here's the proof. And what's cool about this proof is it's very obvious the role played by these invariants 3 and 4. Essentially, what the invariants guarantee is that a red-black tree has to look like a perfectly balanced tree with, at most, a sort of factor 2 inflation. So let's see exactly what I mean. So let's begin with an observation. And this has nothing to do with red-black trees. Forget about the colors for a moment. And just think about the structure of binary trees. And let's suppose we have a lower bound on how long root null paths are in a tree. So for some parameter k, and go ahead and think of k as like 10 if you want. Suppose we have a tree where if you start from the root, and no matter how it is you navigate left and right child pointers until you terminate at a null pointer, no matter how you do it, you have no choice but to see at least k nodes along the way. If that hypothesis is satisfied, then if you think about it, the top of this tree has to be totally filled in. So the top of this tree has to include a perfectly balanced search tree, binary tree, of depth k minus 1. So let me draw a picture here of the case of k equals 3. So if no matter how you go from the root to a null pointer, you have to see at least 3 nodes along the way, then it means the top 3 levels of this tree have to be full. So you have to have the root, it has to have both of its children, and it has to have all 4 of its grandchildren. The proof of this observation is by contradiction. If in fact you were missing some nodes in any of these top k levels, well, that would give you a way of hitting a null pointer seeing less than k nodes. So what's the point is? The point is this gives us a lower bound on the population of a search tree as a function of the length of its root null paths. So the size n of the tree must include at least the number of nodes in a perfectly balanced tree of depth k minus 1, which is 2 raised to the k minus 1. So for example, when k equals 3, it's 2 raised to the 3, 2 cubed, minus 1, or 7. So that's just a basic fact about trees, nothing about red-black trees. So let's now combine that with the red-black tree invariance to see why red-black trees have to have small height. So again, to recap where we got to on the previous slide, the size n, the number of nodes in a tree, is at least 2 to the k minus 1, where k is the fewest number of nodes you will ever see on a root null path. So let's rewrite this a little bit, and let's actually say, instead of having a lower bound on n in terms of k, let's have an upper bound on k in terms of n. So the length of every root null path, the minimum length of every root null path, is bounded above by log base 2 of quantity n plus 1. This is just adding 1 to both sides and taking the logarithm base 2. So what? What does this buy us? Well, now let's start thinking about red-black trees. So in a red-black tree with n nodes, what does this say? This says that the number of nodes, forget about red or black, just the number of nodes on some root null path has to be at most log base 2 of n plus 1. In the best case, all of those are black. Maybe some of them are red, but in the maximum case, all of them are black. So we can write in a red-black tree with n nodes, there is a root null path with at most log base 2 of n plus 1 black nodes. This is an even weaker statement than what we just proved. We proved that some path must have at most log base 2 of n plus 1 total nodes, so certainly that path has at most log base 2 of n plus 1 black nodes. Now let's apply the 2 knockout punches of our 2 invariants. All right, so fundamentally, what is the fourth invariant telling us? It's telling us that if we look at a path in our red-black tree, we go from the root, we think about, say, an unsuccessful search, we go down to a null pointer. It says if we think of the red nodes as invisible, if we don't count them in our tally, then we're only going to see basically a logarithmic number of nodes. But when we care about the height of the red-black tree, of course, we care about all of the nodes, the red nodes and the black nodes. So far we know if we only count black nodes, then we're good. We only have log base 2 of n plus 1 nodes that we need to count. So here's where the third invariant comes in. It says, well, actually, black nodes are a majority of the nodes in the tree. In a strong sense, there are no 2 reds in a row on any path. So if we know the number of black nodes is small, then, because you can't have 2 reds in a row, the number of total nodes on the path is at most twice as large. In the worst case, you have a black root, then red, then black, then red, then black, then red, then black, etc. In the worst case, the number of red nodes is equal to the number of black nodes, which doubles the length of a path once you start counting the red nodes as well. And this is exactly what it means for a tree to have logarithmic depth. So this, in fact, proves the claim. If a search tree satisfies the invariants 1 through 4, in particular if there's no 2 reds in a row and all root null paths have an equal number of black nodes, then knowing nothing else about this search tree, it's got to be almost balanced. It's perfectly balanced up to a factor of 2. And again, the point then is that operations in a search tree and the search trees are going to run in logarithmic time because the height is what governs the running time of those operations. Now, in some sense, I've only told you the easy part, which is if it just so happens that your search tree satisfies these 4 invariants, then you're good. The height is guaranteed to be small, so the operations are guaranteed to be fast. Clearly, that's exactly what you want from this data structure. But for the poor soul who has to actually implement this data structure, the hard work is maintaining these invariants even as the data structure changes. Remember, the point here is to be dynamic, to accommodate insertions and deletions. Insertions and deletions can disrupt these 4 invariants, and then one has to actually change the code to make sure they're satisfied again, so that the tree stays balanced, has low height, even under arbitrary sequences of insertions and deletions. So we're not going to cover that in this video. It can be done. without significantly slowing down any of the operations. It's pretty tricky, takes some nice ideas. There's a couple well-known algorithms textbooks that cover those details, or if you look at open source implementations of balanced search trees, you can look at code that does that implementations. But because it can be done in a practical way, and because red-black trees support such a rich array of operations, that's why you will find them used in a number of practical applications. That's why balanced search trees should be part of your programmer toolbox. In this video and the next, we're going to take it to the next level and peer under the hood into implementations of balanced binary search trees. Now, frankly, the nitty-gritty details of all balanced binary search tree implementations get pretty complicated. And if you really want to understand them at a fine-grained level, there is no substitute for reading an advanced algorithms textbook that includes coverage of the topic and or studying open source implementations of these data structures. I don't see the point of regurgitating all of those details for you here. What I do see the point in doing is giving you the gist of some of the key ideas in these implementations. In this first video, I want to focus on a key primitive, that of rotations, which is common to all balanced binary search tree implementations, whether it's red-black trees, AVL trees, B or B plus trees, whatever, all of them use rotations. In the next video, we'll talk a little bit more about the details of red-black trees in particular. So what is the point behind these magical rotation operations? Well, the goal is to do just constant work, just rewire a few pointers, and yet locally rebalance a search tree without violating the search tree property. So there are two flavors of rotations, left rotations and right rotations. In either case, when you invoke a rotation, it's on a parent-child pair in a search tree. If it's a right child of the parent, then you use a left rotation. We'll discuss that on this slide. And a right rotation is in some sense an inverse operation, which you use when you have a left child of the parent. So what's the generic picture look like when you have a node X in a search tree and it has some right child Y? Well, X in general might have some parent. X might also have some left subtree. Let's call that left subtree of X capital A. It could, of course, be empty. And then Y has its two subtrees. Let's call the left subtree of Y B and the right subtree C. It's going to be very important that rotations preserve the search tree property. So to see why that's true, let's just be clear on exactly which elements are bigger than which other elements in this picture. So first of all, Y being a right child of X, Y is going to be bigger than X. Now, all of the keys which lie in the subtree A, because they're to the left of X, these keys are going to be even smaller than X. By the same token, anything in the subtree capital C, that's to the right of Y, so all that stuff is going to be even bigger than Y. What about subtree capital B? What about the nodes in there? Well, on the one hand, all of these are in X's right subtree, right? To get to any node in B, you go through X and then you follow the right child to Y. So that means everything in B is bigger than X. Yet, at the same time, it's all in the left subtree of Y. So these are all things smaller than Y. Summarizing, all of the nodes in B have keys strictly in between X and Y. So now that we're clear on how all of the search keys in the different parts of this picture relate to each other, I can describe the point of a left rotation. Fundamentally, the goal is to invert the relationship between the nodes X and Y. Currently, X is the parent and Y is the child. We want to rewire a few pointers so that Y is now the parent and X is the child. Now what's cool is, given that that is our goal, there's pretty much a unique way to put all of these pieces back together to accomplish it. So let's just follow our nose. So remember the goal. Y should be the parent and X should be the child. Well, X is less than Y, and there's nothing we can do about that. So if X is going to be a child of Y, it's got to be the left child. So your first question might be, well, what happened to X's parent? So X used to have some parent, let's call it P. And now X's new parent is Y. Similarly, Y used to have a parent X, and there's a question, what should Y's new parent be? Well, Y is just going to inherit X's old parent P. So this change has no bearing for the search tree property. Either this collection of nodes was P's left subtree, in that case all of these nodes were less than P, or this subtree was P's right subtree, in which case all of these are bigger than P, but P could really care less which of X or Y is its direct descendant. Now let's move on to thinking about what we should do with the subtrees A, B, and C. So we have three subtrees we need to reassemble into this picture, and fortunately we have three slots available. X has both of its child pointers available, and Y has its right child available. So what can we put where? Well, A is the subtree of stuff which is less than both X and Y, so that should sensibly be X's left child. That's exactly as it was before. By the same token, capital C is the stuff bigger than both X and Y, so that should be Y, the bigger node's right child, just as before. And what's more interesting is what happens to subtree capital B. So B used to be Y's left child, but that can't happen anymore because now X is Y's left child. So the only hope is to slot capital B into the only space we have for it, X's right child. Fortunately for us, this actually works. Slotting B into the only open space we have for it, X's right child, does indeed preserve the search tree property. Recall we noticed that every key in capital B is strictly between X and Y, therefore it better be in X's right subtree and it better be in Y's left subtree, but it is. That's exactly where we put it. So that's a left rotation, but if you understand a left rotation, then you understand a right rotation as well, because a right rotation is just the inverse operation. So that's when you take a parent-child pair, where the child is the left child of the parent, and now you again want to invert their relationship. You want to make the old child the new parent, and the old parent the new child. And once again, given this goal, there's really a unique way to reassemble the components of this picture so that the goal is accomplished, so that Y is now the parent of X. So what are the laudable properties of rotations? Well, first of all, I hope it's clear that they can be implemented in constant time. All you are doing are rewiring a constant number of pointers. Furthermore, as we've discussed, they preserve the search tree property. So these nice properties are what make rotations the ubiquitous primitive, common to all balanced search tree implementations. So this, of course, is not the whole story. In a complete specification of a balanced search tree implementation, you have to say exactly when and how you deploy these rotations. You'll get a small taste of that in the next video, but if you really want to understand it in more depth, I again encourage you to check out either a comprehensive data structures textbook, check out a number of balanced search tree demonstrations, which are readily available on the web, or have a peek at an open source implementation of one of these data structures. For this final video on binary search trees, I want to talk a little bit about implementation details for the red-black tree data structure, in particular the insertion operation. As I've said in the past, it really doesn't make sense for me to spell out all of the gory details about how this is implemented. If you want to understand them in full detail, you should check out various demonstrations readily available on the web, or a comprehensive textbook, or an open source implementation. Red-black trees, you'll recall, satisfy 4 invariants, and the final 2 invariants in particular ensure that the red-black tree always has logarithmic height, and therefore all of the supported operations run in logarithmic time. The problem is we've got to pay the piper. Whenever we have an operation that modifies the data structure, it potentially destroys one or more of the invariants, and we have to then restore that invariant without doing too much work. Now, amongst all of the supported operations, there are only 2 that modify the data structure: insertion and deletion. So from 30,000 feet, the approach to implementing insert and delete is to just implement them as if it's a normal binary search tree, as if we didn't have to worry about these invariants. And then if an invariant is broken, we try to fix it with minimal work. And the 2 tools that we have at our disposal to trying to restore an invariant are, first of all, recoloring, flipping the color of nodes from red to black, and second of all, left and right rotations, as covered in the previous video. My plan is to discuss the insertion operation not in full detail, but I'll tell you about all of the key ideas. Now, deletion, you got to remember that even in a regular binary search tree, deletion is not that trivial, and in a red-black tree, it's downright painful. So that I'm not going to discuss. I'll defer you to textbooks or online resources to learn more about deletion. So here's how insert is going to work. So suppose we have some new node with the key X and we're inserting it into a red-black tree. So we first just forget about the invariance and we insert it as usual. And remember, that's easy. All we do is follow left and right child pointers until we fall off the end of the tree, until we get to a null pointer, and we install this new node with key X where we fell off the tree. That makes X a leaf in this binary search tree. Let's let Y denote X's parent after it gets inserted. Now, in a red-black tree, every node has a color. It's either red or black. So we have a decision to make. We just added this new node with key X, and we got to make it either red or black. And we're sort of between a rock and a hard place. Whichever color we make it, we have the potential of destroying one of the invariants. Specifically, suppose we color it red. Well, remember what the third invariant says. It says you cannot have two reds in a row. So if Y, X's new parent, is already red, then when we color X red, we have two reds in a row and we've broken invariant number 3. On the other hand, if we color this new node X black, we've introduced a new black node to certain root null paths in this tree. And remember, the fourth invariant insists that all of the root null paths have exactly the same number of black nodes. So by adding a black node to some, but not all of the paths, we're in general going to destroy that invariant if we color X black. So what we're going to do is we're going to choose the lesser of two evils, and in this context the lesser of two evils is to color X red. Again, we might destroy the third invariant. We'll just deal with the consequences later. So why, you ask, is coloring X red and destroying the third invariant the lesser of two evils? Well, intuitively, it's because this invariant violation is local. The flaw in our not quite red-black tree is small and manageable. It's just a single double red, and we know exactly where it is. It's X and Y. So there's sort of more hope in squashing it with minimal work. By contrast, if we colored X black, then we've violated this much more global type of property involving all of the root to null paths. And that's a much more intimidating violation to try to fix than just this local one of having a double red between X and its parent. Indeed, some of the time we'll just get lucky, and it will just so happen that X's parent Y is colored black. And then we're golden. This new node X that's colored red, it doesn't create a double red. There's no other violations of the other invariants, and so, boom, we've got a new red-black tree, and we can stop. So the tricky case, then, is when X's parent Y is also red. In this case, we do not have a red-black tree. We have a double red, and we have to do some more work to restore the third invariant. So suppose Y is red. What do we then know? Well, remember, before we inserted X, we had a red-black tree. All 4 of the invariants were satisfied. So therefore, Y, by virtue of being red, it could not have been the root. It has to have a parent. Let's call that parent W. Moreover, by the third invariant, there was no double red in this tree before we inserted X. So by virtue of Y being red, its parent W must have been black. So now the insertion operation branches into 2 different cases, and it depends on the color, on the status of W's other child. So in the first case, we're going to assume that W's other child, that is not Y, but the other child of W, exists and is colored red. In the second case, we're going to treat when W either doesn't have a second child, Y is its only child, or when its other child is colored black. So let's recap where things stand. So we just inserted this new node, and it has the key X. And our algorithm colored this node red. So X is definitely red. Now, if its parent Y was black, we already halted. So we've already dealt with that case. So now we're assuming that Y, X's parent, is also red. That's what's interesting. Now, by virtue of Y being red, we know that Y's parent, that is X's grandparent W, has to be colored black. And for case 2 of insertion, we are assuming that W has a second child, call it Z, and that Z is colored red. So how are we going to quash this double red problem? We have two tools at our disposal. One is to recolor nodes. The second is to do rotations. So for case one, we're only going to actually have to do recoloring. We're not even going to have to bust out our rotations. In particular, what we're going to do is we're going to recolor Z and Y black, and we're going to recolor W red. So in some sense, we take the reds that are at Z and Y and we consolidate them at W. The important property of this recoloring is that it does not break the fourth invariant. Remember, the fourth invariant says that no matter which path you take from the root to a null pointer, you see exactly the same number of black nodes. So why is that invariant still true after this recoloring? Well, for any path from a root to a null pointer which doesn't go through the vertex W, it's irrelevant. None of these nodes are on that path, so the number of black nodes is exactly the same. So think about a path which does go through W. Well, if it goes through W, to get to a null pointer, it has to go through exactly one of Z or Y. So before we did the recoloring, this path picked up a black node via W, and it did not pick up a black node via Z or Y. Both of those were red. Now, any such path does not pick up a black node at W, that's now red, but it does pick up exactly one black node, either Z or Y. So for every single path in the tree, the number of black nodes it contains is exactly the same before or after this recoloring. Therefore, since the fourth invariant held previously, it also holds after this recoloring. The other great thing is that it seems like we've made progress on restoring the third invariant, the property that we don't want any double reds at all in the entire tree. Remember, before we did this recoloring, we only had a single double red. It involved X and Y. We just recolored Y from red to black. So certainly we no longer have a double red involving X and Y, and that was the only one in the tree. So are we done? Do we now have a bona fide red-black tree? Well, the answer depends, and it depends on the color of W's parent. So remember, W just got recolored from black to red. So there's now a possibility that W, being this new red node, participates in some new double red violation. Now, W's children, Z and Y, are black, so those certainly can't be double reds. But W also has some parent, and if W's parent is red, then we get a double red involving W and its parent. Of course, if W's parent was black, then we're good to go. We don't get a double red by recoloring W red, so we have no double reds in the tree and we can just stop. Summarizing, this recoloring preserves the fourth invariant, and either it restores the third invariant, or if it fails to restore the third invariant, at least it propagates the double red violation upward into the tree closer to the root. We're perfectly happy with the progress represented by propagating the double red upward. Why? Well, before we inserted this new object x, we had a red-black tree, and we know red-black trees have logarithmic height. So the number of times that you can propagate this double red upward is bounded above by the height of the tree, which is only logarithmic. So we can only visit case 1 a logarithmic number of times before this double root is propagated all the way to the top of the tree, all the way to the root. So we're not quite done. The one final detail is what happens when this recoloring procedure actually recolors the root. So you could, for example, look at this green picture on the right of this slide and ask, well, what if W is actually the root of this red-black tree and we just recolored it red? Now notice in that situation where we're dealing with the root of the tree, we're not going to have a double red problem. So invariant 3 is indeed restored when we get to the top of the tree. But we have a violation of invariant number 2, which states that the root must always be black. Well, if we find ourselves in this situation, there's actually a super simple fix, which is this red root, we just recolor it black. Now, clearly that's not going to introduce any new double reds. The worry is that instead it breaks invariant 4. But the special property of the root vertex is that it lies exactly once on every root null path. So if we flip the color of the root from red to black, it increases the number of black nodes on every single root null path by exactly 1. So if they all had the same number of black nodes before, they all have the same number of black nodes now after the recoloring. That completes case 1 of how insertion works. Let's move on to case 2. So case 2 gets triggered when we have a double red, and the deeper node of this double red pair, call it X, its uncle, that is if it has grandparent W, parent Y, and W's other child other than Y, either doesn't exist, or if it exists, it's colored black. That is case 2. I want to emphasize you might find yourself in case 2 right away when you insert this new object X. It might be that immediately it has some uncle which is colored X, or it might be that you've already visited case 1 a bunch of times, propagating this double red up the tree, and now at some point the deeper red node X has a black uncle. Either way, as soon as that happens, you trigger case 2. Well, it turns out case 2 is great in the sense that with merely constant work, you can restore invariant number 3, you can get rid of the double red without breaking any of the other invariants. You do have to put to use both of the tools we have available in general, both recolorings and rotations, left and right rotations, as we discussed in the previous video. But if you do just a constant number of each, recolorings and rotations, you can get all 4 of the invariants simultaneously. There are unfortunately a couple of subcases depending on exactly the relationships between X, Y, Z, and W. For that reason, I'm not going to spell out all the details here. Check out a textbook if you're interested, or even better, work it out for yourself. Now that I've told you that 2 to 3 rotations plus some recolorings is always sufficient in case 2 to restore all of the invariants, follow your nose and figure out how it can be done. So let's summarize everything that we've said about how insertion works in a red-black tree. So you have your new node with key X, you insert it as usual, so you make it a leaf, you tentatively color it red. If its parent is black, you're done. You have a red-black tree and you can stop. In general, the interesting case is this new node X's parent is red. That gives you a double red, a violation of invariant 3. Now what happens is you visit this case 1, propagating this double red upward in the tree. This upward propagation process can terminate in one of 3 ways. First of all, you might get lucky and at some point the double red doesn't propagate. You do the recoloring in case 1 and it just so happens you don't get a new double red. At that point you have a red-black tree and you can stop. The second thing that can happen is the double red propagation can make it all the way to the root of the tree. Then you can just recolor the root black and you can stop with all of the invariants satisfied. Alternatively, at some point when you're doing this upward propagation, you might find yourself in case 2, as discussed on this slide, where the lower red node in your double red pair X has a black or non-existent uncle Z. In that case, with constant time, you can restore all of the 4 invariants. So the work done overall is dominated by the number of double red propagations you might have to do. That's bounded by the height of this tree, and that's bounded by big O of log n. So in all of the cases, you restore all 4 invariants. You do only a logarithmic amount of work, so that gives you a logarithmic insertion operation for red-black trees as promised. In this video, we'll begin our discussion of hash tables. We'll focus first on the supported operations and on some of the canonical applications. So hash tables are insanely useful. If you want to be a serious programmer or computer scientist, you really have no choice but to learn about hash tables. I'm sure many of you have used them in your own programs in the past, in fact. Now, on the one hand, what's funny is they don't actually do that many different things in terms of the number of supported operations, but what they do, they do really, really well. So what is a hash table? Well, conceptually, ignoring all of the aspects of the implementation, you might want to think of a hash table as an array. So one thing that arrays do super well is support immediate random access. So if you're wondering what's at position number 17 of some array, boom, with a couple of machine instructions you can find out. Want to change the contents at position number 23 in some array? Done, in constant time. So let's think about an application in which you want to remember your friends' phone numbers. So if you're lucky, your friends' parents were all unusually unimaginative people, and all of your friends' names are integers, let's say between 1 and 10,000. So if this is the case, then you can just maintain an array of length 10,000, and to store the phone number of, say, your best friend, 173, you can just use position number 173 of this modest-sized array. So this array-based solution would work great even if your friends change over time. You gain some here, you lose some there, as long as all of your friends' names happen to be integers between 1 and 10,000. Now, of course, your friends have more interesting names. Alice, Bob, Carol, whatever, and last names as well. So in principle, you could have an array with one position in the array for every conceivable name you might encounter, with at least 30 letters, say. But of course, this array would be way too big. It would be something like 26 raised to the 30th power, and you could never implement it. So what you'd really want is you'd want an array of reasonable size, say, ballpark the number of friends that you'd ever have, so say in the thousands or something, where its positions are indexed not by the numbers, not integers between 1 and 10,000, but rather by your friends' names. And what you'd like to do is you'd like to have random access to this array based on your friend's name. So you just look up the quote-unquote Alice position of this array, and boom, there would be Alice's phone number in constant time. And this, on a conceptual level, is basically what a hash table can do for you. So there's a lot of magic happening under the hood of a hash table, and that's something we'll discuss to some extent in other videos. So you have to have this mapping between the keys that you care about, like your friends' names, and numerical positions of some array. That's done by what's called a hash function. But properly implemented, this is the kind of functionality that hash tables gives you. It's like an array with its positions indexed by the keys that you're storing. So you can think of the purpose of a hash table as to maintain a possibly evolving set of stuff. Where, of course, the set of things that you're maintaining, will vary with the application. It could be any number of things. So if you're running an e-commerce website, maybe you're keeping track of transactions. Again, maybe you're keeping track of people, like, for example, your friends and various data about them. So maybe you're keeping track of IP addresses, for example, if you want to know who are the unique visitors to your website, and so on. So a little bit more formally, the basic operations, you need to be able to insert stuff into a hash table. In many but not all applications, you need to be able to delete stuff as well. And typically the most important operation is lookup. And for all of these three operations, you do it in a key-based way. Whereas usual, a key should just be a unique identifier for the record that you're concerned with. So for example, for employees, you might be using social security numbers. For transactions, you might have a transaction ID number, and then IP addresses could act as their own key. And so sometimes all you're doing is keeping track of the keys themselves. So for example, in IP addresses, maybe you just want to remember a list of IP addresses. You don't actually have any associated data. But in many applications, along with the key is a bunch of other stuff. So along with the employee's social security number, you're going to remember a bunch of other data about that employee. But when you do the insert, when you do the delete, when you do the lookup, you do it based on this key. And then, for example, on lookup, you feed the key into the hash table, and the hash table will spit back out all of the data associated with that key. You'll sometimes hear people refer to data structures that support these operations as a dictionary. So the main thing that a hash table is meant to support is lookup in the spirit of a dictionary. I find that terminology a little misleading, actually. Most dictionaries that you'll find are in alphabetical order, so they'll support something like binary search. And I want to emphasize something a hash table does not do is maintain an ordering on the elements that it supports. So if you're storing stuff and you do want to have order-based operations, you want to find the minimum or the maximum or something like that, a hash table is probably not the right data structure. You want something more. You want to look at a heap or you want to look at a search tree. But for applications in which all you have to do is basically look stuff up, you got to know what's there and what's not, then there should be a light bulb that goes off in your head and you should say, let me consider a hash table. That's probably the perfect data structure for this application. Now, looking at this menu of supported operations, you may be left kind of unimpressed, right? So a hash table in some sense doesn't do that many different things. But again, what it does really, really well. So to first order, what hash tables give you is the following amazing guarantee. All of these operations run in constant time. And again, this is in the spirit of thinking of a hash table as just like an array where its positions are conveniently indexed by your keys. So just like an array supports random access in constant time, you can see if there's anything in the array position and what it is. Similarly, a hash table will let you look up based on the key in constant time. So what is the fine print? Well, there's basically two caveats. So the first thing is that hash tables are easy to implement badly, and if you implement them badly, you will not get this guarantee. So this guarantee is for properly implemented hash tables. Now, of course, if you're just using a hash table from a well-known library, it's probably a pretty good assumption that it's properly implemented, you'd hope. But in the event that you're forced to come up with your own hash table and your own hash function, and unlike many of the other data structures we'll talk about, some of you probably will have to do that at some point in your career, then you'll get this guarantee only if you implement it well. And we'll talk about exactly what that means in other videos. So the second caveat is that unlike most of the problems that we've solved in this course, hash tables don't enjoy worst case guarantees. You cannot say for a given hash table that for every possible data set you're going to get constant time. What's true is that for non-pathological data, you will get constant time operations in a properly implemented hash table. So we'll talk about both of these issues a bit more in other videos, but for now, just the high order bits are, hash tables, constant time performance, subject to a couple of caveats. So now that I've covered the operations that hash tables support and the recommended way to think about them, let's turn our attention to some applications. All of these applications are going to be, in some sense, kind of trivial uses of hash tables, but they're also all really practical. These come up all the time. So the first application we'll discuss, which again is a canonical one, is removing duplicates from a bunch of stuff, also known as the deduplication problem. So in the deduplication problem, the input is essentially a stream of objects. When I say a stream, I have kind of two different things in mind as canonical examples. So first of all, you can imagine you have a huge file. So you have a log of everything that happened on some website that you're running, or all of the transactions that were made in a store on some day, and you do a pass through this huge file. So you're just in the middle of some outer for loop going line by line through this massive file. The other example of a stream that I have in mind is where you're getting new data over time. So here you might imagine that you're running software to be deployed on an internet router, and data packets are coming through this router at a constant, extremely fast rate. And so you might be looking at, say, the IP addresses in the sender and each data packet which is going through your router. So that'd be another example of a stream of objects. And now what do you got to do? What you got to do is you got to ignore the duplicates. So remember just the distinct objects that you see in this stream. And I hope you find it easy to imagine why you might want to do this task in various applications. So for example, if you're running a website, you might want to keep track of the distinct visitors that you ever saw in a given day or a given week. If you're doing something like a web crawl, you might want to identify duplicate documents and only remember them once. So for example, it would be annoying if in search results, both the top link and the second link both led to identical pages at different URLs. Okay, so search engines obviously want to avoid that, so you want to detect duplicate web pages and only report unique ones. And the solution using a hash table is laughably simple. So every time a new object arrives in the stream, you look it up. If it's there, then it's a duplicate and you ignore it. If it's not there, then this is a new object and you remember it. QED, that's it. And so then after the stream completes, so for example, after you finish reading some huge file, if you just want to report all of the unique objects, hash tables generally support a linear scan through them, and you can just report all of the distinct objects when this stream finishes. So let's move on to a second application, slightly less trivial maybe, but still quite easy, and this is the subject of programming project number 5. So this is a problem called the two-sum problem, and you're given as input an array of n numbers. These integers are in no particular order. You're also given a target sum, which I'll call t. And what you want to know is, are there two integers from amongst these n you are given that sum to t? Now, the most obvious naive way to solve this problem is just to go over all n choose 2 pairs of integers in the input and check each one separately. So that's clearly a quadratic time algorithm. But now, of course, we need to ask, can we do better? And yes, we can. And first of all, let's see what you'd do if you couldn't use any data structures. So if you were clever, but you didn't use any data structures like a hash table, here would be a reasonable improvement over the naive one. So the first step of the better solution is to sort A up front. For example, using merge sort or heap sort, something that runs in n log n time. So you may be asking about the motivation for sorting. Well, again, one thing is just, whenever you're trying to do better than n squared, you might think of sorting your data somehow helps, right? You can sort of do it almost for free in n log n time. Now, why would sorting the array up front help us? Well, then the clever insight is that for each entry of the array A, say the first entry, now we know what we're looking for to achieve this given target, right? If we're trying to get 2 that sum to 100, and the first entry in the sorted array is 43, then we know we're looking for 57 somewhere else in this now sorted array. And we know that searching a sorted array is pretty easy, right? That's just binary search. That just takes logarithmic time. So for each of the n array entries, we can look for a complementary entry, namely for each x we can look for t minus x using binary search. And so each binary search takes log n time. So the sorting up front speeds up this entire batch of n searches, and so that's why it's a win. So in the second step, because we do a linear number of binary searches, again, this is just n, the number of searches, times log n, the time per search. So this is just another theta of n log n factor. All right, so that's pretty cool. I don't think you could come up with this n log n solution without having some basic facility with algorithms. This is already a really nice improvement over the naive n squared. But we can do even better. Okay, there's no reason we're stuck with an n log n lower bound for the two-sum problem. Obviously, because the array is unsorted, we have to look at all the integers, so we're not going to do better than linear time, but we can do linear time via a hash table. So a good question you might ask at this point is, what's the clue about this problem, about this task, that suggests that we want to use a hash table? Well, so hash tables are going to dramatically speed up any application where the bulk of the work is just repeated lookups. And if we examine this n log n solution, once we have this idea of doing a search for t minus x for each value of x, we realize actually, the only thing we needed this sorted array for was to support lookups. That's all binary search here is doing, is just looking stuff up. So we say, aha, all of the work here in step 2 is from repeated lookups. We're paying an exorbitant, relatively, logarithmic amount of time per lookup, whereas hash tables can do them in constant time. So repeated lookups, ding, 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 let's use a hash table. And indeed, that's what gives us linear time in this problem. So from the amazing guarantee of hash tables, we get the following amazing solution for the two-sum problem. Although, again, this is subject to the same fine print about you better use a properly implemented hash table and you better not have pathological data. So rather than sorting, you just insert everything in the array into a hash table. And so insertion's constant time, so this is going to be linear time rather than the n log n we were paying before. And once all the stuff is in the hash table, we just do the same thing as in the n log n solution. For each x in the array, we look for its matching element t minus x in the hash table using the constant time lookup operation exported by the hash table. And of course, if for some x you do find the matching element t minus x, then you can just report x and t minus x. That proves that there is indeed a pair of integers with target sum t. If for every single element of the input array A, you fail to find this matching element t minus x in the hash table, then for sure there is no pair of integers in the input that sums to t. So this solves the problem correctly. Moreover, constant time insertion, so that means this first step is going to be O of n time, and constant time lookup, so that means the second step is also going to be linear time, at least subject to the caveats that we discussed on the previous slide. So it's kind of amazing how many different applications of computer science boil down in their essence to repeated lookup operations. Therefore, having a super fast lookup operation like that supported by a hash table permits these applications to scale to fantastic sizes. It's really amazing, and it drives a lot of modern technology. So let me just mention a couple examples. But again, if you look around or do some research on the web, you'll quickly find many more. So originally, what prompted researchers to think hard about data structures that support super fast lookups was back when people were first building compilers. So this is a long time ago. This is in the 50s or so. And these repeated lookups to figure out, what has and has not been defined before was emerging as a bottleneck in compilers back in the early days of programming languages. And that was one of the early applications of hash tables, was to support super fast lookups to speed up compile time, to keep track of the function and variable names and things like that. Hash table technology is also super useful for software on routers in the internet. So for example, you might want to block network traffic from certain sources. So for example, maybe you suspect that a certain IP address has been taken over by spammers, and so any traffic coming from that IP address you just want to ignore. And you don't want to even let it get to the end host, to the computer on someone's desktop or to someone's mobile device, but rather inside the internet you want to just drop packets that are coming from certain senders. So what does that problem boil down to? Well, you might have a blacklist of IP addresses that you're refusing traffic from, and then the task faced by the router is really a lookup problem. So a data packet comes in at some insanely fast data rate, and what you want to do immediately is look up, is this in the blacklist or not? And if it is in the blacklist, then you drop the packet. If it's not, then you let it go through. So a very different application is for speeding up search algorithms. And when I say a search algorithm, what I'm thinking about here is something like a chess playing program. So something that does game tree exploration. So we've already talked a fair amount about graph search in this class, but in our discussion of breadth first and depth first search, we were thinking about graphs that you could basically write down. You could store them in the main memory of your machine, or in the worst case on some big cluster. So maybe graphs, about the size of the web graph or possibly smaller. But in a context of something like a chess playing program, the graph that you're interested in is way, way, way bigger than the web graph. So what's the graph we care about for a chess playing program? Well, the nodes of the graph are going to correspond to all possible configurations of chess pieces on a chessboard. So every chessboard that you might ever encounter in a game of chess. So that's a massive, massive number of configurations. Okay, you're never going to be able to write down all of these vertices. The edges in this graph are going to take you from one configuration to another, and they're going to correspond to legal moves. So if you can move a bishop from one place to another place, and you get from one configuration to another configuration, there's an edge in the graph corresponding to that move. Now, you can't write down this graph, so you can't implement breadth first or depth first search exactly as we discussed it before, but you'd still like to do graph exploration, right? So you'd like to have your computer program reason about the, at least short-term ramifications of your possible next move. So that would correspond to searching through this graph. Now, how are you going to even, so remember in graph search, a really important property was you don't want to do redundant work. You don't want to re-explore things you've already explored. That would be silly and might lead to infinite loops and so on. And if you can't write down the graph, even just remembering where you've been is suddenly a non-trivial problem. But what is remembering where you've been fundamentally? Fundamentally, that's a lookup operation. So that is exactly what hash tables are for. So to be a little more concrete, one way you'd use a hash table in, say, a chess playing program is you'd take the initial configuration, you would sort of imagine trying all possible moves from this configuration, and then you'd sort of have all moves by your opponent, and then you'd have all your moves in response. And you would always remember, as you were doing this reasoning, every chessboard configuration you'd ever looked at before. And you'd stick it in a hash table. And before you go exploring some configuration, you look it up in your hash table to see if you've already explored it in the past. And if you have, you don't bother. You've already seen it. All right, so chess playing programs operate by exploring systematically as many configurations as they have time for. Obviously in a budget of 3 minutes or whatever, you don't want to waste any work exploring any given configuration more than once. How do you remember where you've been? Well, everything you've explored, you stick in a hash table. Before you explore configuration, you look it up in a hash table and see if you've already done it. So these, of course, are just scratching the surface. I just wanted to highlight a couple, fairly different-looking applications, to convince you that hash tables come up all the time. And the reason they come up all the time is because, the need for fast lookups comes up all the time. It's kind of amazing how much technology is being driven just by, repeated fast lookups. So as homework, I encourage you to just sort of think about, your own life or think about technology out there in the world and come up with some, guesses about where probably hash tables are making something out there running blazingly fast. I think it won't take you more than a few minutes to come up with some good examples. So in this video, we'll take a peek under the hood of hash functions, and I'll discuss some of the high-level principles by which they are implemented. So let's briefly review the raison d'etre of a hash table. So the purpose in life for a hash table is to support super fast lookups. So maybe you're keeping track of the transactions that happened on your website yesterday. Maybe you're keeping track of your employees. Maybe you're keeping track of IP addresses in an internet router. Maybe you're keeping track of chess configurations in a chess playing program, whatever. The point is you want to be able to insert stuff into a hash table and later remember whether something's there or whether something's not there. So the implementations we'll discuss will generally also support deletions. But that's pretty much it. It's a very restricted set of operations, but the hash table is going to execute them very, very well. So basically in constant time, again, subject to some fine print, which we'll discuss a little bit in this video, but then more deeply in a separate optional video. So the two caveats are, first of all, the hash table better be properly implemented. It's actually pretty easy to screw up a hash table, to screw up hash functions. We'll talk a bit about that in a few minutes. And then also, the data should in some sense be non-pathological, and that will be discussed more deeply in a separate video. All right, so let me give you an initial glimpse of some of the magic that's happening under the hood in hash functions. So first let me say exactly what the setup is. The first step is to identify all the things that you might want to be storing. So in other words, the universe of your application. So this would be something like all possible IP addresses, of which there's 2 to the 32. All possible names you might encounter, perhaps with a maximum of, say, 30 characters. All possible configurations of a chessboard, and so on. And one thing I hope you can appreciate from these examples is that in many cases this universe is really big. So the number of IP addresses is quote-unquote only 2 to the 32. The number of all names, you're probably talking more like 26 raised to the 30. All chessboard configurations, I don't even want to think about. And what you want to accomplish is you want to maintain an evolving subset of this universe U. So maybe you want to keep track of all the IP addresses you've seen on your website in the last 24 hours. You want to keep track of the phone numbers of all of your friends. You want to keep track of the chessboard configurations that you've explored in the past 3 seconds, whatever. And again, what I hope is clear from the applications we've been discussing is that this set S is usually of reasonable size. It's something you could store in main memory. Maybe it's tens of thousands of IP addresses. Maybe it's, a few hundred names of your various friends. Maybe it's in the, millions of chessboard configurations, but still way, way, way smaller than the size of the universe. So without data structures, you'd have to resort to rather unsatisfactory solutions to maintaining this set. So the first thing you could try, as we discussed in the previous video, would be you just have an array with one position for every imaginable thing you might want to store in your set. So this is the solution that's going to work well if all of your friends happen to have names that are integers between 1 and 10,000, but doesn't scale when the universe size becomes really big, as in most of these applications. So the good news is of course it's an array and it supports fast random access, so you can access any position in constant time. So if you have an array-based solution indexed by all the elements of your universe, you can do constant time insert, delete, and lookup. The bad news is the space requirement is proportional to the universe. And again, forget about being unsatisfactory. That's just literally impossible, infeasible in many applications in which you'd use hash tables. Now, of course, to get the memory proportional to the size of the set stuff that you're storing, an easy solution would just be to use a list, say a doubly linked list, something like that. Now, with a list-based solution, the good news is your memory is certainly proportional to the size of the set that you're storing, and it's independent of the size of the universe from which these elements are drawn. The bad news is to figure out whether something is or is not in a list, you generally have to traverse through most of that list, and so that's going to take time proportional to the length of the list. So really the question we're faced in implementing a hash table is, can we get the best of both worlds of these two naive solutions? On the one hand, we want to have the constant time operations enjoyed by the array-based solution, but on the other hand, we want to have the linear space and the size of the set that we're storing that we get in the list-based solution. So to get the best of both worlds, we are going to use an array-based solution, but the array will not be big. It'll not be with size proportional to the universe. The array will only have size, roughly the same as the set that we're storing, so somewhere in the ballpark of the cardinality of S. So the first thing we do is we decide on how big we want our array to be. So that length is going to be called n. We're going to have an array of length n. And n is going to be in the ballpark of the size of S. It's going to depend on a few things, exactly how n compares to S, but for now think of n as like double the size of S. We're going to be calling each entry of the array a bucket. So there's n buckets, and then the size of S is about 50% of the number of buckets, let's say. So one objection you might legitimately raise at this point is, I said the set was dynamic, the set S, right? Stuff can be added, stuff can be deleted, so the size isn't always the same. It can fluctuate over time. So what does it mean to define an array which is roughly the same length of this changing set? So for simplicity, for the purposes of this video, to focus on the key points, I'm going to assume that the set size S, while S itself can be changing, I'm going to assume that the size of S doesn't fluctuate too much. So there are additional bells and whistles you can add to a hash table implementation, and they're all quite natural. I think most of you could probably figure them out on your own to deal with the fact that S might be changing sizes. So for example, you can just keep track of how many elements are in your hash table, and when it exceeds a certain threshold, so when it's too big relative to the size of your array, you just double the array, and then you reinsert all of the elements into this new doubled array. Similarly, if you want to, if the set shrinks, you can have tricks for shrinking the array dynamically as well. So I'm not going to discuss these bells and whistles for resizing your hash table dynamically. They are, of course, important for a real implementation, and they are part of the implementations in the standard programming libraries. But I view those as sort of a second order point in the implementation of a hash table, and I want to focus on the first order points in this video. So summarizing, think of the set S. There are insertions and deletions we have to accommodate, but S is going to be roughly the same size, and the number of buckets will be within a constant factor of the size of the set. All right, so now we have our array with totally reasonable space proportional to the size of the set that we're storing. And now what we want is we want some way of translating between the things we care about, say our friends' names or whatever the elements of the universe are, to the positions in this array. So the object responsible for that translation from keys drawn from this universe to positions in this array is called a hash function. So formally, a hash function takes as input a key. So this is going to be an IP address or the name of somebody or a chessboard configuration or whatever. And it's going to spit out a position in this array. So I'm going to label the array entries from 0 to n-1 for this lecture. Obviously, at the moment, this is super underspecified. There's a zillion functions you could choose. Which one do you use? We'll talk about that. But for now, there's just going to be some hash function mapping from elements of the universe to buckets, to positions in this array. Now, as far as the semantics of this hash function, what the hash function is doing is telling us in which position we should store a given key from the universe. So if we have some new friend named Alice, and we run Alice through the key Alice through the hash function, and it gives us a 17. It says we should store Alice's phone number in position 17 of the array. If we have some crazy chessboard configuration, we feed it into a hash function and it spits out 172. It says we should remember this chessboard configuration in the 172nd bucket of this array. So again, given x, which is some key from this universe, we invoke the hash function to get a position in this array, to get a bucket, and that is where we try to store this x and any associated data with it. So that's the high-level idea of how you implement a hash table, but we're quite far from done. And in particular, there's a serious issue that we're going to have to deal with that's fundamental to implementing hash tables, and that's the notion of a collision. So probably many of you have already noticed that this problem might occur, which is, well, what happens if we're storing our friends' phone numbers and Alice shows up and we ask our hash function where to store Alice's phone number, and it says, oh, bucket number 17. And then our friend Bob shows up and we ask our hash function where to store Bob's phone number. And what if the hash function also says bucket number 17 for Bob? What do we put in bucket 17? Do we put Alice there? Do we put Bob there? Do we put them both there? How do we deal with these so-called collisions? So the next quiz is meant to get you thinking about collisions and in some sense how unavoidable they truly are. All right, so the correct answer to this question is the first answer, believe it or not. All you need is 23 people in a room before you're equally likely to have two people with the same birthday as not. So if you're looking to skim a little money off of your non-mathematical friends, this is one way you can do it. Go to cocktail parties with about 40 people and place bets with people that there are two people in the room with the same birthday. So if you have 367 people, well, there's only 366 distinct birthdays. I'm counting February 29th here as one of them. So by the pigeonhole principle, certainly the probability is 100% by the time you get to 367. Now, by the time you're at 57, you're already at 99%. So you already have overwhelming probability to have a duplicate birthday with 57 people. So of course with 184, you're going to be almost at 100%, 99.99, who knows, some large number of nines. And at 23, you're at 50%. So many people find this quite counterintuitive, that you only need 23 people to get a duplicate birthday on average. All right, so this is a quite famous example, and it sometimes goes by the birthday paradox. Calling it a paradox is sort of a misnomer. Paradox, often suggests some kind of logical inconsistency. There's no logical inconsistency here. It's just that people's brains are not really wired to have this intuition for whatever reason. But it's really just math. You can work out the math and you can just solve it. So more generally, the principle behind the birthday paradox is the following. So suppose you have a calendar, perhaps on some different planet, which has k days, where everybody's equally likely to have each of the k days as their birthday. Then it's about the square root of k people that you need in a room before you're equally likely to have a duplicate or not have a duplicate. And the reason that you get the square root effect is because if you think about it, there's a quadratic number of pairs of people in the room. So that's a quadratic in the number of people opportunities to have a duplicate, right? So each pair of people could be a duplicate. There's a quadratic number of pairs, and so that's why once the number of pairs starts reaching about the number of different days, you're going to likely see a duplicate around that point. So you might be wondering why I'm telling you about the birthday paradox in the middle of a lecture about hashing, but really it's quite relevant. So imagine, for example, you defined a hash function in the following way. Now, to be clear, this is not a practical hash function, but just for the purposes of discussion, imagine you have a hash function which randomly assigned every single key to a uniform bucket. Okay, so for each of the 1 over n buckets equally likely, then what the birthday paradox says is, even for a very small data set, you're already going to have a pair of things colliding, right? So if you have n buckets, so maybe n is like 10,000, all you need is roughly 100 elements in your data set, and despite the fact that the table is only going to be 1% full, you're already going to see a collision. Okay, so 99% of them are empty, but you're going to have one bucket that has 2. So that's sort of annoying. So the birthday paradox says you start getting collisions with a hash function, even with really tiny data sets. So in this sense, if you're going to have hash tables, you got to deal with collisions. There's going to be a fair number of them, and you need some method for resolving them. So collisions are a fact of life when you're talking about hashing. Where again, by collision, what I mean is 2 different keys, so 2 different elements, x and y from the universe, that hash to the same bucket, who have the same hash value. So in general, we can think of a hash function as doing a compression of sorts. So we have a huge universe U, and we have this very modest size array A with only n buckets, where n we're thinking of as being much, much, much smaller than u. So, of course, this hash function has to map various elements of u to the same bucket. So what are we going to do about it? How are we going to resolve these collisions? Well, there's 2 different solutions which are both quite prevalent in practice. So solution number 1 is called chaining, or sometimes you'll also see it called separate chaining. And this is a very natural solution. It's also the one that's relatively easy to analyze mathematically. What you do is just for elements that hash to the same bucket, you just revert to the list-based solution that we talked about in a previous slide. So each of the n buckets will not necessarily contain just merely 0 or 1 elements. It will contain a list with an in principle unbounded number of elements. Okay, so when we use chaining, it's then quite straightforward to figure out how to implement all of the hash table operations, namely insert, delete, and lookup. You just hash something to the appropriate bucket, and then you just do insert, delete, or lookup as appropriate in the list that's in that bucket. So just to make clear that everything is type checking, so here h of x, this is the bucket for x. That's what's specified by the hash function. And then in the h of x position of this array A, in the h of x bucket, is where we find the linked list that is going to contain x. So just to give a cartoon example, if you had, say, 4 buckets, maybe the first bucket has exactly 1 record corresponding to Alice. Maybe the second bucket just has a null pointer. No one's been inserted into the second bucket. Into the third bucket, we have, let's say, both Bob as well as Daniel. And then maybe in the fourth bucket, we have Carol. Okay, so because we have a collision between Bob and Daniel, both map to the third bucket, and we resolve that just by having a linked list with Bob and Daniel in some order. So the second solution, which is trickier to talk about mathematically, but still quite important practically, is called open addressing. And the principle in open addressing is you're not going to use any space for pointers. You're not going to have lists. So you're only going to have 1 object per bucket of the array. So now the question is, what happens if you try and insert Daniel, and you invoke the hash function on Daniel, and it takes you to a bucket that already contains Bob? That means there's no room for Daniel. So what you're going to do is you're going to probe the hash table in some other position. So a hash function is now going to be replaced by a hash sequence, where you try the hash function tells you the first bucket to try to insert Daniel, failing that, a second bucket in which to try to insert Daniel, failing that, a third bucket to try to insert Daniel, and so on. And you just keep trying until you find an open position somewhere in the array. So there's various strategies for trying to figure out the probe sequence. One strategy is if you fail in, say, bucket number 17, which is where the hash function tells you to go first, you just try bucket number 18, then 19, then 20, then 21, and so on, until you find your first open slot. So that's called linear probing. And another approach is double hashing. So this is a solution where you actually have 2 hash functions, hash function number 1 and hash function number 2. And the idea is, suppose you're trying to insert, say, Daniel into a hash table with open addressing, and you evaluate both of the hash functions. And the first one comes up 17, and the second one comes up 23. So as usual, the first hash function will specify where you look first. So if it evaluates on Daniel to 17, you look in the 17th position of the array. And if it's empty, that's where you insert Daniel. Now, if it's full, what you do is you use the second hash value to be an additive shift. So Unlike linear probing, where after 17 you look at 18, with double hashing, if the second hash function gives you 23, that's going to be your offset. So after 17 you look at bucket 40. If 40 is already full, you look at bucket 63. If bucket 63 is already full, then you look at bucket 86. So you keep adding increments of 23 until you finally find a bucket where that's empty, and that's where you insert Daniel. Now, of course, if you try to insert some other name, if you try to insert Elizabeth, you're going to get two totally different numbers in general. So maybe you'll get 42 and 27. And so here the probe sequence will be 42, failing that, 69, failing that, 96, failing that, 123, and so on. So a question you should have at this point is, I've told you two solutions to resolving collisions in a hash table, and you're probably asking, well, which one should you use if you have to implement your own hash table? And as usual, if I present you with two different solutions for the same problem, you can probably rest assured that neither one dominates the other, right? Otherwise, I wouldn't waste your time by presenting both of them to you. So sometimes chaining is going to perform better, and sometimes open addressing is going to perform better. And of course, it also depends on what kind of metric that you care about. So there are a couple rules of thumb that I can tell you. So first of all, if space is at a real premium, you might want to consider open addressing instead of chaining. And that's because with chaining, you do have this extra, it's not huge, but you have a little bit of space overhead in dealing with all these pointers and these linked lists. So if you want to avoid that, you might want to think about open addressing. The second rule of thumb is deletion is trickier with open addressing than with chaining. Right? Deletion is clearly not difficult at all, either to code or to understand when you use chaining, because it just reduces to deletion from a linked list, which of course you all know how to do. Open addressing it's not impossible to implement deletion, but it's much trickier. So if deletion is a crucial operation for you, that might skew you toward thinking about chaining. But ultimately, if it's really kind of mission critical code, probably the best thing to do is implement both kinds of solutions and just see which one works better. It's a little hard to predict how they're going to interact with memory hierarchies and that kind of thing. They're both useful in their own contexts. All right, so we've covered the two most prevalent ways of handling collisions, and we argued that collisions are inevitable. No matter how you design your hash function, you're stuck with collisions, and you can do chaining a linked list per bucket, or you can do open addressing, where you actually have a probe sequence and order in which you look at buckets until you find an empty one. And the elephant in the room at this point is, what is this hash function? I've told you nothing about hash functions. All I told you is that there's some mapping from the set of universe, so IP addresses or names or whatever, to a bucket number. So, what kind of function should you use? Excellent question. Tons of research on that question, and to this day, as much art as science. But let's start talking about it. Let's begin by building up some intuition about what we would want from a hash function, now that we know how hash functions are usually implemented. So let's start with a hash function which is implemented by chaining. So what's going to be the running time of our lookup, insert, and delete operations in a hash table with chaining? Well, the happy operation in a hash table with chaining is insertion. Insertion, we can just say without any qualifications, is constant time. This requires the sort of obvious optimization that when you do insert, you insert something at the front of the list in its bucket. There's no reason to insert it at the end. That would be silly. So the plot thickens when we think about the other two operations, deletion and lookup. So let's just think about lookup. Deletion is basically the same. So how do we implement lookup? Well, remember, when we get some key x, we invoke the hash function. We call h of x. That tells us what bucket to look in. So if it tells us 17, we know that x may or may not be in the hash table, but at this point we know that if it's in the hash table, it's got to be in the linked list that's in the 17th bucket. So now we descend into this bucket, we find ourselves a linked list, and now we have to resort to just an exhaustive search through this list in the 17th bucket to see whether or not x is there. So we know how long it takes to search a regular old list for some element. It's just linear in the list length. And now we're starting to see why the hash function might matter. Right, so suppose we insert 100 objects into a hash table with 100 buckets. If we have a super lucky hash function, then perhaps each bucket will get its own object. There'll be one object in each of the lists, in each of the buckets. So theta of the list length is just theta of 1. We're doing great. Okay, so constant linked lists means constant time insert delete. A really stupid hash function would map every single object to bucket number 0. Okay, so then if you insert 100 objects, they're all in bucket number 0. The other 99 buckets are empty. And so every time you do insert or delete, it's just resorting to the naive linked list solution. And the running time is going to be linear in the number of objects in the hash table. So the largest list length could vary anywhere from m over n, where m is the number of objects. This is when you have equal length lists. 2, if you use this ridiculous constant hash function, m, all the objects in the same list. And so the main point I'm trying to make here is that, first of all, at least with chaining, where the running time is governed by the list length, the running time depends crucially on the hash function, how well the hash function distributes the data across the different buckets. And something analogous is true for hash tables that use open addressing, right? So here there aren't any lists, so there's no list links to keep track of, so the running time is going to be governed by the length of the probe sequence. So the question is, how many times do you have to look at different buckets of the hash table before you either find the thing you're looking for, or if you're doing insertion, before you find an empty bucket in which to insert this new object. So the performance is governed by the length of the probe sequence, and again, the probe sequence is going to depend on the hash function. For really good hash functions in some sense, stuff that spreads data out evenly, you expect probe sequences to be not too bad, at least intuitively. And for, say, the constant function, you're going to expect these probe sequences to grow linearly with the number of objects you insert into the table. So again, this point remains true. The performance of a hash table in either implementation really depends on what hash function you use. So having built up this intuition, we can now say what it is we want from a hash function. So first, we want it to lead to good performance. And using the chaining implementations as a guiding example, we see that, well, if we have a size of a hash table n that's comparable to the number of objects m, it would be really cool if all of the lists had length that was basically constant, and therefore we had our constant time operations. So equal length lists is way better than unequal length lists in a hash table with chaining. So we want the hash function to do is to spread the data out as equally as possible amongst the different buckets. And something similar is true with open addressing. In some sense, you want hash functions to spread the data uniformly across the possible places you might probe as much as possible. And in hashing, usually the gold standard for spreading data out is the performance of a completely random function. So you can imagine for each object that shows up, you flip some coins. With each of the n buckets equally likely, you put this object in one of the n buckets, and you flip independent coins for every different object. So this you would expect, because you're just throwing darts at the buckets independently, you'd expect this to spread the data out quite well. But of course, it's not good enough just to spread data out. It's also important that we don't have to work too hard to remember what our hash function is and to evaluate it. Remember, every time we do any of these operations, an insert or a delete or a lookup, we're going to be applying our hash function to some key x. So every operation includes a hash function evaluation. So if we want our operations to run in constant time, evaluating the hash function also better run in constant time. And the second property is why we can't actually implement completely random hashing. Right, so there's no way we can actually just, when we say want to insert Alice's phone number, flip a new batch of random coins, right? Because suppose we flip some random coins and it tells us to put Alice's phone number into the 39th bucket. Well, later on we might do a lookup for Alice's phone number, and we better remember the fact we're supposed to look in the 39th bucket for Alice's phone number. But what does that mean? That means we have to explicitly remember what choice we made. We have to write down in a list, in effect, that Alice is in bucket number 39. And every single insertion, if they're all from independent coin flips, we have to remember all of the different random choices independently. And this really just devolves back to the naive list-based solution that we discussed before. So evaluating the hash function is going to take us linear time, and that defeats the purpose of a hash table. So we want the best of both worlds. We want a hash function which we can store in ideally constant space, evaluate in constant time, but it should spread the data out just as well as if we had this gold standard of completely random hashing. So I want to touch briefly on the topic of how you might design hash functions, and in particular good hash functions that have the two properties we identified on the previous slide. But I have to warn you, if you ask 10 different, serious hardcore programmers, about their approach to designing hash functions, you're likely to get 10 somewhat different answers. So the design of hash functions is a tricky topic, and it's as much art as science at this point, despite the fact that there's a ton of science. There's actually a very beautiful theory about what makes good hash functions. We'll touch on a little bit of that in a different optional video. And if you only remember one thing from this video or from these next couple slides, the thing to remember is the following. Remember that it's really easy to inadvertently design bad hash functions. And bad hash functions lead to poor hash table performance, much poorer than you would expect given the other discussion we've had in this video. So if you have to design your own hash function, do your homework, get some examples, learn what other experts are doing, and use your best judgment. If you do just something without thinking about it, it's quite possible to lead to quite poor performance, much poorer than you were expecting. So to drive home this point, suppose that you're thinking about keys being phone numbers. So let's say, I'm going to just be very kind of United States centric here, and I'm just going to focus on the 10-digit phone numbers inside the US. So the universe size here is 10 to the 10, which is quite big. That's probably not something you really want to implement explicitly. And let's consider an application where, you're only, say, keeping track of at most, 100 or 1,000 phone numbers or something like that. So we need to choose a number of buckets. Let's say we choose 1,000 buckets. Let's say we're expecting no more than 500 phone numbers or so. So we double that. We get a number of buckets to be equal to 1,000. And now I got to come up with a hash function. And remember, a hash function by definition, all it does is map anything in the universe to a bucket number. So that means it has to take as input a 10-digit phone number and spit as output some number between 0 and 999. And beyond that, we have flexibility of how to define this mapping. Now, when you're dealing with things that have all these digits, it's very tempting to just project onto a subset of the digits. And if you want a really terrible hash function, just use the most significant digits of a phone number to define a mapping from phone numbers to buckets. All right, so I hope it's clear why this is a terrible choice of a hash function. Right, so maybe you're a company based in the San Francisco Bay Area. The area code for San Francisco is 415. So if you're storing phone numbers from customers in your area, maybe 20, 30, 40% of them are going to have area codes 415. All of those are going to hash to exactly the same bucket number 415 in this hash table. So you're going to get an overwhelming percentage of the data mapping just to this one bucket. Meanwhile, not all 1,000 possibilities of these 3 digits are even legitimate area codes. Not all 3-digit numbers are area codes in the United States. So there'll be buckets of your hash table which are totally guaranteed to be empty. So you waste a ton of space in your hash table. You have a huge list in the bucket corresponding to 415. You have a huge list in the bucket corresponding to 650, the area code at Stanford. You're going to have very slow lookup time for everything that hashes to those 2 buckets. And there's going to be a lot of stuff which hashes to those 2 buckets. So terrible idea. So a better, but still mediocre hash function would be to do the same trick, but using the last 3 digits instead of the first 3 digits. This is better than our terrible hash function because there aren't ridiculous clumps of phone numbers that have exactly the same last 3 digits. But still, this is sort of assuming, using this hash function is tantamount to thinking that the last 3 digits of phone numbers are uniformly distributed among all of the 1,000 possibilities, and really there's no evidence that that's true. Okay, so there's going to be patterns in phone numbers that are maybe a little subtle to see with the naked eye, but which will be exposed if you try to use a mediocre hash function like this. So let's look at another example. Perhaps you're keeping track of objects just based by where they're laid out in memory. So in other words, the key for an object is just going to be its memory location. And if these things are in bytes, then you're guaranteed that every memory location will be a multiple of 4. So for a second example, let's think about a universe where the possible keys are the possible memory locations. So here you're just associating objects with where they're laid out in memory. And a hash function is responsible for taking as input some memory location of some object and spitting out some bucket number. Now generally, because of the structure of bytes and so on, memory locations are going to be multiples of some power of 2. In particular, memory locations are going to be even. And so a bad choice of a hash function would be to take, remember the hash function takes as input a memory location, which is some possibly really big number, and we want to compress it, we want to output a bucket number. And again, let's think about a hash table where we choose n equals 10 to the 3 or 1,000 buckets. So then the question is, how is this hash function going to take this big number, which is a memory location, and squeeze it down to a small number, which is one of the buckets? And so let's just use the same idea as in the mediocre hash function, which is we're going to look at the least significant bits, so we can express that using the mod operator. So let's just think about, we pick the hash function h of x, where h is a memory location, to be x mod 1,000. Where again, the meaning of 1,000 is that's the number of buckets we've chosen to put in our hash table because, we're going to remember roughly at most 500 different objects. So don't forget what the mod operation means. This means you just essentially subtract multiples of 1,000 until you get down to a number less than 1,000. So in this case, it means if you write out x base 10, then you just take the last 3 digits. So in that sense, this is the same hash function as our mediocre hash function when we were talking about phone numbers. So we discussed how the keys here are all going to be memory locations, so in particular they'll be even numbers, and here we're taking their modulus with respect to an even number. And what does that mean? That means every single output of this hash function will itself be an even number. Right? You take an even number, you subtract a bunch of multiples of 1,000, you're still going to have an even number. So this hash function is incapable of outputting an odd number. So what does that mean? That means at least half of the locations in the hash table will be completely empty, guaranteed, no matter what the keys you're hashing is. And that's ridiculous. It's ridiculous to have this hash table, 50% of which is guaranteed to be empty. And again, what I want you to remember, hopefully long after this class is completed, is not so much these specific examples, but more the general point that I'm making, which is it's really easy to design bad hash functions, and bad hash functions lead to hash table performance much poorer than what you're probably counting on. Now that we're equipped with examples of bad hash functions, it's natural to ask about, what are some good hash functions? Well, it's actually quite tricky to answer that question. What are the good hash functions? And I'm not really going to answer that on this slide. I don't promise that the hash functions I'm going to tell you about right now are good in a very strong sense of the word. I will say these are not obviously bad hash functions. They're, let's say, somewhat better hash functions. And in particular, if you just need a hash function and you just need a quick and dirty one, you don't want to spend too much time on it, the method that I'll talk about in this slide is a common way of doing it. On the other hand, if you're designing a hash function for some really mission-critical code, you should learn more than what I'm going to tell you about on this slide. So you should do more research about what are the best hash functions, what's the state of the art if you have a super important hash function. But if you just need a quick one, what we say on this slide will do in most situations. So the design of a hash function can be thought of as 2 separate parts. So remember, by definition, a hash function takes as input something from the universe, an IP address, a name, whatever, and spits out a bucket number. But it can be useful to factor that into 2 separate parts. So first you take an object which is not intrinsically numeric, so something like a string or something more abstract, and you somehow turn an object into a number, possibly a very big number. And then you take the possibly very big number and you map it to a much smaller number, namely the index of a bucket. So in some cases I've seen these 2 steps given the names, like the first step is formulating the hash code for an object, and then the second step is applying a compression function. In some cases you can skip the first step. So for example, if your keys are social security numbers, they're already integers. If they're phone numbers, they're already integers. Of course, there are applications where the objects are not numeric. For example, maybe they're strings, maybe you're remembering names. And so then the production of this hash code basically boils down to writing a subroutine that takes as input a string and outputs some possibly very big number. There's standard methods for doing that. It's easy to find resources to give you example code for converting strings to integers. I'll just say 1 or 2 sentences about it. So each character in a string, it's easy to regard as a number in various ways. Either just say it's ASCII code, and so then you just have to aggregate all of the different numbers, 1 number per character, into some overall number. And so one thing you can do is you can iterate over the characters one at a time. You can keep a running sum, and with each character you can multiply the running sum by some constant and then add a new letter to it, and then if you need to, take a modulus to prevent overflow. And the point of me giving you this 1 to 2 sentence description of the subroutine is just to give you a flavor of what they're like and to make sure that you're just not scared of it at all. Okay, so it's very simple programs you can write for doing things like converting from strings to integers. But again, I do encourage you to look it up on the web or in a programming textbook. So that leaves the question of how to design this compression function. So you take as input this huge integer. Maybe your keys are already numeric, like social security numbers or IP addresses, or maybe you've already run some subroutine to convert a string, like your friend's name, into some big number. But the point is you have a number in the millions or the billions, and you need to somehow take that and output one of these buckets. And again, think of there being maybe 1,000 or so buckets. So the easiest way to do that is something we already saw on the previous slide, which is just to take the modulus with respect to the number of buckets. Now, certainly one positive thing you can say about this compression function is it's super simple, both in the sense that it's simple to code and in the sense that it's simple to evaluate. Remember, that was our second goal for a hash function. It should be simple to store. Here there's actually nothing to store, and it should be quick to evaluate, and this certainly fits the bill. Now, the problem is, remember, the first property of a hash function that we wanted is it should spread the data out equally. And what we saw in the previous slide is that at least if you choose the number of buckets n poorly, then you can fail to have the first property. In that respect, you can fail to be a good hash function. So if, for example, n is even and all of your objects are even, then it's a disaster. All of the odd buckets go completely empty. And honestly, this is a pretty simplistic method. Like I said, this is a quick and dirty hash function. So no matter how you choose the number of buckets n, it's not going to be a perfect hash function in any sense of the word. That said, there are some rules of thumb for how to pick the number of buckets, how to pick this modulus, so that you don't get the problems that we saw on the previous slide. So I'll conclude this video just with some standard rules of thumb. If you just need a quick and dirty hash function, you're going to use the modulus compression function. How do you choose n? Well, the first thing is we definitely don't want to have the problem we had on the last slide where we're guaranteed to have these empty buckets no matter what the data is. So what went wrong in the previous slide? Well, the problem was that all of the data elements were divisible by 2, and the hash function modulus, the number of buckets, was also divisible by 2. So because they shared a common factor, namely 2, that guaranteed that all of the odd buckets remained empty. And this is a problem more generally if the data shares any common factors with n the number of budgets. So in other words, if all of your data elements are multiples of 3 and the number of buckets is also a multiple of 3, you got a big problem. Then everything's going to hash into bucket numbers which are multiples of 3. 2/3 of your hash table will go unfilled. So the upshot is you really want the number of buckets to not share any factors with the data that you're hashing. So how do you reduce the number of common factors? Well, you just make sure the number of buckets has very few factors, which means you should choose n to be a prime number, okay, a number that has no non-trivial factors. And let me remind you, the number of buckets should also be comparable to the size of the set that you're planning on storing. Again, at no point did we need n to be, very closely connected to the number of elements that you're storing, just within, say, some small constant factor. And you can always find a prime within a small constant factor of a target number of elements to store. If the number of buckets in your hash table isn't too big, if it's just in, say, the thousands or maybe the tens of thousands, then you can just look up a list of all known primes up to some point, and you can just sort of pick out a prime which is about the magnitude that you're looking for. If you're going to use a really huge number of buckets in the millions or more, then there are algorithms you can use for primality testing, which will help you find a prime in about the range that you're looking for. So that's the first order rule of thumb you should remember if you're using the modulus compression function, which is set the number of buckets equal to a prime. So you're guaranteed to not have non-trivial common factors of the modulus shared by all of your data. So there's also a couple second order optimizations, which people often mention. And you also don't want the prime, you want the prime to be not too close to patterns in your data. So what does that mean, patterns in your data? Well, in the phone number example, we saw that patterns emerged in the data when we expressed it base 10. So for example, there was crazy amounts of clumping in the first 3 digits when we expressed a phone number base 10, because that corresponded to the area code. And then with memory locations, when we express it base 2, there are crazy correlations in the low order bits. And these are the two most common examples. Either there's some digits in the base 10 representation or digits in the base 2 representation where you have patterns, that is non-uniformity. And so that suggests that the prime n that you choose, all else being equal, shouldn't be too close to a power of 2 and shouldn't be too close to a power of 10. The thinking being that that will spread more evenly data sets that do have these patterns in terms of base 2 representation or base 10 representations. So in closing, this is a recipe I recommend for coding up hash functions if what you're looking to do is sort of minimize programmer time, subject to not coming up with a hash function which is completely broken. But I want to reiterate, this is not the state of the art in hash function design. There are hash functions which are in some sense better than the ones I've explained on this slide. If you're responsible for some really mission-critical code that involves a hash function, you should really study more deeply than we've been able to do here. We'll touch on some issues in a different optional video, but really you should do additional homework. You should find out about the state-of-the-art about hash function design. You should also look into implementations of open addressing and various probing strategies. And above all, you really should consider coding up multiple prototypes and seeing which one works the best. There's no silver bullet, there's no panacea in the design of hash tables. I've given you some high-level guidance about the different approaches, but ultimately it's going to be up to you to find the optimal implementation for your own application. In this sequence of videos, we're going to take it to the next level with hash tables and understand more deeply the conditions under which they perform well. Amazingly well, in fact, as you know, with constant time performance for all of their operations. The main point of this first video is to explain a sense in which every hash function has its own kryptonite, a pathological data set for it, which then motivates the need to tread carefully with the mathematics in the subsequent videos. So a quick review. So remember that the whole purpose of a hash table is to enable extremely fast lookups, ideally constant time lookups. Now, of course, to have anything to look up, you have to also allow insertions. So all hash tables are going to export those two operations. And then sometimes a hash table also allows you to delete elements from it. That depends a little bit on the underlying implementation. So certainly when you have it implemented using chaining, that's when you have one linked list per bucket. It's very easy to implement deletion. Sometimes with open addressing, it's tricky enough, you're just going to wind up punting on deletion. So when we first started talking about hash tables, I encourage you to think about them logically, much the way you do as an array, except instead of being indexed just by the positions of an array, it's indexed by the keys that you're storing. So just like an array via random access supports constant time lookup, so does a hash table. There was some fine print, however, with hash tables. So remember there are these two caveats. So the first one is that the hash table better be properly implemented. And this means a couple things. So one thing it means is that the number of buckets better be commensurate with the number of things that you're storing in the hash table. We'll talk more about that in a second. The second thing it means is you better be using a decent hash function. So we discussed in a previous video the perils of bad hash functions, and we'll be even more stringent with our demands on hash functions in the videos to come. The second caveat, which I'll try to demystify in a few minutes, is that you better have non-pathological data. So in some sense, for every hash table there's kryptonite, there is a pathological data set that will render its performance to be quite poor. So in the video on implementation details, we also discussed how hash tables inevitably have to deal with collisions. So you start seeing collisions way before your hash table starts filling up. So you need to have some kind of method for addressing two different keys that map to exactly the same bucket. Which one do you put there? Do you put both there, or what? So there's two popular approaches. Let me remind you what they are. The first is called chaining. So this is a very natural idea where you just keep all of the elements that hash to a common bucket in that bucket. How do you keep track of all of them? Well, you just use a linked list. So in the 17th bucket, you will find all of the elements which ever hashed to bucket number 17. A second approach, which also has plenty of applications in practice, is open addressing. Here, the constraint is that you're only going to store one item, one key in each bucket. So if two things map to bucket number 17, you got to find a separate place for one of them. And so the way that you handle that is you demand from your hash function not merely one bucket, but rather a whole probe sequence. So a sequence of buckets, so that if you try to hash something into bucket 17 and 17 is already occupied, then you go on to the next bucket in the probe sequence, you try to insert it there. If they fail again, you go to the third bucket in the sequence, you try to insert it there, and so on. So we mentioned briefly the sort of two ways you can specify probe sequences. One is called linear probing. So this is where if you fail in bucket 17, you move on to 18, and then 19, and then 20, and then 21, and you stop once you find an empty one, and that's where you insert the new element. And another one is double hashing, and this is where you use a combination of two hash functions, where the first hash function specifies the initial bucket that you probe, and the second hash function specifies the offset for each subsequent probe. So for example, if you have a given element, say the name Alice, and the two hash functions give you the numbers 17 and 23, then the corresponding probe sequence is going to be initially 17. Failing that, you'll try 40. Failing that, you'll try 63. Failing that, you'll try 86, and so on. So in a course on the design and analysis of algorithms like this one, you typically talk a little bit more about chaining than you do open addressing. That's not to imply that chaining is somehow the more important one. Both of these are important. But chaining is a little easier to talk about mathematically. So we will talk about it a little bit more because I'll be able to give you complete proofs for chaining, whereas complete proofs for open addressing would be outside the scope of this course. So I'll mention it in passing, but the details will be more about chaining just for mathematical ease. So there's one very important parameter which plays a big role in governing the performance of a hash table, and that's known as the load factor, or simply the load of a hash table. And it's a very simple definition. It just talks about how populated a typical bucket of the hash table is. So it's often denoted by alpha, And in the numerator is the number of things that have been inserted and not subsequently deleted in the hash table, divided by the number of buckets in the hash table. So as you would expect, as you insert more and more things into the hash table, the load grows, keeping the number of items in the hash table fixed. As you scale up the number of buckets, the load drops. So just to make sure that the notion of the load is clear and that also you're clear on the different strategies for resolving collisions, the next quiz will ask you about the range of relevant alphas for the chaining and open addressing implementations of a hash table. All right, so the correct answer to this quiz question is the third answer, that load factors bigger than 1 do make sense. They may not be optimal, but they at least make sense for hash tables that implement with chaining, but they don't make sense for hash tables with open addressing. And the reason is simple. Remember, in open addressing, you're required to store only one object per bucket. So as soon as the number of objects exceeds the number of buckets, there's nowhere to put the remaining objects. So the hash table will simply crash at load factors bigger than 1. On the other hand, in a hash table with chaining, there's no obvious problem with load factors bigger than 1. So you can imagine a load factor equal to 2, say. So say you insert 2,000 objects into a hash table with 1,000 buckets. That means hopefully, at least in the best case, each bucket's just going to have a linked list with 2 objects in it. So there's no big deal with having load factors bigger than 1 in hash tables with chaining. All right, so let's then make a quite easy but also very important observation about a necessary condition for hash tables to have good performance. And this goes into the first caveat that you better properly implement the hash table if you expect to have good performance. So the first point is that you're only going to have constant time lookups if you keep the load to be constant. So for a hash table with open addressing, this is really obvious because you need alpha not just O of 1, but less than 1, less than 100% full. Otherwise, the hash table is just going to crash because you don't even have room for all of the items. But even for hash tables that you implement using chaining, where they at least make sense for load factors which are bigger than 1, you better keep the load not too much bigger than 1 if you want to have constant time operations, right? So if you have, say, a hash table with n buckets and you hash in n log n objects, then the average number of objects in a given bucket is going to be logarithmic. And remember, when you do a lookup, after you hash the bucket, you have to do an exhaustive search through the linked list in that bucket. So if you have n log n objects in a hash table with n buckets, you're expecting more like logarithmic lookup time, not constant lookup time. And then, as we discussed with open addressing, of course, you need not just alpha equal O of 1, but alpha less than 1. And in fact, alpha better be well below 1. You don't want to let an open addressing table get to a 90% load or something like that. So I'm going to write need alpha less than 1. So that just means you don't want to let the load grow too close to 100%. You will see performance degrade. So again, I hope the point of this slide is clear. If you want good hash table performance, one of the things you're responsible for is keeping the load factor under control. Keep it at most a small constant. With open addressing, keep it well below 100%. So you might wonder what I mean by controlling the load. After all, you writing this hash table, you have no idea what some client's going to do with it. They can insert or delete whatever they want. So how do you control alpha? Well, what you can control under the hood of your hash table implementation is the number of buckets. You can control the denominator of this alpha. So if the numerator starts growing, at some point the denominator is going to grow as well. So what actual implementations of hash tables do is they keep track of the population of the hash table, how many objects are being stored, and as this numerator grows, as more and more stuff gets inserted, the implementation ensures that the denominator grows at the same rate, so that the number of buckets also increases. So if alpha exceeds some target, that could be, say, 75%, 0.75, or maybe it's 0.5, then what you can do is you can double the number of buckets, say, in your hash table. So you define a new hash table, you have a new hash function with double the range, and now having doubled the denominator, the load has dropped by a factor 2. So that's how you can keep it under control. Optionally, if space is at a real premium, you can also shrink the hash table if there's a bunch of deletions, say, in a chaining implementation. So that's the first takeaway point about what has to be happening correctly under the hood in order to get the desired guarantees for hash table performance. You got to control the load. So you have to have a hash table whose size is roughly the same as the number of objects that you're storing. So the second thing you've got to get right, and this is something we've touched on in the implementation videos, is you better use a good enough hash function. And so what's a good hash function? It's something that spreads the data out evenly amongst the buckets. And what would really be awesome would be a hash function which works well independent of the data. And that's really been the theme of this whole course so far. Algorithmic solutions which work well independent of any domain assumptions. No matter what the input is, the algorithm is guaranteed to, for example, run blazingly fast. And I can appreciate that this is exactly the sort of thing you would want to learn from a course like this, right? Take a class in the design and analysis of algorithms, and you learn the secret hash function which always works well. Unfortunately, I'm not going to tell you such a hash function, and the reason is not because I didn't prepare this lecture. The reason is not because people just haven't been clever enough to discover such a function. The problem is much more fundamental. The problem is that such a function cannot exist. That is, for every hash function, it has its own kryptonite. There is a pathological data set under which the performance of this hash function will be as bad as the most miserable constant hash function you've ever seen. And the reason is quite simple. It's really an inevitable consequence of the compression that hash functions are effectively implementing from some massive universe to some relatively modest number of buckets. Let me elaborate. Fix any hash function, as clever as you could possibly imagine. So this hash function maps some universe to the buckets indexed from 0 to n-1. Remember, in all of the interesting situations of hash functions, the universe size is huge. So the cardinality of u should be much, much bigger than n. That's what I'm going to assume here. So for example, maybe you're remembering people's names, and then the universe is strings, which have, say, at most 30 characters, and n, I assure you, in any application is going to be much, much, much smaller than, say, 26 raised to the 30th power. So now let's use a variant on the pigeonhole principle, and I claim that at least one of these n buckets has to have at least a 1 over n fraction of the number of keys in this universe. That is, there exists a bucket I somewhere between 0 and n-1, such that at least the cardinality of the universe over n keys hash to I, get mapped to I under this hash function h. So the way to see this is just to remember the picture of a hash function mapping, in principle, any key from the universe, all keys from the universe, to one of these buckets. So the hash function has to put each key somewhere in one of the n buckets, so one of the buckets have to have at least a 1 over n fraction of all of the possible keys. One more concrete way to think of thinking about it is you might want to think about a hash table implemented with chaining, and you might want to imagine, just in your mind, that you hash every single key into the hash table. So this hash table is going to be insanely overpopulated. You'd never be able to store it on a computer because it will have the full cardinality of u objects in it, but it's got u objects. It only has n buckets. One of those buckets has to have at least a u over n fraction of the population. So the point here is that no matter what the hash function is, no matter how clever you build it, there's going to be some bucket, say bucket number 31, which gets its fair share of the universe, maps to it. So having identified this bucket, bucket number 31, where it gets at least its fair share of the universe mapped to it, now to construct our pathological data set, all we do is pick from amongst these elements that get mapped to bucket number 31. So for such a data set, and we can make this data set basically as large as we want because the cardinality of u over n is unimaginably big because u itself is unimaginably big, then in this data set everything collides. The hash function maps every single one to bucket number 31, and that's going to lead to terrible hash table performance. Hash table performance which is really no better than the naive linked list solution. So for example, in a hash table with collisions, in bucket 31, you will just find a linked list of every single thing that's ever been inserted into the hash table. And for open addressing, maybe it's a little harder to see what's going on. But again, if everything collides, you're going to basically wind up with linear time performance, a far cry from constant time performance. Now, for those of you to whom this seems like just sort of pointless abstract mathematics, I want to make 2 points. The first is that, at the very least, these pathological data sets indicates that we will have to discuss hash functions in a way differently than how we've been discussing algorithms so far. So when we talked about merge sort, we just said it runs in n log n time no matter what the input is. When we discussed Dijkstra's algorithm, it runs in m log n time no matter what the input is. Depth first search, breadth first search, linear time no matter what the input is. We're going to have to say something different about hash functions. We will not be able to say that a hash table has good performance no matter what the input is. This slide shows that that's false. The second point I want to make is that while these pathological data sets, of course, are not likely to arise just by random chance, sometimes you are concerned about somebody constructing a pathological data set for your hash function, for example, in a denial of service attack. So there's a very clever illustration of exactly this point in a research paper from 2003 by Crosby and Wallach. So the main point of Crosby and Wallach was that there's a number of real-world systems, and maybe their most interesting application was a network intrusion detection system, for which you could bring them to their knees by exploiting badly designed hash functions. So these were all applications that made crucial use of hash tables, and the feasibility of these systems really completely depended on getting constant time performance from the hash tables. So if you could exhibit a pathological data set for these hash tables and make the performance devolve to linear, devolve to that of a simple linked list solution, the systems would be broken. They would just crash or they'd fail to function. Now we saw in the last slide that every hash table does have its own kryptonite, has a pathological data set. But the question is, how can you come up with such a pathological data set if you're trying to do a denial of service attack on one of these systems? And so the systems that Crosby and Wallach looked at generally shared two properties. So first of all, they were open source. You could inspect the code, you could see what hash function it was that they were using. And second of all, the hash function was often very simplistic. So it was engineered for speed more than anything else. And as a result, it was easy to, just by inspecting the code, reverse engineer a data set that really did break the hash table, that devolved the performance to linear. So for example, in the network intrusion detection application, there was some hash table that was just remembering the IP addresses of packets that were going through because it was looking for patterns of data packets which would seem to indicate some kind of intrusion. And Crosby and Wallach just showed how sending a bunch of data packets to the system with cleverly chosen sender IPs really did just crash the system because the hash table performance blew up to an unacceptable degree. So how should we address this fact of life that every hash function has a pathological data set? And that question is meaningful both from a practical perspective, so what hash function should we use if we are concerned about someone constructing pathological data sets, for example, to implement a denial of service attack, and secondly, mathematically, if we can't give the kinds of guarantees we've given so far, data-independent guarantees, how can we mathematically say that hash functions have good performance? So let me mention two solutions. The first solution is meant more just on the practical point, what hash function should you implement if you are concerned about someone constructing pathological data sets. So there are these things called cryptographic hash functions. So for example, one cryptographic hash function, or really family of hash functions for different numbers of buckets, is SHA-2. And these are really outside the scope of this course. I mean, you'll learn more about this in a course on cryptography. And obviously, using these keywords, you could look it up on the web and read more about it. The one point I want to make is, these cryptographic hash functions like SHA-2, they themselves, they do have pathological data sets. They have their own version of kryptonite. The reason that they work well in practice is because it's infeasible to figure out what this pathological data set is. So unlike the very simplistic hash functions, which Crosby and Wallach found in the source code of their applications, where it was easy to reverse engineer bad data sets, for something like SHA-2, nobody knows how to reverse engineer a bad data set for it. And when I say infeasible, I mean it in the usual cryptographic sense. So in a way similar to how one would say it's infeasible to break the RSA cryptosystem if you implement it properly, or it's infeasible to factor large numbers except in very special cases, and so on. So that's all I'm going to say about cryptographic hash functions. I want to also mention a second solution, which would be reasonable both in practice and also for which we can say a number of things mathematically about it, which is to use randomization. So more specifically, we're not going to design a single clever hash function, because again, a single hash function we know must have a pathological data set, but we're going to design a very clever family of hash functions, and then at runtime, we're going to pick one of these hash functions at random. And now the kind of guarantee we're going to want and we're going to be able to prove on a family of hash functions will be very much in the spirit of quicksort. So you recall that in the quicksort algorithm, pretty much for any fixed pivot sequence, there is a pathological input for which quicksort will devolve to quadratic running time. So our solution was randomized quicksort, which is rather than committing up front to any particular method of choosing pivots, at runtime we're going to pick pivots randomly. What did we prove about quicksort? We proved that for any possible input, for any possible array, the average running time of quicksort was O of n log n, where the average was over the runtime random choices of quicksort. Here we're going to do the same thing. We're going to now be able to say for any data set, on average, with respect to our runtime choice of a hash function, the hash function will perform well, in the sense that it will spread out the data of the data set evenly. So we flipped the quantifiers from the previous slide. There we said if we pre-commit to a single hash function, if we fix one hash function, then there's a data set that breaks the hash function. Here we're flipping it. We're saying for each fixed data set, a random choice of a hash function is going to do well on average on that data set, just like in quicksort. This doesn't mean, notice, that we can't make our program open source. We can still publish code which says, here is our family of hash functions, and in the code will be make a random choice from this set of hash functions. But the point is, by inspecting the code, you'll have no idea what was the real-time random choices made by the algorithm, so you'll know nothing about what the actual hash function is, so you won't be able to reverse engineer a pathological data set for the real-time choice of a hash function. So the next couple of videos are going to elaborate on this second solution of using a real-time random choice of a hash function as a way of saying you do well on every data set, at least on average. So let me just give you a roadmap of where we're going to go from here. So I'm going to break the discussion of the details of this randomized solution into 3 parts spread over 2 videos. So in the next video, we're going to begin with a definition of what do I mean by a family of hash functions, so that if you pick one at random, you're likely to do pretty well. So that's a definition which is called a universal family of hash functions. Now, a mathematical definition by itself is worth approximately nothing. For it to be valuable, it has to satisfy 2 properties. So first of all, there have to be interesting and useful examples that meet the definition. So that is, there better be useful looking hash functions that meet this definition of a universal family. So the second thing will be to show you that they do indeed exist. And then the other thing a mathematical definition needs is applications. So that if you can meet the definition, then good things happen. So that'll be part 3. So now that we understand why we can't have a single hash function which always does well on every single data set, that is, every hash function is subject to pathological data sets, we'll discuss the randomized solution of how you can have a family of hash functions, and if you make a real-time decision about which hash function to use, you're guaranteed to do well on average, no matter what the data is. So let me remind you of the 3-pronged plan that I have for this part of the material. So in this video, we'll be covering the first 2. So part 1, which we'll accomplish on the next slide, will be to propose a mathematical definition of a good random hash function. So formally, we're going to define a universal family of hash functions. Now, what makes this definition useful? Well, 2 things. And so part 2 will show that there are examples of simple and easy to compute hash functions that meet this definition, that are universal in the sense described on the next slide. So that's important. And the third part, which we'll do in the next video, will be the mathematical analysis of the performance of hashing, specifically with chaining when you use universal hashing. And we'll show that if you pick a random function from a universal family, then the expected performance of all of the operations are constant, assuming, of course, that the number of buckets is comparable to the number of objects in the hash table, which we saw earlier is a necessary condition for good performance. So let's go ahead and get started. Let's say what we mean by a good random hash function. So for this definition, we'll assume that the universe is fixed. So maybe it's IP addresses, maybe it's our friends' names, maybe it's configurations of a chessboard, whatever, but there's some fixed universe U, and we'll also assume we've decided on the number of buckets n. Then we call the set H universal if and only if it meets the following condition. In English, the condition says that for each pair of distinct elements, the probability that they collide should be no larger than with the gold standard of perfectly uniform random hashing. So for all distinct keys from the universe, call them X and Y, what we want is that the probability, if we choose a random hash function little h from the set script h, the probability that X and Y collide, and again, just to be clear, what that means is that X and Y hash to exactly the same bucket under this hash function little h. This should be no more than 1 over n. And don't forget, n is the number of buckets. And again, to interpret this, 1 over n, where does this come from? So we said earlier that an impractical, but in some sense gold standard hash function would be to just independently for each key assign it a bucket uniformly at random, with different keys being assigned independently. Remember, the reason this is not a practical hash function is because you'd have to remember where everybody went, and then that would basically require maintaining a list, which would devolve to the list solution. So you don't want that. You want hash functions where you have to store almost nothing, and where you can evaluate them in constant time. But if we throw out those requirements of small space and small time, then random functions should spread stuff out pretty evenly, right? I mean, that's what they're doing. You're throwing darts completely at random at these n buckets. So what would be the collision probability of two given keys, say of Alice and of Bob, if you're doing everything independently and uniformly at random? Well, first Alice shows up and it goes to some totally random bucket, say bucket number 17. Now Bob shows up. So what's the probability that it collides with Alice? Well, there are these n buckets that Bob could go to, each is equally likely, and there's a collision between Alice and Bob if and only if Bob goes to bucket 17. Since each bucket's equally likely, that's only a 1 in n probability. So really what this condition is saying is that for each pair of elements, the collision probability should be as small, as good, as with the holy grail of perfectly random hashing. So this is a pretty subtle definition, perhaps the most subtle one that we see in this entire course. So to help you just get some facility with this and to force you to think about it a little bit deeply, the next quiz, which is probably harder than a typical in-class quiz, asks you to compare this definition of universal hashing with another definition and asks you to figure out to what extent they're the same definition. So the correct answer to this quiz question is the third one, that there are hash function families H that satisfy the condition on this slide that are not universal. On the other hand, there are hash function families capital H which satisfy this property and are universal. So I'm going to give you an example of each. I'd encourage you to think carefully about why this is an example and a non-example offline. So an easy example to show that sometimes the answer is yes, you have universal hash function families H, which also satisfy this property in the slide, would be to just take capital H to be the set of all functions from mapping the universe to the number of buckets. So that's an awful lot of functions. That's a huge set, but it's a set nonetheless. And by symmetry of having all of the functions, it both satisfies the property on this slide. It is indeed true that exactly a 1 over n fraction of all functions map arbitrary key k to an arbitrary bucket I. And by the same reasoning, by the same symmetry properties, this is universal. So really, if you think about it, choosing a function at random from capital H is now just choosing a completely random function. So that's exactly what we've been calling perfect random hashing. And as we discussed in the last slide, that would indeed have a collision probability of exactly 1 over n for each pair of distinct keys. So this shows sometimes you can have both this property and be universal. An example where you have the property in this slide but you're not universal would be to take H to be a quite small family, a family of exactly n functions, each of which is a constant function. So there's going to be one function which always maps everything to bucket 0. That's a totally stupid hash function. There's going to be another hash function which always maps everything to bucket number 1. That's a different but also totally stupid hash function, and so on. And then the nth function will be the constant function that always maps everything to bucket n minus 1. And if you think about it, this very silly set H does indeed satisfy this very reasonable looking property on this slide. Fix any key, fix any bucket, say bucket number 31. What's the probability that you pick a hash function that maps this key to bucket number 31? Well, independent of what the key is, it's going to be the probability that you pick the constant hash function whose output is always 31. Since there's n different constant functions, there's a 1 in n probability. So that's an example showing that in some sense this is not as useful a property as the property of universal hashing. So this is really not what you want, or this is not strong enough. Universal hashing, that's what you want for strong guarantees. So now that we've spent some time trying to assimilate probably the subtlest definition we've seen so far in this class, let me let you in on a little secret about the role of definitions in mathematics. So on the one hand, I think mathematical definitions often get short shrift, especially in the popular discussion of mathematical research. That said, it's easy to come up with one reason why that's true, which is that any schmo can come up and write down a mathematical definition. Nobody's stopping you. So what you really need to do is you need to prove that a mathematical definition is useful. So how do you indicate usefulness of a definition? Well, you got to do two things. First of all, you have to show that the definition is satisfied by objects of interest. For us, right now, objects of interest are hash functions we might imagine implementing. So they should be easy to store, easy to evaluate. So there better be such hash functions meeting that complicated universal hash function definition. The second thing is something good better happen if you meet the definition. And in the context of hashing, what good thing do we want to have happen? We want to have good performance. So those are the two things that I owe you in these lectures. First of all, a construction of practical hash functions that meet that definition. That's what we'll start on right now. Second of all, why meeting that definition is a sufficient condition for good hash table performance. That'll be the next video. So in this example, I'm going to focus on IP addresses, although the hash function construction is general, as I hope will be reasonably clear. And as many of you know, an IP address is a 32-bit integer consisting of 4 different 8-bit parts. So let's just go ahead and think of an IP address as a 4-tuple, the way you often see it. And since each of the 4 parts is 8 bits, it's going to be a number between 0 and 255. And the hash function we're going to construct, it's really not going to be so different than the quick and dirty hash functions we talked about last video, although in this case we'll be able to prove that the hash function family is in fact universal. And we're again going to use the same compression function. We're going to take the modulus with respect to a prime number of buckets. The only difference is we're going to multiply these xi's by a random set of coefficients. We're going to take a random linear combination of x1, x2, x3, and x4. So let me be a little more precise. So we're going to choose a number of buckets n. And as we've said over and over, the number of buckets should be chosen so that it's in the same ballpark of the number of objects you're storing. So, let's say that n should be roughly double the number of objects that you're storing as an initial rule of thumb. So for example, maybe we only want to maintain something in the ballpark of 500 IP addresses, and we could choose n to be a prime like 997. So here's the construction. Remember, we want to produce not just one hash function, but the definition is about a universal family of hash functions. So we need a whole set of hash functions that we're ultimately going to choose one member from at random. So how do we construct a whole bunch of hash functions in a simple way? Here's how we do it. So we define one hash function, which I'm going to denote by h sub a. A here is a 4-tuple, the components of which I'm going to call A1, A2, A3, and A4. And all of the components of A are integers between 0 and n minus 1. So they're exactly in correspondence with the indices of the buckets. So if we have 997 buckets, then each of these AIs is an integer between 0 and 996. So it's clear that this defines, a whole bunch of functions. So in fact, for each of the 4 coefficients, so it's 4 independent choices, you have n options. Okay, so each of the integers between 0 and n minus 1 for each of the 4 coefficients. So that's fine. I've given a name to n to the 4th different functions, but what is any given function? How do you actually evaluate one of these functions? Okay, so remember what a hash function is supposed to do. Remember, how it type checks. It takes as input something from the universe, in this case an IP address, and outputs a bucket number. And the way we evaluate the hash function h sub a, and again remember a here is a 4-tuple, and remember an IP address is also a 4-tuple. Okay, so each component of the IP address is between 0 and 255. Each component of a is between 0 and n minus 1. So for example, between 0 and 996. What we do is we just take the dot product, or the inner product, of the vector a and the vector x, and then we take the modulus with respect to the number of buckets. So that is, we take a1 times x1 plus a2 times x2 plus a3 times x3 plus a4 times x4. Now, of course, remember the x's lie between 0 and 255. The AI's lie between 0 and n minus 1, so say 0 and 996. So you do these 4 multiplications and add them up, you might get a pretty big number. You might well overshoot the number of buckets n. So to get back in the range of what the buckets are actually indexed, at the end we take the modulus, the number of buckets. So in the end we do output a number between 0 and n minus 1 as desired. So that's a set of a whole bunch of hash functions, n to the 4th hash functions, and each one meets the criteria of being a good hash function from an implementation perspective. Right? So remember, we don't want to have to store much to evaluate a function, and for a given hash function in this family, all we got to remember are the coefficients, a1, a2, a3, and a4. you just got to remember these 4 numbers. And then to evaluate a hash function on an IP address, we clearly do a constant amount of work. We just do these 4 multiplications, the 3 additions, and then taking the modulus by the number of buckets n. So it's constant time to evaluate, constant space to store. And what's cool is, using just these very simple hash functions, which are constant time to evaluate and constant space to store, this is already enough to meet the definition of a universal family of hash functions. So this fulfills the first promise that I owed you after subjecting you to that definition of universal hashing. Remember, the first promise was that there are simple or there are useful examples that meet the definition, and then of course I still owe you why meeting this definition is useful. Why does it lead to good performance? But I want to conclude this video by actually proving this theorem to you, arguing that this is in fact a universal family of hash functions. All right, so this will be a mostly complete proof, and certainly will have all of the conceptual ingredients of why the proof works. There'll be one spot where I'm a little hand-wavy because we need a little number theory, and I don't want to have a big detour into number theory. And if you think about it, you shouldn't be surprised that basic number theory plays at least some role, right? As I said, we should choose the number of buckets to be prime. So that means at some point in the proof, you should expect us to use the assumption that n is prime. And pretty much always you're going to use that assumption to involve at least elementary number theory. Okay, but I'll be clear about where I'm being hand-wavy. So what do we have to prove? Let's just quickly review the definition of a universal hash function. So we have our set H, that we know exactly what it is. What does it mean that it's universal? It means for each pair of distinct keys, so in our context it's for each pair of IP addresses, the probability that a random hash function from our family script H causes a collision, maps these 2 IP addresses to the same bucket, should be no worse than with perfectly random hashing. So no worse than 1 over n, where n is the number of buckets, say like 997. So the definition we need to meet is a condition for every pair of distinct keys. So let's just start by fixing 2 distinct keys. So I'm going to assume for this proof that these 2 IP addresses differ in their 4th component. That is, I'm going to assume that x4 is different than y4. So I hope it's intuitively clear that it shouldn't matter which set of 8 bits I'm looking at. So they're different IP addresses, they differ somewhere. If I really wanted, I could have 4 cases that were totally identical, depending on whether they differ in the first 8 bits, the next 8 bits, the next 8 bits, or the last 8 bits. I'm going to show you one case because the other 3 are the same. So let's just think of the last 8 bits as being different. And now remember what the definition asked us to prove. It asked us to prove that the probability that these 2 IP addresses are going to collide is at most 1 over n. So we need an upper bound on the collision probability with respect to a random hash function from our set of n to the 4th hash functions. So I want to be clear on the quantifiers. We're thinking about 2 fixed IP addresses. So for example, the IP address for the New York Times website and the IP address for the CNN website. We're asking for these 2 fixed IP addresses, what fraction of our hash functions cause them to collide, right? We'll have some hash functions which map the New York Times and CNN IP addresses to the same bucket, and we'll have other hash functions which do not map those 2 IP addresses to the same bucket. And we're trying to say that the overwhelming majority sends them to different buckets. Only a 1 over n fraction at most sends them to the same bucket. So we're asking about the probability for the choice of a random hash function from our set H that the function maps the 2 IP addresses to the same place. So the next step is just algebra. I'm just going to take this equation, which indicates when the 2 IP addresses collide under a hash function. I'm going to expand the definition of our hash function. Remember, it's just this inner product modulo the number of buckets n, and I'm going to rewrite this condition in a more convenient way. All right, so after the algebra and the dust has settled, we're left with this equation being equivalent to the 2 IP addresses colliding. So again, we're interested in the fraction of choices of A1, A2, A3, and A4 such that this condition holds, right? Sometimes it'll hold for some choices of the AIs, sometimes it won't hold for other choices, and we're wanting to show that it almost never holds, okay? So it fails for all but a 1 over n fraction of the choices of the AIs. So next we're going to do something a little sneaky. This trick is sometimes called the principle of deferred decisions. And the idea is when you have a bunch of random coin flips, it's sometimes convenient to flip some but not all of them. So sometimes fixing parts of the randomness clarifies the role that the remaining randomness is going to play. That's what's going to happen here. So let's go ahead and flip the coins which tell us the random choice of A1, A2, and A3. So again, remember, in the definition of a universal hash function, you analyze collision probability under a random choice of a hash function. What does it mean to choose a random hash function for us? It means a random choice of A1 and A2 and A3 and A4. So we're making 4 random choices. And what I'm saying is, let's condition on the outcomes of the first 3. Suppose we knew that A1 turns up 173, A2 shows up 122, and A3 shows up 723. But we don't know what A4 is. A4 is still equally likely to be any of 0, 1, 2, all the way up to n minus 1. So remember that what we want to prove is that at most a 1 over n fraction of the choices of A1, A2, A3, and A4 cause this underlined equation to be true, cause a collision. So what we're going to show is that for each fixed choice of A1, A2, and A3, at most a 1 over n fraction of the choices of A4 cause this equation to hold. And if we can show that for every single choice of A1, A2, and A3, no matter how those random coin flips come out, at most a 1 over n fraction of the remaining outcomes satisfy the equation, then we're done. It means at most a 1 over n fraction of the overall outcomes can cause the equation to be true. So if you haven't seen the principle of deferred decisions before, you might want to think about this a little bit offline, but it's easily justified by just, say, 2 lines of algebra. Okay, so we're done with this setup and we're ready for the meat of the argument. So what we've done is we've identified an equation, which is now in green, which occurs if and only if we have a collision between the 2 IP addresses. And the question we need to ask is, for our fixed choices of A1, A2, and A3, how frequently will the choice of A4 cause this equation to be satisfied, cause a collision? Now here's why we did this trick of the principle of deferred decisions. By fixing A1, A2, and A3, the right-hand side of this equation is now just some fixed number between 0 and n minus 1. So maybe this is 773. Right? The xi's were fixed up front, the yi's were fixed up front. We fixed A1, A2, and A3 at the end of the last slide, and those are the only ones involved on the right-hand side. So this is 773, and over on the left-hand side, x4 is fixed, y4 is fixed, but A4 is still random. This is an integer equally likely to be any value between 0 and n minus 1. Now here's the key claim, which is that the left-hand side of this green equation is equally likely to be any number between 0 and n minus 1. And I'll tell you the reasons why this key claim is true, although this is the point where we need a little bit of number theory, so I'll be kind of hand-wavy about it. So there's 3 things we have going for us. The first is that x4 and y4 are different. Remember, our assumption at the beginning of the proof was that the IP addresses differ somewhere, so why not just assume that they differ in the last 8 bits of the proof? Again, this is not important. If you really wanted to be pedantic, you could have 3 other cases depending on the other possible bits in which the IP addresses might differ. But anyway, so because x4 and y4 are different, what that means is that x4 minus y4 is not 0. And in fact, now that I write this, it's jogging my memory of something that I should have told you earlier and forgot, which is that the number of buckets n should be at least as large as the maximum coefficient value. So for example, we definitely want the number of buckets n in this equation to be bigger than x4 and bigger than y4. And the reason is, otherwise you could have x4 and y4 being different from each other, but the difference still winds up being 0 mod n, right? So for example, suppose n was 4, and x4 was 6, and y4 was 10. Then x4 minus 10 would be minus 4, and that's actually 0 modulo 4. So that's definitely not what you want. You want to make sure that if x4 and y4 are different, then their difference is non-zero modulo n. And the way you ensure that is you just make sure n is bigger than each. So you should choose the number of buckets bigger than the maximum value of a coefficient. So in our IP address example, remember the coefficients don't get bigger than 255, and I was suggesting a number of buckets equal to, say, 997. Now, in general, this is never a big deal in practice. If you only wanted to use, say, 100 buckets, you didn't want to use 1,000, you wanted 100, well, then you could just use smaller coefficients, right? You could just break up the IP address. Instead of into 8-bit chunks, you could break it into 6-bit chunks or 4-bit chunks, and that would keep the coefficient size smaller than the number of buckets. Okay, so really you choose the buckets first, and then you choose how many bits to chunk your data into, and that's how you make sure this is satisfied. So back to the 3 things we have going for us in trying to prove this key claim. So x4 and y4 are different, so their difference is non-zero modulo n. So second of all, n is prime. That was part of the definition, part of the construction. And then third, a4, this final coefficient, is equally likely to take on any value between 0 and n minus 1. So just as a plausibility argument, let me give you a proof by example. Again, I don't want to detour into elementary number theory, although it's beautiful stuff. So, I encourage those of you who are interested to go learn some and figure out exactly how you prove it. You really only need the barest elementary number theory to give a formal proof of this. But just to show you that this is true in some simple examples, so let's think about a very small prime. Let's just say there's 7 buckets. And let's suppose that the difference between x4 and y4 is 2. Okay, so having chosen the parameters, I've set n equals 7, I've set the difference equal to 2. What I want to do is I want to step through the 7 possible choices of A4 and look at what we get in this blue circled quantity in the left-hand side of the green equation. So we want to say the left-hand side is equally likely to be any of the 7 numbers between 0 and 6. So that means that as we try our 7 different choices for A4, we better get the 7 different possible numbers as output. So, for example, if we set A4 equal to 0, then the blue circled quantity is certainly itself 0. If we set it equal to 1, then it's 1 times 2, so we get 2. For 2, we get 2 times 2, which is 4. For 3, we get 3 times 2, which is 6. Now, when we set A4 equal to 4, we get 4 times 2, which is 8. Modulo 7 is 1. 5 times 2 mod 7 is 3. 6 times 2 mod 7 is 5. So as we cycle through A4, 0 through 6, we get the values 0, 2, 4, 6, 1, 3, 5. So indeed, we cycle through the 7 possible outcomes one by one. So if A4 is chosen uniformly at random, then indeed this blue circled quantity will also be uniform at random. So just to give another quick example, we could also keep n equals 7 and think about the difference of x4 and y4. Again, we have no idea what it is other than that it's non-zero. So, maybe instead of 3, maybe instead of 2, it's 3. So now again, let's step through the 7 choices of A4 and see what we get. So now we're going to get 0, then 3, then 6, then 2, then 5, and then 1, and then 4. So again, stepping through the 7 choices of A4, we get all of the 7 different possibilities of this left-hand side. And it's not an accident of these choices of parameters. As long as n is prime, x4 and y4 are different, and y4 ranges over all possibilities, so will the value on the left-hand side. So by choosing A4 uniformly at random, indeed the left-hand side is equally likely to be any of its possible values, 0, 1, 2, up to n minus 1. And so what does that mean? Well, basically that means we're done with our proof. Because remember, the right-hand side that's circled in pink is fixed. We fixed A1, A2, and A3. The x's and y's have been fixed all along, so this is just some number, like 773. And so we know that there's exactly one choice of A4 that will cause the left-hand side to also be equal to 773. Now A4 has n different possible values, and it's equally likely to take one on. So there's only a 1 in n chance that we're going to get the unlucky choice of A4 that causes the left-hand side to be equal to 773. And of course, there's nothing special about 773. Doesn't matter how the right-hand side comes out. We have an only 1 in n chance of being unlucky and having a collision, and that is exactly the condition we are trying to prove. And that establishes the universality of this function h of n to the 4th. Very simple, very easy to evaluate hash functions. So in this video, we're going to start reasoning about the performance of hash tables. In particular, we'll make precise this idea that properly implemented, they guarantee constant time lookup. So let me just briefly remind you of the roadmap that we're in the middle of. So we observed that every fixed hash function is subject to a pathological data set, and so exploring the solution of making a real-time decision of what hash function to use. And we've already gone over this really quite interesting definition of universal hash functions, and that's the proposed definition of a good random hash function. Moreover, in the previous video I showed you that there are simple such families of hash functions. They don't take much space to store, they don't take much time to evaluate. And the plan for this video is to prove formally that if you draw a hash function uniformly at random from a universal family of hash functions like the one we saw in the previous video, then you're guaranteed expected constant time for all of the supported operations. So here's the definition once more of a universal family of hash functions. We'll be using this definition, of course, when we prove that these hash functions give good performance. So remember, we're talking now about a set of hash functions. These are all of the conceivable real-time decisions you might make about which hash function to use. So the universe is fixed. This is something like IP addresses. The number of buckets is fixed. That's going to be something like 10,000, say. And what it means for a family to be universal is that the probability that any given pair of items collides is as good, as small, as with the gold standard of completely perfect uniform random hashing. That is, for each pair XY of distinct elements of the universe, so for example, for each distinct pair of IP addresses, the probability over the choice of the random hash function little h from the family script h is no more than 1 over n, where n is the number of buckets. So if you have 10,000 buckets, the probability that any given pair of IP addresses winds up getting mapped to the same bucket is at most 1 in 10,000. Let me now spell out the precise guarantee we're going to prove if you use a randomly chosen hash function from a universal family. So for this video, we're going to only talk about hash tables implemented with chaining, with one linked list per bucket. We'll be able to give a completely precise mathematical analysis with this collision resolution scheme. We're going to analyze the performance of this hash table in expectation over the choice of a hash function little h drawn uniformly from a universal family script h. So for example, for the family that we constructed in the previous video, this just amounts to choosing each of the 4 coefficients uniformly at random. That's how you select a hash function uniformly at random. So this theorem and also the definition of universal hash functions dates back to a 1979 research paper by Carter and Wegman. The idea of hashing dates back quite a bit before that, certainly to the 50s. So this just kind of shows how sometimes ideas have to be percolating for a while before you find the right way to explain what's going on. So Carter and Wegman provided this very clean and modular way of thinking about performance of hashing through this universal hashing definition. And the guarantee is exactly the one that I promised way back when we talked about what operations are supported by hash tables and what kind of performance should you expect. You should expect constant time performance. As always with hashing, there is some fine print, so let me just be precise about what the caveats of this guarantee are. So first of all, necessarily this guarantee is in expectation. So it's on average over the choice of the hash function little h. But I want to reiterate that this guarantee does hold for an arbitrary data set. So this guarantee is quite reminiscent of the one we had for the randomized quicksort algorithm. In quicksort, we made no assumptions about the data. It was a completely arbitrary input array, and the guarantee said on average over the real-time randomized decisions of the algorithm, no matter what the input is, the expected running time was n log n. Here we're saying again, no assumptions about the data. It doesn't matter what you're storing in the hash table. In expectation over the real-time random decision of what hash function you use, you should expect constant time performance, no matter what that data set is. So the second caveat is something we've talked about before. Remember, the key to having good hash table performance, not only do you need a good hash function, which is what this universality guarantee is providing us, but you also need to control the load of the hash table. So of course, to get constant time performance, as we've discussed, a necessary condition is that you have enough buckets to hold more or less the stuff that you're storing. That is, the load, alpha, the number of objects in the table divided by the number of buckets, should be constant for this theorem to hold. And finally, whenever you do a hash table operation, you have to, in particular, invoke the hash function on whatever key you're given. So in order to have constant time performance, it better be the case that it only takes constant time to evaluate your hash function. And that's, of course, something we also discussed in the previous video when we emphasized the importance of having simple universal hash functions, like those random linear combinations we discussed in the previous video. In general, the mathematical analysis of hash table performance is a quite deep field, and there are some quite mathematically interesting results that are well outside the scope of this course. But what's cool is this theorem I will be able to provide you a full and rigorous proof. So for hash tables with chaining and using randomly chosen universal hash functions, I'm going to now prove that you do get constant time performance. All right, so hash tables support various operations, insert, delete, and lookup. But really, if we can just bound the running time of an unsuccessful lookup, that's going to be enough to bound the running time of all of these operations. So remember, in a hash table with chaining, you first hash the appropriate bucket, and then you do the appropriate insert, delete, or lookup in the linked list in that bucket. So the worst case, as far as traversing through this linked list, is you're looking for something that's not there, because then you got to look at every single element in the list and fall off the end of the list before you can conclude that the lookup has failed. Of course, insertion, as we discussed, is always constant time. Deletion and successful searches, well, you might get lucky and stop early before you hit the end of the list. So all we're going to do is bother to analyze unsuccessful lookups. That will carry over to all of the other operations. So a little more precisely, let's let S be the data set. This is the objects that we're storing in our hash table. And remember that to get constant time lookup, it certainly needs to be the case that the load is constant. So we're assuming that the size of S is big O of the number of buckets N. And let's suppose we're searching for some other object, which is not an S, call it X. And again, I want to emphasize we're making no assumptions about what this data set S is, other than that the size is comparable to the number of buckets. So conceptually, doing a lookup in a hash table with chaining is a very simple thing. You just hash to the appropriate bucket, and then you scan through the linked list in that bucket. So conceptually, it's very easy to write down what the running time of this unsuccessful lookup is. It's got two parts. So the first thing you do is you evaluate the hash function to figure out the right bucket. And again, remember, we're assuming that we have a simple enough hash function that this takes constant time. And now, of course, the magic of hash functions is that given this hash value, we can zip right to where the linked list is to search for X using random access into our array of buckets. So we go straight to the appropriate place in our array of buckets, and we just search through the list, ultimately failing to find what we're looking for, X. Traversing a linked list, as you all know, takes time proportional to the length of the list. So we find something we discussed informally in the past, which is that the running time of hash table operations implemented with chaining is governed by the list lengths. So that's really the key quantity we have to understand. So let's give this a name, capital L. It's important enough to give a name. So what I want you to appreciate at this point is that this key quantity, capital L, the list of the length in X's bucket, is a random variable. It is a function of which hash function, little h, we wind up selecting in real time. So for some choices of our hash function, little h, this list length might be as small as 0, but for other choices of this hash function h, this list length could be bigger. So this is exactly analogous to in quicksort, where depending on the real-time decision of which random pivot element you use, you're going to get a different number of comparisons, a different running time. So the list length, and hence the time for the unsuccessful search, depends on the hash function little h, which we're choosing at random. So let's recall what it is we're trying to prove. We're trying to prove an upper bound on the running time of an unsuccessful lookup on average, where the on average is over the choice of the hash function little h. We've expressed this lookup time in terms of the average list length in X's bucket, where again the average is over the random choice of h. Summarizing, we've reduced what we care about, expected time for lookup, to understanding the expected value of this random variable capital L, the average list length in X's bucket. So that's what we got to do. We got to compute the expected value of this random variable capital L. Now to do that, I want to jog your memory of a general technique for analyzing expectations, which you haven't seen in a while. The last time we saw it, I believe, was when we were doing the analysis of randomized quicksort and counting its comparisons. So here's a general decomposition principle, which we're now going to use in exactly the same way as we did in quicksort here to analyze the performance of hashing with chaining. So this is where you want to understand the expectation of a random variable, which is complicated, but which you can express as the sum of much simpler random variables, ideally 0, 1, or indicator random variables. So the first step is to figure out a random variable, capital Y is what I'm calling it here, that you really care about. Now we finished the last slide completing step 1. What we really care about is capital L, the list length in X's bucket. So that governs the running time of an unsuccessful lookup. Clearly, that's what we really care about. Step 2 of the decomposition principle is, well, the random variable you care about is complicated, hard to analyze directly, but decompose it as a sum of 0, 1 indicator random variables. So that's what we're going to do at the beginning of the next slide. Why is it useful to decompose a complicated random variable into the sum of 0, 1 random variables? Well, then you're in the wheelhouse of linearity of expectation. You get that the expected value of the random variable that you care about is just the sum of the expected values of the different indicator random variables, and those expectations are generally much easier to understand, and that will again be the case here in this theorem about the performance of hash tables with chaining. So let's apply this 3-step decomposition principle to complete the proof of the Carter-Wegman theorem. So for the record, let me just remind you about the random variable that we actually really care about. That's capital L. The reason that's a random variable is because it depends on the choice of the hash function little h. This number could vary between 0 and something much, much bigger than 0, depending on which h you choose. So this is complicated, hard to analyze directly. So let's try to express it as the sum of 0, 1 random variables. So here are the 0, 1 random variables that are going to be the constituents of capital L. we're going to have one such variable for each object y in the data set. Now remember, this is an unsuccessful search. X is not in the data set, capital S. So if y is in the data set, x and y are necessarily different. And we will define each random variable z sub y as follows. We'll define it as 1 if y collides with x under h, and 0 otherwise. So for a given zy, we have fixed objects x and y. So x is some IP address, say, y is some distinct IP address, x is not in our hash table, y is in our hash table. And now, depending on which hash function we wind up using, these two distinct IP addresses may or may not get mapped to the same bucket of our hash table. So this indicator random variable is just indicating whether or not they collide, whether or not we unluckily choose a hash function little h that sends these distinct IP addresses x and y to exactly the same bucket. Okay, so that's zy. Clearly, by definition, it's a 0-1 random variable. Now, here's what's cool about these random variables is that capital L, the list length that we care about, decomposes precisely into the sum of the zy's. That is, we can write capital L as being equal to the sum over the objects in the hash table of zy. So if you think about it, this equation is always true, no matter what the hash function h is. Right? So if you choose some hash function that maps this IP address x to, say, bucket number 17, capital L is just counting how many other objects in the hash table wound up getting mapped to bucket number 17. So maybe 10 different objects got mapped to bucket number 17. Those are exactly the 10 different values of y that will have their zy equal to 1. Right? So L is just counting the number of objects in the data set S that collide with X. A given zy is just counting whether or not a given object y in the hash table is colliding with X. So summing over all the possible things that could collide with X, summing over the zy's, we of course get the total number of things that collide with X, which is exactly equal to the population of X's bucket in the hash table. All right, so we've got all of our ducks lined up in a row. Now, if we just remember all of the things we have going for us, we can just follow our nose and nail the proof of this theorem. So what is it that we have going for us? Well, in addition to this decomposition of the list length into indicator random variables, we've got linearity of expectation going for us. We've got the fact that our hash function is drawn from a universal family going for us. And we've got the fact that we've chosen the number of buckets n to be comparable to the data set size. So we want to use all of those assumptions and finish the proof that the expected performance is constant. So we're going to have a few inequalities, and we're going to begin with the thing that we really care about. We care about the average list length in X's bucket. Remember, we saw on the previous slide, this is what governs the expected performance of the lookup. If we can prove that the expected value of capital L is constant, we're done. We've finished the theorem. So the whole point of this decomposition principle is to apply linearity of expectation, which says that the expected value of a sum of random variables equals the sum of the expected values. So because L can be expressed as the sum of these zy's, we can reverse the summation in the expectation, and we can first sum over the y's, over the objects in the hash table, and then take the expected value of zy. Now, something which came up in our quicksort analysis, but which you might have forgotten, is that 0-1 random variables have particularly simple expectations. So the next quiz is just going to jog your memory about why 0-1 random variables are so nice in this context. Okay, the answer to this quiz is the third one. The expected value of zy is simply the probability that x and y collide. That just follows from the definition of the random variable zy and the definition of expectation. Namely, recall, how did we define zy? This just is 1 if this object y in the hash table happens to collide with the object x that we're looking for under the hash function x, and 0 otherwise. Again, this will be 1 for some hash functions and 0 for other hash functions. And then we just have to compute expectations. So one way to compute the expected value of the 0-1 random variable is you just say, well, there are the cases where the random variable evaluates to 0. And then there's the cases where the random variable evaluates to 1. And of course we can cancel the 0. So this just equals the probability that zy equals 1. And since zy being 1 is exactly the same thing as x and y colliding, that's what gives us the answer. Okay, it's just the probability that x collides with y. So plugging that into our derivation, now we again have the sum over all of the objects y in our hash table. And instead of the expected value of zy, let's write that in a more interpretable form, the probability that this particular object in the hash table y collides with the thing we're looking for, x. Now we know something pretty cool about the probability that a given pair of distinct elements like x and y collide with each other. What is it that we know? Okay, so I hope you answered the second response to this quiz. This is really, in some sense, the key point of the analysis. This is the role that being a universal family of hash functions plays in this performance guarantee. What does it mean to be universal? It means for any pair of objects distinct, like x and y in that proof, if you make a random choice of a hash function, the probability of collision is as good as with perfectly random hashing, namely at most 1 over n, where n is the number of buckets. So now we can return to the derivation. What that quiz reminds you is that the definition of a universal family of hash functions guarantees that this probability for each y is at most 1 over n, where n is the number of buckets in the hash table. So let's just rewrite that. So we've upper bounded the expected list length by a sum over the objects in the data set of 1 over n. And this, of course, is just equal to the number of objects in the data set, the cardinality of S, divided by n. And what is this? This is simply the load. This is the definition of the load, alpha, which we're assuming is constant. Remember, that was the third caveat in the theorem. So that's why, as long as you have a hash function which you can compute quickly in constant time, and as long as you keep the load under control, so the number of buckets is commensurate with the size of the data set that you're storing, that's why universal hash functions in a hash table with chaining guarantee expected constant time performance. In the last video, we discussed the performance of hash tables that are implemented using chaining, using one linked list per bucket. In fact, we proved mathematically that if you use a hash function chosen uniformly at random from a universal family, and if you keep the number of buckets comparable to the size of your data set, then in fact you're guaranteed constant time expected performance. But recall that chaining is not the only implementation of hash tables. There's a second paradigm, which is also very important, called open addressing. This is where you're only allowed to store one object in each slot, and you keep searching for an empty slot when you need to insert a new object into your hash table. Now, it turns out it's much harder to mathematically analyze hash tables implemented using open addressing, but I do want to say a few words about it to give you the gist of what kind of performance you might hope to expect from those sorts of hash tables. So recall how open addressing works. We're only permitted to store one object in each slot. So this is unlike the case with chaining, where we can have an arbitrarily long list in a given bucket of the hash table. With at most one object per slot, obviously open addressing only makes sense when the load factor alpha is less than 1, when the number of objects you're storing in your table is less than the number of slots available. Because of this requirement that we have at most one object per slot, we need to demand more of our hash function. So our hash function might ask us to put a given object, say with some IP address, into, say, bucket number 17, but bucket number 17 might already be full, might already be populated. So in that case, we go back to our hash function and ask it where to look for an empty slot next. So maybe it tells us to next look in bucket 41. If 41 is full, it tells us to look in bucket number 7, and so on. Two specific strategies for producing a probe sequence that we mentioned earlier were double hashing and linear probing. Double hashing is where you use two different hash functions, h1 and h2. h1 tells you which slot in which to search first, and then every time you find a full slot, you add an increment, which is specified by the second hash function, h2. Linear probing is even simpler. You just have one hash function that tells you where to look first, and then you just add 1 to the slot until you find an empty slot. As I mentioned at the beginning, it is quite non-trivial to mathematically analyze the performance of hash tables using these various open addressing strategies. It's not impossible. There is some quite beautiful and quite informative theoretical work that does tell us how hash tables perform, but that's well outside the scope of this course. So instead, what I want to do is I want to give you a quick and dirty calculation that suggests, at least in an idealized world, what kind of performance we should expect from a hash table with open addressing if it's well implemented as a function of the load factor alpha. Precisely, I'm going to introduce a heuristic assumption. It's certainly not true, but we'll do it just for a quick and dirty calculation, that we're using a hash function in which each of the n factorial possible probe sequences is equally likely. Now, no hash function you're ever going to use is actually going to satisfy this assumption. And if you think about it for a little bit, you'll realize that if you use double hashing or linear probing, you're certainly not going to be satisfying that assumption. So this will still give us a kind of best case scenario against which you can compare the performance of your own hash table implementations. So if you implement a hash table and you're seeing performance as good as what's suggested by this idealized heuristic analysis, then you're home free. You know your hash table is performing great. So what is the line in the sand that gets drawn under this heuristic assumption? What is this idealized hash function performance as a function of the load alpha? Well, here it is. What I'm going to argue next is that under this heuristic assumption, the expected amount of time to insert a new object into the hash table is going to be essentially 1 over 1 minus alpha, where alpha is the load. Remember, the load is the number of objects in the hash table divided by the number of available slots. So if the hash table is half full, then alpha is going to be 0.5. If it's 75% full, then alpha is going to be 3/4. So what this means is that in this idealized scenario, if you keep the load pretty under control, so say if the load is 50%, then the insertion time is going to be great, right? If alpha is 0.5, then 1 over 1 minus alpha is equal to 2. So you expect just 2 probes before to successfully insert a new object. And of course, if you're thinking about lookup, that's going to be at least as good as insert. So if you're lucky, a lookup might terminate early if you find what you're looking for. In the worst case, you go all the way until an empty slot in an unsuccessful search, and that's going to be the same as insertion. So if alpha is small, bounded away from 1, you're getting constant time performance. On the other hand, as the hash table gets full, as alpha gets close to 1, this operation time is blowing up. It's actually going to infinity as alpha gets close to 1. So even if you have a 90% full hash table with open addressing, you're going to start seeing 10 probes. So you really want to keep hash tables with open addressing. You want to keep the load under control. Certainly no more than probably 0.7, maybe even less than that. To refresh your memory, with chaining, hash tables are perfectly well defined even with load factors bigger than 1. What we derived is that under universal hashing, under a weaker assumption, we had an operation time of 1 plus alpha for a load of alpha. So with chaining, you just got to keep alpha to be, at most some reasonably small constant. With open addressing, you really got to keep it well bounded away below 1. So next, let's understand why this observation is true. Why, under the assumption that every probe sequence is equally likely, do we expect a 1 over 1 minus alpha running time for hash tables with open addressing? So the reason is pretty simple, and we can derive it by analogy with a simple coin flipping experiment. So to motivate the experiment, think just about the very first probe that we do. Okay, so we get some new object, some new IP address that we want to insert into our hash table. Let's say our hash table is currently 70% full. Say there's 100 slots, 70 are already taken by objects. Well, when we look at this first probe, by assumption it's equally likely to be any of the 100 slots, 70 of which are full, 30 of which are empty. So with probability 1 minus alpha, or in this case 30%, our first probe will luckily find an empty slot, and we'll be done. We'll just insert the new object into that slot. If we get unlucky, with probability 70%, we find a slot that's already occupied, and then we have to try again. So we try a new slot drawn at random, and we again check, is it full or is it not full? And again, with 30% probability, essentially it's going to be empty, and we can stop. And if it's already full, then we try yet again. So doing random probes looking for an empty slot is tantamount to flipping a coin with probability of heads 1 minus alpha, or in this example 30%, and the number of probes you need until you successfully insert is just the number of times you flip this biased coin until you see a heads. In fact, this biased coin flipping experiment slightly overestimates the expected time for insertion under the heuristic assumption, and that's because in the insertion time we're never going to try the same slot twice. We're going to try all n buckets in some order with each of the n factorial orderings equally likely. So back to our example where we have a hash table with 100 slots, 70 of which are full. The first probe, indeed, we have a 30 in 100 chance of getting an empty slot. If that one fails, then we're not going to try the same slot again. So there's only 99 residual possibilities, again, 30 of which are empty. The one we checked last time was full. So we actually have a 30 over 99% chance of getting an empty slot in the second try, 30 over 98 on the third try if the second one fails, and so on. But a valid upper bound is just to assume a 30% success probability with every single probe, and that's precisely what this coin flipping experiment will get us. So the next quiz will ask you to actually compute the expected value of capital N, the number of coin flips needed to get heads when you have a probability of heads of 1 minus alpha. As a hint, we actually analyzed this exact same coin flipping experiment when alpha equals a half, back when we discussed the expected running time of randomized linear time selection. All right, so the correct answer is the first one, 1 over 1 minus alpha. So to see why, let's return to our derivation, where we reduced analyzing the expected insertion time to this random variable, the expected number of coin flips until we see a heads. So I'm going to solve this exactly the same way that we did it back when we analyzed a randomized selection algorithm, and it's quite a sneaky way, but very effective. What we're going to do is we're going to express the expected value of capital N in terms of itself, and then solve. So how do we do that? Well, on the left-hand side, let's write the expected number of coin flips, the expected value of capital N, and then let's just notice that there's two different cases. Either the first coin flip is a heads, or it's not. So in any case, you're certainly going to have one coin flip. So let's separate that out and count it separately. With probability alpha, the first coin flip is going to be tails, and then you start all over again. And because it's a memoryless process, the expected number of further coin flips one requires, given that the first coin flip was tails, is just the same as the expected number of coin flips in the first place. So now it's a simple matter to solve this one linear equation for the expected value of n, and we find that it is indeed 1 over 1 minus alpha as claimed. Summarizing, under our idealized heuristic assumption that every single probe sequence is equally likely, the expected insertion time is upper bounded by the expected number of coin flips, which by this argument is at most 1 over 1 minus alpha. So as long as your load alpha is well bounded below 1, you're good. At least in this idealized analysis, your hash table will work extremely quickly. Now, I hope you're regarding this idealized analysis with a bit of skepticism, right? From a false hypothesis, you can literally derive anything you want. And we started with this assumption, which is not satisfied by hash functions you're actually going to use in practice, this heuristic assumption that all probe sequences are equally likely. So, should you expect this 1 over 1 minus alpha bound to hold in practice or not? Well, that depends to some extent. It depends on what open addressing strategy you're using. It depends on how good a hash function you're using. It depends on whether the data is pathological or not. So just to give coarse rules of thumb, if you're using double hashing and you have non-pathological data, I would go ahead and look for this 1 over 1 minus alpha bound in practice. So implement your hash table, check its performance as a function of the load factor alpha, and shoot for the 1 over 1 minus alpha curve. That's really what you'd like to see. With linear probing, on the other hand, you should not expect to see this performance guarantee of 1 over 1 minus alpha, even in a totally idealized scenario. Remember, linear probing is the strategy where your initial probe, the hash function tells you where to look first, and then you just scan linearly through the hash table until you find what you're looking for, an empty slot, the object you're looking up, or whatever. So with linear probing, even in a best case scenario, it's going to be subject to clumping. You're going to have contiguous groups of slots which are all full, and that's because of the linear probing strategy. And I encourage you to do some experiments with implementations to see this for yourself. So because of clumping with linear probing, even in the idealized scenario, you're not going to see 1 over 1 minus alpha. However, you're going to see something worse, but still in idealized situations quite reasonable. So that's the last thing I want to tell you about in this video. Now, needless to say, with linear probing, the heuristic assumption is badly false. The heuristic assumption is pretty much always false, no matter what hashing strategy you're using, but with linear programming, it's quote-unquote really false. So to see that, the heuristic assumption said that all n factorial probe sequences are equally likely, so your next probe is going to be uniform at random amongst everything you haven't probed so far. But with linear probing, it's totally the opposite, right? Once you know the first slot that you're looking into, say bucket 17, slot 17 is going to be the first slot, you know the rest of the sequence, because it's just a linear scan through the table. So it's kind of diametrically opposite from each successive probe being independent from the previous ones, except for not exploring things twice. So, to state a conjectured or idealized performance guarantee for hash tables with linear probing, we're going to replace the blatantly false heuristic assumption by a still false but more reasonable heuristic assumption. So what do we know? We know that the initial probe with linear probing determines the rest of the sequence. So let's at least assume that these initial probes are uniform at random and independent for different keys. Of course, once you know the initial probe, you know everything else, but let's assume independence and uniformity amongst the initial probes. Now, this is a strong assumption. This is way stronger than assuming you have a universal family of hash functions. This assumption is not satisfied in practice, but the performance guarantees we can derive under this assumption are typically satisfied in practice by well-implemented hash tables that use linear probing. So the assumption is still useful for deriving the correct idealized performance of this type of hash table. So what is that performance? Well, this is a utterly classic result from exactly 50 years ago, from 1962. And this is a result by my colleague, the living legend, Don Knuth, author of Art of Computer Programming. And what Knuth proved was that under this weaker heuristic assumption suitable for linear probing, the expected time to insert an object into a hash table with load factor alpha when you're using linear probing is worse than 1 over 1 minus alpha, but it is still a function of the load alpha only, and not a function of the number of objects in the hash table. So that is, with linear probing, you will not get as good a performance guarantee, but it is still the case that if you keep the load factor bounded away from 1, if you make sure the hash table doesn't get too full, you will enjoy constant time operations on average. So for example, if with linear probing your hash table is 50% full, then you're going to get an expected insertion time of roughly 4 probes. Note, however, this quantity does blow up pretty rapidly as the hash table grows full. If it's 90% full, this is already going to be something like 100 probes on average. So you really don't want to let hash tables get too full when you're using linear probing. You might well wonder if it's ever worth implementing linear probing, given that it has the worst performance curve, 1 over 1 minus alpha squared, than the performance curve you'd hope from something like double hashing, 1 over 1 minus alpha. And it's a tricky cost-benefit analysis between linear probing and more complicated but better performing strategies that really depends on the application. There are reasons that you do want to use linear probing sometimes. It is actually quite common in practice. For example, it often interacts very well with memory hierarchies. So again, as with all of this hashing discussion, the costs and benefits are very subtle trade-offs between the different approaches. If you have mission-critical code that's using a hash table and you want to really optimize it, try a bunch of prototypes and just test. Figure out which one is the best for your particular application. So let me conclude the video with a quote from Knuth himself, where he talks about the rapture of proving this 1 over 1 minus alpha squared theorem and how it was life-changing. He says, I first formulated the following derivation, meaning the proof of that last theorem, in 1962. Ever since that day, the analysis of algorithms has in fact been one of the major themes in my life. So in this video, we're going to discuss Bloom filters, which is a data structure developed appropriately enough by Burton Bloom back in 1970. Bloom filters are a variant on hash tables. You'll recognize a lot of the ideas from our hash table discussion. The win that you get in Bloom filters is they're more space efficient than run-of-the-mill hash tables. On the other hand, they do allow for errors. There is a non-zero false positive probability when you do lookups, but that's still a win for some applications. So it's a very cool idea, very cool data structure. You do see it used quite a bit in practice, so let's start talking about them. So we'll go through the usual topics that we do whenever we discuss a new data structure. So first, I want to tell you what operations they support and what kind of performance you can expect from those operations. So in other words, what is the API corresponding to the data structure? Secondly, I'm going to talk a little bit about what it's good for. So what are some potential applications? Then we'll take a peek under the hood. I'll tell you some of the implementation details with an emphasis on explaining why you get the kinds of performance trade-offs that you do with Bloom filters. So to first order, the raison d'etre of a Bloom filter is exactly the same as a hash table. It supports super fast inserts, super fast lookups. So you can put stuff in there and you can remember what you put in earlier. Now, of course, what you should be wondering is, well, we already know a data structure that supports super fast insert and lookups, a hash table. Why am I bothering to tell you about yet another data structure with exactly those same operations? So let me tell you about the pros and cons of Bloom filters relative to run-of-the-mill hash tables as we've already discussed. The big win is that Bloom filters are more space efficient than hash tables. No matter whether they're implemented with chaining or with open addressing, you can store much less space per object. In fact, as we'll see, less space than that of an object itself using a Bloom filter. As far as the cons, well, first of all, this is really for applications where you just want to remember what kind of values you've seen. You're not trying to store pointers to the objects themselves, you're just trying to remember values. So the first drawback of a Bloom filter is that because we want to be so space efficient, we don't even want to remember the object itself, just whether or not we've seen it before, we're not going to be able to store the objects or even pointers to the objects in a Bloom filter. We're just going to remember what we've seen and what we haven't. So some of you might know the terminology hash set for this kind of variant of a hash table as opposed to a full-blown hash table or a hash map. The second con is, at least in the vanilla implementation of Bloom filters that I'm going to describe here, deletions are not allowed. You can only insert, you can't delete. The situation with deletions is very much similar to hash tables implemented with open addressing. It's not that you can't have a Bloom filter that accommodates deletions. You can, there are variants of it, but it requires significantly more work, and we're not going to discuss it here. So to first order, at least for vanilla Bloom filters, you want to think of them as suitable for applications where deletions are not a first order operation. Now the third con, and this is a drawback we have not seen previously in any data structures, is Bloom filters can actually make mistakes. Now, what kind of mistake could this kind of data structure possibly make? Right, all you're really doing is looking something up. Well, one mistake would be a false negative, and that means you've inserted something previously, then you look it up, and the hash table or the Bloom filter says it's not there. So Bloom filters will not have false negatives of this form. You insert something, you look it up later, it's definitely going to confirm that you've inserted it in the past. But Bloom filters will have false positives. That means that despite the fact you've never inserted, say, a given IP address into the Bloom filter, if you look it up later, it will say that you have. So there will sometimes be, in some sense, phantom objects in Bloom filters, objects which it thinks have been inserted even though they haven't been. So given that I'm now showing you two data structures with essentially the same functionality, hash tables and Bloom filters, at least if we ignore the deletion issue, you might well wonder which one is more appropriate, which one is more useful. And because there are these trade-offs between the two, the answer, as you'd expect, is it depends on the application, right? So if it's an application where space is really at a premium, you might want to turn to Bloom filters, especially if a small chance of a false positive is not a deal breaker. If you have some kind of application where false positives are absolutely out of the question, of course, you should not use a Bloom filter, and you want to think about a hash table. So what are some situations where people actually do use Bloom filters, where you either really care about space and or you don't really care about this false positive probability? Well, one of the earliest applications of Bloom filters, this is now a long time ago, this is something like 40 years ago, was to spell checkers. So how would you implement a spell checker using a Bloom filter? Well, first you have this insert phase where you basically just go through the entire dictionary word by word and you insert every valid word into the Bloom filter. Then, afterwards, when you're presented with a new document that somebody's written, you're going to go through the document word by word, and for each word you say, is this in the Bloom filter? That is this one of the legitimate words from the dictionary which was previously inserted? If the Bloom filter says, yes, this word is in the dictionary, we've seen it before, then you treat it as a correctly spelled word, and if it's not in the Bloom filter, then you treat it as an incorrectly spelled word. Now, the false positive probability means this isn't a perfect spell checker. It means sometimes you're going to look up a misspelled word and the Bloom filter won't catch it. It will actually say, yes, with small probability, it will say this is a legitimate word. So, that's not ideal, but, the English language is pretty big and space was definitely at a premium 40 plus years ago. So it was a win for that application at that time to use Bloom filters to implement a spell checker. Another application, which, remains relevant today, is to keep track of a list of forbidden passwords. Now, why would you have forbidden passwords? Well, maybe you want to keep track of passwords which are too weak, or too easy to guess, or too common. You may yourself have used a piece of software or a website at some point where it asked you for a password, and if you typed in something which is too simple or too easy, it rejected it and asked you to type in another one. So one way to implement this list of forbidden passwords is just with a Bloom filter. And the idea is similar to the spell checker. You first insert into the Bloom filter all of the passwords that you don't want anybody to use for whatever reason. Then, when a client comes and tries to type in a new password, you look it up in the Bloom filter, and if you get a positive lookup, then you tell the user, nope, that's no good, you can't use that password, choose another one. And this is an application where you really don't care about the errors. You really don't care about the fact that there's a false positive rate. Let's assume that the error rate is something like 1% or 0.1%. So what would that mean in this context? That would just mean that once in a while, 1 in 100 clients or 1 in 1,000 clients actually types in a perfectly strong password that gets rejected by the Bloom filter, and they have to type in a second one. Okay, but big deal. And if space is at a premium, this is definitely a win to use this super lightweight data structure to keep track of these blocked passwords. These days, certainly one of the killer applications of Bloom filters is in software deployed on network routers. So the machinery out in the internet which is responsible for transmitting packets from one place to another. So what are the reasons why Bloom filters have found fertile application in network routers? Well, first of all, you do have a budget on space. Typically in network routers, there's a lot of things they got to do, and you don't want to waste that much of it on just some random data structure to do one specific task. So you do have a budget on space, and also you need super, super fast data structures, right? Because packets are coming in at this torrential rate which you can't even imagine, and you want to process these packets in real time, sending them off to the next hop. Bloom filters are the workhorse behind a lot of different tasks that is done at a network router. You could imagine wanting to keep track of blocked IP addresses. You can imagine keeping track of the contents of some cache so you don't do spurious lookups. You can imagine maintaining statistics to check for denial of service attacks, and so on and so forth. So summarizing, as an expert programmer, what is it you should remember about Bloom filters? What purpose does this tool serve in your toolbox? Well, as far as the operation supported, it's the same as a hash table. The point is to have super fast inserts, super fast lookups. But Bloom filters are a more lightweight version of a hash table. So they're more space efficient, but they do have this drawback of having this small error probability. So those are the key features you should remember when deciding whether or not you're working on an application that could make good use of this data structure. So having discussed what are the operations and what these data structures are good for, let's take it to the next level. Let's peer under the hood and see how they're actually implemented, because this is really a quite simple, quite cool idea. So like hash tables, Bloom filters have essentially two ingredients. First of all, there's an array, and second of all, there's a hash function, or in fact, several hash functions. So we're going to have a random access of an array, except instead of having n buckets or n slots, as we've been calling them, each entry in this array is just going to be a single bit. Each entry in this array can only take on two values, 0 or 1. And the way to think about the space occupied by a Bloom filter is in terms of the number of bits per object that has been inserted into the Bloom filter. So if you've inserted a data set capital S, then the total number of bits is n. The number of objects that have been inserted is the cardinality of S. So n over the cardinality of S is the number of bits in this data structure that you're using per entry in the data set. Now, you can tune a Bloom filter so this ratio is any number of different quantities, but for now, I encourage you to think of this ratio as being 8. That is, for each object stored in the Bloom filter, you're using only 8 bits of memory. That will help you appreciate just how amazing these data structures are, right? Because maybe our data set is something like IP addresses, which are 32 bits. So what I'm saying here, if this is 8, I'm saying we're definitely not actually storing the IP address. So we have this 32-bit object we're inserting, and we're only using 8 bits of memory to somehow remember whether it's there or whether it's not. And again, certainly 8 bits per object is way less than keeping a pointer to some associated memory somewhere. So this is a really impressive minimal use of space to keep track of what we've seen and what we haven't. And secondly, we need mappings of given an object, so say given an IP address, what are the relevant bits for seeing if we've seen this IP address before or not. So in a Bloom filter, it's important to have not one hash function, but several hash functions. So K is going to denote the number of hash functions in a Bloom filter. We should think of K as some small constant, somewhere, 3, 4, 5, something like that. So obviously it's a little bit more complicated to use multiple hash functions as opposed to just one hash function. But it's really not that big a deal. So recall from our discussion of, say, universal hashing, we had identified entire families of hash functions which will work well on average. So instead of choosing just one hash function at random from a universal family, you can make K independent random choices from a universal family. In fact, in practice, it seems to typically be enough to just use 2 different hash functions and then generate K different linear combinations of those 2 hash functions. But for the purposes of this video, let's just assume that we've done enough work to come up with K different good hash functions, and that's what we're going to be using in our Bloom filter. So the code for both insert and delete is very elegant. So let's start by insertion. So suppose we have some new IP address and we want to stick it into this Bloom filter. What do? Well, we just evaluate each of our k hash functions on this new object. Each of those tells us an index into our array of bits, and we just set those k bits equal to 1. And when we do this insert, we don't even bother to look at what the previous values of these bits were. So 0 or 1, we don't care. We just blithely go in and set these k bits equal to 1, whatever they were before. So what about looking up? How are we going to implement that? Well, all we have to do is check for the footprint that was inevitably left by a prior insertion. So if we're looking up an IP address and we know it was inserted at some time in the past, what happened? Well, we evaluated the k hash functions, we went to the appropriate positions in the array, and we set all of those bits to 1. So now we just check that that indeed happened. That is, when we get a new IP address, we're looking it up, we evaluate the hash function, all k of them, we look at the corresponding k positions, and we verify that indeed those k bits have been set to 1. So what I hope is clear fairly quickly from inspecting this very elegant code is that we will not ever have false negatives, yet we might have false positives. So let's discuss those one at a time. So remember, a false negative would mean that the Bloom filter says something isn't there when in fact it is. That is, we insert something and then we look it up later and the Bloom filter rejects us. Well, that's not going to happen, because when we insert something, we set the relevant k bits to 1. Notice when a bit is 1, it remains 1 forevermore. That's, bits are never reset back to 0. So if anything was ever inserted and we subsequently look it up, definitely we will confirm that all of those bits are 1. So we're never going to be rejected by something we inserted before. On the other hand, it is totally possible that we will have a false positive. It's totally possible that there'll be a phantom object, we'll do a lookup, and the Bloom filter will return yes when we never inserted that object. Suppose, for example, the k equals 3. So we're using 3 different hash functions. Consider some IP address, fixed IP address. Maybe the 3 hash functions tells us the relevant bits are 17, 23, and 36. Maybe we never inserted this IP address, but we inserted IP address number 2, and in its insertion, the 17th bit got set to 1. We inserted some other IP address number 3, and the 23rd bit got set to 1. And then we inserted IP address number 4, and the 36th bit got set to 3. So 3 different IP addresses were responsible for setting these 3 different bits, but whatever, it's not like we're remembering that. And then once we look up this IP address we really care about, what do? We just inspect bit 17, oh, it's 1. We inspect bit 23, oh, it's 1. We inspect bit 36, it's also 1. For all we know, this thing really was inserted, and the Bloom filter is going to say, yes, it's in the table. So that's how we have false positives. All of the bits that are indicating whether or not a given object are in the Bloom filter were previously set by insertions from other objects. So there are 2 points that I hope are clear at this stage of the discussion. First of all, that this Bloom filter idea does suggest the possibility of a super space efficient variant of a hash table, right? So we've been talking about setting the number of bits to be roughly, say, 8 times the number of objects that you're storing, so you're only using 8 bits per object. And for most objects, that's going to be radically smaller than just a simple array storing the objects themselves. Again, if they're IP addresses, we're only have 25% much space as if we actually stored those IP addresses just in an array with no extra bells and whistles. The second point is that we're inevitably going to have some errors in a Bloom filter. We will have false positives where we look something up, it says it's there when in fact it's not. So those 2 points I hope are clear. What's actually not clear is the bottom line. Is this actually a useful idea? For this to be useful, it better be the case that the error probability can be quite small even while the space per object is quite small. If we can't get those 2 things small simultaneously, this is a bad idea, and we should just always use a hash table instead. So to evaluate the quality of this idea, we're going to have to do a little bit of mathematical analysis. That's what I'm going to show you on the next couple slides. So before we embark on the analysis, what are we hoping to understand? Well, what seems intuitively clear is that there's going to be some trade-off between the 2 resources of a Bloom filter. One resource is space consumption, the other resource is essentially correctness. So the more space we use, the larger number of bits, we'd hope that we'd make fewer and fewer errors. And then as we compress the table more and more, reuse bits more and more for different objects, then presumably the error rate is going to increase. So the goal of the analysis that we're about to do is to understand this trade-off precisely at a quantitative level. Once we understand the trade-off curve between these 2 resources, then we can ask, is there a sweet spot which gives us a useful data structure? Quite small space and quite manageable error probability. So the way we're going to proceed with the analysis will be familiar to those of you that watched the open addressing video about hash tables. So to make the mathematical analysis tractable, I'm going to make a heuristic assumption. It's a strong assumption which is really not satisfied by hash functions you would use in practice. We're going to use that assumption to derive a performance guarantee for Bloom filters. But as always in any implementation, you should check that your implementation actually is getting performance comparable to what the idealized analysis should suggest. That said, if you use a good hash function and if you have non-pathological data, the hopes, and this is borne out in many empirical studies, is that you will see performance comparable to what this heuristic analysis will suggest. So what is the heuristic assumption? Well, it's going to be, again, familiar from our hashing discussion. We're just going to assume that all the hashing is totally random. So for each choice of a hash function hi and for each possible object x, the slot, the position of the array, which the hash function gives for that object, is uniform at random, first of all, and it's independent from all other outputs of all hash functions on all objects. So the setup then is we have n bits, we have a data set, capital S, which we've inserted into our Bloom filter. Now our eventual goal is to understand the error rate, or the false positive probability. That is, the chance that an object which we haven't inserted into the Bloom filter looks as if it has been inserted into the Bloom filter. But as a preliminary step, I want to ask about the population of ones after we've inserted this dataset capital S into the Bloom filter. So specifically, let's focus on a particular position of the array, and by symmetry it doesn't matter which one, and let's ask what is the probability that a given bit, a given position in this array, has been set to 1 after we've inserted this entire dataset capital S. All right, so this is a somewhat difficult quiz question, actually. The correct answer is the second answer. It's 1 minus quantity, 1 minus 1 over n raised to the number of hash functions k times the number of objects, the cardinality of s. That's the probability that, say, the first bit of a Bloom filter has been set to 1 after the dataset capital S has been inserted. So the maybe easiest way to see this is to first focus on the first answer. So the first answer is going to be the probability, I claim, that the first bit is 0 after the entire data set has been inserted. Then, of course, the probability that's 1 is just 1 minus this quantity, which is equal to the second answer. So we just need to understand why the first choice is the probability that the first bit equals 0. Well, it's initially 0, and remember, stuff is only set from 0 to 1. So we need to analyze the probability that this first bit survives all of these darts that are getting thrown to the Bloom filter over the course of this entire data set being inserted. So there are these cardinality of S objects, each get inserted. On an insertion, k darts, uniformly at random and independent from each other, are effectively thrown at the array, at the Bloom filter. Any position that a dart hits gets set to 1. Maybe it was 1 already, but if it was 0, it gets set to 1. If it's 1, it stays 1. So how is this first bit going to stay 0? Well, it has to be missed by all of the darts. A given dart, a given bit flip, is uniformly likely to be any of the n bits. So the probability that winds up being this bit is only 1 over n. The probability that it's fortunately somebody else, well, that's 1 minus 1 over n. So you have a chance of surviving a single dart with probability 1 minus 1 over n. There's the number of hash functions k times the number of objects, cardinality of S darts being thrown, right? K per object that gets inserted. So the overall probability of eluding all of the darts is 1 minus 1 over n raised to the number of hash functions k times the number of insertions, cardinality of S. And again, the probability that it's 1 is just 1 minus that quantity, which is the second option in the quiz. So let's go ahead and resume our analysis using the answer to that quiz. So what did we discover? We discovered the probability that a given bit is 1 minus quantity 1 minus 1 over n, where n is the number of positions raised to the number of hash functions k times the number of insertions, cardinality of S. So that's a kind of messy quantity, so let's recall a simple estimation fact that we used once earlier. You saw this when we analyzed Kargar's contraction algorithm and the benefit of multiple repetitions of Kargar's contraction algorithm. And the trick here is to estimate a quantity that's of the form 1 plus x or 1 minus x by e to the x, or e to the minus x, as the case may be. So if you take the function 1 plus x, which goes through the points minus 1, 0, and 0, 1, and of course is a straight line, and then you also look at the function e to the x, well, those two functions are going to kiss at the point 0, comma 1, and everywhere else e to the x is going to be above 1 plus x. So for any real value of x, we can always upper bound the quantity 1 plus x by e to the minus x. So let's apply this fact to this quantity here, 1 minus 1 over n raised to the k times cardinality of s. We're going to take x to be minus 1 over n. So that gives us an upper bound on this probability of 1 minus e to the minus k times the number of insertions over n. Okay, so that's taking x to be minus 1 over n. Let's simplify our lives a little bit further by introducing some notation. So I'm going to let b denote the number of bits that we're using per object. So this is the quantity I was telling you to think about as 8 previously. This is the ratio n, the total number of bits, divided by the cardinality of s. So this green expression becomes 1 minus e to the minus k over b, where b is the number of bits per object. And now we're already seeing the type of trade-off that we were expecting. Remember, we were expecting that as we use more and more space, then the error rate we think should go down. So if you compress the table a lot, so you reuse bits for lots of different objects, that's when you start going to see a lot of false positives. So in this light blue expression, if you take the number of bits per object, so the number of space, the amount of space, little b, if you take that growing very large, tending to infinity, this exponent tends to 0, so e to the minus 0 is 1, so overall this probability of a given bit being 1 is tending to 0. So that is, the more bits you have, the bigger space you have, the smaller the fraction of ones, the bigger the fraction of zeros. That should translate to a smaller false positive probability, and that's what we'll make precise on the next and final slide. So let's rewrite the upshot from the last slide. The probability that a given bit is equal to 1 is bounded above by 1 minus e to the minus k over b, where k is the number of hash functions and b is the number of bits we're using per object. Now this is not the quantity we care about. The quantity we care about is a false positive probability, where something looks like it's in the Bloom filter even though it's never been inserted. So let's focus on some object like some IP address which has never ever been inserted into this Bloom filter. So for a given object x, which is not in the data set, that is, has not been inserted into the Bloom filter, what has to happen for us to have a successful lookup, a false positive, for this object? Well, each one of its k bits has to be set to 1. So we already computed the probability that a given bit is set to 1. So what has to happen for all k of the bits that indicate x's membership in the Bloom filter, all k of them have to be set to 1. So we just take the quantity we computed on the previous slide and we raise that to the kth power, indicating that it has to happen k different times. So believe it or not, we now have exactly what we wanted, what we set out to do, which is derive a quantitative understanding of the intuitive trade-off between, on the one hand, the space used, and on the other hand, on the error probability, the false positive probability. So we're going to call this green circled quantity a name. We'll call it epsilon for the error rate, and again, all errors are false positives. And again, as b goes to infinity, as we use more and more space, this exponent goes to 0, so 1 minus e to that quantity is going to 0 as well, and of course once we power it to the kth power, it gets even closer to 0. So the bigger b gets, the smaller this error rate epsilon gets. So now let's get to the punchline. So remember, the question is this data structure actually useful? Can we actually set all of the parameters in a way that we get both really usefully small space, but a tolerable error epsilon? And, of course, we wouldn't be giving this video if the answer wasn't yes. Now, one thing I've been alluding all along is, how do we set k? How do we choose the number of hash functions? I told you at the very beginning to think of k as a small constant, like 2, 3, 4, 5. And now that we have this really nice quantitative version of how the error rate and the space trade off with each other, we can answer how to set k. Namely, set k optimally. So what do I mean? Well, fix the number of bits that you're using per object, 8, 16, 24, whatever. For fixed b, you can just choose the k that minimizes this green quantity, that minimizes the error rate epsilon. So how do you minimize this quantity? Well, you do it just like you learn in calculus, and I'll leave this as an exercise for you to do in the privacy of your own home. But for fixed b, the way to get this green quantity epsilon as small as possible is to set the number of hash functions k to be roughly the natural log of 2, that's a number less than 1, notice, that's like 0.693, times b. So in other words, the number of hash functions for the optimal implementation of a Bloom filter is scaling linearly with the number of bits that you're using per object. It's about 0.693 times the bits per object. Of course, this is generally not going to be an integer, so you just pick k to be either this number rounded up or this number rounded down. But continuing the heuristic analysis, now that we know how to set k optimally to minimize the error for a given amount of space, we can plug that value of k back in and see, well, how does the space and the error rate trade off against each other? And we get a very nice answer. Specifically, we get that the error rate epsilon, this is under an optimal choice of the number of hash functions k, decreases exponentially in the number of bits that you use per object. So it's roughly 1/2 raised to the natural log of 2, or 0.693 roughly, times the number of bits per object b. But again, the key qualitative point here is to notice that epsilon is going down really quickly as you scale b. If you double the number of bits that you're allocating per object, you're squaring the error rate. And for small error rates, squaring it makes it much, much, much smaller. And of course, this is just one equation in two variables. If you prefer, you can solve this equation to express b, the space requirement, as a function of an error requirement. So if you know that the tolerance for false positives in your application is 1%, you can just solve this for b and figure out how many bits per object you need to allocate. And so rewriting, what you get is that the number of bits per object that you need is roughly 1.44 times the log base 2 of 1 over epsilon. So as expected, as epsilon gets smaller and smaller, you want fewer and fewer errors, the space requirements will increase. So the final question is it a useful data structure? Can you set all the parameters so that you get a really interesting space error trade-off? And the answer is totally. So let me give you an example. Let's go back to having 8 bits of storage per object, so that corresponds to b equals 8. Then what this pink formula indicates is we should use 5 or 6 hash functions. And already you have an error probability of something like 2%, which for a lot of the motivating applications we talked about is already good enough. And again, if you double the number of bits to say 16 per object, then this error probability would be really small. It would be pushing 1 in 5,000 or something like that. So to conclude, at least in this idealized analysis, which again you should check against in any real-world implementation, although empirically it is definitely achievable with well-implemented Bloom filters and non-pathological data, to get this kind of performance, even with really a ridiculously minuscule amount of space per object, much less generally than storing the object itself, you can get fast inserts, fast lookups. You do have to have false positives, but with a very controllable amount of error rates, and that's what makes Bloom filters a win in a number of applications.